So layer lines end up making your prints look cheap and crappy, but there's a few simple ways to make them look really premium and really nice without having to do anything with print settings. So in this video, we're gonna go through all the different ways that textures can make your prints look really premium. One of the first and most basic textures is actually knurling, which comes from machining, where you have just this diamond pattern imprinted into the part. This is a really good texture because it's very simple to model, it's very low effort, it doesn't create a large STL, it doesn't create a lot of surface area, it still prints very efficiently. But it has really good contrast with anything that you might want to print across the front. And again, it's a really simple thing to model. You just model up a triangle and then you replicate it in a linear fashion across the way. And it can be embedded or pulled out. This you will generally see in machining on like the handles of tools and that kind of thing. So it's a very common texture to be used with kind of functional parts. You can use it as a grip, or you can just use it as this really nice cosmetic look. Expanding on stealing textures for machined parts, you have this diamond pattern, which is the same sort of imprint that you might see on like the bed of a truck or on like trims and steel trims and that kind of stuff, a lot of things in automotive. This texture is generally used as a grip surface in order to make sure that you can actually stand on something. But again, it's a really good way of making sort of an industrial looking part or kind of a rugged looking part because it relates to that past brand of those types of pieces. So this texture would be something that you would use for like an automotive dashboard or some sort of console, those type of things, to where the people who are buying the product may have some familiarity with the actual stamped metal versions of this. But again, it creates pretty good contrast, but it has so much flat dead space inside of there that it's not as good as some others and finer textures, but it does work way better than just a smooth part. Now we start trying to get a little bit fancy. This is kind of the same sort of texture, just a linear pattern embossed across the part. But now you're actually almost designing a logo. They are these individual small sort of specialized hexagons that are all molded together. They're not really hexagons, they're actually an isometric view of a cube. A slightly more complex pattern to create if you don't have the design for it, but it's just a linear pattern across there. But generally what people do in this sort of situation is they might actually replace this shape with like their logo or something along those lines so that you have the entire part covered with whatever your design might be. So these could be the logo of your company or something along those lines. Not super high contrast, and you have to be careful about this because it doesn't really create a matte finish like the knurling and those types of patterns, but it is a really good way of branding a product because you can create a fully custom sort of pattern based off some design within your company. This is kind of a continued expansion of it that again is really low bandwidth. This is just a hexagon at 3 or 4 different levels. So you can see that they're not all at the same depth, which creates a really interesting sort of pattern because it's just much more complex. The hexagons aren't great because you can still kind of see the 3D printedness of it. The smaller, finer patterns that break up that 3D printing layer line hide it better. But again, this is a really good way to create sort of a branded part again, where you have something that just looks really unique and distinct. And hexagons are one of those simple shapes that can be really easily linearly patterned across something like this inside of CAD without creating a really large file. So it's easy to upload into services like Teleport and that kind of thing so they can be printed quickly. They also print faster than really fine patterns that can take up a lot of tool motion. So you can sometimes get a cheaper part out of something like this. It's not a very functional pattern. This one almost is entirely cosmetic. It doesn't work well for grip. It doesn't necessarily do much for the contrast of the letters and that kind of stuff here, but it does create a brand identity, and that can be really useful for whatever you're creating. If you want to go even simpler than hexagons, you can just use regular triangles or triangular lines. You can just have these cross over. These are actually triangles at 2 different heights, so you get slightly better contrast on that, and you have the full lines through, so this could actually be a grip surface and that kind of thing because it has channels for water and grit to run away from. But this is probably one of the simplest ones since it just is such a simple pattern. It's really low STL file size, and it can work really well for patterning it across the entire part. So if you're a beginner in modeling, this might be the version for you to use. And it still creates many of the benefits that you want of hiding layer lines and distracting from it because you have these side diagonal lines that are completely opposite from the horizontal layer lines that were used to grow this part. From that view, there's probably no way that you can tell what orientation this part was printed in. It was printed like this. And now we start getting into something really wonky. This pattern is fairly easy to create, but actually creates a really large STL because it's continuous curves and a lot of them. So this is actually a fairly large file to create. but it creates this wonderful organic shape that you can use with like watercolors and blues and greens and that kind of thing to create something soft and more welcoming. You still have the contrast there in case you want to put something out in front. And this is a very simple pattern to create. You just create a single line swoosh and then space them linearly across there. So it's very easy to model. But this does give you a unique aesthetic that starts getting more organic, and many of our patterns going forward are going to be organic. This is taking those lines and refining them even more. You can see as the lines get smaller, you get this really cool sheen off of the part to where now you're starting to get weird dynamics because of just the different reflectivity. As compared to the large ones where it's kind of all the same color, since these are so small, so fine with such sharp corners, you get that really neat kind of linear sheen off of it, which can be really useful because it highlights the logo that we have on side there, and from different angles it starts to look different. So it's a really dynamic sort of a part to use. And again, this is just a squiggly line, a curved line that is then repeated across the part. All right, now we're starting to get fancy with some of them. This sort of cobblestone pattern is, again, not great for high contrast. You can't really see the logo right there, but really good for organic types of parts and pieces. Because you might want to make like a terrarium part that is a rock or maybe a piece of terrain, and you can use this patterning on it. This is probably the hardest to model because you have to kind of individually create these shapes or create one single section that then could be linearly patterned, which can be a bit challenging. But you can also use tools like a Formlabs texture tool to upload basically a negative of this as a black and white image, and then it will be imprinted onto your part. And that's a very simple way of doing it, but you have much less control than if you do it inside of CAD. But these cobblestones are really good for organic types of parts and pieces. Alrighty, 2 for 1. These are the same pattern, it's just the difference between an addition or a cut. So with the cut, we basically cut out a sphere, a hemisphere, whereas on this one, we added in a hemisphere all the way through. So you might be able to see that, how this is cut in and these are actual bubbles. And they look similar, but you get a kind of different dynamics because this one is actually sharper, it's a bunch of peaks, and this one is rounded and smooth. So this one feels a lot different from this one, even though they look pretty similar. And this is one of the cool things you can do with texture. Not only do you hide the layer lines, but you create these different customer experiences to where this might be really good because you want people to have a nice soft experience with something they're gonna hold like a vase, whereas this is something you might want to use in an industrial context where you want people to get a grip on it so that the tips kind of bite into a person's hand if they're grabbing it. So these are an excellent solution of the same pattern, creating two very different experiences based on whether you cut it out or add it in. So adding texturing is something you can do in 3D printing, and it basically adds no extra cost. But you're able to change something that looks like a cheap, crappy 3D printed part into something really premium and beautiful that you have unlimited control over, which has never been possible before. These types of things would be stupid expensive to manufacture just 5 years ago. But now you basically get them for free for the same cost as the smooth part. Now, the smooth part is fine and you can use that and that kind of stuff, but why not use this awesome capability to make your part look really premium, give it a completely different customer experience, hide the layer lines, and get something that is really, really good rather than something that's just 3D printed. I'm gonna show you 7 different ways to design the Skadis Hook so that it doesn't break whenever you 3D print it. Okay, so these little hooks are super handy because you can create all kinds of organizer walls, and you get panels like this, set them up on your wall, and then you can start putting up whatever you want. These things just insert into there, and then they slide straight on, and now you can set up a whole wall of these things to organize your tools, your gadgets, your home crafts, whatever it happens to be. But like I said, the challenge is these hooks are really, really tough to get 3D printed reliably because they want to snap off. If you print it like this, it's gonna snap off right there. If you print it like this, that tongue is gonna snap off right there. So how do you get these done? Well, there's a few tricks that can be used. The very first and most obvious one is to take whatever you're trying to print, and instead of having all the hooks printed the way the thing is gonna sit on there, is to set it all sideways. But now you have generated support falling up underneath the hooks, which can mess with the overall tolerance of the hooks. And when you try to press this into there, the hooks can get a little bit wider, so they're gonna be tougher to pan into the board. Also, the support can get knocked off, especially if you're using auto-generated support. Because if you have a bunch of these hooks or a bunch of variations of it all, this support right here might be that long, and now it doesn't really very reliably hold up to that hook. It might get knocked off during the print process. So while this does make the hooks strong because they're in plane with with the layers, this doesn't really work very well because you have to have all this additional support. Now you can get around the need for support by using designed supports, because now it is exactly where you need it and it's fully independent of the slicer. And that's really important because you don't want auto-generated supports when you can avoid them. Because if you can use design supports, it saves cost on printing, it's more reliable, and this support could be 8 inches long, and you could put small support sprues in there in order to make sure that it's kind of a part of the part and it can't fall over and slop away the way generated supports can. So this designing supports can be a really good way to, again, get the strength in the hooks that you want, but still have everything break away the way you intended. Design supports are also just more reliable because, again, since you're not dependent on the slicer, you know that the spacing can be super consistent, so the hooks will be a lot more crisp than with generated supports. Something else you can do if for some reason you can't print the part on its side, printing this on the side would be a little bit tough. You can actually move the hooks so that they are flush with the side. On this dish, they're not flush. You actually have this gap right here, so support would have to build up underneath this hook, and you want to avoid that. But it's very simple with a 3D printed part to just make sure that the hooks are flush straight there on the bottom of the part. That way you're printing on the bed, everything is as strong as it can be, you don't have any support. But again, you have this issue of these tabs wanting to break off. But in order to get around that, people don't realize that even though this is this traditional Skadis hook design, this is not the hook that you have to use. You just need something that can fit through these slots. And in order to get to that, that means you can adjust stuff. These break off because they're long and thin. So why not just make them short and stumpy? Here, what you can do is you still have the exact same fit that will press right into there and then still slide down and still won't fall out in any sort of way, but it just doesn't engage quite as heavily as these do. But that's okay because you don't need them to. That little lip is enough to hold in there very reliably, and now you have a really simple design that can be printed like this, has no support anywhere. The little stumps are strong enough that they will never tear out of there regardless of what you're holding in. We could make this thing a foot long out to here with a wrench inside of there. They still won't tear off. And if you really wanted to, you could technically make these back nubs longer so that that nub gets beefier and beefier and has more and more material to hold on to. So if you wanted to, you could just stretch that out. Now you might hit a wall, so that could be an issue. But again, the hooks don't have to be the design of the original hooks. You can adjust them. And this is a really simple way to make them stumpier and make them stronger without doing anything really wild and crazy. But before I get to the really weird stuff, let's go ahead and talk about Portals. Portals is a new app that we built that allows anybody to just upload a model and instantly have a 3D print for sale. When somebody orders it from you, it is printed and shipped directly to them on your behalf using Slant 3D's giant 3D print farms. And it's such a fantastic resource for designers, but it's important that designers know how to optimize their designs to make sure the customer always gets what they want. In order to design something that's really reliable and a product that's really good always, you want to make sure that it's independent of the material, the printer, or the print settings. So designing tricks like this are terribly useful so that you aren't dependent on how support is generated or those kind of things. You just get a part that will print always on any machine and will always look fantastic. So if you want to try out Portals to start growing your own 3D printing business completely on the side without having to deal with support, packing, shipping, or running your own print farm, go ahead and check out Portals over on slantpod.com. Okay, so we've run through a couple of basic tricks to get these hooks moved to a place and kind of redesigned so that they're good. But what if you do need a hook like this that's sitting on its side that is inset from it all? Like there's no way that you can move this around or do anything differently with these hooks, but you still need that feature. Well, now you're dealing with overhangs, but you don't want support if you can avoid it. You really want to avoid support. So how do you maintain the strength, avoid support, and put the hook wherever you want to? Well, you don't actually use the hook. You can actually start using compliant features. And one of the simplest compliant features are just a simple little snap. These snaps are fantastic because the trick to them is that they're not actually flat. They are actually chamfered. So it's printed like this so that you have no support underneath it. It is still the size of the standard Skadis slot, but now you have two compliant tabs to where you can take this, shove it in there, and it locks in now. Just a little bit, to where it's still easy enough to pull out, but it can still lock in. And you can make those tabs bigger and chunkier however you want to. Now there is a danger with these types of compliant features, because rather than having a fat chunky part right here, you end up with these really thin features that can have sort of sagging issues if you don't set them at the right angle. Right here, this is right on the edge of being too steep, because you're gonna have overhang issues, and it's a really thin wall in order to keep the compliance, so there can be a lot of dangers there around print quality. And literally literally just changing the color of the filament may change this from sagging to not. So make sure that chamfer is as shallow as you possibly can. I took it straight to the edge here so that you could see what could happen, but these compliant features can be super useful. And again, that center gap, I can technically make the tabs on the outside half the length of that center gap. And that's the maximum size you can make and still have it snap in and hold there just fine without anything terribly weird going on, especially if you have easy things. And then you can still pop it back out. But this compliant feature doesn't give you a lot of strength because they are just bending right there. They can snap off. Maybe you want more play in it so that you can get a bigger grip onto that board. One other really cool one that you can use is not actually one that's two separate tabs, but one that is one single loop. This single loop is fantastic because you have all the lock-in again, and it's a lot tighter. But now the danger with the loop is that you don't have a lot of flex. Here is a dirty little secret. This loop does not attach at this outer wall. It attaches almost a centimeter inside of this block, several millimeters. What this does is it makes the arms of this loop longer so they become more flexible. Because if you have something that's this long and you try to flex it, it's gonna be really stiff. But if you make it longer, it starts to flex really easily. Think of a short piece of grass or a big old long stalk of wheat. The wheat bends more easily because it just has more material to flex. So what I did is I cut this cavity around this thing so that its fins have more room to flex, and now you don't have to worry about the rigidity. Because if I made this loop, attached it the way this one is, it wouldn't flex enough and would be really tough to put on and pull off. But by doing this, it has enough room to flex. You can still pull in and compress, but you don't have to worry about fatigue or cracking right there at the edge. It's a really useful way to do it. You can apply this cavity technique to these if you want to in order to make them thicker and make them stiffer, but it's just a nifty trick in that 3D printing allows you to create geometries that you otherwise couldn't ever create, to create functionality that you otherwise wouldn't ever use. So this loop has a nice compressed single loop of material, this one single strand all the way around. It is long enough from the indent to actually hold up, and it's just a really nifty way of connecting it up because it also guides itself in there without having anything that can really snap off. It is possible that one of these tongues could someday snap off if somebody drops it or anything else, but this will basically never snap off. Again though, it is really important to be aware of your overhangs because this right here, again, it's a really thin batch of material. It's a super thin, basically one strand, maybe two if you really want to stretch it. I recommend going about a half a millimeter to 1 millimeter thick on these types of loops, but when it's that thin, you can have these overhangs that can start to sag. So again, you want to make this just as shallow as possible, or as vertical as possible, this lower edge, while still maintaining the dimensions that you need. And that way you will get something that is really crisp and totally independent of slicer settings. And also just really strong. This is never going to snap off outside of somebody taking a pair of pliers and twisting it off, which is as true of a standard plastic part as it is of a 3D printed part. But there's one more way to make the Skadis mount, which is absolutely perfect and will never break, and you never have to deal with plastic parts. Sometimes plastic hooks just are not strong enough and you need something beefy. It'd be really nice if you could get a metal hook that holds on there just like anything else. And these hooks pretty much aren't ever going to break. But you can't include these with 3D prints, and certainly not on something like Portals, but you can. On Portals, we allow third-party parts, and we actually have these hooks included to where you can upload a model and then you can add in the hook so that anytime somebody orders it, the model and the hook are shipped along with it. So now you can include a metal hook with your design, which was never possible before, so you can actually have it as strong as you ever wanted, so you're not restricted by the strength of plastic hooks. So you can design in these loops into your parts if you have that much room in it, but that way you can have the hooks be the primary mounting point on the Skadis board, but then you can create whatever you want that integrates with these hooks. So you no longer are restricted by the slots, you are restricted by the metal hook. So hopefully this was helpful to you and showing you there are many different ways of skinning any given cat. So you can design all kinds of solutions in order to make something mount up to this board because you are not limited by the geometry. You don't have to make a hook like this. You're using 3D printing. You have a lot of options. You can modify this hook, move this hook, redesign this hook, or create not a hook at all, or even just go ahead and add in something else that was never able to be added in before and still make a product that is really amazing that your customers will love and can be made on any machine, anytime, anywhere in the world, so that you can go from making one model to selling millions of the parts overnight without having to worry about your design having some weird cases where it just snaps off because you just made a 3D printed version of the old style. You can do new stuff. and it's always exciting to see what everybody creates, and I can't wait to see what you make. Yes, we all know you can take this tab and make it thicker to make it stronger. We also know that you can reorient it to make it stronger. That is not what we're talking about in this video. We're gonna talk about something interesting about how to make a tab part like this that's mounted to a wall actually strong so that these holes do not split out. Okay, so what is this scenario? Well, a lot of people want to mount parts to the walls, 3D printed parts to the walls. You might want to run screws into them, you might want to put up a handle, you might want to just mount up an electrical enclosure or something. And people will always print a part in this orientation with the layers going up, screw it into the wall, and then very promptly have the layer lines break out and split along the holes. So what are ways of getting rid of that? Well, it's important to understand the mechanism that's happening here. You're dealing with the layer adhesion of the part. Can those layer lines stay stuck together strong enough in order to not split when put under pressure? This is based on the adhesion of the material itself, but also the surface contact area. Now, this is a design video, so we're going to talk about surface contact area. If you have more contact between the layers, you will have stronger layers. So let's go ahead and look at the very first version of that. The simplest way of doing this is actually to just put threads in the holes, which seems counterintuitive because they can introduce stress concentrations, but what you are also doing is increasing the length of the layers right next to the hole where the pressure is, so there's more surface contact area around the hole. Threads are basically a way to thicken the walls around the hole so that now you have more material around the hole where a crack can start. That's a very simple way to model it, but it's not the best way because, like I say, all of those are points inside of the hole, and when you have a point right up against some piece of force, it can cause a crack that then propagates through the rest of it. So what are some other ways of getting this done? Well, you can thicken, you just don't have to thicken the entire thing. You can extrude the area around the hole and either deepen the area around the hole so that that hole is supported by material just locally around it, which can be very helpful because now you have more contact area, but you've also increased the space for infill, so it can be a little bit of a double-edged sword. A way of fixing this is to, instead of simply having an offset, is to just put rings around the hole. And now you're wrinkling the front surface to where if any crack formed, it would have to go through all of that space before it gets to the main meat of the part holding it up. And those rings are very simple to model. They are still just the simple offset, but with a few more indents into them. But ultimately what they can do is just create some structure around the hole so there's just more material there holding the hole together. And this can be incredibly useful. There's a few other ways of doing this. You don't necessarily have to use circles. Everything splits in just this direction. So you can create kind of linear solutions to it, where you have just struts right alongside that are very localized area of thickness so that it has to split through this whole big old thick area of material before splitting into the rest of the part. And again, this can be easier to model and can be useful in particular sort of use cases. But all of those are external features. Sometimes you still need the thing to be flat and you just want it to be solid in that area. Now, most people would say you would use a slicer for this, but a slicer is a wrong sort of tool for this because you should be able to create a model for an object and then send it to machinery and have any piece of machinery make that model to spec without having to worry about settings or materials or the rotation of the earth, which is what you do when you start messing with slicer settings, because one slicer will slice differently from another, one machine will print differently from another, one material will print differently than another. So if you're using slicer settings, they're very fragile, but if you design these types of features into your parts, they can work anywhere, anytime, at any scale, always. So what I would like to do is model into the part ways to make sure that it is solid around the hole. And the way you do that, you cut up the part. This is going to sound counterintuitive, but what you can do is around the hole, basically just put a disc and you cut it so that it's like a 0.1 to 0.2 millimeter thick cut. And what it does is it just induces any slicer to create walls around that area, which are not viewed from the outside. So if you have a 1 millimeter thick wall and a 2 millimeter thick part and you create a small cut between the middle of it, you just created a solid part. So what I like to do is put these discs around holes, and now you're able to create a fully solid area around that part. It's not a lot of extra modeling. It's a lot stronger and it's a lot more controllable because it will work on any machine or material without having to redo all your slicer settings. And if you want to do this over a thicker part and that kind of stuff, you can just repeat that pattern over and over again and you create these solid rings around your hole. You do want them to be vertical because you want the layers to go along it. You don't really want to do holes all the way around or those types of micro features, which you might use in other scenarios. For these, you just want a small cut, little slats inside of your part, and it creates something that can be really, really strong because you are creating a lot more surface area, basically a solid printed part that is pressed together. And you're able to use any slicer anytime, anywhere, and no one ever sees that you did it. So now, instead of giving people a big old recipe of how to make the part, you can just hand over the part and that part will be made perfectly every time. And this is why it's so important to create it, because if you want to mass produce these parts or send them to a manufacturer, you want it to be made the way you anticipate. And slicer settings don't do that. So for using portals where you can just upload a model and start selling in like 30 seconds, it's really important to just upload a model and get what you want and get it selling in 30 seconds without needing modifiers or your particular material or your particular brand. If you model it in specifically into the part will always be what you want and you don't have to worry about any of the other details. This makes a part that is really easy to manufacture, really robust, and is way more affordable too because there's a lot less work to keep it straight. So hopefully this has been a good demonstration of how to design side mount holes that are actually sort of strong rather than just 3D printed layer splitting problems. You don't want to perforate your 3D printed part, you want to reinforce your printed part. And these are a number of different ways of reinforcing those types of holes. If there's other sorts of features that you want to see us kind of design and break down about how to make them better using 3D printing to produce those actual products, comment down below and we'll try to hit them up in a future video. So let's talk about how to design a part so it just won't warp when you're 3D printing it. So warp is a very common problem inside of 3D printing because warping occurs with every plastic. When a plastic is heated, it expands slightly, and as it cools, it contracts back down. Now what this leads to, and why warp is such a big problem, is if you're printing something small, it doesn't have a big effect because warp is measured as a percentage. Something will shrink 1%. Now if you're shrinking a 10 millimeters 1%, well that's a tenth of a millimeter. It's not gonna move or change the size of the part very much. But if you're printing something 100 millimeters 1%, that means it wants to shrink a full 1 millimeter. And that creates a lot of tension in the outer surface of the part. So the longer single continuous streak of material you have, the more stress and pressure to warp that part has. That is why parts like this are so darn difficult. This is a simple square plate. It is a little bit thick there. We have 1 millimeter thicknesses all the way around, 1 millimeter thick walls, tops, bottoms, and a 25% infill, which is the standard that we use at Portal, so it's a good baseline. But this will have quite a bit of warp, as you can see from here. The top, you can see the wrinkles where the corners have warped up because the bottom layer lines are diagonal to where they're pulling there, and you have a maximum length straight across there. Now, there are a few very simple things that you can do to reduce warp. One of the easiest is just don't have sharp corners. Go for rounded corners like this. What these rounded corners do is they actually spread out the force so that rather than having it the longest and largest force coming right at this point where it can start unzipping and just start peeling that tiny little part that's stuck to the bed and then take more and more and more, it instead has a nice broad surface to start to pull from. So even though there's a stress concentration up here, it is spread out and distributed over more bed contact surface, because for it to warp, something is stuck down to the bed and it'll start trying to peel up. If there's a large amount of area contacting the bed, then it won't peel as easily. But if you have just a little corner or a little tab, then it will peel up very easily. So the simplest thing you can do is just round the outer corners. The other things you can do from a design perspective that add extra work are like design in mouse ears, and mouse ears would go at each one of these corners, which again gives you a big old wide broad contact area, but would still allow you to have these sharp corners. And we have other videos where we talk about how to design a first layer for these types of things, so I recommend checking those out. But those are all kind of the understood ways of minimizing warp for a part like this. But let's go to something more advanced. Well, if we understand that warp is induced by just long continuous areas of filament to where you have a long area that's trying to shrink down enough that it causes warp, then the simplest thing to do is to just shorten those areas. So how would you do something like that? Well, the simplest way is to just put a checker pattern on the bottom of your part. Now, instead of having one continuous line across this, you instead of have just a single continuous line across this, a single continuous line across here, and so on. So instead it is these small squares that have to shrink enough in order to shrink the entire part with you. And this can work reasonably well. But the issue with this is that you just increased your complexity of your first layer, and quite frankly, let's admit it, most of us are lazy, so we're probably gonna do it as squares. And these squares still have sharp corners on the bottom of them, so they will still have the potential warp individually. The way to cut these out is literally to just take it up like a 0.5 millimeter cut into it all. Some people will go deeper, but then you really have the opportunity to warp. But what you can do is cut up like 1 millimeter into the thing, and then take another 0.5 millimeter up from the bottom so that you now have these small cuts in the first layer down here. And what we have done is we've broken up that 1 millimeter thick first layer so that it doesn't have continuous areas of really big shrink. You do still have this first layer, but the first layer is close to the high heat of the bed, it's controlled, it's stuck to the bed. It's the stuff higher up that can really start to pull and start to peel up the piece. As far as the number of these cuts to actually make, it varies. It varies on the size of the part. There's no real true standard to it all. Right now we're spreading them about 1 inch or about 25 millimeters, but you can go less and you can go more depending on what your material is. PLA doesn't tend to have a lot of shrink. We're using matte PLA here, which does tend to have a lot of shrink. So it will depend on what your material is, how you design for it, but to be safe and to be universal, the smaller chunks you can cut it up as, the better, so long as you're not radically increasing the complexity of the part. So generally about 1 inch is fine given whatever your part might be. So okay, we have split up the first layer, which can warp, and then we have made it simple by giving it a single coat that's basically a single layer thick so that it doesn't look like a complex first layer, so it's still sticking to the bed reliably. But that doesn't really take care of these sidewalls because we still have these big old long shrinking areas that both conjoin at a corner and then both pull backwards from here. So all of these sidewalls are still trying to shrink the part, and the top is still trying to shrink the part. So what do we do about those? Well, before we get to that, let's just go ahead and talk about why this stuff is important. The reason designing these types of features into a 3D print are so important is because this will allow them to be printed on any machine with any material. If you design your STL, your raw 3D CAD model, to be printable in that you don't have corners and everything else, and you have mouse ears included, and you have these types of features in it, it means it can be printed on any machine in any size with any material with kind of any print settings regardless of layer height or anything else. It just makes a part that is very robust and very manufacturable. This is compared to like using slicer settings. You could just turn on Brim on this, but if somebody downloads this model and then tries to print it, they might not turn on the Brim, or they might not know what that is. So designing your part to just have everything in it that it needs to print reliably is way more powerful. And there's also a lot more secrets that you can do with that because in CAD you have full control of the geometry, whereas in slicers you're dependent on what the slicer is able to do at any given time. I can make this part stronger, weaker, flexible, soft, hard, whatever it happens to be inside of CAD if I know what to do, and we have other videos talking about this. But you can't always rely on your user to understand how to use the slicer, and the slicer settings are very fragile. They only work with a specific material. They only work with a particular machine. So just designing the part well means that it can be produced anywhere at any time. So that's why it's so important to design this way. But let's go ahead and talk about what to do with these sidewalls. Well, we made all these slits down at the bottom to break up the first layer. If we want to break up the sidewalls, well, we can just take those slits higher. We can start to break up the sidewalls. Now, assuming that this doesn't hurt anything in the strength of your part by having kind of a cut through the middle of it, it can work quite well. And this is one of those right here. And it actually does help break up the warp from this part because just rounding the edges and putting these slits right into here can help a lot. But now you do have a slit inside the part. It breaks up the sidewalls so you don't have such a long area pulling and shrinking and causing a problem in there, but you have kind of compromised your part. But ultimately what we did here is we just gave the filament some place to stretch to. And there's other ways of kind of getting this done that can be more and less subtle and far less structurally damaging than putting a slit through the middle of it. Though this is fine if you're doing like cosmetic pieces. You can instead just go ahead and wrinkle the outer walls. Now I've done this very chunkily just so that you can see the wrinkle that we're talking about, but these sorts of ripples could be as small as 1 millimeter or maybe even smaller, because here what we're doing is kind of an inverse sort of a trick. If you have a big old long straight line, it's going to shrink down directly. But if that line is snaky and wrinkles, then as it shrinks down, it kind of straightens itself out, but it has slack to pull from individually. So wrinkling the outside of your part can reduce warp because now all of the shrink has some place to go rather than simply pulling on this straight corner that has everything concentrated right at that point. This instead is able to kind of pull out the slack inside the wrinkles so that it doesn't actually cause warp. And if you want to be more subtle with it, like you can do it just by like avoiding a straight wall. These are straight walls, super easy. You can wrinkle them up and ripple them a little bit, or you can add just a slight amount of curve to them. And you can see there's sort of an indent cut on this, which didn't fully solve the warp because you can see from these corners right here, but it does help because as these walls go down, they're bowed just like this, and as they shrink, they can kind of bow back out like this, which can be very helpful to help reduce warp. So there's a number of different ways of doing this, of basically putting slack into the walls so that they don't warp as much as they want to. And this is important to realize. All of these solutions are demonstrations, but they're not necessarily universally used demonstrations. The concepts are break up a long straight line so that it doesn't shrink as much, or give it slack so that as it shrinks, it's actually able to pull out that slack and not actually impart it onto the part to create all these stresses inside of it. So that takes care of the first layer where you have solid long streaks. You you can cut that up into a checkerboard. The walls you can wrinkle or cut up into a checkerboard also. But what about the infill? Because on these parts, you still have infill in here, and it is generally going diagonal, even if you're using different types of infill. We generally use grid because grid is one of the stronger infills, but grid goes diagonally, so you have these long infill lines in there pulling on it. Ways of doing this and dealing with this can be very simple and also help to reinforce your part. On this piece, it looks just the same as all the rest of them. But the thing is that there are 4 circles cut out of the corners here. And what that has done is that has broken up the layer lines on the inside, the infill lines that are going across, because rather than going straight across from corner to corner, it goes from here to this circle, skip across, then here to that circle, and then skip across, and then across again. And this, again, breaks up the infill tension, pulling at the walls, which can then create some leverage, which peels up the corner. Breaking up the infill very often can be one of the most useful ways of doing it. Now again, different types of infills have different levels of shrink. For example, gyroid doesn't really pull at it because it's a wrinkled infill on the inside, but you cannot rely on your ultimate user to slice it the way you intend it to be sliced. So if you are dependent on slicer settings for your part to work, your part is not well enough designed yet because it should be universal. You should be able to use any sort of printer settings and still have the part come out reliable. That is your goal with all of those things. So if you were designing a perfect part, you would use a combination of all of these things. You would checkerboard the first layer so that it's broken up and doesn't have continuous long streaks of flatness inside of there. You would cut out some cavities on the inside to break up infill. They could be something as simple as a slit on the inside of the part in strategic areas so that the infill can't go fully across. And then you can also wrinkle and modify the outer surface. This is why curved parts very often don't shrink as badly as square parts with straight corners. So just simply having that curve or that slack inside of it can help so much. And now you can design a part that can be printed with ABS on an open bed machine and it will still print reliably. So hopefully this gave you some insight as to how the actual mechanism of warp works and what you can do to design your parts so that it just doesn't come about. And as a final word, just make sure you're doing the right things right. Fillet the sharp edges, chamfer the first layer, and make sure that you're not doing anything silly with overhangs and other kind of stuff. And your parts will come out fine.
So you want to 3D print a cube, which is super easy, right? You just make a cube and then you print it out. But that's not actually the case. In this video, we're going to look through how a beginner makes a cube, all the way up to how an expert designer would make a cube. So how does a beginner make a cube? Well, a beginner mocks up a cube inside of any software that they happen to have, and then they drop that standard catted cube straight into a 3D printer and prints it. And very often this is just fine, but there's many issues that you have with it. You have sharp edges all over the place, so one of the corners is going to be a little bit out of whack. The corners aren't actually perfectly sharp, and you have just inconsistencies in how the sides and surfaces look. You have the top, you have the bottom, you have the 4 sides, so using just kind of a default cube probably isn't the best way. What if you're an intermediate designer, someone who watches this YouTube channel kind of on the regular, and you know many of the basic design rules of 3D printing? Well, then you would go into the cube, you would go ahead and round all the vertical edges at least 1 millimeter or so. This allows the nozzle to travel around those edges without banging up against a sharp corner, so those edges become more precise, more beautiful and smooth, rather than having a sharp corner that just bangs into the end and then moves in a different direction, which can cause splurges and purges and all sorts of terrible issues. After rounding the vertical edges, you would go ahead and put a chamfer on the bottom. This allows elephant footing and other sorts of issues to not be a concern at all. And in order to make sure the whole thing is symmetric, you would put that chamfer on top. Now at least the cube is refining. It's a little bit better, it's a little bit more robust. It can be made on basically any machine in any resolution at any time, anywhere in the world, without anyone having to do like custom slicer settings for it. This cube is also higher tolerance because since you have rounded out those corners and you no longer have the dangers in odd sorts of scenarios, it is a more precise sort of a cube. And those are both fine and reasonable, and they will make you a cube. But let's go ahead and make a perfect cube. Now this is going to take some work because you don't get to use the slicer. Using a slicer is the way of letting someone else do all your thinking for you. So now we're going to go ahead and just design the whole thing so that it can be printed anywhere, anytime, and be exactly what we want it to be. Okay, the first big problem that we're going to go ahead and address is the cube sides are different. You have the bed, you have the top, you have the sides. You don't want 3 different side styles inside of this cube. You want the cube to be a cube where all the sides are identical. In order to get this done, what we're going to do is instead of chamfering just the bottom, we're going to chamfer a single edge, and again, doing the top in order to make it symmetric. Then we're going to take that cube and we're going to turn it at 45 degrees on the diagonal. We have just changed the base layer. The base layer is now no longer the big broad face of the cube, it is now one of the corners. Now this of course necessitates that we round out the vertical edges that are now present. This makes sure that you don't have to worry about overhangs or issues or warping of the material, which sharp edges can generally lead to. Again, keeping the precision of the cube throughout the entire process. But now, here's where the magic comes in. We are going to put in support fins. Now, support fins are a CAD-designed tool. The reason you use support fins rather than generic painted on support is generic painted on support doesn't actually touch the part. Support has to be able to peel away. If it merged straight into the part, well then you wouldn't be able to remove the support. But with painted on support, you now have this cube teetering inside of the support structures, which means you have lost all of your precision once again. So we are going to use design support that is still removable and reliable, but is actually merged directly into the part, so that when this support grows, it holds that part rigidly where it belongs. The support fin is placed slightly in from the outer corner. You don't necessarily want it straight on the corner because if a person runs their fingers along the corners, which is the main tactile area, the sprues that we're going to put in here could leave some residual bumps. So we're going to pull it in just a little bit from the outside so they can be cut flush with the surface of the cube. Technically this is enough. It is a tripod kind of an outline for that first layer, but we want this stable. And when you have such a small amount of contact area with the print bed, you want it held down on the print bed because again, if you're printing with some random material, you may have a high amount of warp. So you want the supports to basically hold the print down. And we're going to use these this way. So we're going to go ahead and do a rotational pattern to put the supports on the other corner as well. Now we have fully held down this part. We know it can't tip either direction, and we know that both of its edges are held down and reliable, so we don't have any warp on this particular corner. The sprues and the tines of these support fins are merged completely with the part. They are about 0.5 millimeters thick and up to about 1 millimeter wide, and that's okay. You can go to 0.5 millimeters wide, but then you have to make the whole support fin thicker in order to deal with it. It's just easier to make it 1 millimeter wide, and we'll see how it looks when it comes on out. Okay, that's the CAD design. We're gonna go ahead and print this out. You still have those little nubs on it though, which is not the greatest. So we are gonna add just a little bit of noise to the surface of this cube. And this also has the benefit of eliminating the layer lines. The layer lines kind of give away that it was printed diagonally. We don't really want that. We want it to just look like a final part and no one knows how it was made at all. By putting a little bit of noise on the outside of this part and then printing it that way, you now no longer see any of the stuff left on it, and now you have a perfect cube. And hopefully that kind of highlights how to design a cube perfectly from beginner all the way up to expert. There's many other ways and solutions and methods that you can use for these types of things as well, so let us know if there's other sorts of primitives that you want us to design to see how to design it from the beginner all the way up to the expert.
The first real golf tee was patented in 1889 by, oddly enough, a couple of Scots named William Bloxham and Arthur Douglas. Their first tee was not what you would traditionally recognize as a modern golf tee. It was basically a stand that sat on the ground. And while it wasn't a modern tee, it was the first one to be patented. Up until that point, the rules of golf said that a ball could be teed by being placed on top of some sort of object, such as a chunk of wood or a pile of dirt, which was most often used because it was soft and forgiving for the ball as you swung through with the club. But it wasn't until about 30 years later that the modern golf tee took shape and was patented by a dentist named William Lowell. This is exactly what you originally recognized, which is a stake placed into the ground with a cupped upper surface. But what if the golf tee or a similar object was being invented and manufactured today? What would the process be? And would you actually be able to mass produce an object as simple as this with 3D printing rather than what you might traditionally expect? In this video, we're going to go through how you would design that type of an object and then what the actual costs are as compared to traditional processes like injection molding. So the traditional golf tee is a very simple object. It is just a circular stake, and today it hasn't really changed since it was originally patented in 1920. It still has a cupped upper surface to hold the ball and is of varying lengths. Some people have been a little bit creative in changing it up, making rubber versions and changing the design of the upper cup, but ultimately it's always just about the same. Most golf tees today are manufactured with injection molding, and there are millions, if not billions, of them replaced because there are most certainly billions, if not trillions, of them lost and broken on the golf courses every year. But since they are manufactured at such high quantities and have been around for so long to where the cost of the molds doesn't matter because any manufacturer knows that they will move a certain number of these each year, the cost is very low. So a modern golf tee is manufactured for about 3 cents a piece. But what if it was not so ubiquitous? What if you were creating an original product? You might start with the traditional design, but 3D printing has reached a point to where it can mass produce objects and it should be considered. But if this was to be manufactured with 3D printing, it would be prohibitively expensive and likely not yield the type of result that you want. Round objects like this are not really ideal for printing because if it was printed in this orientation bottom up, it would be very brittle and it would also not look very good. It might snap inside the bag. It has non-isotropic properties. From a material standpoint, it's not very good and it's not very attractive, especially when compared against wood. So if you have the new process available and you want to utilize it, you have to design for that process. Now, injection molding is restricted to this sort of design. You can't really get much more creative than this because the mold would be prohibitively expensive or would cause issues around shrinkage or other sorts of problems. So what would a golf tee look like if it was 3D printed? Well, let's assume we want to maximize strength along the axis of the tee or whatever object it is that you're making. What you would first want to do is with 3D printing, you want to maximize surface area. You want as much strength in the skin of the part as possible, which means you want to create something fat. But it is a stake. It has to go into the ground, so it has to be very easy to press into the ground, so it can't have a large cross-sectional area. You can't have a railroad spike going into the ground. It just doesn't work. It's uncomfortable and no one will want to use it. So you start out with an overall outer area that you want, and then you can cut it and rib it in order to make it reliable. And then of course you put a dish into the top of it so that it's able to hold the ball. And on first draft, you would end up with something like this. This is the optimum 3D printed golf tee. Notice how the outer ribs are very wide and as far out from the center of the tee as possible, but since it's cut out almost like a tent stake, you do not have a large usage of material and you do not have a large cross-sectional area, so it's very easy to press into the ground. And of course, we made the impression on the top just right to fit a golf ball. But what is optimal about this is that this can actually be printed in the optimal orientation for a 3D printer, which is on its side. That way, all of the layer lines are moving lengthwise of the axis so that this part can be reliable and strong and not necessarily break after every tee off. Now, that can be a preference. You have to understand what your users want. Do they prefer it to break off with minimal resistance at each tee off, or do they want their tees to be somewhat reusable and reliable? This will guide your engineering and your early design process of whether you want to go for very minimalist and disposable or slightly more durable and rugged. But if you wanted this to break off, then you could then change the orientation and print it in this way so that the layer lines are going this direction. That way these would break off. You could then print it in a biodegradable bioplastic so that it is the same as a traditional wooden tee, but it is not then taking up trees. This gives you a lot more design freedom, so if you're creating a product that requires iteration that you don't know for sure is correct, then you can iterate over time. To get to the original golf tee actually took about 15 to 20 tries by different inventors between 1890 and 1920. So if you are the inventor of whatever the object may be, the ability to change over time for very low cost but still get to mass production can be very, very attractive. But ultimately, it also comes down to cost. Was it useful to design for 3D printing or to just use a traditional molding or machining technique? Well, if this was to be produced with injection molding, you would of course have the cost of the mold. In order to make 10,000 of these overseas, where the molding and manufacturing costs are the lowest, the cost of the mold is actually about $3,000. That is about 30 cents a piece.
So 30 cents just for the tooling of one of these if you were producing your first 10,000. Now, of course, that could be amortized if you were producing 100,000 or a million, at which case it would then reduce to 3 cents and 0.3 cents, but it is still quite expensive. But at the 10,000 unit volume that we had this quoted, it actually cost about 50 cents a piece to have those first 10,000 produced. So basically 5,000 for the actual parts and 3,000 for the mold. So ultimately for your first 10,000, you are paying 80 cents for each one of these tees. If this tee was instead produced what it was intended for with 3D printing, it could be produced for somewhere under 25 cents down to 9 cents, and if you were going to hundreds of thousands, it could go even lower. But at the 10,000 unit volume, the cost for this part would be about 10 to 12 cents a piece, which is a full 1/8 of what it would be with injection molding, simply because you do not have the tooling. By the way, we also did not include the cost of warehousing and the cost of shipping. Those 10,000 units would have to be shipped across an ocean and then stored in a warehouse for the entire time, whereas the 3D printed versions would be able to be produced basically on demand in smaller batches so that you can figure out if people really want your product as you iterate up to what the perfect version would be. So is this the way that golf tees should go? Well, that's a question up to golfers, but this is a demonstration of the scale of 3D printing. If you design for the process and you create a product that uses that process in the appropriate way, which you have to do with any manufacturing process ever in existence. Machining is different from molding, is different from casting, is different from printing. But the advantages of printing are that you do not have maximum quantities. You're able to change your design rapidly, and you still have the same or better scale than traditional manufacturing processes. It allows you to create something that is truly unique and competitive and can stand apart from what has been around for 100 years. So when designing your next product, make sure that you consider the current state of the art and the technologies that are available, because you might just be able to create something completely original.
Layer lines are really easy to make disappear, but more fundamentally than that, they just don't matter and shouldn't be a concern at all. Everyone always points to 3D printed layer lines and say, those are terrible things. We have to figure out ways to get rid of those. But why are layer lines frowned upon? Well, in the early days of 3D printing, they were just garbage because garbage 3D printers would leave blobs and skips and yes, fat variations of layer lines all over the place. But today, 3D printed parts don't really have that problem. They just have a slightly linear texture that almost goes down to a linear matte on a really good 3D printed part. But even then, why do people still think that an injection molded part is better than the layer lines of a 3D printed part? Injection molded parts are not better. Injection molded parts are smooth because they are forced to be smooth. Injection molding is not allowed to have really any sort of texture whatsoever because it makes it unmoldable almost immediately. Textures are fantastically expensive and almost unachievable in any context inside of injection molding. So the idea that layer lines are an inferiority is just silly. They're just simply something that's different. 3D printed parts are allowed to have textures. They're allowed to have a diamond pattern or fuzz or matte finish or maybe full-on hair. All of that can be done with 3D printing and is absolutely impossible to do with injection molding. So it's very easy to say that 3D printing is a vastly superior process to molding because you can have absolute textures, which molding physically cannot do. So now that we've got that all cleared up, let's go ahead and look at how you actually apply these textures to a 3D printed part. In this context, we're going to talk about just FDM because that's what we do here at Slant 3D, mass production 3D printing. If you want to get textures onto a part, there's about 3 core ways that you can get it done. The best way is to do it inside of CAD. So you go into some software, whatever you happen to be using, and you create a small patch of pattern. And then you can replicate it and pattern it across the entire part. This is a little bit difficult to do because with more complex parts like curved surfaces, applying a pattern can be tough in a lot of programs. The other issue that you have is that there's a huge amount of computation to keep all of that pattern contained and controlled. So it's not very resource efficient or computationally efficient. But if you're making a final product, you should have a little bit of resources set aside in order to make that possible in order to create a good quality product. The way to design these patches is a whole kind of topic in and of itself, so we're not going to go too deep into it. But it's a way, if you have a generative software like OpenSCAD, then you can do all kinds of cool tricks to randomize it and make sure that it doesn't appear like a repeating pattern all the way through.
The other option is to just use the Cura Fuzzy feature. The Cura Fuzzy feature is wildly underutilized because it allows you to just basically create some noise on the outside of the part so that as the extruder nozzle is going by, all it does is wobble just a little bit to create a little bit of roughness. Or it could create a lot of roughness. You can have that wobble be as deep or as intermittent as you want it to be. Those settings inside of Cura are defined, and there's a help section that explains them in more detail, but it allows you to create basically a roughened surface on a part, so it can be really useful. The other option that's available is to actually use slicers like Idea Maker, where they allow you to import a black and white image, which is basically a height map, and then that height map is imprinted across the entire surface of the part. This can be a little difficult to do depending on the geometry of the part, but it's really not that bad. But it allows you to create very custom features with very low bandwidth, because you can create a 2D map from any sort of texture or download an image online and then imprint that onto your product. But it is less controllable because it's happening inside of a slicer. So the best option is CAD. The second best option is Idea Maker kind of height map references. And then the third best option is to use Cura because it's just limited to random noise. But ultimately, again, layer lines don't matter. Design your product for the texture and created by that process. Materials like wood are premium materials and it has layer lines. They do not matter. The problem is that many people are trying to 3D print injection molded designs. At that point, the layer lines do become an issue because the part is expected to be smooth. You are setting yourself up to fail. It's just the incorrect process. So, don't worry about layer lines. They are a feature of the process. They are not a bug. Use them, control them. You are able to have any texture you want with a 3D printed part where injection molding can't possibly have it.
This is a very difficult part to print because of this beak. Pieces that are like these upside down icicles here can be really tough to reliably print, partially because of this. They can't even be seen by slicers very often, so if you have many of them, you actually have to place support in here manually, doing something along these lines. But in order for that to be really reliable, you actually also have to spread support all over the place to actually cradle the piece. Right here you can see the support is barely holding on to it, and as this part is grown, it has a very narrow base that then goes up to a very top heavy type of piece before it reintegrates with the main body. So in order to make this reliable, you have to actually add in support all around to cradle and kind of nest it into a well-supported position. But that is a lot of work and doesn't necessarily guarantee that the part will print reliably. Because in order for these supports to be removed, you have to have horizontal spacing so that even though it is cradled all the way around, there is still some potential for shift and wobble as this beak part settles into its little nest before it comes back in the part, which can create these type of wobbles within the finished piece. So how do you get around this? Well, the ideal situation would be to have none of this support at all. Just clear it all out and have a nice flat beak down there. But you don't want to round off the beak. You don't want to make that a flat surface. So we went ahead and created a different way of doing it. And that different way is something like this. This is called a thumbtack. And I'm going to show you how we made them here. So within the standard model, there are several ways of getting this done. And a thumbtack is a very simple little CAD model that comes in here. This stem is 1 millimeter wide so that it is exactly 2 rounds of a 0.4 nozzle with a little bit of room there for space. But you import it here inside of something like 3D Builder or some other modeling software, and then you can move it right into position. And then this serves as a wide foundation for the beak there, or other narrow feature. And then when you are finished printing it, you can just break it right off. And it's very quick and easy to process, while still having a very reliable amount of support underneath it. Because since it's a nice wide platform, support automatically populates underneath it, and again, you have very little touch with the main beak, but a reliable support surface. So this is a really easy way to support these type of hanging points that would normally be quite difficult to print with auto-generated support. But that's just a standard thumbtack. And it's kind of boring because it can't always work in every situation. What if you had to reach in from the side, say for like this feather right here? It sticks out a little bit, it might need a little bit of support there, but you don't want this type of standard support where it grows up alongside the neck like this, because this can fall into your print while it's printing because it has no foundation on it. So for this type of situation, what you actually want to use is a more omnidirectional type support. So for this, we created the spherical one. The spherical one allows you to orient the Thumbtack basically any way that you want, so that it can reach in at a slight angle and really support whatever the feature is that you happen to be messing with. So here in this case, I'll have it reach into the side of the beak. But again, you can put it over there on that feather or any other sort of feature where you need to reach around. That traditional Thumbtack wouldn't work because it would embed in the part itself, because it can only be oriented vertically. But the spherical one still has a lot of surface area to be supported and actually cradled in, and you can reorient it to reach in from the side to support a part. But that took a lot of effort to reorient this and get it in the right spot. So if you're a little bit lazier and you don't even want to go to the effort of orienting that part, you can use the omnidirectional Thumbtack. And this one is actually the quickest and easiest, because all you have to do is kind of get it close to the main area. And since you have these multiple different spines sticking out, you align very quickly. And it's much less effort to kind of get set. You can see here, you want these cylinders to be pressed in as far as they can to the point, but still make sure they're behind or in the non-front facing area, so that when you snip them off with something like flesh cutters, there can be a little bit of a pockmark in the back there, because it's a lot like resin supports, where you snip it off and there's still a little divot or pimple in the back there, basically from where you removed the Thumbtack. But this is a nice, easy support, which still gives you the ability to have reach around and very quick way to orient. I put it back here underneath the beak so that it reduces the amount of support that is needed and actually blocks some of the support underneath the chin where it's not needed as much. The support now just goes up to underneath the Thumbtack and around the edges of the lips, but it doesn't use quite as much. But you can take this idea even further. Thumbtacks can be used to support these types of faces. So the underside of his chin here, if you were using a standard support, you get this type of support where you have a very wide base. And you can increase the density and lower the support angle so that it covers more, but ultimately the chin is still falling into the support. So you're gonna have some amount of vertical spacing there. If you don't want that fall off and the distortion that comes from it, you can use something like a comb. And a comb Thumbtack is actually quite useful, even though it can, again, leave quite a few pockmarks on your part, obviously. But what you do with this is you can line it up underneath the chin, like so. Get it right up underneath there. And maybe scale it down a little bit. Again, these are sized just right for 0.4 nozzles, so you don't want to scale them up or down too much. Otherwise, they'll become invisible to your slicer if you make them too small, depending on your nozzle size. But you shove it right up underneath the chin there. Make sure it follows the line of the chin, so it's along the lowest point of it. And then place it right in like that. And now you have 5 small sprues that have to be removed, rather than having the whole entire bottom of the chin being distorted from falling into the supports. So this can actually be quite useful, but it depends on your machine though. This isn't always the best option or better than standard supports, but it can be. If you have something like the arm of a character or like the fingertips of a character that you want to support, this is a way to have all 5 fingers at the end of these sprues, and then you just trim the nails of the fingers so that you get more detail from those fingers of that action figure you might be making. So this is a good, reliable support where there are multiple small hanging points or a long bridge area like this where you want to have the supports spaced off from, and you don't mind the pockmarks from this. Ultimately, again, using Thumbtacks is a lot like using the supports inside of resin prints, but for an FDM application. These supports are going to be available on our Patreon, which we have just gotten started. So if you want to go over there and download them, you totally can. And let us know if there's other types of features or other styles of these that you'd like to see. These are the ones that we use most often in production jobs and that kind of thing, because they are a really good way for supporting these type of narrow tapered features that generally don't work very well with auto-generated supports.
So there are all kinds of different vent covers that go on all kinds of different devices. It might be the cover of the fan on your computer, it might be the cover of a power supply or something inside of some piece of ducting or industrial equipment. But the way people design them right now hasn't really changed. They just make a pattern and they punch it through a plate and then they mount the plate on the duct to protect people from putting their fingers into the fan blades. But there's so much more that you can do with this feature. With 3D printing, you're able to create geometries and styles that are more manufacturable for the process, and also can give you new capabilities that had never been possible before. So in this video, we're gonna go through how to optimize the design of a fan cover so that number one, it is maximally manufacturable with mass production 3D printing, like what we do here at Slant 3D. But then we will also talk about applications and variations of this that can only be produced with 3D printing so that you can get features and benefits that were never before possible. So this is a fairly typical fan vent cover design, a bunch of holes popped through a single plate. And this is fine, traditionally is a very good way to do it, even though it creates a lot of pins inside of like a mold. But this is a very complex design to print for what is a fairly simple part. If you're using 3D printing, you want to avoid what are called islands. Basically, as a layer line goes up through here, you don't want to have to stop and move to a different place and then move to a different place. Each one of these cross sections of these holes looks like a bunch of little mountains, and that can introduce the possibility for errors and stringing and additional post-processing and all kinds of things that you just don't want to have to deal with, especially if this is exceptionally small, because then you're dealing with the detailed resolution of the nozzle that the part is being printed with. So this can turn into a very expensive way to do it. But a way to make it cheaper is to actually just use slots. And slots are a really good way of making a fan vent cover, except for the fact that if they are a certain distance, generally about 1 inch or longer, they have to have support. And again, the support is now introducing more post-processing. So you don't really get very much benefit because all of this stuff right here has to be pulled out of those slots, which is just a cumbersome process, and you gotta tear it out and you might damage your part or whatever else it happens to be there. But that extra support, that introduces the problem. When post-processing, if you have support materials, you can potentially damage the part, mar the part, cause issues that would cause the part to be rejected down the line. So while this is okay, you really only want to do kind of long rectangular slots. So like side vents and that kind of thing are best done with slots. And the reason for this is that it only has to print over here and then it only has to print over here, rather than with the traditional vent where it has to go to that hole, then go to that hole, then go to that hole, then go to that hole, which can create a lot more errors too, because this part could also be broken more readily because you have essentially created a perforated edge there. A much better option than traditional slots is to use still slots, but just make the minor modification of having them cut through the plate at an angle. By doing this, you now increase the cross-sectional area so you don't have that breaking issue that I just demonstrated there on that last one, but you also are able to get much longer slots with much less support. Some support is still necessary, but you can sometimes get past that by just putting small little support ribs in along those supports so that now you have that minimum bridging distance that we were talking about there. So you can basically put a rib down the middle of this and you could eliminate this little bit of support on the back here. But this support is very easy to remove because it has much less surface contact with the part, so it can almost be popped off the part as soon as it comes off the machine. But these angled slots are a really good way to build a vent that still has great airflow, that doesn't really mess with you in any sort of way. And it also has the side benefit of not having as much pass-through of like light. So if you're doing something with like RGB and you don't want light to shine through your fan shroud, these angled holes can enable that. But you can take that idea even further. We're using 3D printing. It doesn't have to shoot straight on through. Instead, you can actually have something curve through. This fan vent, you cannot see through it at all. And the reason for that is because these holes actually make an S-turn through the part. As you can see right here, each one of the holes takes a basically U-turn through the center of the piece so that you can now totally block any sort of light pass through. Now this design is a little bit cumbersome because you have to have a thicker plate than you normally would with like a traditional slot or hole, because in order to accommodate that curve in a reasonable sort of way, you have to have a fairly thick piece. Or you can make the hole smaller so that you can get more curvature in there without having the issues of intersecting with the other tubes that you're creating. But this is unmanufacturable with any other process. You cannot make a curve like this with any sort of other manufacturing process. And I'll take this a step further. What if you don't want to just make a U-turn through the part, but you actually want to create some kind of geometry that might actually catch dirt? You could create curves to where you kind of create a high velocity flow that sends dirt out into the edges of the vent, where you could have pockets that could catch it and collect it over time, and then when you reverse airflow, it blows that dirt back out. That's basically something like this, where you have a bunch of holes in the front, but then inside they actually make an S-turn and then come out the other end. Again, this makes a part that's very thick, but it's not that big of a deal because, again, you're trying to get some additional functionality of this. But when you're creating a lot of these snaky tubes inside of the part, you can start to run into intersection issues. If these tubes are not all exactly the same, if they're even more complex, and there's something like this, now you don't really get very much overlap with them in the same plane. But the way to get around that is to literally just slightly adjust the holes and stair step them so that you can overlap these tubes. And now you can have the same amount of density and the interior just looks like spaghetti because you've created so many holes and tubes overlapping and intertwining with each other that you don't have to worry about it. Another option, rather than just putting holes on a slightly stair-stepped cadence, is you can actually rotate the tube patterns inside of here. So this one would be flat, this one would be 90 degrees, this one would be 90 degrees from there, and then repeat that pattern around so that they overlap and combine a lot. So there's a number of ways to pack in a lot of distance inside of this part because, again, it's impossible to manufacture this any other way, but printing does not have a problem doing this type of complex geometry. And now these S-curves, as air flows through here, you could design it so that it has little pockets that would like catch dirt and create vortices so that this almost acts like a filter. You might want to be able to change the speed of the airflow so you can change the diameter of these holes. You can do some very complex engineering so that what was just a cover to keep people from putting their fingers in the fan is now a functional part of your device and can help to improve its longevity and improve its overall customer experience. All of that is enabled by this geometry. But there's all kinds of other things that you can do around this type of geometry. Sure, the S-curves are a really easy one that cannot be made any other way, but one that is a bit more mundane is just little vortex generators. So in this case, we created a grid of square holes, and you could pack these tighter if you wanted to. But each one of these square holes has little saw teeth on them. And what those do is as air is moving through this part, they create vortices within that air. So that might be useful to disturb the air more if this is on top of a heat sink, because chaotic air is better at exchanging heat than smooth laminar air. So churning it up as it's moving through the duct is a way better way of getting better heat exchange on the part so that you can pre-prep the air. So again, rather than just going from a few holes letting air through, you can go through a few holes that are actively stirring and churning it. And since these little teeth are designed in such a way, this could not be made any other way. You'd have to go through and make like a screw hole or something like that in order to create these types of ridges that would disturb the air in just the right way. And now you can also modify that geometry so that you can disturb it in a very engineered sort of way, which gives you a lot more capability about what you can do. So we've gone through all the different ways to have a flat plate with holes in it. You have so much more control now with 3D printing because you can create complex structures inside of that to either catch dirt, increase noise dampening, disturb the air and make it chaotic so that you have better heat exchange, or just block light so that you have control of how your product looks from the outside. But also, you can just make it more manufacturable than standard holes by just modifying the design a little bit by putting tapered holes through there. But there's one step even further we can go with this. All of this goes from one side of the plate to the other side of the plate, going from here to there, basically in a straight line. But again, we can do whatever we want. What if you don't want to pull air straight through? What if you want to pull from someplace else or not even have this front-facing pattern of holes showing up? Well, now you can do something like this. This is a round plate, but each one of these holes, and you could increase the density in the showing of this so that the fan could mount here on top, but then the holes themselves, the intake holes, or possibly the outtake holes, I don't know what you're trying to do, can be along the outer diameter so that now air comes in through here but then shoots out sideways. Now you always have to make sure that you're engineering your airflow appropriately, But again, this sort of geometry is really tough to do, and you get it for free with 3D printing. You could also re-engineer this so that it could be printed with like copper or some kind of thermally conductive filament, so that you can now mount this sort of design on top of what you're trying to exchange heat with, and you've got a fan right there, airflow going out the sideways, and you could create all kinds of grid patterns and a high surface contact area right here so that there's a good air exchange, and you can create a fantastic heat exchanger rather than simply an air direction management system of just a fan duct. So 3D printing enables all kinds of new capabilities because you can create geometries that were never possible before. And with mass production 3D printing, with large print farms like here at Slant 3D, you can actually produce those at scales into hundreds of thousands or even millions of parts. So whether it's a consumer device or an industrial product, you can get the parts that you need quickly and reliably, but now you can actually design for the process to get capabilities that are never possible before, or just make it more manufacturable if you just want to stay with a plate with holes in it. For that case, just make sure you're cutting the holes through at an angle.
So you want to 3D print a vertical rod, but you don't want it to split in half. Today in this video, we're going to talk about how to prevent that, not through slicer settings, but through actual design. Now this is a real common problem. People don't want their 3D printed parts to just break in half whenever you push along them. But how do you make them tougher? 3D printed parts break along the layer lines. No, they don't. 3D printed parts admittedly are weaker for the material because of the printed layer lines, but that just means you design around them. If you're gonna make an airplane out of wood, you're gonna design it a little bit differently than if you make it out of aluminum or cloth. There are different rules. So with 3D printing, if you wanna make a part a little bit stronger, what a lot of people do is they go into the slicer settings and they make the walls thicker. That's actually correct. For cantilevered beam, thicker walls are actually good because they put the material out where the actual compression and flexure is inside of the beam. As it bends, the top spreads and the bottom compresses. So having thicker walls puts more material up there where it matters. But the issue is now you're dependent on slicer settings. If you upload that file to a manufacturer to have produced, you're now transferring files and then they don't translate to the machine and everything just goes to heck. It's terrible. So what you want to do is you want to actually design your 3D model so that it has wall thickness where you need it. But you're going to say, hey Gabe, if you design a rod, well, you're not going to be able to control the wall thickness. Incorrect. You actually can control the wall thickness. And here's how I'm going to tell you. It's a little bit of a hack. What you do is you can actually embed a pattern, basically a bunch of holes around the outer part of the part. For example, with this rod, I just put a bunch of circles around the outer edge and cut holes through it. What I have now just done is thicken the walls of the entire part, because now there is more material around the outer edges because you're filling in the walls rather than simply having infill go out to the outer skin and then coming back. This is a way more reliable way to produce more material. Now, even though you can just design holes and put them around the outer edge, there's a few different ways that you want to go about it. We're going to post a video over on the Tangled Testing channel about the design of these different holes that will go into more detail about what the right way to do it is, because some are good, some are very bad. Now, the designs that we went through in this video are outer ripples, holes around the outer edge, kind of an arrow pattern around the outer edge, and what we call ribs, which are just slots along the outer edge. All of these induce the slicer to create more material out in the outer edges. But the trick with all of these is that they're exceptionally thin. Each one of these features is basically 0.2 millimeters wide. And the reason for this is that is large enough for most slicers to identify it, but small enough to where when they print along it, the walls basically fuse together. Because the last thing you want are the walls to be spread out, because if you do a ripple around the outer side and it prints spread apart as two separate walls, then all you did was create a sleeve around a center core, which actually makes it weaker. So you make these features very, very small so that they just make more material go there, but they don't actually split the part across or create any sort of stress concentrations. Of the ones that we used, the ribs was actually the best. When we ran our test with a simple cylinder that just had a simple infill and a simple 1 millimeter wall, it was almost a third as strong as the ribbed design that we did. If you uploaded it to our API, the ribbed version would use more material and be a little bit more expensive, but it would be so much stronger, and you would not be reliant on the slicer settings to create that more strength. You wouldn't have to say, oh, I need the wall thickness to be 4 millimeters or something like that. You simply design in very thin features that are 4 millimeters thick, and they induce that wall. Now, if you get fancier with this geometry, what you're doing is you're now creating a 3D printed rod inside of a 3D printed part. So you are able to build up strength across the part without having to add additional features or worry about the homogeneity of it. Now, of course, the easiest answer to all of this is just do a solid infill part. But barring that, when you want lightweighting but controlled strength in particular areas, what you can do is you can introduce these microstructures, which then cause the slicer to put more material where you want it inside of a part, so that when you want to print a part, it doesn't break anymore. So first of all, let me just say that a birdhouse is a terrible product, but with any terrible product that is totally commoditized to where you can buy it for a nickel, there's an opportunity to create a new product that is way more compelling and way more interesting. And with 3D printing, that is now possible. So through this video, we're going to talk about how you would design a birdhouse so that it could be mass produced with 3D printing, and how you can create something way more interesting than what is currently out there. So it is possible to produce a birdhouse with mass production 3D printing. The scale is there, but how can you actually utilize it? Well, let's go ahead and just look at the traditional birdhouse, the normal design that's a box and a roof that everyone has seen hanging around in their grandmother's yard someplace. This design is not very manufacturable with 3D printing. It was designed to be put together with boards and balsa wood and sold for a nickel. But if it was a design that you wanted to make with 3D printing, there are some optimizations that can be made here. First of all, you don't want to print it in its normal orientation. You have to put support up underneath the eaves and inside of the hole and underneath the peg, and this is all adds to the cost of the part so that it loses the scale that 3D printing can provide. So the first thing that you would want to do is actually probably flip it over upside down. Now it has a pointed roof, so that's not the greatest thing to do, but so what you would want to do is actually crop the top of that roof just a little bit so that it has about a 1/4 inch wide strip that can be printed on, and now the entire house can be printed upside down with virtually no support at all. And all you had to do is make a very minor modification that doesn't majorly change the aesthetic of the birdhouse. And if you carry that through the entire design, it's not a big issue. Now, the other issue though you have now is the landing peg, and that type of feature, there's a couple ways of getting it done. The most obvious would be to just drill a hole in the side of the thing and have that printed with a hole and then have somebody insert a peg after the birdhouse is done. But that's not something you really want to do in mass production either, because it adds another step to the production process where human hands have to touch it, and that's something you want to eliminate. It also reduces the opportunity to do print on demand, which 3D printing can really enable, so that you don't have large inventory stocks. So the best thing to do with that little landing peg would be to design it with a chamfer on the bottom. But ultimately, support underneath that peg is not the end of the world. There's not a lot of it, and it takes basically a flick to get it knocked off. You have to make sure that the process is set up well to make sure that there's no sort of defects in the front from that support being there, but that's pretty addressable, and any competent manufacturer should be able to do that for you. But that is modifying an existing design. You're not differentiating yourself from anybody else. Your 3D printed birdhouse will look like every other 3D printed birdhouse and have basically no advantages. So let's go ahead and take advantage of the process that you're using. 3D printing can create some really interesting characteristics. First of which is, rather than a flat board in the back, how about we curve that? Now you can mount it to a telephone pole, to a tree, to a branch, to some kind of rounded house, anything that you want to, which wasn't traditionally possible before, because those flat board birdhouses would always have to be mounted straight against and try to be flush, but never could be. You would be able to make a birdhouse that can actually fit flush against the round object that it's mounted to. You can also put a hole through the top just like any traditional birdhouse that would be perfectly strong. The fact that it's 3D printed would not hurt that at all. It would last for years just fine. But that's not that big of a step. You still have a birdhouse as everybody always imagines it. It's not very interesting. And if you were really optimizing it all the way, what you would do is actually turn it into an A-frame. And the only difference on little trick that you would need to know on this is to put the little landing dowel flat flush against the base of the birdhouse itself. That way there's no support underneath it. It prints as part of the first layer. Make sure that you round it out. And this birdhouse is actually really unique because it's able to come off of a printer straight into a box. So it enables you to do print on demand. Again, eliminating inventory, eliminating a ton of shipping, and ultimately increasing your margins because you don't have excess options and you can just focus on creating large numbers of designs of birdhouses. You could give it different trim, different designs. You could give it shingles of different designs to match in with different areas, and you could print it in different colors. This is actually a really good baseline and very manufacturable. And you could make 1,000 of them, or you can make them just as people order them and plug your website into something like the Slant 3D API. But that is still a birdhouse that is all flat sides. It could be made out of wood. So if you're using 3D printing, why not take full advantage of it and create something really, really unique? Well, first of all, one of the first unique capabilities of printing that I really want to highlight here is the fact that it can make thick walls. Most birdhouses are not made out of plastic because they would have to be thin, which means that the birds inside are either going to be very hot or very cold because there's no insulation, and thick wood has always provided insulation, even after the birds built their nests. But 3D printing is actually able to make really thick walls with infill inside, so it's like traditional foam insulation, but way more efficient than traditional plastic. So you can make a thick-walled birdhouse that protects the residents quite well, just the same way wood birdhouses would. So let's take this a step further. You have 3D printing, you're able to create any geometry you want. Well, what is most different from a square box birdhouse? A round one. Why not make something spherical, make something bobular? You can make a perfect sphere that looks like the Death Star and put a little hole in the front of it and let the birds live inside of that. You have so much more creativity than what has ever been possible before. And you can even see examples of this out in the world. Inside of the 3D printing community, people have made birdhouses and designs that are completely unique and far more detailed than could ever be manufactured traditionally, but can now be manufactured for the same cost as the old balsa wood models. So use that. Inside, you could put internal furniture and have some fun. If you were really going into the product design, you might want to make a birdhouse that's like IoT enabled with a small webcam on it so that you can see inside with the birds, which is really easy to manufacture with 3D printing. The possibilities get so much more open. And if you were running like a store that focuses on birdhouses, you can now create hundreds, if not thousands, of versions of the same birdhouse without having to do tooling for each one of those versions. So it gives you tremendous advantages that you never had before because you're able to produce stuff on demand or at a smaller scale until you find the thing that works, and then you can really ramp up using large print farms like Slant 3D that has hundreds to thousands of machines to really mass produce the product if somebody like Walmart comes a-calling. So we went ahead and did this. What would be the impossible design that doesn't really come out very often? Well, it turns out one of the most basic designs is wood. What if you want to make a birdhouse that you don't really have to look at, that isn't loud and ostentatious? You can make a birdhouse that looks like the trunk of the tree, and you can make it merge and look like some wart or a knothole or anything else. And something like this is basically impossible to manufacture any other way because it has really thick walls and a complex texture. And we added even a secondary texture to it. And we made it 2 stories so that you can have a couple families inside of there. And it doesn't stick out in your yard as a large, ugly piece of lawn furniture that fades over time. You mount it to the side of the tree and you can move on with life. So this is a really nifty design that was never possible before. And now it's something that you could add to your web store and get early access and early feedback without having to order thousands of these, basically just uploading the model. Now, a few notes about this for people wanting to manufacture outdoor devices. A birdhouse is something that is exposed to weather and sun. What are the materials that you would want to use for something like this? Quite frankly, we would recommend most likely PLA, because number one, PLA will last for extended periods of time, both outside and in the sun. If you want it to make sure that it doesn't fade over time, literally all you have to do is do a clear coat of UV protectant, and you no longer have to deal with UV resistance, so that it will hold its color for a long period of time. An object like this too, we would probably recommend some kind of post painting to give it like some green moss and that kind of thing, so that it really blends in with the natural area of your tree. Or you can buy mixed and filled filaments that just have a more natural looking color and blend to them. Almost like a dirty, almost reject filament that goes from gray to black back and forth, just like the bark of an aspen tree. Or if you are an artisan yourself and you're wanting to create really premium birdhouses, you could use like a printed on-demand app like what we have, buy the part for it, and then do your artwork on it, and then you don't have to deal with the 3D printing itself. So there's a lot of directions to go there. But ultimately, the birdhouse is something that today is a very simple device that is commoditized, and it's not something that you would want to make. But since you have this new manufacturing technology, it is an example of a product that can be innovated within, because you can create capabilities that were never possible before and business models that were never possible before. 10 years ago, if you wanted to make a birdhouse, you would have to get molds or buy some lumber yard in China and have them produce 1,000 of these things, and then you store them for forever and hope people buy all your birdhouses. Now, all you have to do is create a design, make sure that you're making it manufacturable, and and then upload that design with some photos of the final printed product when it comes out. And then when somebody makes an order, that product can be printed and shipped directly to that customer, and you never have to deal with upfront cost of tooling and machinery and that kind of thing. And you're able to create impossible geometries with great insulation, so they protect the denizens very well and can blend in a way that was never possible before, or stick out in a way that was never possible before. You can create capabilities that had never existed and could never be made before. So there's now a chance to make a common and basic product way more exceptional and create new companies around it. So there are a lot of different ways of sticking two parts together. You can screw them together, you can glue them together, or you can design in fasteners themselves into the parts so that they snap together. But in this video, we're gonna go through some basic connectors to join larger 3D printed parts together if you're trying to make a larger one out of a few smaller ones. So the first and very simplest way of doing this is with a peg and hole, but most people would generally go to a round peg and a round hole. You don't want to do this. A round hole will sag and be dimensionally off a little bit to where you don't have a good grip, and a round peg can't really be printed in a horizontal orientation to where it can be strong. You don't want the pegs to be in plane with the layers because they'll just snap off. So instead, to avoid all of these problems, take a square peg and make it diagonal. Turn it sideways, and now you have a diamond hole and a diamond peg. This diamond hole makes sure that there's no overhang areas, so it's very dimensionally precise, and you're able to print the square peg horizontally on the print bed so that it's as strong as it would ever need to be to hold the two parts together. But it's only held together by the actual friction of the parts themselves. Now the square peg is fine, but what if you want something that's kind of low profile? Maybe you have a really thin part or you're trying to peg around the outer edge. You don't want to do small little diamond holes, and you want something a little bit more universal and robust. Well, in this case, go ahead and do like a slab and slot. This is really easy to do, and you're able to create something really reliable. Just make sure that you are tapering the ends of whatever the peg is that you're putting inside of there, the slab that we're going to shove inside of there. Taper it off, round it off so that it slides in and then gets tighter as it goes in, because it can connect with the walls of the part even better. And this is how you can create a really low profile connecting option. Now these are both fine, but pegs have an issue. Pegs can have a really big gap in between, because as you're pressing a part together, if you have a really broad face, it can flex because it's plastic. And if it flexes and you press the two things together, and on the outer edges they come together, but then the flex pops them back loose a little bit. So you end up with a bigger gap that you can't really overcome without making the part just stiffer so it can't flex as much, but that increases cost. You don't want to do that. So you need something that is able to press together easily, but then hold and retain in a precise position, and even stronger than what you would normally have. There's a couple of options for this one. The first one we're going to look at is basically just a little S bracket. You design in a hole into the part to where you can slide in the side bracket and then slide it into a slot to where it will snap into a small slot inside of the part. This is a really good way of doing it. It is symmetric, so you can replicate that hole all throughout your part, and you can change the size of the connector piece in order to increase the amount of compression on there. This is a really good way of combining two pieces, and it's a very simple piece. Of course, make sure you round it all out so that it has nice, easy corners and is easy to print, but you can make this as thick as you want to make it stronger, but this is a very simple way to have a very precise joining position. Another way of doing this that's a little bit more complex and a little bit less reliable is to use basically snap fits, where you design a double-sided C-clamp to where you can press it into a slot and then it slots into a couple of holes inside of the part. This is a really good way of doing it. It's very easy, it's very intuitive, it doesn't require a lot of training like the S one kind of does. But it can be less robust because it has to be able to flex. The S is a piece of hardware being shoved into a piece of hardware. This is a mechanism, and as a mechanism, it might need to be designed just right so that it can squeeze and have enough pressure, and the latches have to contact just right. It can be tougher because you're pressing things together again rather than squeezing them together to where you can kind of do an over-centered clamp thing. So of all of these options, the peg is the easiest. If you're going to use some glue, just go ahead and use a peg. Use the slab if you are going around a thin profile of a small part. You can use the S if you want it as strong as possible and still very concise and tight. And you can use the snap fit if you want something really fast and easy that doesn't require any pressure and still has a pretty tight and reliable fit. But again, these are not the only ways of combining parts. There are tons of ways, and we've done another video about how to actually embed these sorts of features into the parts themselves so you're not printing this third insert peg that you have to use on all these parts and pieces.
So we were recently contacted by a perfume brand who wanted to create custom retail and final packaging for their perfume. And the reason they reached out to us is that the packaging of standard types of perfumes is very often almost as expensive, if not more expensive, than the actual material itself. So in creating the experience for this type of a product, you invest very heavily to create something that is unique and stands out from everything else. So very often just a cardboard box or standard plastic packaging just won't do it. The bottle itself and the experience of opening it up and storing it has to be very carefully tailored, as well as the presentation of it inside of a store. So they reached out to us because 3D printing could create something that was fully unique and different from what anybody else had ever done with perfume. So the first place we started with this was with actually the retail presentation. We first started with how to display the bottle itself, and we started with these very simple kind of shapes that had cutouts in them in order to display the bottle in a very unique kind of situation. But of course, black is a very harsh color, not very often very effeminate, so it's not a color that was used. It could be used for like men's cologne, but it wasn't that good, and it disappears and the detail disappears. So we started exploring kind of more organic shapes around stone and gold and kind of metallic-y colors. And this one was fine and actually tested pretty darn well because it looks like the bottle is embedded in rock. And we tried different colors around silver and some reds and that kind of a thing. But the overall shape of this wasn't quite right. So they ended up going a slightly different direction. But this is a great way of displaying a piece of retail merchandise because you're able to create something that was never possible before. This type of case or stand for a piece of retail is very difficult to manufacture and very difficult to do so affordably. But then the challenge that we had with this was actually the fact that since it was so complex, the layer lines start to appear on top of the rocks here because they shallow out. So we would generally want to do a sharper sort of crystal rather than simple rounded stones or the tops there. Something really sharp and jagged, something like this is a better option in that context because you're able to ensure that it doesn't look 3D printed at all. And in fact, this does not. It looks like something that was sculpted and carved rather than something that was molded or plastic. But ultimately, we ran through a number of different ways of displaying the bottle. This is something that would appear inside the retail store in order to show off and be kind of the hero image for the product. But eventually you have to put that bottle into packaging, and that is where we came up with this. This is the packaging for the velour perfume. And you can see the outer side of it is a textured surface, almost looks like fabric or felt, even though it is in fact plastic. The logo itself is inset and it is smooth in order to make sure that it pops out from the pearlescent white box that we've got here. And then inside, you went with a metallic copper color where the bottle is firmly displayed inside of there. And in fact, we wanted to mess with the fit a little bit more so that the sound doesn't sound plasticky like that either. We would generally recommend using something like felt or some other sort of fabric material around the outside of the interior part in order to catch it, much like a jewelry box that you would run into or like a ring box where everything is velvet and smooth and doesn't have that grind as it's pulled out. But it was still early in the stages of the design here for this one. But you can see that the bottle is now perfectly displayed in a nice little slot there. It could be pulled out, but it looks like a jewel embedded in a bunch of metal, as if you had just mined this crystal from the rock itself. And at the same time, it's inside of this nice pearl outer case that is elegant and simple. Now, one of the tricks that we did with this is that you do not want to print these upside down or anything silly like that because you end up getting the bed texture on it. So this was printed vertical just like this, and then this was printed upside down on the printer like this. And that allowed us to create this angled upper surface right here, and equally an angled upper surface inside of this box itself. That way they align like this, and you do not have to worry about any sort of overhang sagging, so that the fit, when it goes together, is perfect and flush all the way through, and you don't have to be concerned about manufacturing difficulty there. All the edges are beveled and rounded slightly. And again, the interior also has that same slightly roughened texture as if it was sanded, but it also gives it a very naturalistic sort of appearance that you can't really get with other types of manufacturing. It's a piece of noise that we add inside of the slicing. So whether it is just the retail display itself or the actual final retail packaging, you can create really fantastic pieces for premium products with 3D printing that were never able to be created before in the same way and with the same type of features until now. So springs are pretty useful. So in this video, we're going to go through and discuss how to design different types of springs and many of the common types of springs that can be designed and mass-produced with 3D printing. So we're going to go over several different types of springs, from spiral to torsional to extension type of springs. And 3D printed springs have to be very different from any other types of springs. The one spring that we will never make is a coil spring. Coil springs don't work for 3D printing because you are not able to have a continuous, cohesive kind of path in order to create a coil spring. You would end up having the layer line split if you printed it vertically, and if you print it sideways, well, you actually can do that, but it's not really a coil spring. It's not combined in the way that you would normally do it. If you want to create an extension spring, a standard type of coil spring function, what you do is that instead of doing a spiral, you just look at that spiral from the top and create that profile. And now you have a very simple flat pack extension spring. These types of extension springs are really useful if you want to have some sort of resistance on a switch or a button or whatever it happens to be, or if you need something that just gives really easily right there. All it is a simple curved path going back and forth, and you can change how that path works. Most of the time, the easiest way to do it is just kind of design a set of pattern slots and make sure you round out the edges. Do make sure you round out the edges. Sometimes people make these springs like perfectly square, but the problem with that is that you then have a stress concentration at those corners. Make sure it's round. Now, do these springs compare to regular circular extension springs? Well, quite frankly, they're not quite as good because regular circular extension springs are phenomenally efficient because they distribute the force perfectly continuously all the way around that coil. Whereas with these types of extension springs, the force is concentrated at the rotation points. So if this breaks, it's going to break right there just below the curve where this thing is bending. Now, as far as the actual design of these, what you can do if you really want to engineer these things is you are looking at the part of the stress strain diagram of a material before it goes into permanent deformation. That is what this is doing. This is a bunch of small rods bending, basically. So you can design this spring based on the thickness of that rod and the numbers of them in order to determine how much extension and how much force you want. But that's probably a little bit too deep for this video generally. The easiest way to do it is make these things thicker. If you want it to be stiffer, make them thinner down to 1 millimeter if you want them to be softer. And one other way of making it a little bit tougher is to go from a very flat design to a very thick design, where now you have a lot more material which is able to bend, so you can get a lot more resistance than what you would normally have. So those are the traditional kind of extension springs. But there's a lot of ways of rejiggering this because 3D printing lets you create weird and interesting geometries that generally don't come up very often. So what if you want just like a stabilizer ring? This is something where you would like mount something to a wall or to a brick, and then you would have the actual item mounted on the inside. It might be some sort of transfer or transmission, or just something that you want to vibrationally stabilize. These types of springs can stabilize in this direction because they're basically a set of extension springs around the outer side, or it can serve as like a trampoline where you can mount something up there and then this gives and gives slack in that way, kind of like a membrane. This is a very useful type of spring for push buttons and that kind of stuff. If you had a box and you wanted to have a push button on the inside, you can design this type of spring so that this becomes the big red power button for the box and then depresses whatever is underneath. So that's kind of the utility of these types of springs. Now we start getting into other types of very traditional types of springs. Leaf springs. Leaf springs are another sort of mounting, stabilizing sort of spring where you want something to stay in position for the most part with a little bit of compliance. These can both compress and also slide side to side. They can be very useful because with leaf springs, you're able to create items where you want kind of tight control. You can create effectively like parallel mechanisms with leaf springs so that you can keep the orientation of a part in the same place as you move and depress it around. So leaf springs are useful for creating kind of controlled mechanisms while still having all the vibration, dampening, bending, and return that you want from traditional types of springs. However, these can be really finicky. You only have 1 or 2 bands of material to work with, so changing their strength is generally only through thickening something up.
And now these can be really useful because a leaf spring is basically the material itself flexing by itself. So a leaf spring can be anything from a flat printed plate that's then bolted into place to these nicely little designed rings that again are printed in plane. This is the most important thing with 3D printed springs. All of the force has to be in plane along the layer lines to make sure that you don't have something snapping off. If you try to print this spring at an angle, you just ruined the spring. It has way less return. And this is actually the type of issue that we ran into with our snap fit video, where we discussed that design problem. Snap fits are effectively springs with little nubs at the top of it all. So we went through that a little bit over there. I recommend checking it out. But leaf springs are terribly useful. And then last, but certainly not least, spiral springs. These springs are very often, you see these in clocks. These are great for storing energy. You can twist them up and then return it, so you can make toys, all kinds of useful things there. If you really want to just have a fidget spinner, you can do those kind of things, but those aren't really what they're intended for. Coil springs are generally energy storage devices. As compared to all the other ones, which are stabilizers, vibration deadening, that kind of stuff, coil springs are really about storing up energy because you have all these coils very densely packed. And again, you can make these springs thicker the way we did with this so that you can store up a lot more energy inside of these. So wind up toys, mechanisms for lids, all those types of things can be done with coil springs. It's a very tight, compact way of getting twisting motion into a space. You can make the hole feed thicker in order to make it much stiffer on the outside if you're just wanting a spring for like opening a lid and then closing a lid. Or you can make it thinner, have many more coils, and then make it thicker in this direction in order to create much more energy storage. But those are the primary types of springs that you will see with 3D printing. One side benefit of almost all of them is that since they are printed flat, many of them can be printed within a print themselves. So if you have some plastic part that has been printed like this, you can continue printing the spring inside of the part and fully encase it in a way that you cannot with other processes. So you're effectively assembling a machine as it's being actually manufactured. So you can have springs embedded inside a system so that you now have a deadening, dampening feature inside of the part that otherwise would have had to be installed or built in 3 pieces or something like that. 3D printing lets you grow up an entire part with springs and mechanisms inside of it, which is pretty darn cool and something that has never been possible for with traditional manufacturing. So you're able to create new types of products that are way more competitive than anything that has come before, because nothing before could make this type of stuff.
Hello everyone, and welcome to this episode of Design for Mass Production Printing. In this episode, we're going to go through how to actually design holes. A simple feature, and yet at the same time, very easy to mess up if you don't know what you're doing. So let's start with the very basics. Let's look at a hole that is punched through the side of a part, just like so. This hole you can see, it catted up, it is just a generic hole. There is no modification to it at all. But if you look very closely at it, you can actually see that there's a little bit of rippling right there. The reason for this is that these are perfect corners, which don't exist in real life. The tool head is limited to the diameter of the tool, and you're limited to the motion of the machine. So you can actually cause a defect and deformation of this hole by just punching it through natively. The correct way to do it is actually to go ahead and add some small fillets around the hole. This rounds the outer edges and gives the tool path a smoother bit of motion so that it's able to create a much cleaner hole. But now if you look at this hole that is now punched through the side of this part, you'll notice that the top is actually kind of sagging. And while that's not the end of the world in most applications, especially if you're making an electrical enclosure or some piece of industrial hardware, it's not always ideal if you want something super precision, because it can cause resistance to the screw to where you have to basically manually screw the screw in all the way rather than just punching it through a through hole that's supposed to be a loose fit. The way to get around that is to actually add a point to the top of the hole. This small point makes sure that there's no way for the layers to sag in any sort of way, but still maintains the primary outer profile of the hole so that it can reliably constrain the outer edge of the screw that you're putting inside of here, or the dowel, or whatever happens to be going in there. So these little points are very easy to add and a very quick addition that can help improve the sagging and kind of the ovality of the hole. Because when the hole is 3D printed, the upper surface is like a flat line straight across, which means it can cause a little bit of sag as the layers are deposited. And if you look very, very closely here on this, you can kind of see that. Basically, the layers layers are built up, and then they have to cross what is essentially a bridge, which causes a little bit of deformation in the top of the hole, and those points get rid of it. Now, side holes are fairly simple, but what about top holes? Well, traditionally, people would just punch a hole straight on through. But the problem is when you print a hole like that, you end up with this kind of a mess. And the reason for that is that the hole is an unsupported area. As the first parts of the layers are going side to side, they come out there and then they hit the hole and then they go back to the outer edge. Basically coming from here, going in, and then coming back out, going in, coming back out. So they have nothing to actually clasp onto, which can cause issues with how the part is printed, and you end up with these sort of stranding pieces that stick out of the hole and either need to be removed or are kind of foreign objects within your assembly if you allow people to just punch through it. And you would have to generally support this hole from underneath in order to make sure that that is not an issue. Now, support can add a lot of extra post-processing because it has to be plucked out at the bottom, so one way of getting around it is to use a sacrificial layer. Now, this is only a mild improvement from the previous because you still have post-processing. You have to remove all of this stranding that is in here in order to punch through here, or you can take the rod and shove it straight on through. But now you have the additional problem of not only having the foreign objects that can break loose inside of there if this stranding goes loose into your part, but you also have the delamination on the bottom layer itself, because if you punch through on this, then you can potentially just tear out that whole bottom layer and kind of compromise your part. So sacrificial layering is generally fine for very small holes that are not super strength focused, but for larger holes, they generally have to be supported. The best way to make this large hole would be to have it supported from underneath so that it can grow up, and then the outer profile is crisp and clear. And the support can actually be removed more quickly than this stranding. Now, if you're looking at a non-through hole, there's a couple of ways to do this. And the main thing to be concerned about is the actual tolerance of the hole itself. 3D printing has shrinkage and side material extrusion that you sometimes have to compensate for. So you don't want to just punch the hole straight in. Again, you want to make sure to fillet the top. And in order to make sure that it takes the part easily, very often it's best to also chamfer the top of the hole just a little bit as well, so that the part is able to get started, but then is able to shove in and tighten as the hole gets narrower and narrower. That way you have kind of the finding feature at the top of the hole, which creates a very good fit without having to worry about the tolerance of the hole. However, sometimes you need a little bit more flexibility or a tighter tolerance. You want the hole to be a very strong press fit. But then you still don't want to plunge a hole straight into the material because you'll have side-to-side variation. The best way to go about that is to design the hole basically at true diameter and then add relief features on the outer side, which allow the part and the walls themselves to spread and split so that the piece can press in there very firmly, but still have some release features so that the hole doesn't resist it and doesn't get stripped or deformed in some kind of a way. It's some sort of permanent deformation. So these little relief features are a very easy thing to add, but you can actually increase these and basically rotate them all the way around to create what are called crush ribs. Crush ribs are parts that are meant to be deformed rather than having a solid wall where it has to basically stretch the material. These features are kind of sacrificial so that when the part is pressed into them, it kind of strips them away, presses them away, and you have a perfect press fit. This is an easy way to get to that perfect press fit because each one of these things can be made as thick or as thin as you want so that it is easier and harder to actually essentially strip them out, but you can get a stronger grip on the part when it is pressed in there. These are basically a one-use type of a hole, so you install it and then you're done. These types of relief features also provide really good options for glue, because if you're making a hole, you need someplace for the glue to go once you put it in there. So these types of ribbons allow you to really strongly adhere a part together if there is some piece to be inserted into here. But very lastly, there is an advanced feature of hole that it depends on the application that you're doing. If you want something to be removable and have a long life, then you might use grip fins. Grip fins are basically a small flexible feature that goes around the outer edge of the hole and allows the hole to change in shape and to bend. This is a really good way to have a hole that grips with constant grip force. Rather than being forced in and being sucked in or glued in, these are meant to just hold whatever rod is inserted in there at a constant force. So when we press this rod into there, It is fairly loose and easy, but it will always grab it at the exact same force as before. They essentially act as springs compressing the rod that's inserted inside of there. So this hole is often used for disassemblable parts or sort of like tool jigs and that kind of thing, to where you want to be able to use this hole over and over again, but you still want it to be able to grip with some force. And you can change the thickness of the fins and how much tolerance they have against the hole. Like if this is a 12 millimeter rod, you might make the actual inner diameter of the grip fins like 11 millimeters so that they grip it more tightly. But that is almost a whole video in and of itself. So hopefully that was useful to you, and now you know how to make holes down through the top of a part, as well as how to make holes down through the side of the part.
So one of the enormous advantages of mass production 3D printing is that you're able to make thick, chunky parts that could never be manufactured before because material properties wouldn't allow it through material shrinkage or just overall cost of the part, because there'd be too much material wasted or thrown away if you were to make something big and chunky. But in order to go through and show how this is now possible with 3D printing, we're going to show you some handles that you can mount up anywhere in your home with command strips. So before we get to the actual handles that you can mount around your home, let's actually start with something super basic. And this is actually just a handle for a bucket. This is a grip. It's a simple device that is meant to go over a wire or some other sort so that you can actually get a grip on it. While this is a trivial part, it is a cylinder with a curved slot through the middle. It is actually very difficult to manufacture traditionally because you would have to have a large brick of material that would then be carved away. Or if you were molding it, you actually couldn't because it's so thick that you would have shrinkage and deformation of the surface of the part. But since this part is 3D printed, the interior is basically hollow, so there's really not that much more material being used. You're still able to create a complex inner shape with that curve so that you can put the top of a bucket into this thing and not have to worry about it popping out as you go along. But it is actually a part that is still strong and durable. And then on top of that, we also applied a nice grippy surface to it so that it is comfortable to hold. This part, though trivial to look at initially, is actually very difficult to manufacture the old ways because it would actually be pretty expensive to put a slot into a big old dowel. But that is just the basics. So let's actually move on to something a little closer to home for everybody. Let's go ahead and look at a standard handle. So this handle would be like the grip that you would see on like an old fridge or something along those lines. The way we've designed it is the way we design many industrial types of parts, is you have it print on its side so that all the layer lines are in plane so that it's super strong and as strong as any other part would be made. But we were actually able to make it very thick and chunky. There is a lot of surface area on this part, which again contributes to the strength of it. When you have the strength in the skin, which is where most stresses are, you're able to create something really reliable. So this part is able to hold quite a bit. In fact, using this in practice, the failure point would actually be the point of adhesion. We designed this to be connected with command strips so that you can mount it up onto whatever you need a handle on. It might be the front of a fridge, it might be some box or something else that you just want to have a handle on, maybe a door or closet door or anything else. However you want to mount it, you can. Now, the things we did do in order to design this a little bit better is, since it is mounted via these command strips, we went ahead and gave it a forward positioning kind of foot right there so that they're mounted forward, so the point of rotation is right there and you don't have leverage on the back that would cause them to peel up more easily. It's almost more of a direct pull rather than a twist. You can also notice that the sides of it are all chamfered. This allows the first layer to go down and to be very symmetric with the top layer. You don't have to worry about elephant footing or the first layer being odd or different. In addition, a nice little subtle piece that we were able to do is actually adding small indents to the back of this part that allow these command strips to match almost flush, and we would be able to change the depth of those. So based on the depth of whatever your adhesion device is, this appears to mount flush even though there is room for whatever the mounting system is. But again, this piece right here, if this was made with old manufacturing, it would be machined from a block of solid plastic. But this way, it's actually super lightweight. It has no heft to it at all. It literally weighs maybe a few dozen grams because this interior is entirely hollow, but you still have all of the structure because it's honeycombed inside of there. But now this handle could actually be mass produced without using a lot of raw materials and without being exceptionally expensive. Moving on from that a little bit further, this is kind of an evolution of the previous handle. This is a top grip style handle where you mount it up right there and then you're able to grab it like this or flip it around sideways, whatever it happens to be. This is a nice kind of barn door style handle. And again, chamfers all the way around the outer edges. It's printed like this so that it's as strong as it can be in the plane. You have a little bit of an issue with the mounting points right here because you do have quite a bit of torsion, whereas with that older one, you had the mounting points kind of moved forward. So that's something to be aware of if you're ever working with this type of hardware. But again, we really liked this shape, just the overall simple L shape right there. It's smooth, it's simple, and it's never really been able to be made before because what would have to happen is there'd have to be a big old giant cutout out the back of it that is full of ribs so that it still has structure, but it doesn't actually have a good grip point. And back in here would be all ribbed out, or there'd be a big old slot through the side or something silly like that. But now you can produce thousands of these without a mold, without tooling, without a ton of waste. This comes off of a machine fully complete because you have the chamfers on the bottom. There is no support. Everything is enclosed. There's nothing really special about this. This type of hardware is a fantastic example of how to design accessories and add-ons and upgrades that look great, work great, and are something that could never exist before. Now, going on from that, there's a little bit of a twist of one here, and it's this. It looks like a brick, but that's kind of the intention. This is a side-mounted handle to where you can put it on the side of some box just like this, and then you have a grip up underneath, and you can see that grip right there. And again, it is a command strip style handle where again, we have those indents and that kind of thing. We also use the texture on the outside, so there's no way to really even tell that this was 3D printed. It is a very simple shape, but again, very chunky, very durable. And since it's such a low profile, it doesn't have a lot of torsion on the actual mount points. So you could actually mount this up with command strips and it's still very, very strong. But again, you could design it to have mount holes on there, and look at our other videos talking about those types of things so that you could actually screw this onto the side of some box or feature or product that you happen to be using. We liked the peel and stick because everybody has command strips inside of their home, so they're an easy way to just stick this up wherever you need it. Again, maybe the side of a toolbox, maybe some door handle, maybe the handle of a fridge or something along those lines. But we like this handle because it's very low profile, it's very simple, it's almost bordering on kind of elegant because people always went for thin stuff or ribbed things or whatever it happens to be in order to minimize material. But all of that minimization is able to happen under the skin in the honeycomb, so you don't have to worry about the overall use of material when making a thick part that is very strong and durable. But we always use these videos, we always show the basic stuff. Everybody's seen a handle like this. They have existed before. They've been carved out of steel and metal and wood and so on and so forth. But 3D printing lets you create things that could never exist before, geometries that could never exist before. So with that in mind, we made this. This one's a little bit different because this doesn't really look like a handle. It looks more like a wall hook or something like that. And what you can do with this is actually mount it on a corner, so that you can put some handle on the side of a toolbox or the corner of a toolbox or something along those lines. And it's a type of handle that gives you a lot of grip. You could almost hook a chain or a rope through this and use it as some kind of grommet on your ship or your boat or whatever it happens to be. And since it's so thick and so chunky, you have all the strength out in the outer skin to where you can't really break it off. This is a type of handle that we would actually encourage to be glued rather than mounted with screws because it is printed in this direction, and in fact it's not actually printed this way, it's printed this way. And the reason it's printed upside down like this is that number one, you have minimum contact with the bed so that when a part is done, a machine can eject it and move on to the next one very easily. But it also ensures there are no overhangs. This hook is pointing upwards rather than pointing downwards, which would be the silly way of producing it because now you would have to have support underneath that hook. But if you make a very simple design decision and design change, you can now print it like this and it comes off the machine fully complete. And even though this could be machined or even molded, it's a fairly complex design, so it would be quite expensive, and you'd have to cut ribs and chunks out of it in order to make sure that there weren't big old chunky side pieces that would shrink when the mold was done. So that is one of the odd ones that's almost uniquely 3D printed and can't really be made other ways. But let's take this a little bit further and let's actually look at this one. Number one, this gives you a nice context of like the texture and the color and the feel, and also has the nice little interesting bit of these teeth on the inside here that you can see that are added on to give extra grip. This is an off-center type of lifting handle to where you can put it on some beam or board, grab it like this, and then you have friction on it and you can lift it up. These are really handy for like movers and that kind of thing, so it has to be really durable. In order to make sure it's durable, you make sure there's no stress concentrations by putting fillets in here. The reason we're using fillets, or chamfers, chamfers in here. Straight ones are chamfers, round ones are fillets, but the chamfers just look really good and go with the overall aesthetic because it is printed in this direction. The handle is on the bed so that it is all perfectly flat and the first layer is there, and there are no weird overhangs. The center teeth are not actually perfectly round. They are less than a semicircle. They're pushed in just a little bit to make sure that there is no instant horizontal and then a curve. It goes right into a curve, kind of at an angle the first time it starts hitting one of these teeth, which is really important to make sure that these teeth don't sag when they're being printed. Overall, we have the texture around the outside, which can give better grip on the interior. If I was redoing this part, I would probably do it in a slightly tackier type of material, like maybe ASA or even nylon, in order to make sure it's really durable and tough. Though this piece would be able to hold up a person, and we'll probably do some shorts showing all of these things, holding up people and doing different types of tasks. Because again, when you look at the stress or the strength of a part, all of this stress always appears in the outer skin. So when I'm pulling up on this handle, the place it's gonna break is gonna start right here on the outside of it, and then the crack would go through. But since there is so much outer surface, because you're able to make these really thick parts, that stress is spread out over a much wider area than it would be with like a molded piece where you would have ribs in here and then a thin skin that as soon as it breaks, it takes the whole thing. But this has so much more skin because it's fully enclosed to where it can be so much stronger. Now, that's all fine and dandy. Let's go one step a little bit further. One that's a little bit odd to make is actually this one. This little dome is literally just a bump to mount onto the side of something to give somebody extra grip. Basically a climbing rock. It's not really that interesting, except for the fact that it's fully enclosed. You could maybe blow mold it, but then it would be totally hollow and would squash like a balloon. But having it 3D printed, you have internal structure, you have high rigidity, you have stiffness and toughness, and you can beat these things together and not really worry about anything. There's not give on it. It is durable, it's reliable, and we have the nice texture on the outside so it doesn't look printed. But this thick, chunky blob of otherwise would have been plastic that you'd have to slap against the floor is a hollow part that uses very few grams of material, so it's very efficient to produce, but still has that exterior strength. So even though this is a stupid basic part, making a dome that is enclosed and has no ribs or anything else is actually kind of amazing and new and different. So even though it's simple and basic, much like the handle at the beginning, it is difficult to make before mass production 3D printing came along. Now, finally, the very last one that we've got was one that we just kind of did for the fun of it because it was a cool design and looked really nifty, and that is this handle right here. This handle is another side mount one, very much like the yellow one right here, where you would take it and you would shove it onto the side of whatever you want. Again, all of these designed for command strips, so you put 5 or 6 or 12 command strips back there, shove it up against whatever you want, and then you have this nice grip right here. Again, just like with the other dome before, you have this really thick, massive part. This is literally about 2 inches of depth that would have to be solid material in the past, but is hollow in this case, but still has structure. It's a honeycomb, it's a composite for all intents and purposes, a composite of one single material that has different macro structures inside of it. So this piece is very tough and very reliable. The one little trick with this is that even though the slot looks horizontal, it's actually going in at an angle so that there is no support inside of here. You actually have this angled roof, and if we were doing it well, we'd almost give it kind of a smile to where it's domed perfectly so that you never have any kind of straight overhang. But that kind of messes with the ergonomics as well. This is a really nice handle to get a hold of when it's flat like that. But it also has a very wide back surface so that it's easy to mount up someplace with glue or with screws through the front if you wanted to, and it has this nice front dome that just kind of looks pretty nice. And of course, we applied the texture to the outer side so that it doesn't look like it's a printed part. The point of all of this is not just to show ways of designing handles that you might be able to use in your own projects, or just get a hold of the files download and mount some handles up around your house if you have a fridge door that's broken. But this is to show that these handles actually are fantastic because they could not be made as efficiently as they are 10 years ago. The fact that they are basically hollow but still have structure means you use much less material. You're able to produce many more of these, and you're able to do it much more affordably than you ever could before. A part like this was very difficult and very expensive to manufacture in the past just because it was chunky. But now, because you have large print farms like ours here at Slant 3D or other options like that, you can make parts that are chunky, that are thick, that are strong, that are reliable, and that are smooth and have an aesthetic that you could never really hit before. And it's an opportunity to create products and create differentiation from your competitors that they may not have caught on to before. Most of the time, when somebody tries to make an electrical enclosure like this, they either end up printing it vertically like this or horizontally like this, flat on the print bed. But there's a third way to do it that we're going to talk about in this video. Now, very often those two most common orientations are the way that everybody does it, because if you have a large format machine, you can print it down flat like this, and this creates a good, rigid, reliable part where the layer lines are all horizontal all the way through the piece, and it's solid and it's reliable and it sticks down well to the bed, and that's fine. But if you have a smaller print bed, you might want to print it vertically. But in this case, what you run into when you design a part like this is you end up having support underneath here and support inside of the piece, and that just turns into a lot of post-processing that can really jack with the cost of the part, especially if you are intending to mass produce it, which is what we do around here. So how do you actually design an electrical enclosure like this to not be printed in either one of those directions? Let's just go through the basics of the design of the enclosure itself. First of all, you're using 3D printing, so you can make chunky parts of the part. You can make these flanges on the outer edge really thick so that you can have a good solid screw point to the piece. You can still have all the same features as another enclosure. This part was actually inspired by an existing enclosure that needed to be replicated. But in order to make sure that you have the same length fasteners, you can make the thinner areas just as you normally would so that you can use the same mounting fasteners that someone had intended originally with the project. From there, you can have thick walls that can either be 2 millimeters kind of minimum up to 5 or 10 millimeters. Again, you don't have to deal with the shrinkage of traditional plastics manufacturing. And since of course you're not going to be wasting all the material from having to machine something like this, it's just easier. You can get any geometry that you want. And by allowing those thicker features, you're able to create an interface ridge on the top of the part that a lid can interface with. So when you end up with the lid like this, you have this nice thick outer edge that you can then put a lip on the interior of in order to make this mount onto the box more reliably. But let's go ahead and look at the other way of printing this, because this actually is best done inside of CAD. What you want to do when you're printing a part like this is not actually print it flat or vertical. You want to print it diagonally. Now, this is not very common or very easy to do very often, because what you have to do is if you print it like this, now the center of mass is over, not the center of the touch point on the print bed. So you're going to have the part fall over. So you have to have support back here. But you don't want to have that be auto-generated support because it's just nasty and it ends up creating a lot more material and not always being very reliable. If you're using traditional auto-generated support, it will have a little bit of distance from the part to be removable, so you would end up with flex and wobble as the part is printed. So you have to use designed support. And the way you design this support is just like this. You create effectively a fin off the part. You can do it at a 45-degree angle because a 45 degrees is the best way to print the part. That way you don't have overhangs that can potentially sag by having a steep area over here, even though it's shallow in the back. From there, you design this fin to be about a 0.5 millimeter to 1 millimeter spaced parallel to the back of the enclosure or the part that you're trying to print. Then you take sprues and horizontally design them to run and merge into the part. You now have this nice little set of ribs that run up here along this fin, and you have this awesome piece of support, which when it's done, all you have to do is break it off and it comes clean, and all you have is a few divots that could be sanded down or you can just live with. It's a very clean way of producing supports. It's also very, very reliable. And you can actually design these a little bit more so that they break closer to the surface of this part if you want to put just a little bit of a break tooth or a notch inside of them. Once you make that part, make sure that the back edge of the flange is also flattened a little bit so that you have a part of the part against the bed. But now you have this part that was printed diagonally diagonally, but is really, really reliable. The other thing that the diagonal angle does is it allows you to create a really durable part all the way through. If you print it vertically like this, you can have splitting along these lines because that might be a flexural plane. Same thing goes for printing like this. You can have splitting along this direction as somebody installs it or pulls a screw that breaks the layer lines. But by printing diagonally, you have maximum strength through every feature. So like these holes for mounting the lid onto the top of this, they are actually looped all the way through. So they're not like this where they could split this direction if you put a screw in there too large. They are strong, reliable, and durable. As same thing for the side planes and everywhere else. This is a very good, solid, durable part. Now, the final icing that we did on this was actually to add a little bit of noise to the print so that you end up with this textured surface that just looks really, really beautiful. And then we went ahead and designed the lid, which was then also printed at a similar angle, not quite as steep. We printed this at about a 35-degree angle rather than a 45-degree angle. But now this part is able to merge into the top of it, and you have a fully complete electrical enclosure that is durable, reliable, looks great, and has a bunch of features that are either thick or stronger than what traditional manufacturing would generally allow while still being affordable. This type of enclosure you can produce thousands of and do it affordably as traditional enclosures out there, but you're getting a custom box with features that you need, and you are able to get a style, a look, and a durability and capabilities that you can't get from some off-the-shelf solution that would probably be similar cost at large volumes. So when designing an electrical enclosure, sometimes you actually want to mount it to something. So in this video, we're going to talk about the different types of features that you can design directly into the part that were never possible before and can now be fully custom and just as reliable as any other alternative. So first of all, let's just go ahead and start with the enclosure itself. If you're designing an electrical enclosure to be manufactured with 3D printing, the first thing you want to do is make sure that you can print it on an edge, not flat down on a build plate. That really restricts volume and increases the cost of the part. Instead, put it up at a little angle, and we will put a rib underneath it and print it like that. That creates a more uniform surface finish, better strength, and makes it more producible overall. And in order to do that, all you have to do is add a little or a big chamfer to the outer edge so that there's a flat surface for it to balance on. And of course, if you have any standoffs inside of the enclosure, please place a chamfer all the way around them. 3D printing does not care about volume. You can make a part as chunky as you want. It doesn't add significant material, but it adds a lot of strength and a lot more reliability. So those are the baselines for the enclosure itself. But now you want to mount it up to something. Well, there's a lot of different ways of doing this. Let's go ahead and start with one that's a little bit more eclectic and a little bit more surprising. A belt strap. Sometimes you might be doing an enclosure for like a camera mount or something that is going to be strapped to a pole where you just want to cinch it down. For this, you can just create a slot on the back of the enclosure. And with this, the only thing to be aware of is to make sure that this slot is parallel with the layer lines themselves, because the layers end up creating basically thousands of loops around that the belt can then go through. So it's very strong and very reliable. You don't have to worry about the layer lines delaminating, so long as the enclosure is printed in the correct orientation. So that's the easy one. Now, very often with electrical enclosures, you're putting them into some type of cabinet in industry. There's a lot of extrusion, there's a lot of dim rails. Since you're using 3D printing, you can now integrate those type of mounting features that might not have been native to the part before. They might have had to have been assembled or added onto the enclosure down the line somewhere. But here you can actually add them in the design itself. So you can make a dim rail mount or something for aluminum extrusion to where the enclosure actually slides together and fully joins with what it's going to be mounted onto. And this is a really great opportunity because this would have radically increased the cost of molding. But with this, it's basically a free addition for a traditional type of enclosure if you're making it with 3D printing. Now on to the more standard types of mounts. A lot of people won't mount with dim rail mounts. They just want to glue this thing to the wall. Of course, you can glue it, you can tape it, you can command strip it, you can use all of those options. But holes very often end up being a popular option. If you're making holes in a 3D printed part, what you generally want to do is kind of reinforce those holes. So just make the area around them a little bit thicker than you normally would. And again, you'd want to go as thick as you possibly can. If you have room to go in there, make it a frickin' sprue inside of the box. But if you can just subtly add a couple of millimeters there, that reduces the stress concentration around those holes so you don't have to worry about breakout when somebody's putting the screw in, or fatigue over time if the enclosure is in a high vibration environment. And those holes you can place anywhere you want inside the box. Again, it's really easy to add these customizations so that it aligns perfectly with your application and you don't have to do some drilling down the line. Now, that's okay if you want to access the screws inside of the box, but if you don't want to remove the lid to get to the screws to remove the box, you might want tabs on the outside. Tabs are fine, but again, you want them to be as thick as possible. If you have steep overhangs somewhere, you want to avoid those. So rather than doing just straight tongue tabs that stick straight out the outer side, make sure just to add a chamfer on the bottom edge of them so that they blend together with the part. Again, volume and adding material does not add much cost in 3D printing. It's not like injection molding where you have to try to strip everything down to as skeletal as possible. You can have big, chunky, lugubrious parts which look a lot better and are a lot more reliable for the process. Now, that's a traditional sort of tab, but what you really want to do is rather than just having a flat tab that sticks out the side, is actually make a monolithic type of tab that kind of grows out the side. This one is merged into the part where you basically have this protrusion that you can then cut the hole into, and you can cut a relief into it, a countersink into it, and then cut the hole through, and now you have a really reliable mounting point that is super strong, and you don't have to worry about tabs breaking off after a couple of years of the box being used, mounted, or in a high vibration environment. Again, you can make this thick, chunky stuff that's really, really reliable. So there are a lot of reasons to make electrical enclosures in order to protect a chip or a board or a box or whatever it may be, but every once in a while a box won't actually do it for you, and you have to get a little bit more creative. You might want it to kind of blend in with its surroundings or look like something completely unrelated to what it actually is. So in this video we're going to talk about how to design an electrical enclosure that doesn't look like an electrical enclosure. So the first question becomes, why would you want not a box for an electrical enclosure? Boxes are fine, they're used all over the place. But the problem is, electrical components and pieces often have to be used in places where a box just looks ugly. Imagine those cell phone towers that look like palm trees. They're meant to blend in so they don't look like an ugly piece of technology in a certain part of the world. It might be an event, it might be the design of a building that just needs to be protected, to where you don't want an ugly router sitting on the wall, so you want to create an enclosure that just looks better than what would normally be there. Something custom or something just outright invisible. Now this is what we've done with this one. This is actually an alien mushroom, which has a slot in the top for the board itself. This allows us to create an electrical enclosure that doesn't look like it at all. So this could be a signal repeater or anything else along those lines, and it could be placed in like a theme park or in an event where you have this sort of thing. You could place these around something like Comic-Con and people would never know that they're Wi-Fi routers if you really needed that aesthetic. But there's other places where this is really important as well. Sometimes you want to place in human-made elements that just blend in with the rest of the surrounding. We've demoed this before when we made a birdhouse that looked like a tree stump. There's a lot of reasons for this type of camouflage, to create an organic shape rather than just a black box that's just stapled to a wall. So how do you actually go about doing this? A lot of times you don't want to design the enclosure slot with the actual organic exterior. That can create a lot of additional labor. Generally, you want to design the two separately and then combine them later on. The best way we found of ever doing this is through a Boolean operation, where you basically take the enclosure area that you would want the chip to be sitting into and create a negative of it. The inverse of exactly whatever you want. You include all the standoffs, any sort of mounting holes that you might need, anything that needs to be included in the actual enclosure, you make a negative of. Then what you do is you take the basic shape that you want to insert that chip into, and you can take that form, which in our case had a big old large plane in order to split it in half, 4 mounting holes, and then 4 standoffs inside of it. And then of course we did good practices around filleting the edges and all the rest of it. But once we had that negative, we're able to add it to all kinds of different shapes. In this case, we placed it right in the dome of the mushroom so that when we subtract it, we get this nice little slot that also splits it into the 2 separate halves with the lid, top, bottom, the 4 mounting holes, and the 4 standoffs so that when we have the chip, we can go ahead and set it right in there. This creates a really easy way to create many different variations. So if we wanted to make a dozen different versions of these mushrooms, we could totally do it because we have that negative that is set to this chip. Now, the benefit with this is that we can now produce this with mass production 3D printing. Since this is an organic shape, it's very affordable to produce because there's not like super high tolerances or even cosmetic requirements because you have texturing and all kinds of other things. And then this would eventually probably be painted. So it is really amenable to the 3D printing process. So you can produce 1,000 of these or 10,000 of these and not have to deal with all the costs of molding. Plus, a design like this, where you have a small interior slot and really thick outer walls in order to create this shape, is very often either very difficult, very expensive, or just outright impossible to produce because traditional manufacturing isn't designed to make these type of bulky parts while still having internal componentry. This is a specific but oddly common type of part that we have to make inside of our print farms. So today we're going to talk about how to optimize a ring with some clamps on top of it. So this design comes up a lot. There's a lot of these types of pipe fittings out there that are meant to connect two things together, or catch stuff, or whatever it happens to be. And it comes up in a lot of different formats too, so like lids of enclosures and that kind of thing, where you have these clamps on top of something else. Now, whenever somebody tries to print this, they put it down on the bed just like that, but now the layer lines are in the plane of the clips. So as soon as you start reefing on it, those snap right off. You can use different materials in order to optimize this, but really it's about the design. So we're going to show you some really nifty designs to get around this. However, if you're stuck with this, if it has to be printed like this, there's a few things that you can do. First of all, like I say, you can change the material. You don't print it in PLA, you print it in something like PETG or nylon or something else, so you get a little bit better layer adhesion. On our side, we're able to experiment more and make those stick a whole lot better if we're allowed to kind of over extrude and if tolerances are really low. So there's a way to get it printed like that to where there's really good layer adhesion, but then the surface finish might get messed up. The other thing you can do is make just minor modifications to the design. If you want to print it like this, that's fine, but then the point of failure again is those clips. If you want to reinforce those, you can just add some chamfers to the outer edges of them so that now they are actually reinforced and able to stay there. In that way, you're losing some flexibility and you have to rely on the flexibility of the ring rather than flexibility of the clips, so it's not always a good option. With the design of this though too, just in general, make sure that you're filleting the lower edge that's in contact with the bed. That way we don't have to worry about elephant footing or other sort of first layer artifacts. It just preps it for the piece if you're stuck with this. But let's go ahead and move on to something a little bit better. The very first and easiest solution is to just print it at an angle like this, not on its side, at an angle. What this does is it now puts the layer lines partially in plane with the clips without requiring support on the clips so that you can actually grow this part up and easily. All of the clips get way stronger because again, the layer lines are almost in plane with them, and it becomes much easier to mass produce. However, sometimes you do require a brim down on the bottom to adhere it to the bed and potentially even some support underneath here. The other issue that can come up is a lot of roughness and nastiness on these back edges that are an overhang because it's a fairly steep overhang and a fairly thin, fragile part. So in order to reduce this, again, fillet it, round out the edges. Sharp edges that are overhangs always warp and deform, so avoid them as much as possible. But that also requires a small cut on the bottom so that you actually have a flat surface to put against the bed. If you don't have a flat surface, then the part is going to fail all the time and you're going to radically increase your costs. Now, of course, you can also extend this out to the traditional piece itself. Taking the same chamfered piece makes it even better because now you don't have to worry about the overhangs of the clips themselves, and you're again able to balance it up right here on its edge just as it's sitting there. Now, going a little bit further than that, with those fillets and those chamfers, when you're printing on its edge like this, you have effectively eliminated the overhangs. And you can take this a little bit further by adding an octagonal outer pattern. This is only necessary if the strength of the clips are absolutely critical and you need to maximize that. In this situation, you want to print it on its side. Printing it on its side allows all of the layer lines to be in plane with the clips. In this case, you also want to make sure that the clips themselves are at a 45-degree angle to horizontal, because if you have one on top and one on the bottom, now they're again in a plane where they can break off because the layers can delaminate. Putting them on the diagonal side makes sure that they're not able to do that. So you're printing it on its side like this. Now you're running into a different issue that you have to be aware of, in that there's this effectively overhang inside of here. The best way to deal with that is with designed interior support rather than auto-generated support that we might provide if we were prepping the parts for you. If that's done incorrectly, you can end up with a lot of this kind of nastiness on the top, where you have this sagging and weird sort of delamination of the layers, and it just doesn't look very good. You also have to be aware of the tongues, that if they overhang in any way in one direction, which these do because they have kind of an L shape where they go up and then out. So in order to achieve that, you're gonna have an overhang that's just unsupported, and you have support underneath there. You can tweak this a little bit by taking these tongues and moving them closer together so that these two bottom ones interface with the bed and they lay straight against the bed. That way you don't have to deal with supporting underneath them. And then these upper ones also grow into themselves from this chamfer down here. So hopefully that shows you how to make a very simple ring with some clips on it, or how to make any sort of shape that needs these clips. Being able to print on its side reinforces these a great deal so that you don't have to worry about them breaking off, and there's a lot of other geometrical changes that you can make in order to make sure that this part is as reliable as if it was made with injection molding. If you're designing a 3D printed product for mass production 3D printing, here are a few things that you really need to consider to make sure that you're reducing your cost and getting the best possible product out of your design. First of all, make sure that no wall has a layer thickness less than 1 millimeter. A standard FDM printer nozzle is 0.4 millimeters, and in order to make sure that you have a nice reliable wall, you want to be able to use 2 nozzle widths, which is 0.8 or up to 1 with side extrusion. So make sure that every feature of your part is at least 1 millimeter in width in order to ensure that that nozzle is creating a good quality vertical wall. In the vertical direction, you can go a little bit smaller than that based on what your layer height is, but generally just assume that you have a 3D pixel size of 0.4 millimeters. So make sure that you're going at least 1 millimeter thick to make sure that it's reliable and strong. Avoid horizontal overhangs. On a part that has a single arm sticking out the side, we have to put support underneath it. This both causes that area that is supported to be slightly deformed and creates a lower quality appearance. It also adds on additional labor of having to post-process that part, whereas a part without that overhang could go straight into a box and ship out the door, which is way more affordable. The way to avoid overhangs like this is to just go ahead and put a chamfer underneath it, and we have a whole video talking about this particular topic. Make sure that the first layer of the print is as simple as possible. Avoid sharp corners and don't put text on the first layer. When the first layer is going down on a print bed, you want it to adhere reliably and well, and in order to do that, you want it to be as simple as possible. You don't want a lot of detail, and you want to get as close to basically a perfect circle as you can. Again, we've discussed this in another video in quite a bit of depth of how to optimize and the direction to go, but just eliminate as much detail as you can and make it as round as you possibly can, and that is the best way to make a good first layer. And with that, rounding is very important. Make sure that you round or fillet every vertical edge of your part. The reason for this is it will improve the print time of your part because sharp edges with the nozzle of the printer moving around cause it to slow down and speed up because it has to go to the corner, basically stop and change direction. If you round that outer corner, it's able to travel through it like a car going around a tight turn. If a car had to go to a turn, stop, back up, and then go the opposite direction, it would make the lap a lot slower. But if you round that corner, the nozzle is able to fly right around the edge, it's able to print faster, it creates a better looking part, and it just is more efficient overall. Do not put cavities into your part. This is a vestigial idea from old manufacturing methods. Everyone is used to trying to remove material from parts, but 3D printing doesn't have this issue because we're able to fill in large volumes with honeycomb structure, which makes the part stronger. You can actually make a fully solid large cube with all 6 walls enclosed and have it be an enclosed volume that you could never make before. And do remember that this is a different type of process. If you want more strength, add more volume. Historically, everybody is used to cutting out material, but by cutting out material, you make thin walls. When you're printing those thin walls, they can be weak. In addition to this, remember that the layer lines do exist and don't create thin features that can cause the layer lines to unzip. We don't want those stress concentrations. Go for a thicker, chunkier part to make sure that you have the strength that you need. And this is a good time to remember that there are layer lines. Design for the layer lines. Put a texture on your part and that will hide the layer lines. Don't push for higher resolution, that'll increase your cost. Apply a texture either in CAD or request a texture be applied by us where we can digitally add a little bit of noise to the outside of the part so that it no longer shows the layer lines. If you have a high tolerance feature, make it compliant. Don't attempt to go for a really high tolerance center hole in the side of a block. This can create a lot of extra cost because it has to be very carefully checked, and oftentimes you have to compensate for material shrinkage and other sorts of factors. Instead, design the hole to be compliant. Give it some flex features. Either make some cutouts on the edge and make it a little bit smaller, or use options like grip fins in order to allow it to grasp the part that has to be inserted into it. And last, minimize bed surface contact. In order to mass produce a part with 3D printing, you don't want to have people have to pull your part off of a printer. But if it's a pyramid with a big old wide base that fills the entire print bed, it's going to be very difficult to not remove it manually. If you can design it to have a minimal contact surface on the first layer, then it becomes ejectable, where our machines can automatically remove them and then move on to the next part. It also eliminates the surface defect of that first layer looking different from the rest of the part. So design your parts to
sit on an edge at a 45-degree angle. If you're making an electrical enclosure, instead of printing it broadside down, turn it at a 45-degree angle, and now you can mass produce it very quickly, very reliably, and almost everything will be in the correct plane to where it's all very strong. So if I was to sum up this entire video with just a few rules and a single statement, make your part thicker, make it rounder, and minimize the first layer contact area, and avoid supports as much as possible. Those are the main things. Otherwise, you're gonna end up with a part that is really thin and looks like some kinds of terrible injection molded part that will end up causing problems in the 3D printing process. You cannot put a square peg into a round hole. Printing is a different process. You have to design for that process, otherwise you will be disappointed with the result. So hopefully that was a good summary of all the kind of main things to be aware of when designing for FDM. You want to make sure that you have these principles in mind when you're designing your part to make sure that it's fully optimized for mass production. Almost everybody ends up doing this wrong. So today we're going to talk about how to design side loops on 3D printed parts. Now the challenge with side loops is that very often they're just a brittle part. They're a component that can be pulled out very easily because you have layers that do not have a lot of support around the outer side, and you're not able to make them very thick in order to get what you want out of them. A lot of people end up designing kind of these wiry sort of side loops, which again, just don't have a lot of material. If somebody puts a lot of force on that, they're gonna snap off. Heck, if they get dropped, they could potentially snap off depending on what your material is. Now, while these can be reinforced by picking good materials, it's better to just do the CAD correctly in order to create something that is reliable. So the very first and simplest way of doing this is actually not to do like a full loop, but just have a hole in a plate basically on the side. You can make it elliptical or perfectly round. Make the side loop plate as large as you possibly can to give it as much meat as you possibly can, and then just to punch a hole right through. That could be for your zip tie, for your cord, whatever it happens to be. This is a good, simple way of modeling it up and gives you the material that you need to make sure that this thing is reliable. But there is still the potential for pullout. So if we wanted to reinforce that a little bit more, you can take it kind of a step further. And the way I like to do this is actually to put a rib on the outside of the plate. This way, this rib can act as a reinforcing actor. It can go all the way from the base of the side loop to the very top, or you can actually design it to be kind of like a little T flange on the outer edge, where it's just adding material right at that pull-out stress concentration without having any issues. Throughout all of this, of course, make sure there are no vertical overhangs so you don't have support. Make sure everything is angled so that every part can grow on the part previous to it. And then just make sure you fillet everything. Please make sure you fillet everything. And of course, the very simplest solution of fixing all of this is to just make these side planes really, really thick and fat. You can have them loop the entire part or whatever it happens to be in order to make sure that they're reinforced and strong. But ultimately what you're trying to do is you're trying to add more material, more reinforcement around the pull-out area in order to make sure that it's strong and reliable. Do not just leave a simple plane of vertical layers on the outside that's going to be thin and is going to be delicate. This way you can make a part that's really robust, can last as long as you need it to, and can actually replace a traditionally manufactured part very reliably without any issues. Because these features that we just discussed are not typical inside of normal design. A lot of these could not be molded or produced with traditional sort of methodologies, but 3D printing enables them now, and it also necessitates them in order to have a reliable part. You really should not be using a slicer to make brims. They actually really suck at it. So in this video, we're going to talk about how to actually do a brim correctly and how to not have to use a slicer so you don't have to rely on that piece of garbage just messing up your part. Now, when I say messing up the part, I do mean that. If you place a brim onto a part, what you end up with is a bottom edge that has either marred up from any sort of deburring that might have to be done, or potentially just a place of weird extrusion because you have the brim left over there. But the brims are very often necessary. If you're making a part with really sharp or thin tendril-like features, you kind of need a brim because those features can't just necessarily reliably stick to the print bed. So you need to give them a larger surface area so that they actually can stick to the bed. Everyone always flips on the little brim feature inside of the slicer and the brim pops out. But then you spend tons of time cutting at it and polishing it and sanding it and cleaning it up and that kind of stuff. And in the context of things like our print-on-demand applications where you can upload a file and then have the product shipped to your customer on like your Etsy or your Shopify store, that can introduce the opportunity for problems because you introduce the chance for some sort of error to happen. And the more brim there is to be removed, the more opportunity there is for that. So you actually want to optimize the brim, especially if you're going to make 1 million of these
these things. When your product catches and you actually have to mass produce it, you do not want to be pecking at the brim for an hour for every part. It increases cost, it wastes your time. You want the brim to be optimized, and there is no way to do that inside the slicer. Slicers are terrible at almost everything. Their job is to turn a 3D model into machine motion. Once you start using a slicer for CAD itself, where you're trying to make thick walls and give it a brim and have a raft and have it generate new features, you're now following into this generic profile that just is not very reliable and cannot catch all the situations that you're going to design for. But you can catch all of those in CAD. So this is why we want to talk about brims in detail. Now, if you're designing a brim inside of CAD, the first rule is make it 0.2 millimeters thick. This is a nice generic catch-all. You can make it up to 0.3 too, that's okay, it'll still appear inside the slicer, but 0.2 is also a good catch-all, and then you can know it's thin enough. You do not want to make it thicker. If you make it thicker, it's now more than one layer thick inside of the print profile, and if you upload it to a system like ours, then it would definitely be a couple layers thick if you made it like 1 millimeter through. Now that is no longer a brim to be removed, that is a feature that is a part of the part, and we're not going to touch it. So just make sure it's very thin. The very simplest brim that you can do is a single shape on the bottom of your part. So like in the case of this star, you can just make a circle underneath it. You can also make a square, but a circle is better because rounded features on the build plate are easier to print because they don't have peel out points. You're trying to eliminate corners as much as possible. So a circle is the best way of going. You take that, you extrude it up into the part, and now you have a brim. It's an oddly shaped brim, but a brim nonetheless. And here's the very unique feature of this. With traditional auto-generated brims, they basically create multiple perimeters of the part on the outside. And then they print to the part itself, which has rastering in the side-to-side bottom infill pattern. The problem with this bottom infill pattern and with this outline is that the outline format can sometimes create pull-up and all sorts of other sorts of issues. And then the rastering itself creates a point of separation and some weird looks. Basically, there's a mismatch between the bottom of the part to where it can't really all adhere because it does the outlines and then it does the infill. It's much better, and you have much better adhesion if you have long continuous lines where there's not interruption in the pattern of the part. That way you don't have to worry about deviation or bed adhesion issues if you're dealing with complicated materials. So by modeling the brim, you create a single uniform bottom layer. So this whole circle that we just created is printed as one single pass that is trimmed off, which means that it prints very reliably and you don't have weird little tool motions that could potentially disrupt your first layer. This is a really big benefit of using designed brims rather than using auto-generated brims, even beyond all the other issues with it. But this is kind of a brute force way of doing it. Putting a big old cylinder underneath the part is a nice clean way of doing it, and if you're not really deep into modeling and don't have a lot of time to put in like a complex part, it's a good way of doing it because it doesn't create that many issues and trimming it off is not a big deal. With these brims, however, if you're running it through an automated system like one of ours for like Shopify or Etsy, just make sure that you like put the word remove or something on it so we know that it's not an intentional part of your part. And as we do more of these, we need to be able to differentiate. So if you can put a remove on there, that gives us the signal that that is a removable feature of the part. Now, there is a simpler way of doing it. If you have a nice symmetrical part, like in the case of this star, you have these really sharp features that need to be tied down, but it's really only the tips of the stars that need to be pulled off. And the rest of it on the internal is really in the way, and again, it's just adding labor to it. Removal of all that stuff is cumbersome, and it's just not helpful. So rather than doing just a big old circle that encompasses the whole thing, do an outer ring. And you can modify these and design them in different ways. But that outer ring, again, creates a nice uniform first layer. If you are printing at home, you can use something like a concentric pattern so that you have a nice outer ring that's reliably put down just like a normal brim. And then it's very quick and easy to remove. Those are the two simplest ways of creating a brim. But one subtle thing, a brim adds material to the first layer of your part, which means that area can potentially be wider. If you want to make sure that a brim doesn't leave an artifact on your part, regardless of how good the post-processing is, what you can do is design the part correctly for 3D printing. In every video, we talk about applying a chamfer to the bottom of your part. This is even more important when you are using a brim. We have a 0.2 millimeter brim coming up into these parts. What we applied was also a 0.5 millimeter chamfer. What this does is it has the point of contact of the brim slightly in from the outside of the part. And that chamfer also serves as a guide area for the blade that is trimming off of that part. This makes sure that the brim doesn't add more material to the part. And if it does, it's not noticeable. It goes from a slightly chamfered edge to a square edge. So this is a good way of having a part held down with a brim and ensuring that the brim does not mess with the tolerances of your pieces. Applying that chamfer makes sure that the brim can be trimmed off, and if for some reason it's not perfectly trimmed off, it still creates a reliable part without overhangs or elephant footing coming out the side from that brim contacting it. It also has the dual benefit of that chamfer and that brim coming together, creating a stress concentration right in there, which means that now the brim can be more easily peeled off because it has a very tight break point created inside of it. And you can play with this a little bit more if you want to go into super advanced brimming. You can make the brim actually thicker away from the part and then thin at the point of the part so that basically you can just pop it straight off. But that's beyond the scope of this video and is not always useful. But I'm going to throw it out there as a tidbit for you anyway. Comment down below if you want the follow-up for that. Now, sometimes you don't have a nice simple shape like a circular star. Sometimes you have something weird that's going off in all kinds of different directions and you have one little tendril sticking out the side. In this case, you want to use kind of a subset of a brim called mouse ears. Mouse ears, we've done an entire video about the actual design of these. They are a very specific feature that can be used in all kinds of different ways. Now, very quickly, for the purposes of this video, a mouse ear is basically a circular tab holding down that edge out there where it's needed so that you have a lot of surface area tacking down that area of the part to the print bed. This eliminates the problems with warp a lot and is very useful. The problem with mouse ears is that they do have to be manually placed, and if you have a really odd looking part, it can be a lot of work. But again, if you're making a million of these, you want to design them correctly. So those are the generic types of brims. There's big old shape underneath the part. There's kind of a refined shape where you start minimizing the contact area of the brim. And then there's individual mouse ears if you have just an odd part where there's particular localized areas that you need to hold down. We have talked about many of these features before. Like I said, we had a video about mouse ears, and of course we've talked about rafts in our other Design For videos. Ultimately, a slicer is a really bad way of creating features. These features are kind of lazy add-ons to help compensate for an inferior process in the olden days. But if you are able to design for it, you should design as many of the ancillary features as you can so you know you get exactly what you're looking for. Because as systems scale up and people use print-on-demand tools like our API and those kind of things, having more control of the CAD ensures that you're not beholden to whatever our settings may be for support. That way you can optimize your design at home and know that whatever goes through the system will still be what it was that you designed. And you don't have to go through an iteration process of trying to adjust to the features of the slicer or whatever it happens to be. The slicer cuts the object, creates layers of that 3D model, and does it within tolerance. It doesn't add features, it doesn't move anything around. It's just what it is. You can create something much more optimized, much more reliable, and something just better that has less labor and a better quality output than what those generic menu items are that pop up inside of these slicers. Now, knobs are a very simple sort of object. How much could they really possibly change when you now have mass production 3D printing and print on demand available to produce them? Well, the answer might surprise you because you can create a knob that has never existed before because you can create geometries that never existed before. So today we're going to go through around how to design cabinet knobs. Now, cabinet knobs have been around for a really long time. As long as there has been something that you've wanted to grab, we have made handles and knobs to make grabbing of it easier. And there have been many ways of producing these. People have twisted steel, they have injection molded stuff, they have sculpted balls of clay. Basically, all you need for a knob is some object that a person can get their hand around and a hole in the bottom. It's really not that complicated. Now, when we're designing knobs, of course, designing all that basic functionality is really easy. You make the thing and you put a hole in the bottom. Done. But there are some subtleties here. Since you're doing 3D printing, you can now actually input threads into the bottom of it so that you no longer have to deal with additional processes like tapping it or assembling threads into it. So that can be a lot easier than it was before, so that now instead of having to make a knob and then make all the post-processing components to finish the knob can just come off and then you throw it in a bag with a screw and now you're done. That whole assembly is finished. So 3D printing can be a lot more efficient. And since you're using 3D printing, complex geometries become very simple to where things that would have to have a very custom process built around them just kind of appear and you don't have to worry about it. But what's really interesting is that throughout the world, there are thousands of knobs that have been created, many for different applications, many for different aesthetics. And these are kind of expensive to have created. If you think that there might be 100,000 to 1 million knobs out there, even this most simple kind of cylindrical one has a mold that will cost somewhere between $500 to $5,000 depending on how long you want that mold to last. So if you have 1 million of these out there, you've spent almost $1 billion to $5 billion creating all the molds for all these knobs in the world. All those molds are now obsolete because this knob appeared without any molding costs at all. So the fact that knobs are so high mix and so high variance lends themselves very substantially to 3D printing. Because instead of having to create a knob, create a mold, and then produce 1,000 of those knobs that are stored, you can instead just design the knob, and then you upload the file, and then when somebody wants it, they can order it, and the part appears. Nothing is ever needed until somebody actually orders the item. So you eliminate all those millions of dollars of upfront cost creating the molds for all of these, and then all the long-term waste of having to store them, because again, they're made in a warehouse where the shelves make the product. And this lets you chase down designs. Physical products now become as pliable as actual digital products. You can update your website to a new color, you can update a knob to a new color, you can create a new variation of it so that a whole new customer segment opens up. Whereas before it would take millions of dollars of molds to create all these variations of cabinet knobs, you can now just design cabinet knobs, have an AI help you out, do all these basic things. But you're still designing knobs. 3D printing hasn't really enabled anything except around the business model. But how does it change the engineering? Now, on this channel, we usually focus on high-level concepts and ideas for designing 3D printed products, not the technical details of how to design in CAD. But if you're looking to learn how to create your own designs inside of CAD, we highly recommend the sponsor of this video, Skillshare. Skillshare is the largest online learning community for creatives, offering thousands of classes on everything from illustration to 3D modeling to photography, so that you can learn how to create your own designs and figuring out how to sell them to customers who really love them. One class I've been loving is Introduction to 3D Printing, an easy start to your first 3D design. It's perfect for beginners, teaching you how to model a print-ready object with free online tools. No prior experience required. Skillshare's on-demand platform lets you learn at your own pace and start creating right away. The first 500 clicks on my link down in the description will get their first month free of Skillshare. So go ahead and click that link and start designing your own custom 3D printed products, like these knobs. So let me tell you a story about this knob. This is a knob for a very simple oven. You need to select the location that you want on the oven. What heat do you want it set to? These knobs break all the time because some people like to use their ovens for an extended period of time. Now here's the challenge. Historically, if you wanted to make this knob, you would have to make a knob with a hole in the back of it for each variation of that oven. One that has a shaft an 1/8 inch big and one that has a shaft 3/16, and then D-slot, and then round, and then tooth, and so on. You have to create a bunch of variations in order to fit all of the variations of ovens out there, and you can't know them all until customers tell you. But 3D printing lets you create a universal knob. So if you look at the bottom of this, that is not a standard hole. While it adds basically no cost to the actual production cost of this knob, you have a very complex mechanism that's down there. This is called a compliant mechanism. It is basically two halves that are pressed together with leaf springs that are able to press onto whatever size rod you want. And since they are semi-square, they are able to fit onto D shafts and tooth shafts, and they're able to grip it and adjust to the size very easily. This geometry is impossible to make because these springs, even though they're all part of the same part, are actually cut free to where they flex inside of there. That has never been possible to manufacture before unless you wanted to stack together a bunch of layers, which if you're stacking together layers, why not use actual additive manufacturing that's designed to stack stuff together in layers? So this knob, you're now able to not only create many variations of shapes, but you're able to create more robust mechanisms because you're able to embed mechanisms into these knobs themselves basically for free so that you can create something that works everywhere really reliably. So now we have an oven knob that will work on every oven, and we don't have to know what the size, shape, or style of the shaft is, because we're able to build in a system into the part itself that prints with the part, is a part of the part that will readjust itself to wherever it's being used. So looking at this, knobs seem like a simple thing, something where you just say, let's make some knobs and let's keep on making them the way they are. But now, with mass production printing and print on demand, these become actually phenomenally exciting. You can make every variation of knob that anybody would ever want, still keep them in control, and build them on universal standards that are now possible. So you both create a new business model where you can have a store with infinite selection of cabinets knobs, but zero inventory, because none of these have to be made until somebody buys them. And you can create variations that never existed before. So now you have a competitive advantage over anybody else who just wants to upload their past models of knobs that they've been making for the last 100 years. They have to recreate these, which gives you a whole new edge, whereas a traditional knob can most certainly be manufactured, and if you're a knob manufacturer, reach out to us. We can get all your past defunct inventory back into production. But if you want to invent something new, there's some cool stuff that you can do. 3D printing lets you create new business models and also lets you create new engineering solutions that were never possible before, but are possible now. They're faster, they're greener, they offer more selection to your customers, and they offer a better experience. So today we're going to talk about the design of domes, a relatively simple part, but something that can have all kinds of twistiness, especially on the inside. So a traditional dome is really easy to design. You take a sphere and you cut it in half and boom, you have a dome. But the issue with domes is that they're actually fairly complex in order to get a good quality part out of mass production FDM, which we do here at Slant 3D, because the interior creates this overlap where you have the lines basically print out in space, so you end up with this dragginess look inside of it, and that's not the greatest thing in the world. And if you're doing a thin-walled dome, then it can get even worse because that distortion can actually propagate to the outside to where you can't really get rid of it. So how can you get rid of this distortion, and how can you design a dome to be more manufacturable than just the traditional hemisphere? Well, the first thing you can actually do is to just change the design of the dome itself a little bit. Make it a little bit more egg-shaped. Pull up the top just a little bit and also taper the inside so that it comes more to a point than it traditionally otherwise would. That way you get away from this flat overhang but still curved and start bringing it up to a tighter point to where that can be reduced inside of there. But again, this can require quite a bit of stretching to make it disappear entirely. So in order to get the exterior dome shape without having to actually deform the shape of it all, you can actually go ahead and change the interior without changing the exterior. This is not a molding process to where you have to be a constant thickness all the way through. You can design a dome to have an exterior that is a perfect hemisphere, but then the interior be kind of a sharp angle. That way you get a really clean print on the inside, but the outside still looks exactly the same as the original. This is a really good way to make it more manufacturable and to create a cleaner interior without actually changing the exterior geometry. But if you need that interior geometry, then you can get into a tougher spot. If you have to have the inside actually be a perfect circle all the way through, many people would just say, well, support it on the inside. But generated supports are actually really terrible with the domes because, again, the same factors that create this sort of overlap and dragginess inside of there actually contribute to making supports bad because supports tear off and merge and all the rest of it. It's just not a good way of doing it. But if you have to, the best option is not actually auto-generated supports because you don't know how much control you have of them if you're doing print on demand through like our Etsy app or mass production in general. You want to have it dialed straight in. So designed supports can often be the best, where you have an interior kind of mushroom that is supporting that upper arch. This needs to be spaced out about 0.5 millimeter from the top, maybe even more. That way you know that this has perfect amount of spacing to support that really nicely to make sure that that entire upper curved dome is printed really reliably. Of course, design supports you want to create as minimal as possible while still making sure that they're stable. So have the nice wide upper cap for this little mushroom that's supporting it, and then a thin stock below that is still stable enough to print by itself. And that way you have a really good piece of support. If for some reason you don't want to put in the time to design supports, or if you're making a dome that is so large that you want something more efficient, generated supports are generally more material efficient than design supports. So in that case, what you actually want to do is still have the exterior dome traditionally as you would, but then the interior, go ahead and cap off the very tip of the dome on the inside. That way, auto-generated supports have a very clear delineated area where they attach to, and they're able to pop off
really cleanly and easily, because again, they don't have a really steep angle that they're kind of merged into and can interface with. There's a really clean, nice top, smooth, flat area that they're able to plug right into and then pluck right off of. So it's very easy to have them be generated in a very clear area while still being really easy to post-process. And this is a great way to mass produce a dome to where you have a minimal amount of support material in order to still get a really good, clean, crisp part all the way through. So 3D printing has a lot of trouble printing parts like this that have a smooth dome that gradually changes over time. It ends up creating a lot of layer lines. And the reason for this is as you go up this part, the slope of the part changes so that as each new layer comes up, which is essentially a planar pixel, when you move up one area down here, it's just the layer height change that you can see visually. But when you move up the height up here on the top where the angle is very shallow, the edge of the layer not only moves up, but moves inward a good distance in order to follow the curve of the upper surface. This ends up making layer lines appear much more distinct at the top of a curved surface than on the sides, which is an undesirable appearance. So how can you fix this? Going through this video, we're going to talk about a number of solutions of getting around this and hopefully show you some ideas that you've never seen before. So the very first and most obvious solution is to increase the resolution. The layers are moving up and shifting in because that previous one was a 0.3 resolution. But if you take it down to a 0.1 resolution or even smaller, then the change in the curve is not so substantial that it's really noticeable, and you end up getting a much better surface finish along the top of the part. Now, this is okay, but it doesn't always do it perfectly. There's still kind of a transition point at the very tip of the part that isn't the greatest, and increasing the layer resolution is really expensive because it adds a lot of print time to the part and can add a lot more cost when you're trying to make tens of thousands of these in a mass production context. So changing the resolution isn't always the best idea, even though there's some ways to make sure that even though we increase the resolution from 0.3 down to 0.1, there are ways to make sure that the print time isn't dramatically as increased as like 300%. It's just made about 50% slower than the traditional part. But that takes a lot of setup and requires much more confirmation, which you don't really want. The very best solution is to just make sure that there is not that upper surface. Design your part so that it can be printed on its side, so that rather than printing like this to where each layer goes up and eventually causes a stair step at the top, design it so it can be printed on its side. That way each layer is exactly the same throughout the length of the part. This way you get a much more consistent surface finish, but it does require that you do things like put a chamfer on the bottom so that there are no steep overhangs, and to design your part to make sure that everything else can allow it to be printed on its side. This isn't always viable for like the top lids of electrical enclosures and that kind of thing, unless you're really designing for what the process is. Now, another solution is to just get away from the smooth round curve as a whole. This might not be necessary if you're making an industrial piece of equipment, or if you're really early in the industrial design process. You can get around having to use curves and instead use flat edges. Flat edges have a consistent slope the entire distance, so it's much easier to maintain a consistent surface finish. So something as simple as a triangle is a good example of this. Rather than having a smooth curve, just have a triangle or pyramidal shape. This way you have a consistent slope all the way up so that each layer line is exactly the same as the one below it, regardless of how high up in the dome you are. Now you can play around with this, and if you have the capability, you can do multiple facets to where there's a consistent surface finish on each plane. Even though this plane has a more distinct layer surface, it's at least smooth and consistent, so you don't have like the top circle version where it just gradually becomes more distinct. This is very consistent and very defined. It also enables better post-processing because it's like, that surface just needs to be gone over in some kind of a way. But you can take this even further. If you don't want to have angles at all and instead want to kind of lean in to the layer lines, and rather than trying to hide them, you can basically pixelate the part more. This is a really exaggerated example. You can make these steps as small as you want to, but by creating these stair steps on this part in order to create the dome and pixelating the part essentially, you no longer have layers moving in on each other. Every layer is vertically on top of the other, and then you have these top surface layers, which means that you get a change in appearance from side to front of surface finish, but it's still very controllable. And again, you can take these down to as small as like 1 millimeter stair steps, or even bigger, basically. So this is one way of kind of changing the design paradigm in order to get the same functional interior volume without having to compromise the outer surface finish. But you do create a new type of kind of part aesthetic. So there might be applications where you can't really use this because it just doesn't fit with the brand of the product. And one last solution is to use digital noise. And we use this a lot of the time. It's where we input just a little bit of kind of rattle into the machine or apply a very subtle texture inside of CAD to where the part basically smears the outer layer lines and creates this almost pinned sort of look, which can be really useful because you end up getting this nice kind of roughened part that was never really possible to be created before, but you get rid of the layer line aesthetics as you're moving up the curve of the part.
So electrical enclosures can really benefit from mass production printing because very often they're customized to the individual PCBs. The molding cost and the upfront cost of getting them started can be so great that it's better to just produce the parts themselves rather than tool up for them. And since printing does not have that tooling cost, it's an ideal way to create a very nice looking custom box for whatever your electrical component may be. And we've talked about electrical enclosures in many different contexts in the past, talking about the design of them in order to further optimize the cost by designing for the 3D printing process itself. But in this video, we're going to talk about the actual lids themselves, because there's some tricks you can do in order to ensure that you're getting the optimal cost per part out of an electrical enclosure design. So when working with electrical enclosures, very often you will have some kind of bottom component and then a lid up on top of it. And that lid will have some sort of a lip or finding features in order to allow it to lock with the center component. But what almost everybody does, and rightfully so, is they just cut a line straight through the middle of it. And that creates a very standard type of lid. Well, you crop off the top of whatever the box is, and that is going to be your lid. But the problem with this is that you introduce a number of different problems. Number one, how do you actually print this? Do you print it flat like this facing up? Do you print it on its edge, which is ideal and better for auto ejection? Or do you have to print it upside down in order to have a nice uniform outer finish? This is necessary because this allows the layers to all align completely right, but you end up with a top that is the rastering of a standard 3D print, which is not really ideal because it does not match the sidewalls. If you print like this, all of the walls match, but then you have rastering up here and the bed material down on the bottom. And of course, if you print like this, you now have the bed texture on the bottom and the layer lines around the other side. It's much better if a component has a uniform texture all the way around. So what are some ways of achieving that? Well, one of the simplest solutions is to take the enclosure and instead of cutting it straight across, cut it at an angle. If you cut it at an angle, now what you have done is you've made the two halves print as individual kind of pyramids, which means that the layer lines go all the way around the entire circumference and outer perimeters of the part. This means that the outer surface is much more uniform. Now, it does mess with your geometry a little bit, and if you have internal components, it can mess with how those are actually mounted. So this can sometimes be challenging, but you don't always have to have a full 35 or 45 degree angle. It can be more subtle, and that is doable. But ultimately, what ends up though is that the layers do all align, and it looks like these two halves were printed together basically at this angle like this, but then have a matching parting seam. So this is a very good way to create a very uniform looking part where every surface, no matter how you look at it, looks exactly the same as any other. But there's a variation of this. You can't always cut a part directly diagonally down the middle. There's a variation of this that is slightly less controlled and slightly less uniform, but still viable, which is printing the part diagonally. Now with these original enclosures, we have these back chamfers. So you could print the part like this so that the bed layered part is only this small chamfer on the bottom, and that only has the bed surface, and the rest of it is the nice uniform part. But again, you have that exterior part, but you can't mount it up like this because there's nowhere to balance. But you actually can. Let's go ahead and redesign this so that it can be printed belly down, but at an angle. This is what you would end up with. You have the enclosure just like so, the lid pops off like this, and now you have this flat space of the main core enclosure that you're able to print like this. This does have this downside of requiring support along this front surface to make sure it doesn't fall off, and if the part is really long, you need to have quite a bit of support. But overall, the outer surface finish of this part is very, very uniform. every side of this piece matches. And then when you get the lid is printed flat, which gives it better strength. Or you could actually figure out a way to print this diagonally as well. But you have this little lock-in feature that can be handy, right, like this. But then this also leaves the top surface of the lid to take on any sort of text or monitoring, or just be separate from the rest of the part, because the lid is separate from the rest of the part. So that change in texture can be kind of a notifying feature to allow the person to understand what side of this part is actually the top of it. So this is a very simple way to just cut basically a dog leg through the part so that you can pull off the lid, print it flat, and then take the angled upper component and print it facing down so that the outer surface finish of it is totally uniform without any sort of variation between what is against the bed or vertical or the top or the side or anything else. All the sides are exactly the same, which creates a nice looking final part that you can then mate with the upper lid. And if you want to print the lid vertically or on its side or anything else, you can totally do that. This is ideal to print vertically. The reason we like to print vertically is that number one, it's easy to knock parts off, and it also allows you to print larger parts because they can be stood up on end where there is greater vertical distance on our production machines.
So there's a style of feet that don't really go anywhere. They're actually meant to keep an item in place, and that's what we're going to talk about inside of this video. Many products actually need feet. They are small protrusions of plastic at the bottom of the part, which can make sure the item sits flat. It also improves the overall aesthetic of the part. Rather than having a big old block sitting down flat on the table, you can have it lifted up just a little bit. You might also have a functional application for this, where maybe you're putting it in a moist environment and the feet can lift it up so that water and liquids can flow underneath. So feet have a lot of applications, but people don't always design them correctly. They often are an afterthought, which is weird when they're so important in our normal day-to-day lives that we don't think about that when we're actually engineering them. So in this video, we're going through the actual design, and more specifically about how to make them mass producible for 3D printing if you ever wanted to make 10,000 of a 3D printed part at a print farm like ours. So the very most basic version of feet are just cylinders extruded out of the bottom. A lot of people do this. It's a very common way of lifting the part up off of the ground just a little bit. But what almost everybody messes up is making these cylinders straight cylinders. You shouldn't do that. Very often, if there are feet on the bottom of the part, you end up printing that part up on its edge so that the feet stick out the side. This makes sure that the feet are most uniform, and you most certainly don't want the feet on the bottom of the part, because then the whole bottom of the part would have to be supported for the little distance that the feet are lifting it up. That's kind of silly. So we're going to print all of these parts on their side, or at least on the diagonal. And we've talked about that in other videos. You can check that out over there of how to print on a diagonal. But the feet are sticking out, printed on the side. Okay, cool. But now they're an overhang if you just extrude them out the side. That's a terrible way of doing it. You don't want to design features like that, because now support is going to be auto-generated. If you upload it to something like our Etsy plugin, you're going to have support show up. It's going to increase the cost of the part. Blech. It doesn't even look very good too, because now you're going to have the feet slightly deformed by the first little layer that sticks out into thin air. It's all terrible. So make sure you chamfer them. Make sure there is a chamfer around the outer side. It doesn't hurt the aesthetic at all, and make sure that you do not have any sort of overhangs. There you are. That's the most basic version of the feet. Now, not all feet are round. Sometimes you want them square. You might design the feet so that they actually control the part in certain directions. You might want it to slide in a direction, but not the side to side. Now, of course, you can do these through a circular pattern on the bottom, but again, make sure that you're chamfering them all of the time. However, if you have these flat kind of tab-like feet and you want to make them long, make sure that you're rounding them off as much as possible to, again, make sure that they do not create an overhang anywhere. This is the fundamental rule of designing feet. And when you have these features that are coming out the side of the part, make sure that you are rounding every single possible edge. People very often leave sharp corners within 3D prints. That is a mistake. Make sure that you fillet the edges of them. It radically improves quality, it improves print time, and it makes sure that the overall part is just more manufacturable, because you don't have points of errors where there could be retraction points or anything else. So make sure that you're rounding all the edges and blending those feet as much as possible. Now, there is one other version of feet that you can also use, which is less ideal because you're not able to get them all in a single print, but sometimes you want high friction feet, and doing print in place isn't always possible. If you're printing out in PLA, it's going to be pretty slick. So they're mainly acting as standoffs, not necessarily as points of friction. However, if you do want points of friction, you might want to put some sort of adhesive feet on the bottom, little rubberized half hemispheres or tape or whatever it happens to be, so that your product is able to sit stably in a location. Even with this, even though you might be gluing something onto the part, you don't want to glue it onto just a side surface because there's less support of that. What what you actually want to do is create small insets, inverse feet basically, for the feet to then go into. With these insets, you're able to have the same exact surface to mount to, but you're able to embed the adhered feet onto it. And these are a really good option for just creating a different way of assembly for the product. Normally this type of feature would be fairly expensive if you were like molding it, but it's free with 3D printing. So you can add these insets, but this only works if you're mass producing the part. It doesn't really work for print on demand because the feet can't be added after the part is printed out. So if you are using a print on demand option, you want to use the designed feet, but if you are mass producing it and you want a part that sits stably on a surface, then you might want to look at the adhered feet, because then you can actually have a rubberized point of friction on the surface. You know, sometimes you want multiple parts to stick together, but you want to do it in a way to make sure they stay together consistently, reliably, and continuously. So in this video, we're going to go through joining features, how a lot of people design them, and some better ways of actually getting them made to have your parts stick together really well. So the first and most common type of joining feature is really just a tongue and a slot. And this is a decent way of doing it because it's easy. You make a square on one side and a square on another side, and then you have them slide together or press together. And this isn't a bad deal, but it's kind of not very useful because they don't hold together very well. But if you are designing these, make sure that you chamfer the insert just a little bit. That way it's able to wedge into the main slot. And then the 3D printed layer lines can actually cause them to lock together pretty reliably. But again, you don't have any sort of pull or forcing to make sure that there's no gap in between the two pieces. Also, it's just kind of cumbersome because there's a lot of tolerance issues within it. So this isn't the greatest type of locking feature, though it's the one that a lot of people go to. But let's move into one that's a little bit more robust. Another option that a lot of people use are T-slots, and T-slots are actually pretty decent because they actually have some lateral support, so I can't pull these apart. And they're actually not too bad to design, and you can actually use the same kind of chamfering on the top of the tongue itself so that it angles up and locks into there. And this is fine, but the problem is that you now have several different tolerances to have to deal with. You also have a pretty complex first layer where this can warp and curl up when it's going down on the first layer if you're using a high warp material or want something that's robust in manufacturing. So even though it is functionally okay, it's not great. And again, you have the tolerance issues of having to keep that seam pulled together. And based on material shrinkage and other types of issues, this won't always work very well. So having something that is tight and flush, just like this, isn't always a very viable option. But there's an upgrade to the T-slot, and that is this. You can actually take the T-slot and curve it just a bit so that now you have taken the two outer flanges of the T-slot, and instead of them being straight to where they press into a hole with a friction fit, they are instead acting like springs. So that now you have a part that is able to go into the slot and lock in so that now there is no jiggle, no tolerance issues at all, and you're able to have kind of flexible tolerances that you can deal with material shrinkage and other types of issues. The other thing that we've done is, since we don't want this complex first layer on the part, we went ahead and angled this slot. And you can apply this to any of these, but by applying that angle, you now have a very simple square first layer that with some rounded filleted outer edges so that you have good corners. And then the rest of the complexity happens later in the print to where it's very easy to control and you don't have to worry about warpage on the bed or adhering to the bed. You just have it print. So you make sure that it's chamfered there, and then the two outer flanges are chamfered as well. And now you have something that can lock together super tightly, super reliably, has no jiggle, and has a very nice tight seam that will always be a very nice tight seam. The one downside of this is that you have basically this hole in the bottom of your part, which isn't always necessarily desirable, but you would also have the hole in your bottom of the part with any other types of slots, just have it outlined. So long as this is a non-customer facing feature, it can work pretty well. But there's some other types of slots that we can use. One of the more common ones is the eye slot, where you use a circular flange for the tongue. Now, the benefit of this is that it is easier to design than the T-slot because you're not doing all the XY tolerancing that is necessary. You just have one single circle that is dead centered dimensionally to the other circle. And then, of course, you chamfer this so that the two of them can lock together. And again, you get that advantage of 3D printed layer lines basically binding together so that it doesn't really want to come apart very easily if it's a really tight one. and you have a decent flushness. But again, the other problem with tongues in general is that you can have this spread at the top, this angling, to where the bottom slot is holding together, but the top of the part is not held together, so it kind of flexes like this. And that again is a problem with those kind of short, stumpy slots. You can of course make them deeper, but then you're dealing with a lot more friction in putting them together, because this can be a decent amount of effort to put together. But the eye slot is really useful because it's very easy to design, very easy to tolerance, and is generally a nice looking design. It is also technically a simpler first layer. So if you have a tongue that has to be printed face down to where this has to be against the bed and you can't do the angled thing that we showed on the spring T-slot, this is a way to get around that because these are nice smooth curves all the way around, so there's a low chance of warping or any sort of other issues on first layer that can come up. But you can also take the eye tongue and slot and change them just a little bit. You can actually use grip fins. Now, grip fins are a flexible feature that you have to design pretty carefully. They cannot be connected to the roof of it, but they are these small tabs all the way around the hole. And these small tabs allow you to take a much larger eye tongue and shove it right in there to where it locks in, and you have the flexibility of these outer features holding it in place. Now you can have it be a rigid feature like the regular eye slot to where you just have a very low tolerance hole right there, which can be useful in certain situations because it gives you some flexibility. But it's also useful to actually make flexible joints or semi-flexible joints to where you can use those grip fins to hold on to the eye tongue so that you get just a little bit of give inside of there. And it also pushes back and forth and you have flexibility throughout while still holding onto the part reliably and centering it. And you can change the stiffness of these fins by making them thicker, making them longer, so that they grip that eye tongue even harder than they normally would. But all of these assume that you have to use tongues where two separate parts insert into each other like this. And while this is fine, it's not very robust. And again, you have that first layer problem. None of these really pull it in except for the flexible T-slot. So what is a design that we could actually use where we take advantage of 3D printing really at a large scale? Because all of these parts can pretty much be made with any other process except for the grip fins, which are impossible. They use an impossible geometry. What if we could take all of these, put them together, and make something that can't really be made any other way? Well, if you were to do that, you would end up with something like this. Now, these are just locking tabs, and the reason these don't really exist generally is because they are impossible to manufacture. This internal hole right here has two recesses inside of it, which cannot actually be machined or manufactured or molded with anything other than 3D printing. So what we are able to do is create those two recesses and then create two locking bumps on either side of this part so that these two little tongues, these flanges, flex just a little bit. And now you're able to take them and press them into that slot and have it lock. You can change the tolerances so they pull tighter. You can also change these bumps so that they are actual lock-in. Right now we made them bi-directional, so you put it together and pull it back apart. So if you're making a building kit, this can be really useful. But you can make these so that they lock in there permanently and pull it in super tight so that there is no flexure at all. But it's very quick and easy to assemble, and you don't have to deal with all the other tolerance issues of the other pieces or the first layer issues. In addition to this, we also print these parts just like this. So this brick actually sits on the build plate like this, and these flanges do not need any sort of support at all because we angled them on the bottom. So this part can come off fully complete. This part can come off fully complete. They have very simple first layers where we don't have to be concerned about some complexity that would cause them to fail or warp. And they lock together very quickly and easily, and they give you an advantage that has never been possible before. So if given the option, I would recommend doing these because these use just a smidgen less material, they're more reliable, they're easier to assemble and work with, they're also fairly easy to tolerance. So if given the choice between all of these locking tabs, I would use these. But hopefully that gives you some insight as to how to design locking features or joining features so that multiple parts of either terrain or an architecture model or maybe just a building kit can be put together in a way that is reliable and very manufacturable without having to worry about high cost or high rejection rates because of complexity inside of the model itself. From toys, tools, and water bottles, a lot of items have small little plastic loops that allow you to connect a keychain to them or some other type of tassel. But in this video, we're going to go through how you can actually design them for mass production 3D printing, because most of the time people do it wrong. So it is super common to design some sort of loop for a cap or other sort of attachment on a product that you might be working on. And most people generally design those loops like this, where it is parallel to the flow of the cap itself, so that you have a hole going through this direction that the keychain then attaches through. But the problem with this is when you are 3D printing an option like this, is that the nozzle has to move from here over to the outer edge. And when you do that, you create these layer lines that are very easy to snap off. This is not as durable as it could potentially be, and not as durable as when it's made with some other options. But this is not the best way of making that. If you were to mass produce a cap like this, rather than having the loop on the side be like this and then optimizing it, rounding it out, blending it into the part as much as you can, instead, you would actually make that loop horizontal so that it comes through the part like this. This way, you have everything in the layer planes and it's a continuous loop that is interconnected with everything else. This is as strong as any sort of other plastic part. So you can take this loop. This is the very simple, most basic version of it for replacing this traditional kind of perpendicular loop. But then you can take it and expand it and push it. You can make it larger so that it becomes basically a finger hold rather than just a keychain hold. You can make it thicker and wider and fatter and bigger and smaller. This is a very, very useful core feature that can be used in almost any of these applications and is super, super useful while still also being extremely durable. But you can see that this loop is perfectly flush with the top of the cap. And that is so it can be printed on the bed like this. But sometimes you don't want to print the cap like that. Sometimes you want to print it like this. But in that case, you would then have support material underneath this loop, which is a part that you do not want. You want to eliminate supports in order to reduce cost of processing and cost of the part. So in order to do that, what you would do is you would actually make the loop a little bit thicker and then apply a chamfer to the bottom of it. Now this part can be printed like this, and it has no supports whatsoever, but you still have the same basic function and basic loop, and then you can expand it, contract it, make it bigger, thicker, however you want to, just as you could with the traditional simple one. But that is making a regular loop kind of inspired by the old way of doing things. But we are using mass production 3D printing. With mass production printing, you have a lot more options about what you can actually make, because you can create impossible geometries that were never really possible before. So with that in mind, you can start looking at these types of connectors where they actually embed into the part and curve and snake through. These sort of connectors are super useful because they allow you to embed it in the part so that the profile doesn't change and you don't have some wart sticking out the side of your part. And since it's in the plane, it's still exceptionally strong. And then of course, if you have just one of them, you can add in more so that you have an omnidirectional points of connection without adding any extra cost. If this was to be traditionally manufactured, then you would radically increase the cost of your tooling by adding in these extra holes, which is why so often you only have the one. But there are cases where you want many. So you can expand this as much as you want to, because this added geometry does not add extra cost. But you can take this even further. These are cutting through basically diagonally through the corner of the part. But if you want to do a tassel or something else that is very flush and very consumer focused, then you might do something like this. This looks like two holes, but actually this is a loop going through into the part and then coming back out. This is something that you could push a paracord through or anything else so that you have a very good strong fit, but also a very flush kind of a fitting and a very smooth connection on the inside so that you do not fray or wear on whatever the clasp or the tassel or the rope or string happens to be. So this is probably one of the most difficult to do with traditional manufacturing because it's actually an impossible geometry. So those are kind of the basic options for how to design a keychain clasp with mass production 3D printing in mind. The most basic is to just make sure that you make the loops in plane with the cap that you're actually doing or whatever the object happens to be. But then long term, you can go into more complex kind of connectors that can go around square containers and anything else, or almost scale this up to the full size of a handle and still have the same functionality, or even do impossible kind of internal geometries that can't really be done any other way. So now you can create a product that was never possible before to truly differentiate what you're manufacturing from what everybody else has ever manufactured. So we want air to go through this, but we want water to not. So how would we design a vent to do something like that? Fortunately, it's actually possible with 3D printing. So this comes up actually fairly often. There are a lot of industrial electrical enclosures out there where they need to be washed and cleaned or just put out in the rain, but they still have to have vents in order to allow the fans to cool the internal components and that kind of thing, which is kind of an odd situation because water and air are both fluids and therefore can both go through basically anything that has any sort of porosity. So how do you design a vent that can actually stop water but still allow airflow to go through reasonably easily? It's not as easy as you might think, and there's a few ways of going around it. A lot of the ways people deal with it is just by having vents that are closed off. Somebody will come up, close down the latch on the vent to the box, and then spray it down, and then they'll open it back up again. There's a few kind of one-way vents, but they're very, very expensive. This is really a situation where 3D printing can really, really shine, because 3D printing is able to make really complex geometries, but not have to worry about assembly of them afterwards. You can get something right off the machine ready to go. So what are a couple of ways of doing this? Well, a lot of the nerds out there would immediately go, Tesla valve! Tesla valves are actually a decent way of doing this. A Tesla valve has the ability to allow airflow in one direction and not fluid flow in another direction. Because of how it's designed, water will flow through, but then get turned around back on itself and then get shot back out the other side. So it's a reasonable way of stopping viscous fluids like water from going through, but still being able to pull some amount of air through, even though you've radically kind of increased the amount of drag on there if you're pulling air very quickly, because it still creates a ton of turbulence for that. And the Tesla valve is actually something that was kind of intended to be used as a version of a jet engine, like pulse jet engines will use Tesla valves in order to prevent explosions from propagating up. So it's a way of doing this. It's not necessarily a good way of doing that, but we did design one. The other issue with it though also is that Tesla valves are kind of a bulky version of this because they need so much rotational space in order to actually operate. Getting enough slats in this brick is actually sort of tough. So even though you could breathe through this sucker, and there is a Tesla valve in there all the way, it's still not necessarily perfectly ideal because it's just taking up too much space, it's too thick, you don't have as many layers of Tesla valves in there as you might actually want. So it's not necessarily the best, but it is viable, and it's a great demonstration of creating a really complex geometry inside of a brick that could be mass produced in a giant print farm like ours. But an even better way of doing this is really very simple. Just imagine that the water is bullets, and if you want bullets to not go through something, you just need something vertically in their way. But air is able to move around and bounce up and down and that kind of thing in a way that water really isn't, because water has to fight gravity because it's so heavy. So what you can do is basically create slats, where you have one slat right here, one slat overlapping back here, and then another slat up in front. And then you end up with something like this. This is very lightweight and actually has multiple layers of slats inside of there. You can't see through it, but air can flow around the various slats inside of here. So we have multiple layers this direction, each one of them offset from each other. And then if you are to spray water into this, it hits the front slats, goes through a few of the cracks, but then it hits the slats immediately behind that. And then if it got even further, it would hit the slats immediately behind that. And then it drips down and can come out the bottom as a drain. So this is a really good way of preventing it because it's actually dang near foolproof. It's very possible that with super, super high pressures and really long times, you could force enough water through here because maybe it just can't drain out quickly enough. But if it's just being sprayed or rain is just falling or whatever it happens to be, you can do it. Now, since a lot of these vents have drains, orientation can be a concern with them because you might have a drain in the bottom, and if somebody turns it upside down, well, people would start spraying into here, and then it would drain in here, and then it'd pool up, and then it'd run out the backside. The easy way of fixing this is just to put a drain in all directions. However, if you put a drain in all directions, now you have water running in from the top, which means that it just bypassed the main vents. So it is best if the drain is only on the bottom because it prevents rain from collecting in the top and potentially getting past all the slats. This is a unidirectional type of event. Now, angles can come in from all sorts of ways here, but you don't want to have a shortcut in the top that's meant for drainage but is actually used as an ingress point if that's not what's intended. Now again, this type of part could be manufactured with other methodologies. Basically, you would cut out those 5 layers and then you would sandwich them together. But the problem with that is that you're now doing 5 different parts that all have to be designed, machined, and then reassembled. You have a ton of human time. Or you can just use printing, which can create a really complex geometry like this, and it would be less than the cost of the molds, and certainly less than the cost of assembly of that type of a complex system. This thing can cost a couple dollars pretty easily, or even less if you're going into large volumes above 10,000. But this isn't it. Now you actually have to optimize it because a yellow brick isn't that attractive. This looks like something that's industrial. This is a version of the vent that is actually meant to screw into a round inlet hole, and it has the exact same setup slats. Now, the challenge with this, though, that a lot of people miss is how to actually print it reliably. Many of these are designed to be printed either vertically or on edge like this, and that's fine, except for the fact that now you have these large bridges right here. The way to make sure that those large bridges don't require support or something silly like that is to insert sort of ribs inside of it. If you have ribs along there to where it's not bridging more than like an inch or maybe 2 in a big old stretch, then you don't have to worry about it, and this can print supportless. Now, a lot of people will make the mistake of designing it like this, orienting it like this, and then having the slats print this direction. And that's doable, and technically this isn't under a lot of stress, so it's not an issue, but you want those to be reliable, and you want to be able to press down on them and not have them break. If I press down on these, I could potentially snap them. And if the layer lines are going this direction, those slats will snap. So we put in interior ribs, which help support them a little bit and give a little bit more structure. And since they're in the plane of the actual leak right here, water flows in and then flows down here. The ribs are running this direction so they don't impede anything. And they're really thin so they don't cause any issues. But we'd rather have it print upside down. And now this hurts scale a little bit because you no longer get to do auto ejection. But again, this depends on your ultimate application. If you want the most durability, this is the way to do it. We then orient the layer lines so that each pass is going lengthwise along these. So that even though these slats are levitated above each other, all of the lines go in the path of the slats. So you basically have these very long, continuous plastic parts right here, which won't break off. They're both supported by ribs, and all the layer lines are in plane and running lengthways along there. A few people would design them incorrectly to have like the rastering go sideways across these lines, but that can be a mistake because now you introduced a point of failure. So just orientation is really critical with this. If you want to do mass production, you do want to design this to print vertically just like this. And in order to strengthen up those slats a little bit more, you might put them at a 45-degree angle so that they have more in-plane kind of layers. And then you design a support rib on the backside to hold it up so that there's no support needed anywhere else. But if you print it like this, you can actually make the slats thinner. This right now is about 1 inch thick because we have 3 to 4 layers of slats inside of there. And each one of them is about 1.5 millimeters thick just because we were overdoing it. But you could take them down to as thin as 0.5 millimeter if you're printing this direction and still have the water stoppage that you need. So if you need something really condensed and thin, that's absolutely doable. But if you're able to, 3D printed parts like to be chunky, so if you can keep them chunky, that's great. This is kind of a fully optimized design to where you now have a circular profile. It looks really sexy, it looks industrial, and overall you still have that function where water would spray in here, it would bump up against the bullet walls basically where the droplets would hit and then drain out the bottom right there outside of the enclosure rather than flying into the enclosure and ruining whatever you have there. But at the same time, you can still have a fan mounted back here that is able to pull air through here in order to make sure that you're actually able to circulate and cool the electronics on the inside. And the actual final design of it can vary. You can have the slats larger and smaller and vary the distance and spacing so that there's better airflow. This is simply a demonstration of how the concept would work. Hopefully that was useful to you all, and hopefully you learned how to kind of design vents and how 3D printing is really able to enable something that was never possible before. If you were having to stack up tons of these, you'd probably avoid it and deal with just like a low-cost vent close, and then people would leave the vent closed and you have all kinds of other human error type of problems that can come up. But by using 3D printing, you're able to create something very industrial, very professional, very reliable, with really complex geometries that weren't really feasible before in a single part, to where you can just grab it, shove it on the box, and move on with your life and never think about it again. Every once in a while, you have to design a 3D printed tab, something like this that might have a hole in it. If you are designing a tab like this, you end up having support underneath it, which adds a bunch of cost in production and actually makes it look really nasty underneath. So you want to avoid these if at all feasible. But if you are making these, just make sure that you round out all of the corners of them so that they flow really well. And you make sure to also round out the bottom so that you get the cleanest undersurface and supported surface that you possibly can. But again, these types of tabs can add a lot of cost to the part because you have that support and the additional labor that goes into it, and they just don't look very good. So if you want to make a tab or an overhang part with a hole in it, you should do it like this. This is the exact same tab, but instead we made it go through a chamfer on the bottom. This way you no longer have support, you haven't really added very much material, so you don't really add to the cost of the part, and it's much more durable than that tab would have ever been. So this methodology allows you to create something really durable, really reliable, and it is pretty simple to model, but it just gives you such a better feature with the same functionality as before. So it can still slot into wherever it needs to go, and the two things can connect together, but you don't have all of the shenanigans of this deal that includes extra post-processing and that kind of stuff. But this doesn't just apply to tabs with little holes in them. This can also apply to clips and clamps and that kind of stuff. If you have a part that clips onto it, a lot of people will design a clip a lot like this, where it's just sticking out into thin air. But that's not what you want to do, especially if you're making a clip. In that case, you want to chamfer the bottom of it as well. And what this lets you do is you're able to create something that is still durable and reliable, but again, it looks really clean, it looks really crisp, it looks beautiful, so that whatever it is that you're snapping it onto fits well, is durable, and all the rest of it. Now, of course, you have to kind of tweak parameters to make sure that these fingers flex the right amount that you want and that kind of thing when you end up making it thicker, but you end up eliminating so much support and you create a much cleaner, more refined and final surface finish, so that you can produce tens of thousands of these without having to really worry about overhangs, which can just introduce problems in mass production. But this also applies to other types of features too. It's not just clips and holes. You can also do like wire retaining loops and this kind of stuff. Wire retaining loops can help to be guiding features on the outside or the inside of the part. Again, very often people will try to do a traditional overhang because that's how it's always been designed. But with printing, you want to eliminate support. And if you want to have these sitting up in space, you want to put them wherever you possibly can. But you can see it's this kind of sideways loop that the wire is meant to be held through, and it might snap or be tighter, or however you happen to design it. You can have an actual snap feature there. But what you want to do is actually design it with two angles, because you actually have two surfaces. You first chamfer the front right here, and then you cut in and chamfer the other edge there so that it's up and then up again. That way you never have a horizontal overhang that can sag. You end up again with this really nice, crisp looking surface finish. The feature looks great, it functions perfectly. You can make it as tight or as loose as you want to, but you get that retaining ring without having to add the potential defects of support underneath each one of these features, as well as all the labor down the line. So hopefully this video was helpful to you, showing you how to make overhang features, mounting features that generally people just kind of misdesign because it's so easy to go into this mode of making this. But this ends up adding a lot of cost down the line and creates an inferior product. So how do you actually design some hinges? Today we're going to go through that and probably show you some hinge designs that you've never seen before. So hinges are pretty darn useful, but they're actually quite challenging to do inside of 3D printing because you have to deal with orientation as well as the strength of the hinge. So we're gonna start with kind of the least complex going up to the most complex types of hinges and how they can be useful and in what context they can be used. Now let's go ahead and start with the very simplest, a simple flat sheet compliant hinge. Now this is something that has to be printed directly against the bed. You're using the flexibility of the material to do it. Now the challenge with this is that since it is flexible, you need to be very cognizant of the material that you're using. This is PLA. PLA, when it bends past a certain point, will basically just snap. So if you're not careful, you can end up with a kink in your hinge that will never come out again. And then eventually it'll wear out. This is generally best for PETG, or again, if you made that really long to where there's a big old loop that it can make, then it can work with PLA. But this hinge is really simple to create and is good for just kind of joining two parts. You can actually use this type of hinge as a consumable too, just make it really small so that all the parts come off the bed together and then people can basically bend and break them off. This is really good if you're planning to upload them to like a service or something like that, because it can improve the overall adhesion of the piece. Rather than having this one come unstuck over here and this one keep on printing, they both are kind of linked to each other, so it's all a failure or everything is good. But how would you improve this hinge if you wanted to take it even further? Well, there's this type of hinge that is used in woodworking in order to allow the wood to twist to create hinges and joints and curves. And what this does is it gives you a lot more ability to create tight corners with a lot less material so that you don't have to create a big old long sheet that is able to bend. And the way you design this, you basically just cut out a lot of slots so that each one of these individual sprues is able to twist, and then you create the hinge that you want there. These are really, really useful. They're a little bit difficult to model compared to some of the others, but they're really great for simple compliant hinges that are also really reliable, really robust, and can be gone through a whole mess of cycles without causing an issue. Okay, now let's get into more kind of traditional mechanical hinges. Well, one of the easiest ones is just a simple mechanical linkage. You have a loop and you have a solid rod going through the middle. Now, the trick with this is that it does have to be printed in this orientation. This orientation is super important because you need that center pin inside of there, that is the crossbar. You want that to be in the plane of the layers, because if we print it like this, it's no longer in the plane of the layers, so it could potentially break off if you just have a central hinge because it'll tear out through the layers. Now, there's ways of dealing with that, and we'll get to that here in another couple of hinges, but whenever doing this sort of hinge, you want to print it effectively horizontally. And we've done demos of enclosures and boxes that use this style of hinge before. There's a lot of leeway with it and it can work fine. But the biggest thing with this also is to just make sure it's chunky. Some people try to make this really small and really fine and really petite, and what you end up is having the outer loops break off. So whenever using one of these types of mechanical hinges, just make sure that you're making it beefy enough to compensate for the inner layer adhesion. It doesn't cause a problem, it's just the design style that you have to follow. And you can create a really good, reliable hinge, but just make sure it's printed horizontally so that everything is as strong as it can possibly be. But Gabe, what if I don't want to print it like that? What if I do have a box and I need to print it up on edge? Well, now you can use one of the more unique sort of hinges. This hinge is basically a cone-shaped hinge. You can see that even though it's level there, I can't actually pull it out of the hole that it's inside of. And the reason for that is that the inside of this actually splays out and is coned so that it's all print in place, but you still have freedom of motion and no side travel. So this hinge actually can be printed vertically with both sides flat on the bed. It's still all retained, it's still all constrained, it's held together, but you get really good free flow motion in the vertical. Now, the issue with this is that this is a weaker hinge. Right now, all the layer lines are like this, so if I twist really hard right here, I can potentially break off this hinge. But again, if you make it large and chunky, you can compensate for that a little bit, and there's one more hinge type that is actually way better at getting this done. That hinge type is this one right here. This hinge is basically two cones on the top and on the bottom. And what this allows you to do is create a really robust contact point that doesn't have leverage. This can break off because there's a lot of leverage on that arm. All of the force from down here is applied up here, so you can break right at that corner up here at the top. But this one doesn't have a lever arm on it. The cones going into it are only about a couple millimeters or so you have a lot of motion and a lot of strength here, and you're never gonna break this off. Now the challenge with this type of a hinge now is, since it's not constrained the way this one is, this is a cone going up to the top and it's free, this one doesn't really have any overhangs that are an issue. This one has overhangs that are an issue and can cause fusing inside of the part. Even right here, you can kind of see the messiness because the top loop has to settle onto this bottom loop. And that causes an issue because now you have the material kind of falling down onto the other one so that one link of the hinge kind of acts as support for the other link of the hinge. This is not the end of the world, but it's not very robust. So there's a few things that you can do to kind of readjust around this. The way of doing that is basically taking this hinge and then just making the second half of it so that you have cone and then back up and then cone again. This way you are able to create something that doesn't really have the overhangs because everything blends into itself. And even though you have that center spiral, it can't break off because you have that baseline chamfered and really strong and reliable. So it's kind of a hybrid of this just standard one with just cones on top and then a center area and then a bottom. You actually connect to those two top cones, so it's a lot easier. The other thing that you can do in order to refine this even more is to put one cone on the bottom and then one cone on the top of the other link. This way you have nothing falling down onto the print at all. It's all just perfect vertical roofs that are a lot more reliable to print with. And the one other option is to again change orientation. This hinge right here has the top link falling down on the bottom. This hinge is this hinge, but printed on its side. This allows you to now put those cones in plane. And since those cones are inside of there and they're cones, they have no overhang again. So you end up with a really tight and reliable hinge. This linkage is really good for high tolerance parts and pieces. But this is printed on its side, whereas this one is printed in this orientation, this one is printed in this orientation, as if this was on its side. This is really strong, really robust hinge, generally has really good tolerances, but again, it has to be printed like this, which can be limiting because sometimes you have a hinge going up the spine of some sort of a part. But if you ever have to print something vertical like this, you need to be really wary of the overhangs because you cannot rely on slicer settings of it works on my machine, why doesn't it work on this machine? It's just not robust because different materials, different dyes, everything can change how that interaction occurs. So you want to make a robust print that's really reliable. Ultimately, the hinges that I love the most are really this compliant hinge right here, and then this side printed cone hinge. This has really good tolerance and really good mechanical properties, whereas this one also has really good mechanical properties, but creates a result that's just really nice. So hopefully that gave you some insight around how to design different sorts of hinges and the things that you can do with them. The reason this is so important is because there's a lot of applications where you don't want to be reliant on your particular 3D printer. If you wanted to upload something like this to our teleport plugin, where you want to sell a bunch of them, but you don't want to have to run a print farm, you just upload the model and then when a customer orders it, we print and ship it to them for you. If you want to do that, you need a robust model because our machines are not your machines. You want the model itself to be reliable and not have to rely on the slicer settings or the material or anything else. Just design well and all the slicer settings become irrelevant.
Hello everyone and welcome to this episode of Design for 3D Printing. Today we're going to talk about rods and how you can actually design them to be optimal for whatever your application happens to be. So starting here, let's just start with a standard rod. It is a perfect cylinder and it's designed to be printed vertically like this. If you're designing something like this, always make sure to chamfer the bottom of the cylinder so that you don't have to deal with any sort of material deformation and you're able to get a nice clean base off of the part. This piece is viable and can be produced okay, and there's not too many issues with it. In fact, it's kind of optimal because it's very easy to be ejected from the bed. However, the issue with printing a part like this is overall strength. It has slightly less strength in the Z-axis so that if it is very long, it can actually be broken fairly easily. So this is fine if you're looking for reasonably high detail and fairly short. If you're making it too tall, then you can start to get material shrinkage issues and even vibration issues up at the very top of the part. So printing like this isn't always the optimal way to produce a very tall, skinny part. If you are making something tall and skinny, you probably want to lean it sideways. This way, when it's printed, the layer lines are in the plane of the rod itself. That way you have something that is much stronger or as strong as really any other process would ever produce. But the issue with doing that is that if you lay it sideways, then you have a part kind of like this, where you have a very small surface contact area with the bed, which needs some type of additional support like a brim. And you don't always have a high level of reliability because with so little contact with the bed, the part can actually cause high rates of failure like this. So while you want to print it on its side, you don't want a perfectly curved surface against the print bed itself. You want to ensure that it is always
has a decent amount of contact. In order to do that, what you could do is just take the rod and then flatten a single side of it, just like so. This way it has a flat surface to sit on the bed and can reliably be printed. When creating the flat side of one of these circular rods, make sure that the tangent angle from wherever your cut is at least 35 degrees. That ensures that this rod does not have any sag on the outer side. And it's a very simple definition of what the maximum cut can be. But now you have a circle with a slight flattened area that is not always ideal. So this might not be the optimal way of getting it done, but you do have 95% of a circular profile on this rod, which is just about all you need, but flattening one side of the circle is a very easy solution. But this all assumes that any rod or shaft that you have to create has to be circular. It does not. You can actually use hexagonal type of patterns, and these types of rods are fine. You can actually take it all the way up to almost a 10-sided profile where it will still be able to print reliably, but you want to ensure that the single bottom angle is not more than 35 degrees. So you're kind of restricted to almost an octagon at the highest. But this allows you to have a high level of contact area with the bed and a generally circular profile, though you may have to change the holes that it is going into. So hopefully that gives you a little bit of information about how to design rods for 3D printing. You can go vertical and that's okay, but once it gets tall, it can get a little bit finicky. Laying it sideways, you have to make sure you have a flat surface, which means that you either have to flatten the side of the rod or you have to go for an overall hexagonal rod so that you have good strength and a good consistent outer profile and geometry across the entire part.
You know, on those days when you just finished up a hard workout, you just got done sacrificing sweat to the gods of iron at the temple of swolitude, and now you're ready to take your workout recovery formula and you reach in and you pull out that scoop. We're going to talk about that scoop a lot today. So the design of a scoop actually opens up a lot of really interesting situations because even though it's a very simple object, there's a lot of things that go into actually designing it well if you want to mass produce it for 3D printing or if you want to print it on demand through something like our Etsy or a Shopify plugin. So we're going to go through how that scoop could be designed to be printed and how you can completely recreate it so that it's actually perfect for 3D printing. So let's just start with the normal scoop, the cylinder with a handle out the side of it. This thing is terrible for 3D printing. First of all, if you go ahead and start printing it, you have the handle up in the air, which means that you will have to support that handle, which means the handle is going to be rough on the underside, which means that you have a bunch of wasted material from the support, and now you have just a terrible product coming out of 3D printing. This is a very traditional situation where someone attempts to 3D print something that was designed for injection molding, and that is an easy street to a screwy, terrible product. What you want to do is make just a few tweaks in order to make this object actually really good. The very first one you can do is turn it upside down and print it facing down, face down on the build plate. Now the issue you have is that you now have the bottom of the scoop at the top, and that means that you potentially have overhangs that could catch all kinds of stuff. It could be all kinds of issues there. Now, instead of having just a flat bottom to it, you could instead round it out. You could apply just a fillet to the inside of it. Now it's domed, so at least now you don't have to worry about the overhang problem as much, but you still do. Actually, fillets are the worst for this kind of an option because a fillet goes from vertical to eventually horizontal, which means that you potentially still need support. If you want to go fully supportless while still having really tight layer lines and a very refined surface finish on the inside, what you want to do is use a chamfer. And while this looks a little bit weird from a CAD standpoint, it is a better way of doing it because all of the layers will be tight and secure and reliable and you don't have to worry about anything. And on the outside, the scoop looks the same as a normal scoop, so no one would ever have any issue with it, so long as you make it just a little bit bigger so it still has the same internal volume as a regular scoop. And since you're using 3D printing, that extra volume of material is actually filled up with air and infill. It doesn't actually really use much more material because you don't have to fill in that whole volume with material as you would with any sort of traditional process. So turning the scoop upside down and putting a chamfer in the bottom lets you create what is now a very good product. It looks the same from the outside, it functions the same on the inside, you're able to use the process and you're able to get a good result out. However, there is one other thing that I have to emphasize here. When you turn it upside down or when you print it vertically, any direction, make sure you apply a 1mm chamfer. to the bottom of it. This makes sure that there's no way that that first layer can extrude sideways or inward and is always perfectly crisp and has nice clean edges and not some little sharp or kind of catchy edge, which can happen when you have a feature called elephant footing happen, where the level of the machine might be off just a little bit or the flow might be a little bit different. Applying that small chamfer ensures that is impossible and can never really happen, so that you have a really crisp and reliable part, and you can produce tens of thousands or hundreds of thousands of them in a large print farm like ours. Now, all of that was how to make this scoop that was meant for injection molding 3D printable. That's kind of a bad way of doing it because it starts with a bad premise. You are starting with something that doesn't want to be 3D printed and you're making it 3D printable. But what if you wanted to just make a 3D printable scoop? Okay, here we go. Now we get to get interesting. Well, if you want to make a 3D printable scoop, you do want to print it bowl up. You want to have that facing up in the air, but now you still have that pesky handle on the side. Well, the very first and simplest solution of this is to put that handle not on the top, but on the bottom. Now you have the handle against the bed. You have the bottom of the scoop against the bed. You have the bowl upward, so you don't have to have that chamfer on the inside and have to worry about overhangs at all. There are no overhangs. And from a user experience standpoint, it is no different, and in fact would be even better. If you've ever used one of those little powder scoops, then you get your hands in the powder when you're scooping along there. But the reason they have that handle up on top is because that is where the mold comes together, and that's the easiest place to put the parting lines, so putting the handle at the top is easier. But putting it down at the bottom is better still, but they can't do it. You can with 3D printing, however. So with 3D printing, you put the handle down at the bottom. Now when you scoop, you're fully isolated from whatever it is you're scooping, because the top of the scoop is actually the diagonal distance to the tip of the handle. So you have improved the product now while also making it vastly more manufacturable for this particular process. That is the simple solution. Now, if you decide that you really want the handle up on top, or that kind of form factor and ergonomics, then rather than having the handle down at the bottom, extend it upwards. Make it a slab out the side. Make it a flat edge. And again, it's not really adding that much more material or even that much more print time to the whole thing. So now you have a nice big gripping area that could be thick and chunky if you want it to. If you do want to add more material, you can improve the feature of this. In the context of this discussion, we're talking about a tiny little scoop, but this applies to any sort of scooping object that you happen to do. It might be a ladle, it might be an oil can, whatever it happens to be. But going back to our little whey protein scoop, the scoop now has a wide handle along the outer side. Again, make sure you're chamfering the bottom of the whole thing to make sure it stays clean and clear. Now, if you do not want that whole handle and you want to optimize that supportless handle, you don't have to have it all contacting the build plate. And in fact, you sort of don't want it to be, because having extra contact with the build platform increases chances for errors with the build plate. You could have contamination, you can just have warp, you can have all sorts of little artifacts from just layers smashing against each other on the build plate. So to avoid that, you minimize build plate contact. You can do this by just cropping off that handle, applying a chamfer to the bottom of it so that it grows up to where the handle is. People can grab from the top. It's fully supported without having support auto-generated. So you have a very clean, crisp, known product where you know that it will come out and be reliable every single time. Now you've created a new version of the scoop that is fully optimized for 3D printing and has features that were never really usable before because everybody else was always minimizing everything. So this is something to be aware of. A lot of people right now at the time of filming of this video try to take an injection molded design and 3D print it, and that is a losing battle right from the start. If you do that, you will almost always fail because injection molding is designed with completely different rules. It is for minimizing material and putting in struts and ribs and that kind of stuff, and all of these things to minimize and squeeze and push and all the rest. Whereas 3D printing lets you make really fat and chunky parts, and if you lean into that capability, you're able to create completely original parts that are both more competitive because they're truly different than all traditional past processes. They differentiate you from your competition, and you're able to create new features that were never very easy to do before. This technology enables so many new ways of making stuff, but you have to understand it as well. It has limitations. You have the bed adhesion, you have overhangs, you have all these different factors to consider. So you can't simply pigeonhole an injection molded design into 3D printing. You can
make some adjustments in order to refine a molded design. But you ultimately want to start with a 3D printing design because it gives you so much more freedom and an entirely new direction to where you can now be competitive against what anybody else is doing. Holes seem like something that should be pretty darn easy, but when you're trying to make holes that fasteners are supposed to be inserted to, it can get a little bit more challenging. So in this video, we're going to go through all the different ways of making holes for screws to go into, and the ways of designing them so that they can be optimized for mass production. So the very first version of any hole is actually the most basic, which is to just design a hole that is slightly larger or even slightly smaller than the fastener that you plan to go into it. And then you can either use a self-tapping screw or a standard screw itself that just binds into the plastic and sets itself. This is fine for low criticality situations, but even though these are pretty simple to do and are actually benefited by the layer lines of 3D printing because they provide the ridges for the threads to go into, it's not always the most optimal because there's a limit to how much you can bite into a 3D printed part without causing things like layer splitting, and you have a limited amount of control of the dimensionality of those holes, especially when they're small. If you're doing a hole from the top, doesn't really matter. Just make sure that the walls are quite thick, at least 1 millimeter. If you're doing it in from the side, sometimes the holes can sag just a little bit and you end up with a slightly squashed circle. The way to compensate for that is to actually make the hole slightly oval. This makes sure that you end up with a perfectly circular hole as a result, and a screw can screw in more easily. However, that's the only if you are wanting to do standard holes without a lot of effort or adding in other hardware. You can improve the strength of threaded holes by doing things like heat set inserts. Heat inserts are a very easy way to add threads to a plastic part because you essentially just melt the threads into it by adding in a small metal part that is sunk into the holes. With this, you want to engineer the hole so that it has room for the insert going into it, and also want to ensure that the part as a whole is almost solid and there's about 1 to 2 millimeters of material around the hole itself. This is something to explain to us in manufacturing in order to ensure that you have a part that is reliable and can accept the heat inserts. Or have us quote the insertion of the heat inserts itself so that we can make sure that the parts are good and can produce them and deliver a final part with heat inserts in it. However, this is a kind of an old traditional way of creating threaded holes inside of plastic parts. With 3D printing, you're actually able to do impossible things that have never really been possible before. Right here, this part has metal threads inside of it, even though you can't see them. And the reason is because we have inserted a nut into the part in both directions of the holes. The reason for this is since we are additively building this part, you're able to grow up the part, create a slot for a nut to be dropped into it, and then the part is able to continue on printing. So now you have an embedded nut inside of the plastic part, which has never been possible with any other manufacturing process and is a unique benefit because now you can have a very large flange back in the center of the piece so that pull-out is effectively impossible. Whereas with heat inserts, you only have the wall adhesion essentially holding that insert in there. With a flanged nut inside of the part, you are able to ensure that pull-out is not really a possibility at all. And you can create something very robust and you can have any size of thread that you want and very reliably. But what many people end up doing and wanting to do is going back to just the standard plastic hole and adding threads to the model itself. While this can be done, and in some cases is very useful because you eliminate the secondary processing that nuts or heat inserts do, there's a limit on the size of these because this case has very small holes with M3 threads put into them. But you can't really see the M3 threads because they are so small that the nozzle of an FDM machine can't really print them. And even in the side hole, they're so fine that the nozzle is wider than the threads themselves. So you basically just end up blending them out and they're not really effectively there. If you're going below a fastener that is smaller than 1/8 of an inch diameter, very generally the threads will be too small to actually be printed. You want any single feature to be at least 0.2 to 0.4 millimeters in size. And since threads might start there, but then go down to a taper, they very often are just immediately ignored and you end up with a hole that in the model has threads, but in practicality really doesn't. And this is something to be aware of. If you are going to do 3D printed threads inside of a part, you need to ensure they're quite large. And you end up with
size fasteners like this that are so much larger. Now these are great because you have them integrated to the part, so you've eliminated that post-processing, and they're also reasonably high strength because they're part of the part. You don't have to worry about pull out or adhesion issues from secondary inserts. But what you do end up with these sorts of situations is the threads coming in from the top are fine because everything is vertical, but the threads coming in from the side, you end up with that hole sag that we discussed before, where the overhangs right here at the top end up creating kind of an oval hole, and the threads aren't really present at the top or the bottom because the very tip of the thread is a point, which is so small that the nozzle doesn't really identify it because it's 0.4 millimeters in diameter. You can ignore it, but then you have the sag and the hole can change the diameter, and the screw-in force can vary within the part or within the design. So if you want something very controllable that will definitely print successfully on the first try and into the millions, which is something you definitely want to pursue, you want a feature like this, where you effectively cut out the top and the bottom of the threads to where you still have the threaded sides where it's strong, reliable, and firm because it's in the plane of the layer line, so it's the strongest point anyway. But you also eliminate the overhangs on the top and the narrow islands at the bottom that wouldn't be present otherwise. And you're able to pull them away and create a perfectly symmetrical hole with two cutouts on the top and the bottom that have a reliable threads throughout so that you can put a fastener into here quickly, easily, without resistance, and ensure that every one of these holes prints perfectly every single time.
So if you're exploring the option to have a product 3D printed, there's a number of things that you just don't really want to do, because if you're going to produce hundreds of thousands or millions of this piece, you just don't want to have potential for errors or problems come up. And one of those main issues that can come up is the need for support. These things are really undesirable because at the very least, they're going to increase post-processing, having to go through a tumbling process in order to have those knocked off. Or in the worst case, it can radically increase the cost of a part because they require a human to come by and pull these off, because for any individual part, it might not be automatable. So in order to maximize the efficiency of the 3D printing process, you really want to minimize support and have as little of it as possible. And if you're able to design your part so that these things just are not necessary, that is the ideal situation because it'll make a part much more reliable, much more affordable, and very often just makes it look a whole lot better because you no longer have the interface areas where a part of the part is falling onto support. So in this video, we're gonna go through some of the most basic solutions to get rid of all the nastiness that can come from having support material of like a traditional slicer. So supports are necessary. For example, on this piece, when you have this horizontal edge that sticks straight out into the air, this has to be supported. Otherwise, these edges, these bottoms of this part, when it's printed and the nozzle is coming along here, would just drop and sag. So you can't have that. You have to have something underneath it to support it. That is the most common issue. So this might be the fingers of a part or some edge, or in this case, like a structural right turn. But then there are also bridges, and bridges are when there is just a long gap from one vertical to another, the space between a pillar. And that has to be supported as well, because again, as a nozzle is laying down that first layer, it can partially sag. Now, supports are fine and you can have these automatically generated inside of a slicer, but the issue with that is that you don't have an exceptional amount of control. And again, you have all of this waste material that could be embedded into the part. So instead of having material that is torn off and thrown away, you can have material that is part of the part, making the part better. So one of the most simple examples that many people default to is to use fillets. And fillets are fine because you now take what is like a long bridging distance and you turn it into a dome so that it no longer has that sort of supported bridged area, or you have it slowly raise up there so that you don't need as much support. But the problem with arcs and fillets is the fact that they do eventually become horizontal. That is the nature of a fillet. It is tangent to the place where it starts and to the place where it ends. So if you have a very long horizontal overhang, you still might need just a tiny bit of support right there that has to be pulled off. And that's not really great because you just lost the benefit of the thing. However, sometimes the design of it requires that you use arcs. Maybe there's a hole or a pin or something inside of there. So it's an option, but it's not really an ideal option and it's not always the most optimal option. The most optimal option is to use chamfers. And chamfers are great because they actually eliminate the need for any other sort of support. Since they are a 45-degree angle and a consistent angle all the way up, you no longer have the sudden horizontal feature that can come up with like standard fillets. Fillets have an issue, chamfers do not. The other option is that you can actually go all the way to the tip so that there is no support needed anywhere. And chamfers on this channel, we have said many times, are really awesome because they just have no exterior need, other post-processing. This part could come off of there fully complete. And the thing that you want to hit on, because now the machines can automatically eject parts, move on to the next one, and it can produce hundreds of thousands of this part and have it be more affordable and scalable than other processes that you might have it mass produced with. So when you can use chamfers, this is really the option that you want to use. Now, here's the thing though. Ultimately, within all of this stuff, the best option to use is no supports at all. So if you have a cavity or a bridge or an overhang, really the very best solution is to just fill it in. Go through and change your CAD model so that it is filled in with solid volume. Because rather than simply having these empty air gaps right here, we'll fill them in with material and with infill, and they will basically have very close to the same amount of material anyway. So anytime you can just get rid of these overhangs or these indents or anything else and just fill it in as a solid block, that is the ultimate solution. Now, sometimes you have to have an area that is supported, and that just happens. The geometry will require it. But again, you don't really always want to default to the manufacturer slicer because there is differences in settings. There are all kinds of variations in how things actually work. So if you can control it inside of CAD within the parameters of a standard machine that has a 0.4 nozzle and a certain flow rate and that kind of thing, it's much easier to design supports inside of CAD. That way they can go right where they need to be. They are absolutely minimal and they're very easy to control and tweak as opposed to trying to find the magic recipe that your printer was using when you were making your prototypes. And that is a situation like this. In this situation, we use designed supports. And with design supports, they're basically just a small block that is printed completely hollow that then comes up to a point wherever it needs to be supported. And this is a great solution for helping these types of parts because at the end of it all, not only is it well supported and a minimal amount of material, but it breaks off exceptionally easily. Now for this part, the center support here, you want to actually make them kind of a teardrop shape because since they are sort of interfacing with the lower part of the part, there's a lot of friction right there and giving it a rounded lower surface is ideal for that sort of situation. Just slightly rounded, not a ton, because again, it has to be built reliably and you don't want an unstable teetering piece of print there. But it is very easy to make this sort of designed support so that you have a good, reliable part that has all the critical features that you need, but is not wasting big old blocks of material like this in order to support an area. Instead, it's using very minimal amounts of material like this to support an area. So hopefully that runs you through the very most basic ways of just getting an overhang supported in a mass production part. Obviously, the best solution is to just not have that overhang. But if you do need to use supports, please try to design them in CAD because you can make them much more reliable, much more consistent, and much easier for your contract manufacturer, like us, to actually get deployed without having to worry about any sort of translation issues between whatever machine you might have been prototyping on and the machines that we actually use inside of our large print farms.
So a sphere is one of the most difficult things to print in all of 3D printing. So in this video, we're gonna go through 8 or 9 ways to actually print a sphere and have it be just as crisp as possible. So why are spheres so tough? Well, the sphere is mainly difficult because it has no flat edge to it. Everything is perfectly curved. And whenever you have a curved surface straight against the bottom, you have it go from basically horizontal up to a little bit less horizontal and then finally into an angle that works. But that means that you have all sorts of issues with it. So we're gonna go ahead and show you a few of the other models. We have 8 different versions here, but let's go ahead and start with the most basic. The most basic version of printing a sphere is to set the sphere down on the print bed and then let support support generate around it, and that is this one right here. But the issue with this is that you end up with this kind of unintentional little flat side here, and very often the support is not even that good. If we pop that off, you can kind of see how you have this deformation on the bottom. It's not bad, but there's this outer ring to where it kind of goes from flat up to starting to curve, and then you have some shrinkage there, and it gets really tough to make it really clean and crisp. And then of course you have that little flat edge, which just kind of messes with the look of the sphere. But from the side, and hopefully you can see it here, from the side you can see that it sort of has this bowing in it, kind of this ripple, this suck in on it. It's just not that great. So the standard way of printing a sphere generally is not very good because you just don't end up with anything very crisp. This style of putting the sphere down on the bed is also super unreliable because if that first tiny little part doesn't stick really well, then the whole sphere can get ruined. Now you can get around this and you can just design it with a small flat on the bottom anyway at the correct angle. So you design this so that at 60 degrees, that's where you cut off the bottom of the sphere. So you can get something that is much more crisp and much more intentional looking without all the randomness of the overhangs that come with a standard sphere. And then if it's sitting down on the table, it's fine. No one would ever know it's not a regular sphere anyway. And you get rid of this messy little pock mark on the side and you instead have a stand base. But this isn't technically a sphere, so we can't talk about this. All right, so if we want to eliminate that little pock mark, that bed surface area spot, then what we can do is lift the sphere up off the bed, like what we've done with here. Now, some slicers don't allow you to lift it off the bed. So in order to design a sphere that is lifted up to where it's entirely supported, what you can do is you can design it with a disc down against the bed and then space the sphere out from that. That way you know when this model is uploaded, that sphere will always be printed up off of the bed, and then support can generate underneath it. And let's see how that looks. It's a little bit sticky. There we go. So this is when it is totally supported straight from the bottom. You know, it's not that bad. It actually has a little bit less deformation than the other one, and you don't have as clear of a dot. So this is the one that was against the bed, and this is the one that was sitting up in supported area. That's not bad. This one would probably be a little bit easier to sand down if you were doing that, but this one, it's not that much of a difference because you still have kind of that infinite overhang to where the layer lines are just spaced so far apart that you're gonna get some sort of deformation down there on the bottom, and you can see it right there a little bit. They both kind of have it. So supporting the sphere really isn't quite the correct solution because you have this really flat surface that then really gradually starts to accelerate, and you get this deformation as it transitions up. So it's not the greatest situation there. The other issue with supported spheres is that the sphere isn't really sitting on the support. There is spacing between the sphere and that support, which again can lead to failure because if your support is too far away from the sphere, then it can just break loose and the sphere falls off the support and doesn't print really well. Now, again, I want to emphasize why this is so important. The design of objects is so important because you might want to have them mass produced. You might want to upload them to a service like Portals where they can be printed and shipped straight to customers for you. And in order to do that, you cannot rely on print settings. So the best way to make a part that is manufacturable is to make a part that can be made anywhere, anytime. And you do that inside the CAD. So it's really, really important to make sure that you are designing parts that are reliable and robust so that they can be uploaded to any system at all and be produced reliably. So how do we get that sphere held down? Well, the very first thing you can do is just design a little spike up into it that holds the sphere up where you want it to be, but then it holds the base of the sphere steady and solid so that it can't move around inside the support and you can get something a lot crisper. That is what one of these is. So if I twist this, you will see down on the bottom is a small circle inside of there because I designed this peg straight off this bat. And this is a little bit of a fatter peg. So let's go ahead and see if I can just leave the peg there. You can see it comes off very cleanly, very nicely, and you can see the sphere still kind of has that deformation. And since this peg is so fat, the issue that you run into is that you now have a hole in the bottom of the sphere rather than a flat edge. So we haven't gained a whole lot because again, that outer edge, that transition basically from like 30 degrees to 45 degrees, you end up with this shrinkage. And you could tune slicer settings for until the cows come home, but then as soon as material or the color changes, then it would all break down. So you gotta find something really reliable. I went ahead and made another version of this that has a really small pin on the bottom. So this is super small pin. So at least now you don't have the hole on the bottom. And if we take a look at that, that doesn't look terrible. Like, again, you still have that deformation ring right there or so, But that smaller pin did what we wanted it to do. It held it steady. You now have a nice little reliable print that has auto-generated support around it. But again, we're not to a perfect sphere yet, and we're trying to get to a perfect sphere. So what can we do? Well, it seems like the slicer is actually what's stopping us from doing a good job on this. It is the thing that is giving us all the guff because it can't generate support that is tight enough or cool enough or has enough room around it. So what I did is I went ahead and designed the support myself. So we'll see how this works. This is a very simple version of design support. Again, the sphere up in the air. That cylinder underneath is an offset design that is 0.2 millimeters from the sphere. But the sphere is not simply resting on it. I didn't want that. The auto-generated support is a sphere simply resting on it. You can see that curved surface right there that the sphere sits into. But that's obviously not working based on all our other things. So I designed this support to have several sprues inside of there that hold on to the sphere. Because if we have this issue where it's shrinking right here, then what we need to do is hold it so that it can't shrink in and move. So we'll see how this looks. I haven't actually seen if one of these works right, so we'll just give this a twist. Oh, that felt really good. So all the sprues just snapped off and it broke loose. And you can see right here, that's the support itself. That all looks really nice. It looks really crisp and clean, and it's also really easy to post-process because it's a solid thing. But there's that deal. And you know what? Here's an interesting situation. So the shrink line problem that we've been having on all of these appears to be right where you transition from support to the regular sphere. So it's not really contact with the support, it's actually seems to be more of a cooling issue. But right here, you can see this is the one that has the design support here. And you can see just a little shrink line right there, which is directly in line with where the support disconnected. But the bottom of it looks really, really good. Like, so this is one supported with the pin, the fat pin. And you can see it's a little bit more deformation from just standard supports, whereas the designed one is just really, really consistent. And this again is a 0.2 spacing all the way around. That looks really good. Like, I think that's really warm. But we've discovered now that there is a shrinkage problem. When it's down in the support, there's not much airflow going by, but then as soon as it becomes exposed to the air, then you get a different amount of shrinkage and your sphere kind of starts to deform and you get that kind of shrink line. So what if we never had it exposed to the air? Again, you can't do anything with standard supports, but you can do something with design. So I designed this. This is basically a set of finned supports that does the same things as that cylinder that we were looking at before. But hopefully these fins all the way around the outer edges will give it much more airflow while it's printing. Other than that, all the spacing is the same. Alrighty. Oh, this is fascinating. So this is what the support looks like. Again, just a finned star pattern holding it up. But if you look at the bottom, you can see the star pattern. You can see where the shrinkage happening, because right here next to where the stuff is holding it up, heat is condensed. There's a lot of material to be cooled down, and even when you're blowing on it, it's going to cool differently than in between these tines. So now you have this star shrink pattern. You can see some of the little pips from where the sprues separated, but it does have less of the shrink line than the perfect sphere did. But you can see that, yeah, just the pattern is there a little bit. So clearly though, design support is working way better than standard generated support because you just get such a crisper amount of control of it that's very detailed and very defined. You generally don't want to go much smaller than 0.2 because you're going to end up with issues of the STLs being fixed and thinking that there's an error in the actual model itself. So you don't want to do that. But there are a lot of ways of refining these. But there's also one last and final trick, which is a little bit of a cop-out that I want to show you. So the warping issue seems like it's a problem with the actual geometry of the sphere, and there's not a lot of ways of getting around that, even by having fully custom designed support. So the question might be, do you actually need a sphere? Now this is really important. You might not need a sphere, you might just simply need a curved object, because if a sphere is giving you these sort of bottom deformations that are not really what you're looking for, then you might be able to just change the shape
just a little bit to make it slightly oblong, start to make it a little bit oval, because now you start to have a steeper incline. So with this one right here that's a little bit egg-shaped, if we pop it off with all the exact same design features and then trim this down, we have a sphere over there again, and then we have the slightly egg-shaped one. And it's not a ton better, but you do kind of eliminate that large shrink ring because it is able to just move up more quickly. So since it's a steeper angle, the layers are able to stack on top of each other so that you don't have potential shrinkage or overhangs that can be a really big issue as compared to a regular sphere. But I would say from this, it's not really substantial. So there might still be better ways of getting it done, but let's go ahead and take it straight to the extreme. If we take this one and look at this, now you can see it's pretty darn crisp. But again, you have this initial steep area where you have a layer and then another layer way far out from the side. So trying to get a perfect sphere right off the bat is almost impossible without just flattening the edge. So hopefully you were able to learn a little bit about how to design spheres and all the things involved with it. Really, you're just dealing with a very complicated geometry when you're dealing with 3D printing. And regardless of the resolution in 3D printing, the smaller the sphere, the steeper the angles, the higher the overhangs, the more problems you can have. So while these are all tricks that can be used around designing support, making sure spacing is right, using sprues and that kind of thing, spheres are just very difficult by the very nature of the geometry.
Hello everyone. So today what we're going to do is go through how to design pins for additive manufacturing and 3D printing, mass production 3D printing. This is kind of the traditional way of designing pin and holes for finding features. It might be the lid or something else of some device. If you do have a design that for some reason requires these pins, generally what we would try to do is print them vertically just like this, but that would require that there be support underneath these pins, which is not the greatest option. It can kind of deform them, and then you'll have to kind of redesign these holes to be a bit larger. You just lose a lot of precision if you have to print this vertically. So you always want to be able to print stuff horizontally, laying flat on the bed just like this, if at all possible. So what we're going to go through is actually optimize this and show you a few different solutions that can improve this quite a bit. One of the simplest solutions is to actually just go with a chamfer here. If these are simple finding features that don't need to have a press fit or a friction fit of any sort, just go through and turn them into something like this. This allows them to be printed in any orientation, and even though it looks like they're increasing the volume of the part, they don't actually increase print time or print material because you're not filling that up fully solid. So this makes it easier to find if you're doing just a standard finding feature, and you can adjust the size of these cones as much as you want. And now these pins are no longer really brittle, because when we didn't have those chamfers on them, if these were printed, they would break along these layer lines very easily, so you'd have kind of a limited lifetime on them. But if you then add these chamfers, it becomes really easy to produce them. And of course, you'd want to clean it up and optimize these to the angle you want, making sure that they're within 30 degrees. So that's solution number one. Another thing to point out, these pins are redundant. If you have 4 pins on a top of a surface that only has to be restrained in 2 directions, you do not need 4 pins. So here, I'm just going to crop these out very quickly just to show what it looks like. Generally, you would want to do this very early in the design to make sure that you don't have something silly left around there if you don't need them. Literally, all you need is those 2 pins, and this lid would still be fully constrained and would not rotate or move and would still square up just the way you need it. So do not add extra features if you don't need them, because they just increase the complexity of manufacturing. So that's just kind of a side point of things to be aware of. But neither one of those are the good options. Pins are not really the best option for printing because they're just not very efficient. So what is the way to get this done? Well, we're going to start right here. Imagining that this is an enclosure and it's a lid and we don't actually have a block that just is being screwed together, I'm going to go ahead and create this. I'm going to make that 40. That way we have a nice clean 5 millimeters on either side of it, and move this in from here to there by 10. And then we should be able to just mirror that right over. -5, take that in there just like that. By a happy little accident, I had that designed right into the main plane. And then over here, what we're gonna do is we're gonna create fins. Those are the slots, these are the fins. So with fins, what's great about them is that they're very reliable, very robust, and can be placed all over the place, but also be designed to be really optimized for printing. Let's go just like this. And then unfortunately, this one will do the same thing, but I'm gonna have to create a new plane. I want that to be 7. There we are. Now, here's the thing. If we want these fins to be really strong and not broken off, and we don't want to do like the traditional chamfer or fillet where we put a great big old fillet over here on the side in order to strengthen it up, which we don't want to do, we're going to actually print these boxes vertically, which might not always be possible. If it's not possible, you'll have to reinforce this with chamfers or something else along those lines. But you still have more inner surface area so that if it's printed like this, it's still stronger than an individual pin because it's supported laterally, and you could actually do something where you do like a cross beam in order to find the locations rather than circles, which aren't that great. So what I'm gonna do is I'm gonna create a mid plane just like this, and then let's mirror that over. Mirror this feature just like so, and then mirror plane right there. Okay, cool. So now these fins will go into these slots, and that's fine, but we want to be able to print these vertically, and you don't want a vertical overhang right there. So we will be using chamfers just like this in order to turn these into a bit of a finding feature while also improving their manufacturability. And we're gonna take that all the way down to the 7, just like so. Now it will fully center and line up over there just the way we wanted, but you can now print this vertically and that fin won't have any sort of problems, but it will slot right into those slots very quickly and easily. And you will have something that can be like the top of an electrical enclosure. You can make this larger and put the fins around the outer rim of it. And what's great is we only have these 2 fins. You do not need to have horizontal ones there because it's supported in 2 dimensions. You could actually get away with just 1 single fin if you want to. And again, eliminating features is always a good idea if you don't need them. So that's kind of the layout for creating an alternative to traditional pins and holes, which can be very brittle when printed, and instead find something that's a lot easier to place because no longer are people having to find holes, they're just having to find a big old slot. So assembly gets much easier as well.
This is a machined pulley taken off of a piece of industrial equipment, a piece of our industrial equipment. The problem is that this pulley is really expensive and there's really no reason for it to be. So in this video, we're going to talk about why this pulley costs what it does and why this pulley is so much cheaper. So first of all, let's look at this pulley. This is a machined pulley. It has started out as a block of steel and then was carved down and sculpted until it made this pulley. It's very durable, it's very reliable, and it's very expensive. This pulley or ones like it cost anywhere from $100 to $200 to $300. Because turning a block of steel into a refined geometry is difficult, and when you are making it for industrial machinery, it's not necessarily very high volume. If this was a car part, it might cost like 20 to 50 bucks. But since it's for something fairly specific and fairly uncommon, even though it's a timing belt pulley, which is not that weird, it's still very expensive because there aren't millions of these. There are maybe tens of thousands of these made per year. But it has to be made this way. You wouldn't make this out of plastic because since it's so thick and chunky, plastic through traditional processes like injection molding would cause shrinkage, which would deform the teeth and deform the outer area and most certainly deform the inner bore. So in order to have a part that is structurally reliable, you have to make it from machined metal. You could potentially cast it, where you would throw it into like a sand mold and get it out, but then you would still have to do a final pass with machining. So you kind of lose the cost advantage of that process because it's a reasonably precision part. The problem is that metal is way too strong for what this does. It is a timing pulley. It's not under high tension. In our application, it actually runs a puller on our filament extruder that is making filament for you guys and for within our giant print farms to reduce our material costs. This pulley is not under stress. From a structural and kind of strength engineering standpoint, it's fantastically over-engineered. So what did we do? Well, we went ahead and like good little engineers, we 3D printed it. Now that's all fine and dandy and everybody knows that you can 3D print, copy and 3D print a part. But that's not the end of the story and the value of that is kind of lost on folks. First of all, many people say, oh yes, we can 3D print that ourselves, we got a printer in the office. But the cost of that print is not the cost of the material. That has nothing to do with it. The material cost for this, yes, is trivial. In fact, when it's made out of steel, the material cost for this is trivial. It is all the time that goes into it. Having an engineer redesign this pulley costs $150 to $200 per hour of their time modeling this. Having that engineer then run a printer takes a bunch of time. Convincing everybody that that plastic pulley is okay takes a lot of time. So the cost is not zero. But let's look at this in a production context, and let's compare to this gear. The reason we had to recreate this pulley is because we needed one that was bigger. And we ended up creating a couple of different sizes. And that is where the value of this really came in. This pulley, to get a different size of it, was very expensive, and to return it and move it around was all really tough. And it's also very heavy. It's tough for the machine to move around. Making it out of plastic gives us a pulley that is lighter weight, therefore easier for the machine to start. It has less inertia on it. It also allowed us to iterate through sizes. We were able to try about 3 different sizes of these pulleys in the printed format to be used. But what people don't realize is that even though this pulley was made out of plastic, it is also actually functionally as strong as the steel. This is not running the gearbox for a drag race car. This is turning some wheels on a conveyor belt. Plastic is fine. Most certainly this is impossible to mold. This would also have been machined historically, where you would have had a block of something like Delrin, which is a plastic, and then carve it down to a pulley shape. We did not have to do that. You simply had to upload the design, and then this came out. And since it was made within a print farm, we could make hundreds, if not thousands of these, and make them for a fraction of the cost of these metal ones. And they perform their job just as well. Because a plastic strength, the shear force of a plastic tooth on one of these pulleys, is as high as what the belt would require, because it's a rubber belt. This is just as strong as the belt itself. Having metal is redundant. It's more energy intensive to make this, it's more costly to make this, whereas making this is absolutely trivial because all you have is the cost of electricity and the cost of plastic. The other thing about this is you might have noticed that it is fully solid, even though it's still lightweight. Inside of here, you do not need solid material, so we're able to make this partially hollow. So this is not a full brick of plastic, so you're using fewer resources and less energy to process this pulley, but it's still very, very strong. Also, since it is printed, you don't have to worry about shrinkage, so we're able to get a very good tolerance all the way around and a very thick, chunky, reliable, strong part. And it was never possible to do that before 3D printing. Metal was the only way, the only viable way to make this type of part. But now printing allows us to make a better part. Now that's the engineering side of it, but for the business case, this pulley is fine, but now instead of having to machine and create each one of these pulleys and have some preset sizes, instead once you have the engineering of the baseline design done, it's now possible to create hundreds of variations of the same pulley. We tried to source this specific pulley for our specific machine. It was very, very difficult, to where it was easier to have it recreated than to just source the part. A company that was controlling these pulleys or wanting to sell these pulleys could create the CAD for a single one and then create hundreds of variations from 50 teeth, one tooth up continuously to 500 teeth, whatever it happens to be, and create every pulley that anyone could ever possibly need. And the cost to create that is basically trivial, because once the engineer creates one design, creating all the other variations takes a fraction of the time. So now you have increased your product options without increasing inventory, because printing is able to produce these on demand, whereas tooling up for these, even to machine them, is quite a job. You have a part that is more economical because it uses a low amount of material, a more common material that could even be made from recycled stuff, no longer requires expensive machining or subtractive manufacturing that wastes everything that wasn't used to make the actual pulley itself, and you still get the geometry, you still get the strength, and you still get a part that you actually need. So
It was kind of interesting when we went into designing a new pulley for our machine. We just thought nothing of it until we realized how difficult it was to do this 5 years ago. And now you're actually able to make a polymer version that is just as good, if not better, because now it's lighter weight, you have more optionality, and you have more design control, because you don't have to machine a block of steel. This spool was actually made for our extruder out of our crystal clear filament, and it is tough PLA, which actually works really well for gears because, again, they're not under stress if they're well designed. They just have to pull along and you have to do shear. So PLA is actually one of the strongest materials for like gears. So lids are a thing. In this video, we're going to go through how to actually design lids well for mass production 3D printing, as well as the common ways of creating a lid, so you know all the different ways that you can have a thing attached to the top of another thing. Now, the very first rule of making lids is that generally they are smaller parts, so please make sure you put chamfers on all the corners that are on the first layer at least, and make sure you round out any vertical corners on the part. This ensures that the part is as efficient to print and comes out with the highest quality consistently, because when you're making 10,000 parts, there's a likelihood that something might go wrong, and doing these very small design changes reduce the probability of those things going wrong, which reduces the cost for the client and improves the quality of the parts overall. So with that, let's get right into it. The first and most common type of lid is basically one that just presses onto the top. Now, many people make the mistake of making this an interference fit where just friction holds it together. That's not entirely the right way of doing it. You want to have something better than just a tube going over the top of a cylinder. So in order to design these correctly, the thing you want to do is actually add just the slightest sense of a chamfer into the part. That way, the lid definitely has a place to start where it can go on very easily, get a little bit of engagement, and then depending on how tight the user wants to place the lid on, they can press until it's tight enough. This gives you also additional material because with these kind of friction fits, when they pop off and wear out over time, you have more and more material to wear away. Whereas if you had a pure cylinder in a tube, then once it wears out, it's completely done and there's no longevity to it at all. With these types of fits though, also you're restricted a little bit by layer height, because if you have a really coarse resolution on these parts, then those layers interlock with each other. So these friction fits can be very, very tough if you're not doing it quite right. So there are some tricks you can do with this in order to reduce the amount of surface contact between the two parts. You might add ripples to the interior or something along those lines, just so that you don't have too much contact. Now, those friction fits you kind of want to avoid because since they are a high tolerance part, the shrinkage of the material and everything else, it's tough to tune those. But there is one other version of this. Most people believe that the cap should attach to the outside of the part. That's not always true. Sometimes you can make a lid that's a plug. And with the plugs, you follow the exact same rules. Very slight chamfer to the outside of the plug so that you have a good interference fit. And if you want to reduce the amount of surface contact, you can go ahead and change the geometries a little bit for that. And of course, chamfer and fillet everything. Now, moving on to traditional type of mechanical attachments, threads. Threads are great. Make sure that you're always using a triangular thread, and ideally one that's at a perfect 45 degrees, because then you reduce the overhang and you don't have to worry about threads slightly sagging and therefore causing a really tight sort of fit. You might even not necessarily use like a default type of thread. If you're designing the lid and the container, you can design a custom thread by just using a coil or something to make sure that it has a good profile that is very useful and manufacturable. Because again, with 3D printing, you have overhangs. If it's less than 30 degrees from horizontal, you may have some trouble with that being reliable. And again, when you're making thousands of these, you want to make sure that the part is robust within the process as it can possibly be. And with threads, you can do the exact same kind of version as you did with the plug or cap, either having threads inside of the container or threads on the outside of the container. Now, last but certainly not least, one of the more difficult to model, but one of the more useful to have, is basically what we're going to call a nub and slide. But what you can do is you design a little nub on the outside of the container or on the inside, and then you have basically a channel that this nub locks into when the cap is pressed down and then twisted just a quarter turn to put on. This is really great because it's a great user experience because the user doesn't have to twist and twist and twist and twist or shove it on or any of the rest of it. It's very intuitive, very quick, and very easy. If you want this lid to tighten down, you can change that channel to have a little bit of an angle to it. You can also put in nubs inside of the channel to have it lock in place. surface, there's a lot of stuff you can do with this. The main thing to be aware of with this design though, again, is overhangs. That channel either needs to be less than 2 millimeters deep, especially if it's on a curved surface, or you need to have a chamfer at the top of that channel. Otherwise, you will have sag, especially on a curved surface, where the first line down will basically try to pull across it. So make sure this is really reliable. Ideally, you would take the nub and the channel and basically just make them pyramids of each other, a very angled channel. That is a better way of getting it done, but that can take a lot more modeling depending on what your timeline is. Make sure that the nub has as much overhang protection as possible, otherwise you will have support going all the way from the base all the way up to the nub, and you could still potentially have a failure mode where that nub kind of sags. So make it as small as possible, make sure it is supported as much as possible, and then the channel itself, make sure that it has no horizontal overhangs in it anywhere as well. So hopefully that gives you some context of ways of attaching lids to the top of parts. Like I say, this really optimizes the cost of the part in production and ensures that there is a better quality part coming out. Like doing simple chamfers and simple fillets and those kind of things can make such a big difference in the quality of the output that you receive. So all over particular factories, you will see these types of panels, a red button and a few other buttons and lights and LEDs around. These electrical panel covers are very common and they're made for all kinds of electrical enclosures and machinery. But they're actually fairly expensive to produce because even though in industrial machinery you're going to make a fairly low quantity of units, you generally have some sort of tooling or machining cost in order to make these panels. 3D printing can really help to solve this issue because you no longer have the cost of tooling. That's much more affordable than machining to produce these types of plastic pieces. But you do have to make sure that you're designing for the process to create a good quality product and create it affordably. So in this video, we're going to go through those design steps of creating an electrical panel cover. So let's start with the very basics. When designing a panel cover like this, number one, you really want to lean into the fact that you are not restricted to a particular thickness of material. You can make it as fat and chunky as you want because you can have all of that rigidity and we will fill it in with infill. But in this case, we made a panel cover that was 2 to 3 millimeters thick throughout, just because that's very often what comes back towards us from existing design. So we're going to try to pull from that. What you want to do is you want to make sure that the entire panel is chamfered all the way around the outer edges as much as possible. We want 45-degree angles. You don't want to do rounding or beveling because that actually creates problems with manufacturing where you can end up with ripples on the bottom of the part where those areas actually create a sag. So if you do have to fillet some part of the part, you want to make sure that it's as small as possible. So we did fillet the outer corners of this part a little bit just to round off the edges so that they can align with whatever box this might be mounting onto. Now the holes themselves, of course, you want to fillet just as much as possible too because you don't want any kind of drag or any kind of hitch happening in these areas. You can make slots for LEDs, you can make slots for the individual buttons that you might be putting in, whatever kind of display options you need in this you can do. As far as mounting up of these devices, if you're doing like an LCD screen that needs to have multiple screws around the outer edges to mount it up, I recommend looking at one of our other videos where we talk about screw holes and sprues in order to view that. Now, once that whole panel is done, you also have the text. The text itself you can separate from the rest of the panel. Very often when people 3D print them, they produce parts like this, where there's not very much contrast with the text. What we have done is we have actually applied a texture to this panel, which is applied digitally so that it is actually printed with this texture on it, which gives it a very nice pinned look that is not very common and is way better than like the virgin 3D printed look for this kind of stuff. But while the main surface has that texture, the text itself is totally smooth, which gives it a nice bit of pop and contrast compared to the rest of the part. This text is raised up anywhere from 0.5 to 0.75 millimeters, and that ensures that it's separated far enough away to really be distinct. You don't want to go up to a millimeter, otherwise text can start to sag and deform, and you don't want to go smaller than that, otherwise you can't really get it contrasted from the rest of the part. Now, those are all the basics. You want to chamfer everything as much as possible, design around the texture, that way you have this really nice surface finish, and do some basic stuff with text, and that gets you a panel. But here is the thing. Most of the time when people go to attempt to print these sorts of items, they print them flat, horizontal like this, and they have them facing upwards. This, number one, is a terrible idea because the text itself is individual islands, individual areas that the tool head has to operate on, which means you're now limited to tool head diameter. You can't have very small text.
you always want text on the side of a part because it can be very crisp. So you don't want to print it like that because there is text up here. The other side of it is you want the surface finishes to be uniform, and up here on top you cannot apply a texture to it. That will just be the printer printing straight across. So you have that rastering look, and again, it can lead to a lot of errors in production. The other issue is with a large flat part like this is that it is very well adhered to the print bed. So it has almost no scalability at all because each time a part is done, it has to be removed from the bed by hand or through some other fairly intensive process to separate it from the bed. We generally try to pursue auto ejection, which is a part being removed through automated methods from the printer once it is done printing. And we can't do that when it is large and flat and broad like this. So what is the solution? Well, you put it up on end. Now, people do not want to put it up on end very often because it seems unstable. And that is true if you are prototyping with like a bed slinger machine or something like that. But this is not an issue for our machines because they don't disturb this. That being said, you never want a tall part because as it grows, it can cause little amounts of warp. And you can actually see that appear on some of the prototypes that we've done. Here's one where you can see some of that kind of Z banding, which is from the part warping and bending as it goes up. So in order to reinforce this part, you actually apply some feet to the bottom. This makes sure that it can't fall off and that it doesn't warp or deform. These designed supports are better than standard support because number one, this does not exist. These are basically fins that stick out the outer side. They interface with the panel in the back on the inner seam so that when we work and break them off, they break away cleanly and you can't even tell that they were ever there. But they provide a tremendous amount of support to this part as it's growing up. Technically, you only really need one of these in the back of the part because that will give you a triangle of stability as far as the footprint that the part is sitting down on. But a couple of them is always good just for redundancy, and these don't really add any material and they are a trivial amount of post-processing. But then you end up with a very crisp, nice looking electrical panel cover that looks as professional as anything else that could be produced. And you get your text printed on there without having to do any sort of post-processing like adding stickers, and the part itself just looks very crisp and clean, and you did not have the cost of tooling to produce it or the long lead times of machining and the cost associated with that. Printing is a much more scalable process, and you can get nice final products for your electrical component covers very quickly, very easily, very reliably, and at a very high standard of quality.
Propellers are a really useful type of item. This is a standard house fan blade that we designed in order to show how to design propellers for 3D printing and the things to watch out for. In this video, we're going to go through all of those different details. So with a standard propeller, the things you're dealing with are the number of blades and then the actual pitch of the blades, this angle right here. Now, generally you're dealing with 3D printing, so you want to make sure that this angle is always higher than 45 degrees if you possibly can, but that's really not very optimal for 3D prints. So when you have to go shallower, there's some tricks that you have to do. But before we even get to that, propellers designed like this always need to be printed with the build plate right here. This makes sure that all the layer lines are in plane so that you have a part that is reliable and rigid and won't fly apart for some reason if you ever get it up to high speed. You can then, of course, change all of the parameters of how the propeller is built so that you have something really reliable and does exactly what you need it to do. So this could be an HVAC fan, it could be a household fan, it could be low noise, high throughput, whatever it happens to be. You can design these air screws to do exactly what you need it to do. You can also adjust the holes however you need it to do, and 3D printing enables all of that. But as designing one of these things, like I said, you want to deal with the support. If you ever go shallower than that, you don't really want to use auto-generated support because it can be kind of unreliable. Instead, you want to use this designed support. And design support is really useful because it's much more minimal and doesn't have a lot of post-processing. Each one of these just needs a simple twist in order to get knocked off because they have the spacing of traditional support, generally about 0.3 millimeters or so, but they allow you to create a really nice refined edge and not have to worry about a lot of extra waste or some sort of deformation. This also makes this really robust in production because you can have it printed on demand and never be reliant on slicer settings. When designing any sort of part, you never want to be reliant on slicer settings. But then, of course, you can also expand the number of blades on the propeller as well. So if you have a 3-blade here, you can have a 5-blade over here and continue to expand from that. But if you really want to make these really robust and strong, you can go even further and put an outer ring onto it. We actually recommend this because the outer ring both serves as a form of support for really steep sort of blades. It also just gives more stability to the fan as a whole, even though it can add a little bit of weight. One benefit of 3D printing is that we don't have to print stuff solid like in the good old days. You can use these infills in order to lighten it quite a bit, but again, good design practices always help. So making this outer ring as thin as possible is pretty good because you don't need a lot of extra force out there. But that outer ring can make it a lot more reliable and serve as permanent support, basically, rather than temporary support. So if you're really trying to go for manufacturing throughput without a lot of extra post-processing, rings throughout the fan can be really useful. You can put another ring right there and so on to serve as the support while still having all of the action on the air that you want, because those rings are really low profile. But fans actually have the other benefit of 3D printing, which is the fact that you just don't have to be limited by any sort of past design rules. If something like this was molded, you have limitations on the geometry in order to make sure that it can be pulled out of the mold. That is not the case for 3D printed fans. You can add extra features that can help to either control the air better or reduce noise or do all types of other sorts of features. So these little blades right here are generally for like reducing turbulence on the fan blades, which can lead to lower noise. But this is really just an example to show what it can be. You can put serrated front edges. You can do all types of other things in order to control the airflow to create a fan blade that never existed before. But really, 3D printing just gives you the ability to create large numbers of variations so that you can iterate through a design and evolve it, going from some sort of traditional fan model all the way up to a much more advanced one that you can continue to iterate on because each part can be printed on demand.
3D printing is able to create impossible geometries and able to produce those parts at a very large scale. But where is that actually practical? Well, today we're actually going to talk about how it makes stuff stick together way better than it normally would. So there are a lot of parts out there that have to be glued together, and when gluing together any type of a part, you have to deal with the glue itself. How much space does it take up? What are the tolerances when you squash it together? How far is it going to spread apart the parts? And then how well is it going to adhere to the surface? Do you have to prep that surface? Do you have to change it? Do you have to drill a hole for the glue to go into? Do you have to combine it with screws so that the glue acts as a sealant and the screws press it together? There's a lot of factors that go into that, which require a lot of extra design and a lot of extra effort on the production of the part. But 3D printing is able to integrate a whole bunch of features into the part. And one of these is actually like the part surface itself. If you are using a 3D printed part and you're going to glue a couple of them together, what you can do is actually design surface features that allow the glue to stick to the part even better. Now, of course, just roughing it up is really good. A lot of people will use sandpaper on traditional parts to do that, but 3D printing can go a step further. Since we can make parts with relief cuts, parts in designs that couldn't ever be manufactured before, you're actually able to make a hole that gets wider as it goes in, and you're able to make hundreds of them and make them really small. So now when the glue is spread across the surface, it goes into those internal cavities and is effectively able to grab onto the part mechanically rather than just through adhesion. You get a way stronger bond because you have the part itself embedded with the glue rather than simply having the glue on the surface. These relief cuts also allow the glue somewhere to go, so the actual tolerances of the part mechanically designed are what they are rather than having the glue spread the parts apart by building up on a flat surface. So this is a way more reliable way to do it. But if you're actually running a production system, you might not want just a large surface that glue is smeared across. You might want to actually control and direct where the glue goes. And again, since you have so much control of the design, you can do patterns like this so that you denote where the glue belongs. And people just put glue there, glue there, glue there, glue there. And now you're able to basically put some direction into the design of the part itself, so in production fewer errors can happen. Because with this, there might not be enough glue down here in this corner because people are just smearing it across and there's no clear indicator if it's been placed. Whereas with this, there's a very clear patch where it belongs and how much you need in order to cover that, so it directs people implicitly in the part itself. Now, of course, that's the more interesting way of doing it, but there's really traditional things that you can do with glue slots as well when designing for 3D printing. You can just put a relief cut inside of there, and sure, you could pattern this up, rough it up, give it some ribs, all kinds of nifty geometries to make it more durable. But just having a bead to run like hot glue down or something along those lines is really useful because you can embed it straight into the part. It doesn't add any sort of post-processing. But where this gets interesting, these types of channels get interesting, is if the part is already assembled and you want to insert glue. In that case, you're able to basically create an internal channel. So we could basically create this inside of another part to where we want to deliver glue to particular areas after an assembly is made. And then once you press this together, you're able to shoot glue down from the top and it fills that entire channel. That way you don't have to prep the channel or worry about orientation as you're turning it upside down and that kind of thing. You can stick it to the surface so that it's ready and clamped down, and then you can shoot glue in from the side and it fills the entire cavity, and machining this type of a part isn't an issue. Now, of course, the slot can be made, but if you wanted to do something more interesting, like having these slots go down into a threaded insert and then fill up the threads with whatever Loctite you might be using, that could be more interesting and much more necessary if you have to deliver glue through a series of channels. Ribs are a real common feature in most plastic products, but how do you actually design them, and how can you design them so that you can produce those products with mass production printing to avoid the cost of molds and shipping and warehousing? So ribs are used all over the place, and the main reason has been is because they improve rigidity of a part. With traditional machining and injection molding, what they do is they remove material and make sure you don't have any thick walls that can cause shrinkage inside of a part. This isn't really relevant though to 3D printing, and actually ribs very often cause issues with 3D printing. If you're looking at a part like this, each one of these pockets might have to be supported based on how large it is, which means that you are increasing post-production. Somebody will have to come through and pluck out reams of support out of this part, whereas it could have come off the machine fully complete if you had designed it appropriately. So with ribs like this, what you always want to do is try to eliminate the need for support. So like this center pocket right here, actually you can see starts sagging because those ribs are basically horizontal features that go out into thin air and have nothing underneath them. So you have to either build removable support or build in designed support. And that is basically what these center cross beams are. They split the distance that a thing has to reach out into thin air so that it can actually make it before sagging starts setting in. So if you are designing ribs, please make sure to put in as many verticals as you possibly can. However, that's only a solution for ribs in general. Sometimes you can't put in those types of cross supports. If you have ribs, you have to realize that 3D printing actually allows you to make really thick features that were never possible with any other process before. So actually, you can take the ribs and make them thicker, make them rounded, chamfer them so that they no longer have an overhang. So rather than having this horizontal shelf inside of there, you're actually able to put a slot underneath them and turn them into a triangle or a rounded rib or a pyramidal rib, which gives you much more rigidity and also does not really add material because these would actually be made hollow with 3D printing. But now you have a very thick, tough, strong part that is actually very easy to produce and doesn't have any need for support whatsoever. You can see these two ribs right up here, even though they are reaching the full distance, don't have any sag, but this bottom one that does not have that chamfer underneath it is sagging, which causes a very low quality looking product there. Now, of course, the very best option for ribs is to not have any at all. Again, printing can create solid, thick, chunky parts, which has never really been possible before without adding a lot of extra weight or a lot of extra material or being in danger of shrinkage. But since printing is able to additively add in layers and use infill so that you're not really adding a lot of material, you can create a solid, thick, chunky part. So rather than having a bunch of ribs in there creating rigidity with the same thickness piece, you can just fill it all in solid. So if you have a spot or an electrical enclosure that has a bunch of ribs and sprues and everything else, fill it in there and put in the hole. So you don't need the ribs. The ribs are an artifact from a means of manufacturing that is not necessary anymore. You don't need to put in rigidity by adding in these little strengthening trusses and features. You can just have a solid block of stuff that has internal stresses within it that allow it to be really strong and really durable, but also make it very simple and improve the appearance of it quite a bit, because now rather than having all this chicanery inside of there, you just have a nice smooth inner surface. But that's not always the case. Sometimes you actually need the ribs because they create pockets and space for whatever you might be inserting into the enclosure or the product or the toy. So if you do have to do ribs, what you want to do is design them so that they are not going to have any sort of support. The chamfer is kind of a brute force way of doing that, but it's an easy way with existing methodologies. If you started out with ribs like this, you put chamfers in there, or you put sprues and spacers and supports inside of there, and that's an easy way of getting it done. But if you really want to design ribs for 3D printing, what you would do is you'd start thinking in diagonals, and you'd end up with something like this. These diagonal ribs never have a horizontal overhang, so there's never an opportunity for them to sag. They grow up iteratively and stair-step their way up with each new layer that's added onto this part. So you get the same features of the ribs and you get all the space that they can provide you, but you don't have to worry about overhangs or sagging or any of the rest of it. But there's also one step further that you can go. If you are stuck with these types of ribs that have to be perpendicular to each other and in this position on the enclosure, rather than printing the enclosure like this, you can actually take it and print it diagonally like this. That then allows you to grow this whole thing up diagonally so that none of these ribs or overhangs again, and this part actually becomes more manufacturable. But it requires changing the aesthetic of your part, which is something that we don't generally want to do because you end up requiring chamfers on the outside. So rather than printing on a flat side like this, which is what everybody wants to do, you have to give it kind of a faceted look, print it like this, and then you also have to make sure that the part is not so tall that it can fall over while printing, which means you might actually have to print it sideways like this, which might change your aesthetics because the bed material is a little bit different. It's just unhandy. So you don't really want to go down that route, but this is a really good way to very easily manufacture a part without having to redesign everything. But if you're at a white sheet and you're thinking about how you're going to design it, number one, remember that you don't need ribs. You can just make a thick, chunky part to make it strong. If you have an existing old part that you're just upgrading, add in chamfers wherever you can or fill in the gaps so that you can actually use the old design quickly and easily. Or you can just add in more spacers and sprues so that the ribs are not hanging out in free space, which just improves the quality of the part. And if you're in a situation where you absolutely have to have ribs, you cannot fill them in, you cannot chamfer them, and you're going from clean sheet to where you're designing this product, just make sure to design in diagonals. That way you don't have any overhangs, but you have all the same features and quality that you need without having to worry about the process itself. So at Slant 3D, a lot of clients come to us wanting to design electrical enclosures that they can produce 1 or 10 or even 100,000 pieces of. But there's a few versions of those that are very difficult, and this is one of them. Electrical enclosures that are round and curved, having domes and smooth rounds and vents and everything else, are actually quite difficult to 3D print if they're not designed appropriately. So in this video, we're going to go through this injection molded design and talk about how you would modify it in order to make it as manufacturable as possible with mass production 3D printing. So there are a number of key features of this part that make it really difficult. Number one, there are the vents around the outer hole. The reason these are difficult is as they are made right now, they are very thin features, and 3D printed parts don't prefer thin features. They end up becoming brittle. Also end up leading to certain parts of error because each one of these is an individual tool move that has to be very precise and can lead to deformation or warping or drop off or break off or whatever else it happens to be. So these are really not that great of an option. The other issue is the fact that it both has a small curve on the top, a very shallow curve. And the problem with a very shallow curve is that it's inconsistent and causes all kinds of layer stepping because each new layer comes up, it moves inward, which ends up creating some cosmetic rings that might not be really that ideal. And then on top you have this other little vent right here and a kind of push button flexible area. Now, on the back you have a battery port and some slots and stuff that are not that big of a deal. Though I do want to call attention to this bottom chamfer. This bottom curve right here goes and becomes quite steep, as in it's almost horizontal when it starts. And this is not ideal because it'll cause sag and warp inside of a 3D printed part, so we'll address that as well. When you get inside of the piece, of course you have all the electronics in here and ways of mounting it up, but then you also have these various ribs and sprues and standoffs and that kind of thing. Most of these are not a huge concern, but there's a way to eliminate a lot of them, reducing your overall design time. So let's start with the first kind of feature here, which is its roundedness. Since this part is round, it cannot print in our preferred orientation, which is sideways. Each one of these pieces has to be printed flat on a build plate like this. If we were redesigning this whole part from scratch, if we were there at day one when this concept was starting out, we would recommend going for a design like this, something straight and faceted, because this allows you to print it on its edge like this, which means that both halves are able to be printed vertically, which means they can auto eject much more easily. There's less surface contact with the bed, so that it has a higher quality bed interface layer. And overall, this is a fairly good look, but it is a little bit intense for a lot of home type products, which this is for. But whenever going for the best surface finish, you always want to go for very faceted designs because they're very controlled and consistent as the part rises. And then if you want to eliminate the 3D printed look, it's very easy to apply a texture to this piece so that you can't really tell that it's 3D printed. But this is not possible with this rounded part because if we printed it on its side, well, then you have support and this side deforms and all kinds of silliness happens. So that's not really an option here. So given that constraint, it has to be round from a user industrial design standpoint. How would we go about this? Well, we would go ahead and design it basically the way it is. So the way we've done this is we will start with the bottom layer here. The bottom, the side profile, we changed just slightly. So rather than being a chamfer that curves all the way around to horizontal, it's truncated. So it curves a bit and then cuts off right there, which doesn't really change the cosmetic from the original very much, but is something to be aware of. Otherwise you end up with this warp and kind of nasty first surface. The vents themselves, the vents were challenging because there's a lot of them and they are straight and small features. So what we do there is we actually make them longer. And what we did is we made the vents cut into an angle at the wall. And what we did to achieve that is we made the wall a little bit thicker. That was possible because inside of here, there were ribs around the exterior of the part in order to stiffen it and to act as finding features, which essentially take up the same volume as a thick wall, but that is done in injection molding in order to make sure that there aren't maximum thickness parts and pieces around that would cause shrinkage and other sort of issues. So by making the wall thicker and then cutting the vents through at an angle, you have much larger features so that the tool head has more time to deposit material reliably and more structural stability so that you have a very good looking exterior part, and these vents still have the same amount of airflow as before. And it is a little bit higher quality because now people can't look in there and see all of your electronics around. Also, these vents are a very expensive molding feature because there are a lot of individual pins that have to go into that or have to be machined. It is a fairly complex mold. So moving to 3D printing reduces your startup costs by an enormous amount. And then you have the internal circuitry and battery case and that kind of stuff. Rather than using individual sprues, small cylinders with holes in them sticking up, we would combine all the holes into a single plate layer so that they're able to be printed all at once, which creates a very strong, reliable set of holes and doesn't have to worry about snap off or anything along those lines. So that is basically how the bottom layer is made. This is a little bit unhandy because you have an entire large broad surface against the bed, which means that this bottom surface is prone to errors. This might not be a big issue because we could either paint the entire unit to get rid of stains or deformation if that happens to be an issue, but this is also a non-customer facing part. So if it's an industrial type of use, then it's not really that big of a deal. But ideally what we would do is go through here and make a number of cavities, kind of like this battery hole, so that the bottom layer is as minimum surface area as possible in order to minimize those types of errors. And then the individual standoffs and things, those would be individual features that you would design for printing individually, and we go over other videos in those types of features there. This is mainly about the roundedness. Okay, moving on to the top cap now. The top cap was probably the most challenging part of this because you have that smooth curve up top, which is really not desirable because you end up with these curved layers where each stair step creates a ring on the top of the part. But what we did with this is we actually leaned into it. This original design had a number of rings around the outer edge. So we used those and we spread them around to make them kind of blend in with the rings from the 3D printed layers themselves, so it looks much more intentional. We controlled the texture and used the texture so that it just has a lot of concentric circles, some more emphasized than others based on the CAD that we did. The top button was easy, there's no problems there with that at all. You go ahead and press on that and that's not an issue in any sort of fashion. The little vent on the front, right now these holes are this direction, which is fine, but again you end up with these really thin features that have to be printed. You always want grids to be in plane with the layers. So what we did is we just made them curves going with the circles themselves, which means they also blend in with those outer lines quite well and create a nice looking feature. And then inside you do have this rougher bottom side, which has to be supported, which is not ideal. This part has to have post-processing, manual post-processing. And there's not really very many ways to get around that. Unless, again, if we're going back to the original design, this is all assuming a 90-degree horizontal kind of layout where this prints this direction, this prints this direction. But what you can do in order to eliminate support in the lid and in other parts like this is rather than cutting straight through like this, you cut at an angle. If we made this part line at an angle here, it would mess with some of the cosmetics and the overall industrial design of the part, but you would eliminate support because now this lid gets to kind of print on its edge to where it is able to be grown without support underneath it because there's nothing that's a direct lone overhang anywhere. Lastly, the thing you would want to do is, since this part would be printing like this in order to maintain a good overall texture and uniform outer surface finish, you would want to chamfer the lips of this lid just a little bit to make sure that it doesn't have any sort of side extrusion on the first layer. Now, that would be both of those parts. They would be a little bit more expensive because having these large, broad parts on the print beds is not ideal because it's tough to get them ejected, and sometimes auto ejection is not possible if this part is larger, which again is why you really want to go for a flat datum side somewhere on it. This can sometimes be done with these things by like making just a single flat face on this somewhere along the way, so that it could be like a charging port or an inlet or something, access area, so that this can be printed on its side. But then you get into weird issues with the cooling vanes and that kind of stuff. So it's not the best. This part is best printed in this direction. And those are the general kind of rules to get it done so that it looks nice. Now, this is all printed with the Virgin 3D printed layer lines, which are printed at a 0.2 resolution, is generally fine for most consumer and definitely industrial applications. If it was industrial, we'd probably go down to more of a draft layer height. But if you don't really like the 3D printed look, sometimes you want to get away from it. So in that case, what we recommend doing is applying a texture. And that texture right here, we use basically kind of a popcorn orange peel kind of a look, where we just add a little bit of noise to the outside of the part, which gives it this very kind of matte, sort of fuzzy look, which is great because it is much more forgiving in production. This can save you a lot of cost using this type of texture, and it creates a very uniform look throughout the part because it doesn't have, oh, the side of the part, the top of the part, where the 3D printing really shows a transition point. But the other thing with this too is that white is the most difficult color to print with. The pigmentation inside of white is very chunky and almost turns the flow of it into sort of like toothpaste. So if you can avoid using white, you want to. This can be done by printing in some other color and then painting it, or just by printing in some other color. If that is done, you can go with like these grays and that kind of stuff, which create a much smoother sort of finish. The darker the color, the better the print quality and appearance will be because the pigmentation inside of it is a much lower lift as far as flow rate. And you can also mix and match surface finishes. So in this case, we have the smooth upper lid and then kind of the matte textured bottom half, which could be used to help this part like blend into a wall if you're planning to mount this in a lot of spackled houses where it's like an orange peel wall. This helps it kind of transition in that direction, which can be a really nifty trick to try from a design perspective. And then of course using the gray is a much more industrial, but it is a cheaper type of material to work with. And then if you really want to go crazy, if for some reason your product can support this, which most can't because it's a little ostentatious, you can go with just different colors. So like this is a pearlescent sort of white, which again really helps to improve the appearance of the part over just a native 3D printed white, like so here. But it is a more expensive material, but again, it creates a different type of aesthetic that you might not be able to get a hold of regularly. So hopefully that is a good summary. Round 3D printed enclosures for mass production are actually quite difficult to work with. And if you're not designing for the process explicitly, if you just ask us to 3D print your injection molding design, there's a number of problems that can come up as far as quality and appearance and strength and structure. But if you design for the process, you can end up with something that is pretty much equivalent and even indistinguishable from the original that just now happens to be made with 3D printing, which means that you have now reduced or eliminated your startup costs around tooling and shipping, and you're able to experiment with the market and change your design over time without having a large tooling change cost. So we recently purchased a bunch of command strip wall hooks, and these are fine and they're reasonably affordable, but the problem is that after one person bumped into them or pulled on them a little bit tough, they snapped off. So why are these so darn frail? Well, the reason is that if you look underneath them, you can see that since they're molded, they're made with really, really thin walls, which is not really the ideal situation when you have a hook that people might be using all the time and might pull on to break. You also have the problem of like shrinkage, because right here underneath the hook on the inside of the hook itself, you can see there's shrinkage, which isn't a great aesthetic, even though it's okay for something like this. But ultimately, this is kind of a bad way of making these because they're just frail. They just snap right off if anybody does it. So how could we improve this so that it could be made stronger? Well, the easiest way is to make a solid part, which can't really be molded and definitely can't be machined for mass production, but printing is able to address this. So how would you design a command strip wall hook so that you can get something much stronger and something that you have more visual design control of? So the first way to go about it would actually be to do something like this, and this is just a standard hook. It's really similar to the original in many sorts of ways, and you could change it up however you want. This design is actually printed on its side, which allows it to be the strongest version possible. There is no way anybody bumping this would ever break it off. And since we're able to make it kind of thick and chunky, it's able to be extra strong. And since 3D printing uses infill and doesn't really have just empty holes and an empty void behind the part itself, it's much tougher because it's kind of like an I-beam or a composite part. With this design, you do want to be aware of orientation though, because with all of these hooks, orientation can make a big difference. With this one, it's printed on its side, it's very strong, but the aesthetic component of it is the fact that the top will look different from the bottom, which isn't always the greatest situation. But that would be the baseline type of hook. And if you wanted to design it so that it could also be mounted by screw, you would create this inset screw hole so that the head of the screw goes into it, and you also have a very strong, durable place to hold onto the screw without something like splitting or doing something silly. But that is one version of the hook. The other version that is even closer to the original design is this. This design is printed vertically like this, and this is actually the most affordable way to make something like this. Because since it's printed vertically, it's very easy to auto eject from the machine, so you can make millions of these things, and they would cost exactly the same as the mold and cost of all of these deals. But this design has some disadvantages, and the fact that the layer lines are this direction, this tab is a little bit more frail to where it could potentially break off just the same as the molded one did, which, you know, the molded one came off pretty darn easy, so it's not that much more, and again, we can make it thicker so that it's not as easy to snap off or to catch somebody or stab somebody. And this is a great way of doing it. If you were to actually really optimize this part for having even more functionality and mass producibility, you would actually shave off this back arm because you don't really need that extra material, but it is there in order to allow the command strip to press onto the back. And printing like this isn't really an option because now you have a really weak kind of hanger right there that you don't want. So this way is the best way to make sure that something is strong so you can hang a set of suits on top of it and have it still be a reliable part. But there's one more direction that you can go here. You can print the thing on its side, you can print it vertically so it's standing on end. You can also print it on its back, but printing on its back with something like this you don't want to do because now you have support inside of here. So you want to make sure you design for that orientation. The benefit of printing on its back is the fact that the bed surface is actually the one that the command strips would stick onto. So that is the point of this type of design. This design is a triangle with a slot cut inside of it. It's kind of cool because it's actually omnidirectional. You can hang it upside down or forward, and it's able to hang whatever you want to. You can also change the size and shape of this interior circle so that you can get a better hook, but this is printed just like this, which makes it very strong and very reliable and also quite mass producible. But then the back surface is the bed surface of the printer so that you have a nice consistent surface right there that nobody actually sees, so it doesn't change the aesthetic of your part and doesn't create any kind of issues there. Just make sure you round all the corners, and again, yeah, you can change that interior and make sure that these are not overhangs that would require some amount of support, which is not that hard to do. These can go quite a bit steeper. But 3D printing has the advantage of making mechanisms and geometries that aren't really possible with any other process. These are not really possible with molding because they're so thick they would cause shrinkage and all kinds of weird deformation. But the other ones, things like this, can be molded or extruded and controlled in a number of different ways. But printing allows you to create something that had never been possible before. Things sort of like this. This is a wall hook that is generally flat and flush inside of its little slot, and then you can flick out the hook itself to hang whatever you want on top of it. This isn't really that new. You can kind of see these types of things in cars, but why this is really special is because this hook comes off of the machine just like this. There is no assembly. There is no inserting the hook into the outer casing or anything like that. It's just there, and you can readjust it and change the design however you want to. If we were to actually redo this one, we would probably print it face down so that the front surface of this is actually glass smooth, but that can increase the cost of the part a bit. So printing it on its back where it's just like this, and again, super strong, and the hook is tough and the hinge is fine, is actually a good way of doing it. But this sort of combined mechanism, these multiple parts printed in one go, cannot be made with any other process. Whereas printing allows you to create this whole new functionality that had never been possible before. So throughout our 3D printer factory, we have a lot of areas that have these things inside of them. These drawer organizers are located all over the place to hold like spare parts, like nozzles, or within our assembly line for our printers in order to hold individual screws for each station and that kind of thing.
The problem is that they have to be reconfigured in order to have just the number of drawers for just the number of parts in that station, which means that we end up with all of these empty slots. They also are just standard little drawers with little tubs of stuff inside of there, and that's not terribly useful for what we want to do within production and within the context of mass producing our machines. So we decided to just go ahead and redo this because we couldn't purchase a solution that we actually wanted. And in the process of that, when designing something like this for mass production 3D printing, you end up making something like this. So really, there's nothing wrong with standard organizing modules. They're actually fine for the normal person. But inside of a production environment, you want to reduce stimuli and improve information without really overcomplicating anything. And those standard types of drawers just aren't very useful for either one of those things because you have to buy a whole set that has a lot of empty drawers, which gives people duds or just has an empty slot there that is bad information for a person. But within a production system, you want the systems inside the factory to give feedback to a user so that a person knows when something is running low or when something needs to be ordered. And these standard types of drawers don't really do that. Since they're just empty and plastic here, basically made from an injection mold, they are not terribly useful. They don't have any information in them. They're just a bowl that's in the shape of a drawer. But overall, they're very cheap and very affordable to work with, which is their advantage. But we are really going for a very high level of functionality, and these could not be manufactured affordably with injection molding with a high level of reliability because it'd just be too expensive to create the variations that we need. So we ended up making this module. Now here is the drawer again, right here, just like so. But you can notice there's a number of interesting features about it. Number one, the drawer comes with its own little section, its own little module. Now, we're going to talk about this a little bit more, but this module does not need magnets in it to be combined with other ones or anything like that. It just needs to be present because since 3D printing is a digital manufacturing process, there's a number of interesting things we can do here. So the drawer itself, we made a standard handle and it is designed to be printed like this, vertical, just like so. You can see that down here we have a chamfered edge, and the reason for that is that the drawer has a hole in the back. That way the drawer itself has a flat area directly against the bed, so it's well adhered and you don't have to worry about wobble or support or interface between the different parts because this entire assembly prints completely just like this and comes off the machine, fully complete with drawer and outer housing. But that chamfer makes sure that you have contact with the bed, but then not contact with the drawer itself. The drawer itself has a large chamfered area in the back that is kind of thick, which gives it a lot more rigidity, and again, serves as protection for that if necessary, but it shouldn't ever be necessary because this is not going to sag. But this way, this is stuck to the bed reliably, this is stuck to the bed reliably, and it's all printing together as one unit. That way, if you're doing like a print on demand sort of a situation, the entire assembly and all the parts for that assembly are gone in one print, which is what you want to do if you can do it cleanly. You don't generally want to batch parts, but it can be done. The other thing is, the front handle of the drawer itself is angled like this. This way you have no direct overhangs, but you still have a good place to grab. The problem with this is that you have layer lines going this direction, which means that if somebody bumps this outer lip generally, it could potentially snap off if you're using a really brittle material like PLA. So what we did is we added just a small rib to the middle there, which does not affect how you grab it or get a hold of it at all. It's just fine. But that gives it just a little bit more rigidity and reliability so that it can't just split and break off really easily if it was just a thin little layer there that almost acts like a perforated edge. This front face, we made perfectly flat this direction, even though it could be angled in order to better show off labels. Same could be done for the bottom here. Basically, this whole front face can be readjusted to do whatever you want. Within the drawer itself, one thing we tried, we're not sure if we're gonna stick with it, is we actually made the drawer a tad too long. So you can see that gap there. That's basically so you have a peek hole into the drawer to see if there's screws and stuff sitting inside of there without having to open it up. That way people always have a view of what is inside of there as well as the label on the front. That way it has a really quick visual indicator. Lastly, inside of here, you will see there's this little wedge sitting right there, which basically creates a pocket in the back. On this little wedge is the word that says reorder. So this is meant to hold a set of screws at a particular workstation. In manufacturing, there's something called a Kanban system. A Kanban system is basically a visual indicators that tell people when they get to somewhere in the process what to do next. So if you have like a stack of parts, you might take a Kanban tag and shove it into the bottom of the stack of parts so that when people get down to just 10 pieces remaining, that tag says go order more. That is what we've done here. You would fill this entirely up with screws, and then once they are starting to get low, it reveals this tag, this information that says reorder more. And it tells them to reorder before they're totally out, because you still have this little pocket of extra parts in the back. This is a really efficient way to make sure that you don't run down to zero before people say, oh, I need to get more parts. That way you don't have stops in production. And it's a very simple thing to do, but you can't really do it with these because you end up trying to shove sticky notes or make some kind of custom paper logo in there or a secondary little container. It's just really unhandy to do with this kind of stuff. Whereas we're able to build it into the drawer right here. And since it's 3D printed, we can move and adjust this to make sure that it's the perfect quantity left over when people need to reorder. Or this just tells people to go back to inventory and get more screws so that, again, you don't end up with people pulling up in the drawer and the drawer is completely empty. This little reorder tag is there to do that. What we would generally like to do is maybe paint that a color so that it really pops a lot, or use a different color other than this kind of pearl white that we used for these prints. But this is a very handy thing that you're able to add in because we have complete control of the design. Now, that's the design of the drawer. This is now a mass producible part. We can make tens of thousands of these very easily in our print farms, which is all well and good because it makes it competitive with these types of things. And since we're able to design it with printing, we're able to create some features that wouldn't generally be molded because it would be too expensive to get started. And you're able to create functionalities that wouldn't otherwise be available. You can almost create a whole e-commerce store around designs of organizers for specific applications. But now let's talk about that outer drawer that we were discussing before. This outer drawer is useful because inside of the CAD model, this is what you see. But we don't want one of these. Very rarely do we have a station where we want one little drawer. That's just irritating. That's just a bin. You generally want a stack of them because that's what we're used to. But like we said, this stack is unhandy because this is almost too many for some stations where they might have 3 or 4 or maybe 10 screws, but not 15. And you can't order really small sections of these readily or easily because this whole outer frame needs to be made all at once to make it worth it. So in order for us to do it, we took this standard module. And since this is a standard size module, you could design it so it has interlocking features on the outside or like magnet slots, but that's not really ideal for production because now you're dealing with assembly and post-processing. And you don't really want to do that. And if you were to do a 3D printed connecting thing, like inside of our joining videos where we talk about this kind of stuff, that's fine, but it doesn't look very good. All of these blocks stacked up and wedged together or pressed together just isn't very sexy. So you want to make a product. Well, again, we're using 3D printing, which means that when a customer makes an order, you can print and ship exactly what that customer ordered. You don't have to make large quantities of inventory. So we can use this digital file and then replicate it and pattern it into different variations that people are able to use. And this is an example of one of those variations. We took this module and inside of the digital model just replicated it 3 times, or we could go 4 times, or we could go 3 by 3 and make a square. Anything we want to do, we can make a module that would do this. This way, a person could order a single module if they're being silly, or they can order a 1 by 3 or a 3 by 3, and then that entire assembly is printed all at once because these come off the machine just like that, and then you ship them. Also, nifty little side note here that we didn't discuss before. At the bottom of each one of these, right here in the front, there is a small sprue in order to keep this part together so it doesn't rattle all apart in shipping, but then a person just has to pull hard or maybe snip it off in order to release the drawers, which is exactly the same way these things work. They just have tape across the top, which is again another manufacturing step that you want to avoid. Right here, a full assembly comes off of a machine fully ready to ship. You can take this off of the machine, throw it into a box, which is really uncommon. And to be able to make something like this is not easy. You could, if you were manufacturing something like this traditionally, of course, get this molded and then get the outer frame molded, and you'd have to get 5 or 6 different frames to show all the different sizes and that kind of thing. It's just not economical. But with mass production printing, you can print the part off all at once on demand for your customer, and you're able to create solutions
options and colors that you otherwise wouldn't be able to get a hold of. We can now get one that's yellow for one station and black for another station and white for that station and so on and so forth, so that number one, the drawers match the section that they belong with. So if somebody takes out this drawer and carries it off someplace else and they're wondering where it belongs with a case that matches that color. Whereas you don't really have that with these unless you explicitly go through there and paint this or put a sticky note in it or something like that, and then make sure, oh, it matches the outer casing, or putting labels on so everybody's reading. It's just bad for manufacturing. Now, would this always be turned into a product? Not necessarily. This is actually quite expensive to produce compared to this, but the added benefits, the optimization, the reliability that this can add to our factory while people are using it is a really big deal, because it reduces confusion, it improves reliability, and with like the added advantages like the Kanban stickers in there, it reduces back-end kind of post-processing to prep this up so that it can be used in a factory. So the additional cost is not exceptional, but it's present, but it's paid for because you have all these additional benefits of the freedom of the design of the process to create a single module and then modify it, expand it, and change it into whatever we want. You can do an L shape, you can do whatever, and modify these so that they can be used wherever you need them. As a mass production 3D printing company, we're often told what type of products we can and cannot make. And one type of product that we're often told we can't make is a water bottle, something that is food safe, is waterproof, and is durable and reliable. And since we can't make it, we decided to just go ahead and do it. Yeah. So water bottles, when traditionally manufactured, are made either with plastic, glass, or some sort of metal, generally stainless steel. So if it's plastic, what you would have to do is you would have to get a mold, and then you would either injection mold, blow mold, or sometimes rotational mold the water bottle itself. Very often it's a blow mold because that's very fast and efficient and fairly low cost. If you were using glass, it would also probably be a blow mold. Basically a tube with a blob of glass on the end of it that they shoot air into and then expands to fill the cavities of the mold, and then you get the shape of the glass bottle. And then metal is sort of similar in that you would use what is actually a die or a press mold, a compression mold, some type of system where basically a large piston hits a sheet of metal and then forms it into the shape of whatever the die actually is. The problem with all of those processes is that if you are creating a new type of water bottle design, a different shape, a different size, a different style, you have to get a whole new mold or die made. You have to carve some giant rock in the shape of your bottle in order to have the bottle form to that shape. And it's very expensive. It can cost tens of thousands or hundreds of thousands of dollars in order to create that die, which is why we all end up with just standard cylinder water bottles, and the only embellishment that anybody ever puts onto them is printing a new logo on the front of them. Now, that's all fine and dandy if you're making millions of them, but if you're wanting to try a new design or start manufacturing a new product, that upfront expense is very high risk. 3D printing has the huge advantage of not having really any significant startup costs. You don't have molds, you don't have the large amounts of shipping, and you're able to try new things and iterate and change the design over time until you hit what your customers actually want. But generally, when people look at 3D printed products, they consider them to be inferior for these types of food applications. They say, well, a water bottle, 3D printing, especially FDM, is not waterproof. And 3D printing FDM is not generally considered to be food safe because it's very difficult to clean because of the layer lines. And then there's questions about cosmetics and that kind of stuff. So we did literally just want to go through and debunk every one of those because they're all just incorrect. Right here is a fully FDM 3D printed water bottle that is waterproof and can be washed and cleaned, and is as reliable as any other water bottle, and arguably as beautiful as any other water bottle. The design of it, you can see the outer texture of it is kind of peened, which is like being hit with a sand blaster, so that you have a nice kind of sandy texture that is almost impossible to get with other types of manufacturing without adding a huge amount of expense. And then of course we were able to embed the logo on the front. And then with this design, the way it's set up is that if we wanted to go with something other than just this white kind of faceted design, you can actually embellish and create something a bit more unique. This is actually a finned design
where basically you have all of these fins around the outer side, which can be embellished upon in order to create like dragon scales or maybe leaves or some kind of organic shape or pattern. You can make these wavy. We decided to make them straight just to make it easy. But this design is actually almost impossible to manufacture any other way because all of these fins would make it so difficult to make a mold that would be able to release this part that it's almost cost prohibitive to even try. But it looks great, it's very unique, and actually has a functional benefit because these also serve as like buffer protection and that kind of stuff, so you don't have to worry about damaging or denting your bottle because these act kind of as springs on the outside. So you can engineer and design new types of aesthetics and new types of functions that were never possible before. And again, we were able to do this in the day or two that we had to make this video rather than spending weeks, months, and hundreds of thousands of dollars to make the one shot that you have to get right with traditional manufacturing. So how did we actually do this? Well, the design of these is actually set up to be made in two halves. And the two halves look like this. This is one half of that white standard water bottle. It has been optimized for mass production with FDM printing. So it actually prints on the head right here. Since we have this chamfered faceted design, you don't have to worry about side extrusion on the first layer. It's very clean. It comes off looking very nice. And there's a minimum amount of surface contact, so we don't have to worry about like staining of the white light color on the first layer and that kind of stuff, which can sometimes occur. And then over here you have a groove and a tongue. This is so you can print two identical halves, but basically have them pressed together. So you print this part twice, and then you can press it together to make the water bottle. And up here at the top, you can see it's actually angled so that you don't have any sort of supports or overhangs that you have to deal with. And that is how you make the water bottle. But now you might be sitting there and asking, okay, well, how is it actually waterproof in that context? Because these two halves, we must be putting a glue or sealant in between the two halves. And that's actually quite incorrect. What we are doing is we're using what is traditionally used with like processes like cardboard cartons and that kind of thing. If you've ever purchased a cardboard carton of milk, you have seen that it has a small kind of plastic inner liner. Some of these cardboard and paper bottles use like a wax or some variation, but generally some very thin plastic layer that allows it to seal paper, because paper is neither food safe nor waterproof either. But putting that inner layer in it makes it so. So we basically took that same approach and we got a hold of these bladder-based water bottle inserts that we could use for this project. This bladder is not very durable, not very reliable. You can't throw this into a backpack and use it in any sort of way. So the outer casing actually protects this as well as gives it better aesthetics and better appearance. But this is able to hold water reliably, is completely washable, and is very low cost, so it adds very little to the manufacturing of these things. So you take this and two halves together and you end up with a water bottle like this one right here, which is fully functional and reliable. So now we have taken a very low cost internal bladder that uses a very minimal amount of kind of not great plastic, and now we're able to focus on the outer casing, which has the functional benefits, the aesthetic benefits, and the cost benefits, because this costs absolutely nothing to manufacture, and you're able to instead focus on manufacturing the outer casing and put all of the cost of what would have gone into molds for your one shot into designs and iterations to really refine the product into something interesting and reliable. Ultimately, the lesson that we really want people to take away from this, though, is that no process is inherently limited. You are limited by your ability to engineer for that process. 3D printing has incredible benefits. The fact that you don't have the startup costs of molds, that you are able to change the design over time and create something that was basically unmoldable before, create something completely unique that couldn't exist before, allows you to create products that are competitively different from what anybody else has made before. So there's an opportunity to create entirely new types of products, but it does have limitations. It is tough to make a water bottle with purely the printing process. So you have to find the solutions that allow you to create exactly what you want and how you want it without adding extra cost. It can be done, and it is done often by many, but it is difficult and requires a concentrated problem-solving process of how do you get what you need. And basically, it's knowing initially what you need. We wanted a water bottle. So we went ahead and we made a water bottle and found the way to do it. That is the engineering and product design process. So hopefully that video was enlightening. You can create basically any product with mass production printing and produce it affordably, reliably, and at scale. And if you design for it correctly, you can create whatever it is you want, regardless of what the needs might be. Maybe it's a spaceship, maybe it's a water bottle, maybe it's just a toy on your Shopify site. But using printing gives you the advantage of creating new products very quickly and very reliably, so you can test them, find out what works, find out what customers are interested in, and then move on from there without having to swing for the fences every time you try to create a new product and hope that it goes right. So when printing any part, the very first thing you have to think about is the very first layer. In this video, we're going to talk about how to design the first layer to make sure that it is reliable and is able to mass produce a part with the minimum number of errors possible. So in order to set the stage, we made the worst possible first layer in the world. This layer is terrible for a number of different reasons. Number one, it has those triangular holes. Not only are they sharp and have sharp corners, which can create all sorts of deformation on the first layer, they actually don't have to be here. These holes in this case are cosmetic. If you have cosmetic holes or features, rather than sending them all the way through the part, instead embed them. This creates a nice flush lower surface, and you no longer have those holes which can potentially be deformed and warped on the first layer. And then have the holes come out the top the way you want them to. They still look the same, but the first layer is way more uniform and doesn't have this additional detail that's not necessary. The next thing that is also absolutely horrible is this text on the bottom. You never want to put text on the bottom of an FDM part because the first layer will squash it and deform it, or it will drag. And all of those very small features are very tough to get nailed down on the first layer because they may not be deposited just precisely. If you have to have text on a part, I recommend watching this video where we go through all the details of how text should be made. Put it on the side, put it inside, put it on top, put it somewhere else, but don't ever put it on the first layer. It overcomplicates it and makes it really difficult to print reliably, and can actually cause a failure of the entire part in an extreme circumstance. This raises the cost of your parts over mass production and definitely increases the amount of waste. But now finally, we have the outer edges of this part. This part has no rounded corners. This is very difficult on a first layer because the nozzle will go to the tip of one of these corners and then has to radically change direction. Not only does this slightly increase print time because it has basically a full stop and then it reaccelerates again, but it can also again cause a failure because that corner, which has so little contact area with the actual print bed, can drag backwards and cause deformation or warp. So what you can do with this is just round out the corners a little bit, but do the maximum amount possible. The largest fillet you're able to place on a corner, do it. If you can do 1 millimeter, that's fine. If you can go up to 5 or 10, do that. Take this down to a round blob. The rounder and smoother and more circular the first layer is, the better. So let's just go ahead and take that all the way to the extreme. We've taken this star shape that is absolutely horrible to print and blended it all down to just a circle. Now you have no corners at all. This is a really nice first layer, and you can see that the bottom of it is all now uniform and very smooth. But the problem is with really large flat surfaces like that, now you start running into another problem. As that first layer is pressed against the bed, depending on the materials and the situations that's designed of the part, you can end up with these types of artifacts. These are basically small deformations from one line of material pressing up against another one, causing not really a warp, but just a weirdness in it. So in order to fix this issue, rather than having large, broad surfaces on the base of the part, you can actually minimize them down. In the case of the circle, you can actually do this. Basically cut out a cone in the bottom so that now you have just a small outer ring. That outer ring can be as wide as you need it to be. Depending on the material, again, you may need a certain amount of bed adhesion in order to make sure that the part is stable and secure, but you want to minimize the contact as much as possible because this enables auto ejection down the line. So you have a more highly automated part, which means that now you can make millions of them without high cost. And you also eliminate the surface defect feature or the possibility of it occurring. Ideally, if you're doing something with something easy like PLA, you can take it all the way down to 1 millimeter. Now the surface layer is stable, it is reliable, it has no sharp corners, it has no text, but it has a good contact surface with the bed without a large contact surface that can be warped and deformed. This right here is the very perfect first layer because it minimizes the amount of stuff that is out of your control. So you no longer have weird deformation that can occur from having to try to keep text or other sort of features tight and refined on the first layer.
Ultimately, what we're going for is the simplest first layer that you can possibly make. Round it out, eliminate extraneous features. If you have holes all the way through, plug them off if possible. And if you have any other need for any sort of weird feature, just try to push it up as far as you can away from the first layer, where the machine has more control and it's not about the flow characteristics from a nozzle onto a flat surface. The first layer is so important because if it goes wrong, the rest of the part could go wrong. And whenever we're quoting jobs, we will generally give feedback on the first layer, but if we're starting with this, there's a lot of feedback to have to be given. And if for some reason you're not able to round it down and you do have to have sharp corners like this, we have a whole video about brims where we talk about how to actually do brims for these types of features, and I recommend you go check that out. Have a great day, everybody.
Everybody does this like all the time, and pretty much everybody does it wrong. So today in this video, we're gonna talk about how to batch parts in a way that is useful to you and reliable in manufacturing. So batching is when you take a whole bunch of parts, either the same or different, and group them out on the print bed of a 3D printer. There's a number of different reasons that people do batching. The number one reason is really just to get print time back, rather than having 6 2-hour prints that you have to restart over and over again and then don't run through the night. Instead, you put all the prints onto a single bed, and it is an easy way to make a full set of parts. So that is the reason people batch. Closer to home with Slant 3D, people batch in order to get a better deal on 3D printing inside of apps like our Teleport app. The Teleport app is a service that we have where people can upload models and connect to like their Etsy store or their Amazon store, and then when you get an order, we will print the item and ship it to your customer for you, so you get access to our giant print farm. Now, people do that in order to get a cheaper access on Teleport. I recommend going over to the Slant Pod video here to find out more about how that might be changing in the near future. But those are the reasons for batching. Just get more print time out of your machine or get a cheaper deal from a print-on-demand service. But there are a couple of problems with batching that are quite substantial and things you want to address. Most people just lay parts out on a blank bed and start them printing. This is stupidly dangerous because if one single part of that batch fails, all of them go with it. Because if the part like comes unstuck or shifts or has an overhang or causes some debris, then it knocks into the next part, which then fails, which knocks into the next part, then fails, and then you end up with this giant mess of spaghetti. So batching is very dangerous to use. Even though it has the benefits kind of efficiency of print usage, it loses many of those benefits from error rates and failures that can cascade through an entire batch. Another danger with batches, especially with print services, is that print services generally visually verify parts. And all they have is the 3D model to compare against the batch of parts. If you throw in a batch with like a few dozen or a few hundred parts on the print bed and they pop off the print bed into a giant pile, it is almost impossible to verify those parts in an economical way. So the batch will become very expensive, or you will have the danger of parts missing because you have 10 or 12 big giant parts, and then you have a bunch of sneaky little ones spread around inside of there so that when somebody looks at the 3D model, they don't see the little sneaky tiny model. And inversely, if it's done with a computer that can see all the models, all the items inside of the 3D model, but then it looks at the pile, it can't see that the tiny little part is missing. So quality control and inspection of parts with batches is very, very difficult, so you generally don't want to do it for services. And again, we talk about this more in the context of Teleport over on the POD channel. So there's the risk for you, but if you are still wanting to do a batch, there's a few reasons to do it. Number one, you get a full set. So if you are having a part printed and you're like, oh, well, I have this little gadget that has 3 pieces in it, I would rather just put them all on the same bed so that all 3 pieces are finished out at once. They can go into a bag and a full set can be delivered to the customer. I get that, that makes good sense. So let's go about how to do batching well. In order to do batches well, we actually have a solution already from the injection molding industry. You remember if you've ever built small plane kits, how you get kind of a card full of all the pieces of the plane kit and then you snip them out of there and you put the plane together? That webbing of support material is something you can apply inside of 3D printing. Only 3D printing has an even better option, which is not unusual because printing is better than injection molding in almost every way for creating products. Instead of using those sets of sprues, which have to be snipped off and leave burrs on the parts, we are going to use a raft. Now, if you're familiar with 3D printing, a raft is generally used for bed adhesion. It's a way of sticking the part down to the bed without having the part contact the bed. But rafts actually have several other benefits, and one of the biggest ones is not adhesion, but actually organization. Remember earlier when I said if you put 100 parts on the bed, they all pop off the bed and then you just have a pile of parts? Well, what if instead you just had those parts pop off as one single piece? This is the value of the raft. If you just, inside of your design or inside of your group of models, you pull them into a tool like 3D Builder, line them out on the bed how you want them, and then just design a single plate underneath them. Now you have a card that will contain all of your pieces reliably, and in fact, that card is more reliable than the print bed because the card will never be contaminated. You never have to worry about adhesion problems, and it's much lower probability that a single part will failure from getting knocked over because it can physically stick to that card. So instead of just having the parts loose on the bed, you have them contained on the bed. Now let's go ahead and go through the design of that card really in detail, that design of that raft. Again, like I say, you group all your parts and you have them together as a single STL. Or if you're designing them straight in CAD yourself, you go ahead and lay them out in the pattern however you want. Ideally, you would still design those parts well, so you would fillet the edges and follow all the rules we talk about on this channel, chamfering the bottom, so on and so forth, because those are all rules that are still very relevant in this situation, because you want these parts to pop off from the raft reliably. So watch all of our videos about design of first layer. They all still apply. But you design the parts well, and then you put the raft underneath it. The ideal spacing is a minimum of 0.2 millimeters, but you can go up to 0.3, and I recommend just testing this out. 0.3 is a safer kind of direction to go to if they're allowed to pop off loosely and you don't want a really tight first layer. 0.2 is fine, but you do have the danger of them sticking very rigidly to the raft. The raft itself is 1 millimeter thick. That way you know that it's a fully solid plastic part and doesn't have like hollowness in it, and you don't have to deal with like roofing and that kind of silliness when stuff is printed. In addition to this, the thing that people will generally screw up with the raft is they will make it a perfect square. If you make it a perfect square underneath all of your parts, make sure to round the edges. Otherwise, you have a first layer adhesion problem where the raft can peel up if you're using high warp materials like matte black PLA or PETG or any other sorts of materials that you happen to be using that can peel up and warp and have bed adhesion issues. So round the corners, or even better yet, you can just put a circle underneath your group of parts and put them grouped on that circle. Now, there's a few other benefits that you can also get with this raft. Now that you have all your parts grouped on there, yes, you can take advantage of pricing if you want to, but you also have a nice controlled set to where parts can be auto-ejected more readily if you have a set of 2 or 3 pieces. But you can also use that raft as a tag. Many people want to add cards in for items when they're using print on demand and that kind of stuff, but you can't print those sorts of items on paper, but you can print them on the printer. So you can use the raft as like a labeler to put in like a QR code or maybe some text or a thank you for the order engraved onto the raft, and the raft serves as that tag, and then all your parts are piled on top of it. If you want to be really fancy about this, you could design a raft that has outlines for each one of the models on top of it, so that if one is missing, there's an empty gap sitting there, like a little circle saying, hey, there was supposed to be a cylinder here, where did it go? You can also use the raft to number your parts. It's actually a nifty kind of way to use 3D printing to create a really nifty customer experience that otherwise wouldn't exist. And the great benefit of this also is that the raft coming off as one unit just makes it very easy to realize, the whole one unit is there, all the pieces are on there, we know what was available, that's a good situation. So the raft is not simply a way to organize your pieces, but it creates better processes all the way down the line so that you can actually mass produce this part or print it on demand, and you know that parts will be produced reliably, consistently, and to your spec, and you're able to reliably upload them and know that one piece won't get lost or fall off or get forgotten or just be in a pile of bags delivered to your customers. This is just a better way of doing batching, which almost nobody uses. Everybody, since they're on their home 3D printer, they just upload a whole bunch of files all lined out on the bed and then say print them all somehow, regardless of how complex that first layer is or anything else. Batching is a bad thing to do natively, but if you can batch them up on top of a raft, now you have something that is really, really useful, really, really robust, and can radically improve the product that you're producing.
So here at Slant 3D, we produce a lot of filament, and we just started getting in a new extruder for our filament launch that's coming up in just a little while. But this extruder wasn't quite up to the snuff of what we wanted it to do. There were a number of issues with it, and one of them was in one of the cooling tanks. These cooling tanks are designed to cool a filament as soon as it comes out of the extruder. So once you turn the beads into a line of filament, it goes into a water tank that cools it down. That water tank right now has a single pipe that is throwing in a ton of water, which causes a lot of turbulence. You don't want this for filament because it causes the filament, while it's still kind of molten, to wobble, and you can end up with wobbled filament, or it can change the diameter of it because it kind of pulls the filament and stretches it out in ways that are weird. So we wanted this pipe to basically be fixed so that it very gently delivers the water into it. We have to have a continuous flow rate, so we can't change that, so you have to build a dispersion type tool. And this attaches onto the end of the pipe and pushes the water gently out in a number of small holes so that it's very gentle. And we wanted to talk about how you design this for mass production printing, because even though we're just doing one of these, we always use the same kind of design principles. So the way this part is designed is it is meant to go onto the end of the garden hose. But in order to do that, you have to have it interface with that garden hose. And this is how we designed this spout. This is really useful if you're making like a sprinkler or something along those lines. But the spout starts with a lower diameter and then gets wider, which is a very simple thing to do. And then we put a number of grooves up here so that it has some walking features on it. We didn't give them any teeth or any sort of bite because you can't really come down to sharp teeth with 3D printing because they don't really exist. You can only go down to a 0.4 millimeter sharpness or point on anything because that's the size of the tool. So what we went ahead and did was just have them as grooves in general, and they still provide the locking that you want. But what's really special about this is the fact that it is not actually printed vertically. A lot of people would end up printing something round like this. But in fact, ours is octagonal so that it can be printed perfectly flat on the build surface just like this. And that is made possible by the octagonal outer surface because you don't have any deformation. You still have the effective round part, but you don't have to worry about overhangs or supporting it or having it adhere to the bed. You have a nice flat surface to start from. But what we did with that in order to have the splaying that we wanted where it gets wider is you have the hole kind of going through here crooked. It is fatter up on top than it is on the bottom because the hole is going straight through, but the octagonal outer surface is expanding out as it comes this direction. So it's a weird sort of geometry that's not really standard because most people would take this part, put it up like this, and put a round hole right there and shove it down and then have the layers break. This way, this is totally reliable and as strong as any other part. We can reef on this and there's no way you will ever break it off any more than you would with any other plastic part. But then we were able to take advantage of 3D printing. This part has an internal chamber and then all of these small slotted holes out that side. Now with these design of the slotted holes, we designed it again to be printed like this. You don't ever want independent islands around here, which we kind of have down here. But we spaced them out enough to where that's not that big of a deal, and we made the hole small enough to where it's easy to get that done cleanly. Though there's some better ways of doing it. And one of those solutions is to actually angle up the slots like this so that they go in at an angle themselves other than just this slanted angle. It's right here, but then in the second dimension, it's also angled up that direction. That allows them to basically be printed in a continuous loop without having to break the path in order to grow each one of these. And we did something similar up on top where we shoot straight through. To create a geometry that just can't be molded. You cannot blow mold this. You cannot injection mold this. This cannot even be machined. That huge internal chamber with all of these holes going into it can't really be manufactured any other way. So 3D printing allowed us to make this dispersion attachment so that it shoots the water up and forward, which is around where the filament is running because it runs past this right like this. So we don't ever have the force of the water contacting the filament, it just kind of stirs the area around. And since it has so many holes, it comes out very gently because none of these has an exceptionally high pressure. So there's a lot of situations when you want a part to be glued to another part, but very often what you end up doing is you end up coating the outer edges of the part and then gluing it together and dealing with just the surface finish of the traditional part to make it. But this is kind of a waste, especially when you're dealing with 3D printing. 3D printing is able to produce really complex geometries, so why not take advantage of that design flexibility to create a part that glues to another part way better than it ever has before? Today in this video, we're going to talk about how to do that. And the very first step is with what we call just basic make glue slots. You can take that traditional sort of bolt and just add some grooves along the outer side. This both creates more surface finish as well as just a better adhesion area and place for the glue to go. But in addition to that, sometimes you don't want to have to push the part into a hole and have all the glue shoved up the edge as you would with a traditional smooth bore. Instead, you can insert the part and then create channels inside of it so that you can press a glue into the top and then have it ooze out of the sides. You have these delivery holes along the slots so that you're able to deposit glue in it after it's already been placed in place, which creates a much cleaner application process because you have just a single point of entry. So that's a very simple way to have a complex geometry that's very difficult or expensive to manufacture in order to get some added benefits. The glue slots give more surface finish and you're able to deposit the glue after the part's already been assembled. So if there's a situation where you can't actually apply glue and then insert it, this is way more useful. If this rod was way longer, then you would have to deal with that type of a situation. But this adds several other benefits too. This is a very simple one where you just have a large hole that oozes glue out the side and goes along the slots. But again, if this was really long, you need more areas. And in that case, you can actually start depositing holes all the way along so that as you purge glue through this core bore, it's able to come out the sides of all of these different holes so you have a very equal pressure dispersion and you make sure you're getting a very uniform dispensation of it all throughout there. But the glue that you put in here now has an additional benefit. Usually glue is just to stick one part to another, but we are dealing with 3D printed pieces, which means you have a certain amount of strength reduction in the Z-axis. This could snap off along this way. So you can actually use this sort of glue slot methodology to reinforce the part, like rebars inside of concrete. In that case, you would be able to create a much more complex geometry, where you have a single hole in the top, a point of entry, and then the splitting chamber inside of the head of the bolt itself. It then splits down to 5 separate columns to where you're running basically these lines of glue through the center of the part, so that after it's placed, you shoot glue into it, and now it's reinforced by the glue, and you have much more perpendicular strength than you normally would have, which is a traditional 3D printed part. This is a really easy way to reinforce a part without really adding an additional process that's really expensive or difficult. You're able to just run rebar up into the concrete after the concrete has already been run. But there is one more version of this as well. With all of these, this is after the part has been inserted. So once you press this into the slot and you have the glue slots down there, there's no place for the stuff to go. You can actually make this more complex and much more interesting by just adding a spiral to the outer side. This way you have a single channel. So again, you don't have to worry about one channel getting all of the glue and the other one's not getting it. You also are not certain if this is inserted into a hole. You don't know once you've filled them all because there's no presentation of it on the outside. This design actually solves that issue. This twisted thread improves both the strength of the part because again you have full length glue adhesion throughout it, but then you shoot glue through the main bore, it goes to the bottom of the bolt and then it starts coming up the spiral and then it's able to come out the side. So you know when you've fully filled the entire area with glue. So you know you have a reliable seal that gives feedback to the machine operators who are doing final assembly, because they shoot glue in here and then they know it's full when glue comes out the side. But again, you have a very clean spot where the glue exits, so you can see where it is, you can wipe it down, and then you have a very cleanly placed piece that otherwise you couldn't. These glue slots are a really good example of just the advantage of 3D printing. You're able to create really complex and dynamic sort of geometry that allows all types of post-processing that traditionally was never possible before because it was just too expensive or outright impossible to create something like that. A mixing chamber inside of a part is unmachinable, period, ever. It could never be molded, it could never be made any other way. But now you're able to distribute fluids and glue throughout a part in order to have it dispensed where you need it, when you need it, after it's already been assembled. So it's much cleaner and requires much less skill because shooting glue into a single hole is way simpler than telling somebody to evenly coat it all and then press it in and make sure you don't scrape it off as you're going in and that kind of stuff. And it's a great example of how 3D printing gives you these brand new advantages because this process allows all types of geometries that couldn't really be created easily before.
So when designing a handle for mass production 3D printing in a large print farm like this, there's a lot of things that you want to consider in order to make sure that it's designed correctly. So in this video, we're going to go through how to design a handle so that it can be mass produced and how to make sure that it's actually strong enough to do whatever it is that you need it to do.
So handles are a very simple sort of device. They've been around forever, and one of the simplest handles that you can make is the one that you might find all over your kitchen or house, which is a simple crossbar with 2 screws at either end. These are very reliable handles that are very ergonomic and have a lot of artistic expression within them. As you look around your house, you'll probably see them all over. But all of these handles historically have been designed to be made with stamping of metal or carving out of wood, because that's where they were originally designed to be made. But we have new technologies available, things like mass production 3D printing. But if you're going to mass produce a product, you cannot design it for some old style of manufacturing. You have to understand the end process that you're going to use. So you can't just simply do a standard handle where you would then round off the edges and drill a hole in it. It's not a piece of bent steel. It has different structural needs, so you have to design around those. Now, one of the simplest solutions to this is to simply use what we always love to use, which are chamfers, and basically create ribs around where the holes are. These ribs don't really require much support material, and they can be easily mass produced, and they leave lots of room for the hole and for the screw head itself. And this is a perfectly reasonable way to do it. And then you could go around and you could fillet the edges so that it has a nice smooth feel to the touch and it doesn't have any sharp edges. And that's pretty much all you need to do. There's no controlled stress concentrations or anything else. This handle is perfectly decent and could be used for furniture or industrial equipment or anything else along those lines. And you could follow this principle. But it doesn't look very good and it looks kind of amateurish. There's a next step that you can take this to, where you actually use the chamfers and you lean into them completely. Again, this handle is printed on its side, so we have all the layer lines in the right direction, so it has maximum strength there. But again, we're making sure that the holes don't pull out. So why have ribs when you can fill in all the area around it? There's no worry about shrinkage of material or warping or anything along those lines. Use all of the enclosed volume that you can, because you can add more material there in order to reinforce the part. Now you're also getting rid of those large cavities that were left by the ribs. Ribs are really sort of a last century solution when they were limited by what traditional tooling could produce, but 3D printing does not have those limitations. So use that space, use that material, use that volume of the part. Now you can just have a countersunk hole that allows the screw head to enter into it. Now you have a lot of supported material around it that's very deep. You have a very uniform looking part that no longer has cutouts out of it or anything else. And since we like chamfers all the way around, we're going to apply them all of the way around with just a little bit of rounding on the inside to make sure those edges are soft if somebody has some soft hands coming by. But while we're at this, 3D printing allows us to apply textures for basically no cost whatsoever. So we'll also go ahead and put a small grip texture along the inside of it. This makes sure that this has a little bit extra friction, regardless of where its application is or the state of the hands that are using it, making it much better for industrial applications. Now we have a handle that is dimensionally equivalent to any other handle that could have existed, but rather than designing it as if we were bending expensive steel or trying to make it fit into a carved out piece of stone in a mold, we instead have the freedom to create a part that is very uniform and monolithic and strong, while still having the subtleties of texture and fit and finish that you can't really get from any other option. And not only does this handle look really good, especially when we print it out in a nice glossy gold, because we can pick any color that we want. Even if we were producing 1 million of them, we could change them up to have 100,000 in red, 100,000 in green, and 10 over in the gold. It's not that hard to do, because again, we're using mass production 3D printing to make this part. This part is now finished, reliable, and can take the full weight of a human hanging upside down from it. It's hard to find many applications where the person will pull on a handle harder than they can possibly hang from the handle. And that's how you design a handle for mass production 3D printing. We love chamfers, and you always want to make sure that you actually design for the process that you're using. If you try to use some old design style and push it into 3D printing, you'll probably be disappointed. But if you use the technology for all the benefits that it can create, you can manage your supply chain, reduce the cost of tooling that you had before, and modify your supply chain so it's much tighter and easier to get the parts when you need them and in the quantity that you need. You have all those advantages, and all you have to do is make some small design modifications to make a better part anyway that truly differentiates you from what any of your competitors would be looking at.
Hey everybody, so today I had to design a bracket for an Ethernet switch actually going into our print farm. And I figured, well, you know what, we're gonna make this to be mass produced because we have to produce hundreds of these for our print farms as we build them out here. So I thought I might as well just show you how we're doing it. So it's gonna be kind of a clamshell. It has to lift the switch up off of the ground once it's printed. But when you're making a 3D printed part, you always wanna go for thickness. So I'm going ahead and making that 10. These are the outer walls that I'm working on right now. This isn't like the best CAD methodology. Generally, you'd want to do like a center square or something, but I don't care that much. Let's see here. So we're gonna go ahead and do that. I'm gonna go ahead and extrude up the C. And I actually have the part in front of me, so let me do some caliper resin here. So I want it to be 70 tall. This will become a little bit clearer here in a moment. But in order for this to work, what I actually want to occur is it's got a plug coming out of the back, so it's got to be lifted way up off the ground. That'll be fine. I basically need to put a lip underneath here, and I don't want to do it as a traditional lip. I want it to be pretty darn beefy, but you know what? I'm going to do it right here anyway. I don't care. Okay, so we're going to go ahead. I'm just going to close in this space to make sure that I have it. And then I'm going to use a slot rather than a circle or anything like that, because slots are just really flexible and you always want rounded edges. So this gives me all the chamfers right off the bat. Let me, again, measure a thing here real fast to make sure that we're giving it the margin that it needs. And 12, nice. Okay. That'll work. Okay, it needs to be, this edge needs to be nuts. Hang on, I'm going to do this as a standard datum feature because I really want this to be correct. I'm not going to turn that into a construction feature because who cares? That needs to be 12 from that side. There we go, that's good. And then give that a little bit of distance. It can almost be a circle. I'm going to verify it's 13 across, it's dead center. Actually, I'm going to make that wider. I'm going to make that 16. Whenever working on a first-time design, always make sure you have more room than too little because it's easier to put stuff in than to tear stuff away. Okay, let's go ahead and do that. And then I'm gonna extrude this up. I believe it was 30. Yeah, 30. Oh, there we go. Okay, now that's the outlet hole for this thing, but I want it to actually have somewhere for the cord to go. So we're gonna go ahead and do another slot so that we automatically have the overhang built in. This way we don't need any support underneath there. And I'm gonna extrude that through everything. Oh, reverse the direction, I suppose. There we go. Okay, there we go. Now we've got a hole. The switch will be sitting down into this slot and going around. That is generally fine. Okay, now there's one more feature that I want. We want to be able to mount this. This will actually be sitting on a shelf with an Ethernet switch facing upward. But I'm going to go ahead and do it like this. As far as dimensions, I'm kind of eyeballing it here. 3/4 of an inch, so I want it about, oh, but you need room for the drill head. So yeah, we will do that about 30. It won't be a big deal. And then this will need to be about a 5mm hole. Okay, cool, let's extrude that up. Also, we'll take that about 10. Yeah, we want 10. I want a lot of meat on this, just to be sure that we don't have any sort of breakout or anything like that. That hole's a little bit too close to the center, again, for like having the drill eventually hit it. So I'm gonna move that out a ways. That's good. I don't want the head to poke up, so I'm gonna give it a counter bore here. Okay, make that about 10. I'm gonna make that bigger, I'm gonna make that 15. The other thing with the counter bore is that it actually creates solid material so that you're not like potentially crushing infill, because if you get to that, it's not a big deal. So you always want screws up against solid material. So I'm gonna take that back -4. And this way, you only have a 6mm gap right there, which is enough meat, and then you'll have the top and the bottom, which are both about 1 to 2 millimeters thick. So you basically have solid material where the screw is actually interacting.
Okay, so that's the baseline for it. When I did the dimensions for this, I actually gave it about 1 millimeter on either side. I don't need it to be sitting super tight inside of there, and since it's so tall, there won't be a lot of slop. Now let's go through and really optimize this. That's the baseline shape, the base dimensions that we want. Now what we want to do is actually create something useful and make sure that it's manufacturable and optimized here. So we'll put a chamfer here. Going, how far will it let me go? Oh, hello. Yeah. Oh, can't go past the hole. Okay, 25. Sometimes it'll let you, sometimes it won't. But again, you always want thickness because it's the outer skin where the strength of the part really is on all of these things. Let's go, oh, wait, nope. I want another chamfer. This will be an oblong chamfer. This is all wasted material. So we're gonna go a 2 distance one, and we're gonna go 10 and 25. Make that 45. Oops, 45. There we go. And make that 20. And not only does that look cooler, but it just deleted a whole mess of material for us that wasn't gonna do anything useful. Okay, so that's looking good now. And again, the screw will go down in that hole. This will be capped on either end. Since going down on the bed, we want to round out all the outer edges so that there are no sharp corners on any part of this part. Right there. And we want those to be basically as big as we can go without either making the part look weird or causing some sort of issue. If there's an engineering requirement of some sort. I'm gonna go ahead. I like that. Okay. We're gonna actually add in another fillet right here and right there, just for the sake of uniformity. Oh, nuts. Okay, fine. Smaller fillet right there. Cool. That'll be fine. I want to make sure that these front edges are filleted so that there doesn't accidentally, if for some reason we're mass producing these, sometimes for this hardware, we very often put them on like machines that are on their last leg, kind of their final days. So we will let them be sloppy, and just as the belts burn out or something, we'll reduce them. So if we do that, we want these to, the belt bounce, we don't want to cause a problem. So this is a very brute force way of making sure that those corners don't like accidentally catch the part in some kind of a silly way. And just a small fillet right there. It's not really very important. Inside of here, we don't want any stress concentration, so we want everything else to be filleted as well. Right here, right there, right there, right there. And that's also going to be about a 2 millimeter. I'm going to do 1.5. This is a fairly well machined, kind of almost a machined part. And then of course we don't want sharp edges that will catch the wire that we're going to be putting in here, because this is the power cord wire for the deal. Okay, that's all good. If this was a true manufactured part, I would also either put a chamfer or a fillet along the bottom layer. I'll do that here for you guys just so you can see it. It's not really necessary for this and actually can be overkill. Just a small one. Just that helps eliminate elephant foot inside of the main part there. And I don't like a sharp edge because we got it all evened out here. So I'll smooth that down a smidge. And again, to help the whole thing come together right, we'll put just a small fillet up top. Actually, I'm gonna make that a bit bigger fillet. There we go. Now this is ready for production. We have a lip that'll sit down into. The reason I only put one hole in this, since it's going onto an Ethernet switch, there's actually a right side and a left side. So we'll just print 2 of these and both of them will hold onto the switch from opposite directions. So you don't need additional screw holes. We'll print this out and we'll show you the result here in just a minute, guys. Have a good day.
Industrial hardware is a fantastic application for mass production 3D printing because it is designed specifically to do a job. Cosmetics don't really matter, it's not a consumer product, it's just a question of does this do the job cost effectively? And in the case of 3D printing, very often it does. But the problem that we have is that very often the parts inside of industrial manufacturing are designed for other processes like injection molding or machining. But when designing a part with 3D printing, there are different rules and different capabilities that you can get a hold of if you know what you're doing. So in this video, we're going to go through a very simple example of how the design of an L bracket might actually change when you're designing it for mass production 3D printing and the things to be concerned about and look at while you're doing it. Now, the most simple version of the L bracket is literally just the L bracket, a simple strip of plastic that is shaped into an L. This obviously is not terribly useful in very many places because it's just not very strong or very reliable. And it's not very good for 3D printing in general because the layer lines are going to cause it to split along the seam. So it's not really something that should ever really be manufactured with printing, but it's the place to start. But if you want to start beefing it up, the first thing that you would do is go ahead and add a rib, something like this. That's a really easy thing to do, but now with the rib, you can still make it with 3D printing, but you still have the split danger along the layer lines, and you also have kind of a non-balanced bit of strength there because you only have the rib on one side. But since this is not a part that has to be molded and you have to worry about ejection, you actually can add in another rib onto the other side. Now that's all fine, well and good, but the problem with the rib on the other side is that if it is too big, it can sometimes require some sort of post-processing afterwards to remove the support material inside of there. So the other rib, while useful, isn't that great, but again, you have so much design freedom now with printing because you're not limited by the tools themselves. Let's take those ribs and just expand them the full distance. Well, now there's actually two different options that you can end up with. Since 3D printing doesn't have to worry about material shrinkage, basically solid volumes are filled in with honeycomb material, they don't really add material to add volume, but you can add a lot of strength. So if you take the ribs and extend them out all the way and basically fill in the entire set of the arms here of a standard L bracket, then you end up with something like this. This is also fairly standard and people have seen it around before, but this part actually cannot be made with traditional sort of molding because it has so many thick areas that it would cause shrinkage if it was ever molded. But you can get the exact same functional parameters out of this where you have two holes on either side, you just make sure to countersink them and leave everything else filled in. But now, with this part, the question then becomes, how do you engineer it for actual mass production? If you want to make 10,000 of these or even 1 million of these for long term, how do you want to design it to actually be printed? Well, most of the time people would expect to print it like this on its side, but you are having the layer line problem again. You're going to split right along that perforated edge you've created from your screw holes. So most people would then flip it up onto its edge like this, where it's at a right angle, but now this side could break off when it's loaded up on a piece of extrusion like this. So you don't want to print it like that. Well, then other folks would say, well, go ahead and print it forward like this. This is actually a really good idea because now you have the looping of the layer lines actually creating more strength, much like the way you would lash two posts together in a ship by using the strength of the rope to hold them together. This is something that you can do because all of the individual beads of plastic come together to wrap around the holes themselves. But this has the downside of having a lot of surface contact area with the build plate, which isn't always the most ideal situation. So actually, what you really want to do, if you possibly can, is print it like this, standing up on its end. This means that it can be very easily ejected from the machine, but also has all the same reliability and strength as everything else. But the problem with this is that you can have cooling issues if they're very steep overhangs, and you could have rejection issues if the contact area is so small that it causes the part to fall over while it's printing. So you want to make that interface area as big as possible without making it too big. And this is always kind of a case by case on the part, so just be aware of it. But that is kind of the optimum traditional L bracket that you can make with 3D printing. You can basically just add in a ton of volume and get more strength than you would have from any sort of extruded or even molded model where you have to go for as thin as possible. Here you can go for beefy, chunky, so that you can actually get real strength out of a part. But we can take this a step further. 3D printing allows you to create impossible geometries. If we go back and rewind to where we were extending the ribs all the way to the outside, why do we want this to be a system where this L bracket sits on the inside just like that and is then screwed in? You have multiple screws, there's a lot of assembly, a lot of man hours in putting this together. What if you could just eliminate 2 of these screws, or maybe all of the screws even? You could save yourself a lot of man hours in assembly by creating a geometry that wasn't possible before. Well, the way to do this is to actually go ahead and wrap around the outside of this extrusion and basically create a slotted L bracket where the parts socket into it. And this is a really good way to do it. And you end up with something like this, where the bracket itself plugs in and comes together. This isn't necessarily a new idea, but it gives you the advantage of having fewer screws, because rather than having 2 screws to make sure that the thing doesn't twist around and has good grip on it, you can just have one that is basically a finding feature that holds the aluminum in place but isn't really structural. But you also have the advantage of this being the cap as well as the bracket itself. Whereas with this, once you put them together, you still have this naked end sticking out that can need some extra assembly or an extra plastic part. So going with this more covered up kind of looped design is handy. But the problem is that again, we come back to that problem of what orientation did you print this in? Almost everybody will design it and try to print it like this, which means that you might possibly have to have support in there if this is large enough. If you're making a really large piece, then you might need support inside of there. Generally not. But then you also have the strength issue where if it's printed like this, and then you put it into a piece of extrusion and you reef on it, it will break. How can you get the full strength of the plastic out of this part? Well, again, we go back to that orientation thing where you design it to be printed like this. Now, again, as it grows, it's basically creating loops of plastic around the extrusion itself so that there are continuous connected areas where right here, you have a full continuous piece of plastic all the way around the outside and the inside of this aluminum extrusion. So this is as strong as it can possibly be. It's popping, but it's not really gonna break unless I really get on it because it is just plastic, but it's as strong as any other isotropic type of part would be. So this gives you a huge advantage because you can make this thick part that is still very lightweight because it's technically hollow, but you have all the exterior strength that you would have with any other process. So this right here is the optimum way to make an L bracket because number one, it is as strong as any other process would ever create. It is very cost effective because it's been optimized for the 3D printing process, and it gives you advantages that you never had before because you can use fewer fasteners, you get more parts consolidated because you no longer have end caps, and since you can make a big old thick chunky part, rather than having a nasty little bolted L bracket inside of the thing, you can actually have this nice clean end socket that fits everything together, plugs together. You can put in one screw in there to hold it all together. And now you have a part that is not just equivalent to what the old solution was, but better. Hinges are a fundamental part of all kinds of parts, but did you know you can actually make the hinge a part of a part? It's called a living hinge, and if you put a living hinge in any sort of part, you can make those parts actually have a party. So let's pick that apart. So there's a lot of different types of living hinges, but inside of 3D printing you have all kinds of different options because you have a lot more control of the pieces that you're making and the designs that they're able to make. The most traditional living hinge is literally just a thin flap of material, which is made very thin so that it can flex without actually fatiguing. These type of living hinges though do have an issue because they wear out. They're often used on something like old tackle boxes or small enclosures, and they're fine with traditional manufacturing, but they can't be used many times and they can't flex through very long distances. Otherwise they break. Like that. And while that's not an ideal situation you want to have in a lot of parts, you can do it inside of 3D printing with certain types of materials. So a typical living hinge can be done with like TPU or polypropylene or other types of materials, so it can be mass produced and create a good reliable piece. But you also have to consider the orientation of the part. It can only be printed on its side, which can limit it to some degree. There are some variations of that where you can still have a living hinge and have it be reliable, but it's a difficult type of geometry to kind of have to work with. And fundamentally, it's not very good engineering because it is a point of fatigue that'll eventually wear out. And there's so many other options when you have 3D printing. You can reduce the wear on a particular living hinge just by giving it more material to wear on. So like in the case of this circular hinge, all you're doing is giving that stress more places to go by giving it a much larger area to work on. Rather than a very small defined point, you have it on a very big broad point. It doesn't give you quite the same range of motion because you can flex stuff a lot more, but it puts an automatic spring into the hinge so that you now have a lid that automatically closes, and a lot more play and a lot more flexibility in narrow ranges than the typical type of living hinge would ever provide. But you can take that circular hinge a little bit further, and by reducing the amount of material even more and giving it kind of this toothed look, you can give it a lot more flexibility, a lot more longevity, and still have the spring return, but by changing the depth of those grooves and the number of those grooves, you can actually kind of change how that hinge behaves. So the circular hinges are another way of doing living hinges.
but sometimes that circle will pop out too far into a particular geometry, so you might still want that flexibility with much less protrusion. A long time ago on a project that we did with robots, we actually created a gripper finger using this kind of spring hinge. And this sort of living hinge is very useful because again, you get a good amount of flexibility with very little wear because no single part of the hinge actually has to flex very far. This is a good way of creating like long articulated columns or multiple hinges inside the length of a long thin part so that you don't have to have a single plate of wear like a traditional living hinge, but you still have a good amount of flexibility. One of the more traditional hinges is actually the living hinge that you might have seen in like woodworking. And this is where you cut individual slats inside of a horizontal plate that is printed just like this. But those individual slats are able to twist and bend around each other. And by creating that twisting motion and freedom within it, you're able to create something really flexible. It's not just a perforated edge where again, the material is flexing directly. It's just twisting these individual areas just a little bit, kind of the way you twist a rope, just like this. So this is a copying pattern of basically having a piece of material connected right here and then two edges that bend just like this. So that gives you a lot of freedom. It can bend pretty darn well, but you have to design this actually around the radius that you're trying to bend around. This hinge type is fairly easy to manufacture. It's not ideal because you have so much precision in it, but it can be made very chunky, and depending on the end application, it looks really good and it can last a very long time because you have so much distributed motion. You don't have any single force on any single area, so it takes a long time for a hinge like this to completely fatigue and break away. But this is all in the traditional living hinges, and a living hinge is one where you have the material itself flex, and that's not a very good way of making a hinge. What if you could just do the hinge traditionally where it actually moves around an axle? Here 3D printing has a really fantastic advantage because it's able to make parts inside of other parts without actually having to assemble anything. So you have these hinges where you can have a flexible point moving around a central axle that was all printed as a single piece. These are not screws. Nothing was screwed together. This part was grown like this. Now there's a couple of different ways of doing this. You can print this part vertically just like this, which gives you really nice motion around the central axle to where it's nice and smooth and circular and can be pretty high precision, but it can be tough to kind of design, and you have to be really careful to chamfer those inner axes so that you don't have interface or layers falling onto each other. But that can be a little bit weaker because the layer lines are now horizontal. So if you have a lot of torsional force on this, that's not ideal. Just make something thick and make sure you're designing for the process and it's not that big of an issue. But if for some reason you're trying to make this very, very small, then you would want to print it horizontally because then the layer lines are moving through the point of rotation. And now you have basically a traditional solid part. And while you still have the same kind of rotation, it can be a lot rougher. Hear that? That's because inside of the axle, there's a little bit of settling that happens, so it becomes a little bit oval. So this is generally for like cheaper applications. So there you can get away with this. And if you have a large hinge door on this, you have so much leverage on it that there's no way it would ever stick or have an issue, but it just isn't as smooth as the vertically printed option. So there you have it. There are all kinds of hinges that can be made, and with 3D printing, you can actually make impossible hinges that are not possible any other way. So depending on what your application is, use the best hinge that works for you based on the profile that you have, based on what your requirements are, and based on what your cost is. A traditional simple living hinge can be very affordable to put into any part and doesn't really add any cost at all. Whereas this type of part could increase rejection rate, so in mass production it could be an issue, but if you design it right, it's not an issue at all. Just make sure that you're designing for the process.
Hello everyone, and today what we're going to do is we're going to go through and talk about how to design a 3D printed electrical enclosure. Now, you probably are familiar with electrical enclosures from the past. They're just a plastic box, and generally they have some sort of sprues inside of them or some sort of standoff in order to mount the chip inside of the box. The benefit of the 3D printed enclosure is that it can be fully custom and customized to the box. You can make it oddly shaped on the outside. You can give it organic curves. You can give it some textures. And of course, you can do simple things like give it holes exactly where you want them and labeled exactly how you want them. Something like this, which is a really big benefit because you get a fully custom solution, which is not always that easy to do. But the challenges with a 3D printed enclosure is that very often they are not designed for 3D printing. People design for injection molding when they're making one of these, and that's an incorrect place to start. So today I'm going to show you kind of the key features of how to make a 3D printable electrical enclosure that will actually be good and give you those details so you can use them in your own designs. So right here, this is just a general dimensional box of some imaginary PCB that we're gonna put inside of here. And these four slots or holes right here mark the places of the standoffs where the chip has to screw into the standoffs of the box. So the first thing we're gonna do is the simplest way to address this is to just make really thick standoffs. A lot of people try to make these really thin. You do not want them real thin. You want them to be very, as thick as you possibly can. Because the more material you can put inside of there, the more structurally sound it is, and you don't have to worry about putting in any sort of extra support or worrying about like 3D printed parts snapping off if a technician tweaks it with a screw of some kind or a screwdriver. Let's extend those out right there. Okay, so we have these standoffs, and again, making them as thick as you possibly can, but generally you would start running into the leads or the solder points on the bottom of the PCB. However, with these parts, they're not done. You don't want just that thickness. You also want to make sure to use a chamfer, not a fillet, but a chamfer. Cool. There's a fillet. Should be able to do a chamfer here. There we go. But you want to use a chamfer because you can see how it has this nice rise so that there's no orientation requirement with it at all. So you can print this box in any orientation. There is no way that the standoff will break off. And using these types of features don't actually add really that much material because you're just adding basically extra honeycomb on the inside, which might add a gram of material, but it's not significant, especially for the structural benefits that it gives. As far as designing this hole, you can either design it to be a screw straight in and self-tapping, or you can design these holes to be heat set and talk to your application engineer about which one would be best for your particular solution. If you want to use heat inserts, they can give you kind of dimensional info of how to design those. But you can see with like this fillet here, the problem with fillets is that they come down to horizontal, so you would start to have overhang right here if you were printing this box on its side. But we'll get back to that a little bit later. Right here, another option and way of doing this is to actually go ahead and design in ribs. We're going to continue to look at it from the side here as if it's printing in this orientation. In that case, you would want some kind of a rib like this, and you can make it tangential to the thing if you want to, but I'm just going to go ahead and go like this. And we're going to take that up distance to the floor, just like so. And then you have that rib that can sit there. It could go all the way to the outer wall so that, again, you get more support and more structure. Or here in this case, I'm just going to chamfer it off. And you have, again, a nice little rib and chamfer in there. Take it to however far in you want to go, but make sure you have a lot of surface, and that will be fine. But again, mainly with the standoffs, it's just whenever you can add volume to a part with a 3D printed part, you want to, because it gives you so many new structural benefits and generally improves manufacturability because we don't have any overhang problems. So there we go. Those are kind of the four main ways of designing the sprues. But what about the box itself? So we have this box. You could probably live with it as is, but we want to make this highly manufacturable. We want this to be as affordable as possible to create. And for that, you definitely don't want to print it laying down flat like this to where this broad side is against the bed, because that would be dramatically increase the cost and wouldn't really give you very many benefits. Printing on this side is better, but it still could be sticky, and this is a side that the customer or client or end user might be able to see again, so you want to minimize faces that are in contact with the bed. So what we're going to do is we're actually going to go ahead and just chamfer these outer corners. And I go deeper into why this is so important in another video, but you want to make this chamfer just as big as you possibly can too. I'm going to go all the way for 10. Because even though that thin corner is there, it's going to be a very strong thin corner. Oh, that's a special chamfer that was a 2 distance one. I want it to be equal distance of 7. There we go. But now we have this corner. The other thing to do is you don't ever want any sharp corners inside of the part at all. So we're going to go in here and we're going to fillet. Actually, I'm going to save myself some steps. I'm going to fillet these corners first and save myself a couple of clicks. Don't want that face. And again, make the fillets as big as you possibly can. I'm going to go ahead and just go for the 5 that I started with because that's a nice happy medium. But again, if your PCB needs to fit in there stringently, make it whatever fillet you're able to. And then, of course, fillet the bottom just a little bit here. I'm going to give it 5.2 just to make it all uniform because, again, down on the bottom, it doesn't really matter. With all of this, I'm actually going to show you one other option. Let me export this real quickly. Okay, and we're back. We're going to go ahead and suppress basically all the stuff that I just did because there's another way to get it done. Another option is to actually just outline the leads of the board itself. And what I mean by this is that you can design this in here. Again, you want as few islands or as few individual features as you possibly can. So I'm going to go ahead, outline all of these. I'm just going to kind of eyeball it here. I'm not going to give them, well, I'll give them set dimensions. What the heck? It's not that hard. Just like this, because these are going to be the holes, just like so. But then, if the leads are not inside of there, an even better way of getting this done is to take something like this and go here, and then from here to there, and then from here to there. And then again, if you have like a weird, the leads or the solder points on the bottom of the board, if they have a special construction of some kind, you can go through here and make some kind of a random shape that moves out around, and whatever it happens to be. I'm going to let that kind of be that way, even though it doesn't seem very technical. But it's fine, because maybe you have some leads sticking way out here, and it'll make more sense here in a moment once I get this done. I'm going to make it a little more symmetric. There we go. And then we will basically extrude this backwards to whatever your highest lead is. And I'm going to take it backwards 5. Oh, we're just going to take it backwards 3. But you can see now that plate, that PCB, is basically mounting against a solid surface. And you could actually even run ribs across this so that the PCB is really well supported, especially if this is in a high vibration area. That way it's no longer on standoffs. It's basically embedded into a custom inset for the PCB. And this is also really great because, again, there's no features that can snap off, get broken, or in manufacturing somebody ruin. These are really good for heat inserts. And again, that's just another way of mounting the PCB so that the solder points are able to go inward and you don't bend the board, so it's able to mount flush against the screw holes, but still have space back there for the lead sticking out. So let's go ahead and export this, and I'll tell you what those chamfers are so special about here. Okay, so the first thing we're going to look at is that first enclosure that we made. Obviously, it's importing here normally. Like I said, you never want to print an electrical enclosure like this because it just creates an opportunity for the standoffs to break off. Even if they are like this. And again, this is not ejectable. The machines remove these parts from the bed, and if it has a very high surface area in contact with the bed, it can cause an issue. And it can also cause defects throughout the print. So the other option is here on the edge, like we stated before, but again, this might be a customer facing face, so you don't really want that. So actually, the best option is to print it like this. Now there are no direct overhangs. You can see here that because we use this chamfer right here, that standoff is fully supported, unlike this one up here. And actually, let's go ahead and take a look at that real quick. I'm going to go ahead and do everywhere and make that a little bit better here. That way I can show you, if this was if this was a standard type of standoff, then we would have to generate this internal support material, this blue stuff right here, that creates all kinds of issues for us because it's just extra material that has to be removed and thrown away and doesn't actually do anything functional. So what we're going to do now is, now we've got it set up like this, we ideally would have our ribs oriented in the correct direction. So in order to avoid confusion, I'm going to go ahead and rotate this all the way around like this. That way this rib is actually helping. And you can see the fillet again has this overhang that would cause some support, but this chamfered one up here is perfectly clean. The outer walls don't have any problem, and the only outer surface that'll look a little bit different is the single bit of touch right there. The other option you can possibly do is actually chamfer this lower edge so that it leans back, and something like that would look a bit like this. And again, look at that other video, but this has a problem because now the center of the gravity of the part is not over center, so it can cause disconnection from the bed. So it's not the greatest option. If you can, you want it to all be symmetric, just like that. So you can see how that's going. I'm going to take a look at the material used in the print time on this. As it comes out, it's printing in a low resolution and a low infill because, again, this part should be fairly efficiently made. 8 hours, 117 grams. That's quite a bit. But let's pull in this other one that's the inset style. Let that slice. And see, we saved some time and some material there, mainly because we don't have the sprues which add a bunch in. So this isn't a huge benefit, but you can see that it'll come out so much slicker and it'll be so much easier to place the PCB because you basically have this inset acting as a finding feature so that the leads themselves could align with this outer edge and then force the PCB into position. That way your technicians can easily set those screws. The problem with this inset format is that you have to make this back wall really thick, but it is good if it's a side mounted part or if you're allowed to have a hole in there or anything else like that. If you wanted to, you could put a hole in there so that people can poke out the PCB. You can have a row of holes. You can have a new outlet pop out the side. And if you're thinking about the end process of using FDM 3D printing to produce these, you can get ESD safe materials. It's much more affordable than molding most time. And anytime you want to, you can update the design for whatever your new PCB might be, because PCBs can change every day, but the molds, if you had this molded, cannot change all the time, or they're exceptionally expensive to change. Hello everyone, welcome to this edition of Design for 3D Printing. Today the prompt that was given was to create a base for a lamp. And this lamp is going to have multiple different types of overall shades put on top of it. So we wanted to create a base that is fairly universal, that many different styles could be placed on. And when you're designing something for high variability or high adaptability, where it needs to plug in with a lot of different things that still look good, you want to work with really primary sort of shapes. So a cube or a cylinder. There's actually a whole sort of industrial design component to this that we're not going to focus on too much here, but we're going to start out with a square. Since it's going to be turned into a lot of different options, we want to start with something really, really basic. So we'll start with a square here, and it'd be easiest to start with a cube. That is a nice general shape that works fine. However, since this will be a cube with a large lampshade sticking out the top, you don't want this base to be that big. You want it to be kind of understated and sort of hidden. So there's actually a minimal depth that we can have, because we have to put a lamp socket into this. And I'm actually going to measure that up right here right now. And that depth is 3 inches from tip to top. I'm actually going to decrease that even further because the socket is able to stick out a bit. So the minimum depth that we can actually have is 2.5 inches right there. Now that's pretty good, but that is actually also almost too subtle. So I'm going to go for 3 inches because I think that'll be a better ratio with kind of the lampshades that we're dealing with that'll be going on top of this. So there's that. Okay, cool. So that's a nice little box, nice and simple, nice easy cube. What we want to do is design in now the basic socket for the lamp. And this will be pretty easy. We'll just put a hole in the top here. And I know that it needs to be 38 millimeters in diameter. So that'll be that. Oh, wait a second. I don't want to use that sketch. From the bottom, I want to cut a hole because the socket doesn't have, you can't run wires with it. It has a plug and the socket finished up with it. So it's a fully finished unit, and the plug has to come out the bottom. So you always want to start with the smallest hole first, and this one is 32 millimeters. There we go. And we want to start with that first because we don't want to have to extrude something out if you can get away with just cutting stuff. Distance, go through all of that. Reverse the direction. There we go. There, that's that basic hole. And then maybe it'll let me grab that old sketch. Yeah. So the depth of this one, we are going to design this lamp socket to stick out slightly. That way we don't have to make this box so thick. And it actually helps in a number of other ways too. Inches minus 1.5 inches. So about 35 millimeters. There we go. All right, so that's all set there now. Okay, so that's good. So we have this small DIY lamp socket going into the bottom here, and its plug is able to go out this bottom hole. That's all fine and dandy. However, now what we want to do is we want the wire to be able to come out the back. Now, there's a couple of ways of doing this, depending on how you're ultimately making this thing. You can do it like this, and a way I like to do it is actually to use a slot, because it's a very fast, easy way to get some chamfers. You always want to go wider or bigger on your first try in order to make sure that you have enough room, because it's way easier to glue something in than to remove it. So we're going to start here with 7 millimeters wide. And we know overall it only needs to be about a ½ inch deeper. So we're going to actually take that to 0.275 there, inches. There we go. So this is version number 1. And we're going to go all the way up to the other side of this hole. There we are. So there's a nice little slot that the cord could come out through. But the problem with this is that this doesn't really hold the cord, which I don't really like very much. The cord actually has to be glued up in there, which means you have a secondary manufacturing process that can be tough to get done. So actually, we're not going to use that. I'm going to suppress that, and we're going to start again. And there's a better way of getting this done that I like a lot more. And that is basically a hook, kind of a one-directional slot here. What we're gonna do is we're gonna create this larger diameter set of deals here. Another circle right here. It'll get a little bit clearer what I'm doing as it gets in here. But this slot, this hook slot is gonna have all these align so that a cord is able to wrap up and into the part a bit here. Just like this. Hang on, let me set the dimensions of that so nothing's wobbling around. Yeah, it's fine. That's not a big deal. Okay, and then let's go ahead and take a line off of that going down there, and a line of that going off down there. And we're gonna want those tangential to these circles, respectively. And we'd like those lines to be parallel to each other. That way, these should be able to drive the dimensions of a lot of the rest of it. And 5 millimeters, I believe, is the correct. Yeah, 5 will be fine. I'm actually going to go 5.5 just to give us a little bit more room, because again, you always want more room rather than too little. I'm going to wrap that all the way around. Again, this will get a little bit clearer what I'm doing as we go along here, but I'm just adjusting a couple things. Okay, there we go. I'm happy with that. Now we're going to take this. We're going to extrude that, extrude that, extrude that. Wait, finish my sketch. There we go. Extrude that, and go distance to object to this center hole. And now you can see what we've done is that the cord is able to wrap up into here and then wrap underneath. So I'm going to go ahead and suppress this. The reason being is since this part is being printed on a 3D printer, it means this whole surface is going down. And you never want these large, broad surfaces against the build plate of the printer because they create opportunities for defects and large bed adhesion, and they're tough to automate for mass production. And we really want this to be mass producible. So we're going to go ahead and take a chamfer here and go up like this and go, we should be able to go about 50 or so. Okay, it's going to stop us. I'm actually going to go all the way back and suppress this. I don't want to do that either. I'm going to make that less steep. Let's go -1 inch, just like so, because it has to be able to go in there. So that is our limiting factor. But then we'll go ahead and take this chamfer like this. Can I go to 40 yet? There we go. That's what I want right there. So you see I have this nice big old cone here, and what this has done is removed a bunch of the baseline material so we don't have that big old initial build layer, but we'll have a nice clean inner layer. And if you want to cover this up, you can cover it with felt or something like that. And then I'm going to go ahead and take, I believe this sketch, oh no, that was the very simple one. I want to take this all the way up here to the front. Come on, will it allow me? There we go. It will allow me. So now this is the reason to use something like this hook. This hook is way more flexible and allowable for this kind of internal feature than the other small ones. All right, cool. So that's the baseline shape. That is the base of this lamp that we can use. And now we're going to optimize this a bit to make sure that each one of the core features is as reliable and solid as it can be. And for that, it's always about filleting. You always want to fillet everything just as much as you possibly can because rounded edges are our friends. So we want to make sure they're all smoothed out because it creates a much better surface, a much better look, and makes it much more manufacturable. Around here, we obviously don't want sharp edges because it could potentially grab the cord. If somebody like jerked it off the shelf, you don't want it to tear through the electrical cord. That would not be very good. I'm going to take that. Yeah, I want that to be 2 millimeters. I'm going to go back into the design of that thing. Here we go. So I'm going to take this up higher and make that 15. There we go. So that gives us a lot more room. I'm going to see if I can increase the diameter here a little bit because what I want to do is I want to increase the space. There we go, right there. That'll be fine. You can see I didn't really heavily dimension that because I was trying to thicken this up right here so that that isn't a potential danger because that is sort of a break-off point. But again, the cord should never be under any major stress, so it shouldn't be a big issue. Okay, so there's that. We have filleted all of those. I'm going to fillet the bottom of this again to kind of catch the cord. It can be really big because it's at the top anyway, so we don't want it. I'm going to fillet the bottom down here just to clean up some stuff, and it just has to be small and subtle, so that's okay. Well, actually, I'm not going to do that. Because that messes with my other thing right there. Okay, so now we have this nice box, and if this box was right where we were stopping, we would put a fillet right there. Oh wait, nope. Let's go ahead and go right here, right here, right here, and right here. Make that 5 or 1, depending on what you want to do. Even if you don't want a large fillet there, you always should fillet it because it improves the tool path for the machine. So if you want this nice square box, that's the place to stop right there, and maybe fillet the top a little bit here. And I'm going to give that like 2 or 1 there too, just a little bit. Now, we will have this base with a bulb sticking out the top in front of a nice rated housing, and then you can put a lampshade on top of it. So that's all well and good. Now, but there is an issue here. What if you want a different shape? Well, now I'm going to go through here and create a few new shapes. All right, so in order to create these other shapes, the first thing I'm going to do is I'm going to suppress these features. And the reason we went for cube is because it's really easy to take this and then go ahead and just add some fillets to the outer side that are 2.5 inches, and now we have a cylinder, which is a nice, quick, easy way of getting to that point. And then we'll go ahead and smooth this out a little bit, and we'll go to 2. Okay, so that'll be good. And now we can go ahead and save this. And with this one, again, we want to make sure that we go around and put a fillet on the bottom, about 1, just like so. Okay, cool. So that's all set there. And then if we want to go even further, we can take this and make that about 1.5 inches. And now we have a dome. And if I wanted to shorten it up, I can do even more with that. I mean, I could push it a couple different directions, but that's actually pretty good. I'm quite happy with that. And if I want to push this a little bit more, then we could take this up to 1 inch, just like so. And now you have this nice little curved shape that's really just very, very delightful. Nice smooth. It's got some directionality to it, which you kind of want this asymmetry in the vertical direction. That way people kind of know what to follow. It's kind of an industrial design preference. It depends on what you're doing. So make sure that you're just considering whatever your end result is. I'm going to take this 0.5 inches. Interesting. So it'll let me go to 1 inch, but it won't let me go anywhere else. Odd situation. For this kind of a thing, what we'll do is we'll just pull it into the slicer and we'll push it down into the bed a little bit. That way I don't have to model up something else weird inside of here, because this will look pretty nifty. But let's go ahead and save that. Base. There we are. So that's how you can get to a cylinder and then to a dome. So let's go ahead and suppress those, and let's be a little bit more creative with that now. Suppress features. You might want to just kind of go for a more angular sort of motif. So here you would want to go for like a chamfer. Just like this and like this. Oh, let me get that other edge. Cool, we got them all. Here you can go ahead and go for 50. So there you can get this sort of odd cropped design. It's going into the circle on the bottom. You might want to modify that. So I'll just take this down to 40 because I don't want to go back and change that one. I do want it to be symmetrical. So make sure this is an equal distance chamfer. There we are. That looks much better. So you've got a nice hexagonal base for that, which can look quite good depending on what the base of the thing is. So let's go ahead and save that. Just like that. But maybe you don't want to do even that. Suppress features. Maybe you want to go for something sort of pyramidal, and just give it, again, kind of that directionality that I was talking about before. Just take these up like this, like that, and then go to distance. And we'll go 20 and 40. Oh, yeah, that looks quite good. I'm going to make this a tad more subtle. Oh, wait, no, that was not the direction I wanted to go. There we go. Just like that, and take that up to 50. A little bit more. There's the ratio, the golden ratio, and that's kind of what I'm shooting for here with these angles, which is about 1/3 and 2/3. That's not quite true, but you can generally notice the golden ratio just by does it look good and that kind of a thing. That will lead you around. But there we go. So there's that design, which is kind of pyramidal. Of course, you could take these all the way down and you could take that in narrower. I'm just going to call that the pyramid one. Save as. So there we go. So that's looking quite good. And then let's see here, what else could we do here? We've done the hexagonal pattern, we've done kind of a pyramidal design, all based around the same basic platform there. I'm gonna suppress that. I'm gonna go back to that previous chamfered one and just give us a little bit, something to play with here, because there's a neat way of making kind of a faceted design. Modify chamfer right here, right here, right here, and right here. I'm gonna make that 10 actually. Not too darn subtle, not quite yet, but then I'll take that and do a chamfer right here, and we'll create sort of a fractal design, which I think is quite lovely. Let's go 25. Yeah, there we go. That's pretty cool. Let's actually go 40. 50? Too far. Oh, it's not. There we go. Just like that. Oh, that's quite a nifty design there. I'm gonna call this Pyramid 2, just right there. But then you can take this, and maybe you want to not have any vertical edges at all. Then you can go ahead and take a chamfer, put it right here, right here, right here. And in order to kind of create a mirror look, I'm going to put it on these other sides as well. The back-facing side I don't care about as much because it's on its own, but just add a little notch right there. Oh, that looks pretty nifty because now it's kind of like a jewel. Let's go ahead and add one more there for 5. There we go. See, that's a very nice kind of a jewel design, or maybe sort of an industrial sci-fi type of design. The base is still all good, still all solid. We'd want to go through again, fillet all the sharp edges whenever you do something like this, but let's save that. Jewel 1 lamp base, there we go, just like so. I'm actually gonna delete that one, that version of it, and take these in up on top more, but just at a different amount, and go 25. There you go. There's another really nifty kind of a jewel design, and then the bottoms can come in a little bit if you want to, or you can go back to these and make them a tad bigger, just like so. Oh, I want that equal distance. There we go. There we go. Just like that. Ah, that's pretty nice. I like that quite a bit. That's a really nifty. It's got a narrow top. Again, the point of these bases was to not draw attention to themselves, and this is getting into something really complex, but it's sort of fun to mess with. I'm going to take these back down to 40 so that the top is a little bit more even. Oh no, I'm going to take that back to 15. There we go. Take that back up to 50. There we are. There we are. Now this top is a lot bigger. It doesn't draw quite as much attention. This is sort of a large face right there, so I would like to take that back. Again, I would reduce this cone inside of here so that we could really take up that chamfer, and then you can create all kinds of hexagonal patterns. You could carve around the outer side with some kind of a wobble, but ultimately what I was trying to get to with this design was something very monolithic and very simple. So file, save that. We'll save that as Jewel 2. There we go. So yeah, there are many ways to skin this particular cat, but hopefully this shows you kind of the way of designing and optimizing this large slot, making sure that you're filleting everything, always thinking about kind of the end goal, but then kind of have fun with it. The fact that 3D printing allows you to create these variations really quickly, we could theoretically take these lamp designs, post all of them for sale on some e-commerce site, and then whichever one does the best, you focus in on that design and then you expand it some more. So it's very easy to create new products very quickly.
So you've made a part that you want to mass produce with 3D printing. Great, happy to have you. But you probably want to put a little bit of text on the side. It might be a logo, it might be a patent number, it might be an identifier or a barcode. Anything along those lines can be embossed or engraved onto the side or onto some side of the part. But in 3D printing, orientation really matters. So today we're going to talk about how text should be placed onto the sides of 3D printed parts, what to be aware of and what to be concerned about, and the things that you should probably avoid. So let's go ahead and get started. First of all, let's just look at text on the side. If you're looking at text on the side, generally there's two options. You can emboss or you can engrave it. That is, you can cut the text into the side of the part, or you can have it expand and extend out of the part. If you're doing this on the side of the part, that is the best place to put text. You really want it there because you have that smooth
smooth, clean surface that is controlled by a 0.4 millimeter nozzle or some variation thereof. And that nozzle creates very fine detail that is very clean and very legible. Now, that being said, you want to control the height of this text. If you're cutting in, you only need to go in about a 0.5 millimeter. That will create enough contrast. If you need really, really stark text, you can go deeper, but depending on your font, you might want to be careful because that can create problems in the actual production of the part that can create defects within that text. So try to keep it as shallow as possible, no shallower than 0.5 millimeters. Another way that you can do text, if you don't want to cut into your part, then you can extend it outward away from your part. This is also wants to maintain about a 0.5 millimeter depth, because if you make the text any higher, then you will end up with it sagging on the bottom or requiring support, which means additional post-processing, and those are things that you just want to avoid, because making it taller does not improve the legibility much at all when you are embossing text on the side of a part. So hopefully that covers the depth of the text. Now let's go ahead and talk about size. Generally, since you're making this text on the side of this part with a 0.4 millimeter nozzle, you definitely don't want to go smaller than a 0.5 thickness of text, then the nozzle won't be able to actually print it. But even more than that, you generally want to avoid text that is thinner than 1 millimeter, which can create some chunkiness, so there's variation there. Somewhere between 0.5 and 1 millimeter features of the text. And as you can see right here, if you start with a very large font, it's very legible. When you get smaller, it starts disappearing. And if you try to do very small, like 10-point font, which is about 1 millimeter, actually this is more about 6-point font, it is so small that you're not even going to see it. It is a divot, a wart, a mole on the side of your part that has no legibility whatsoever and might not appear at all. It might be ignored completely by the slicer. So make sure that you are designing text that is an appropriate size, that has each feature of that text somewhere between 0.5 and 1 millimeter thick. Lean into the bolds, lean into the heavy sort of fonts, especially if you want to maintain that type of information. Now, sometimes people want to put text on the top of the part. This is not desirable because number one, the text breaks up the upper surface, so it can create all kinds of weird artifacts as far as appearance that are tough to control. So you want to avoid text on the top of a part as much as possible. But if you do have to do it, it is better to dig the text in and engrave it than to emboss it. The reason for this is because since 3D printing would have to move through basically islands of sections of the text, so like moving from the outer edge of an O to the center of an O, that motion is an extra retraction step, which can cause, again, some defects, can cause stringing, could again then produce more post-processing down the line, or could slur or smear the letters if the plastic doesn't settle just correctly. So this is why you want to avoid text on the upper surface. It's a very complex kind of shape that you don't want to have in mass production because at some point over the course of 100,000 units, something will probably go wrong, and you don't want to increase your rejection rate because it increases the cost of the part. Engraving the text reduces this, and it is a more robust way of creating text on the top of a part than embossing it, where the text is raised. With that, you now have very distinct little islands. They're all concentrated heat because they're small features where the nozzle deposits material and then moves from one point to another, which means it's very easy to smear. If there's not exceptional amounts of cooling, it's just a very fine-tuned feature that requires a lot of things to go right. And you always want to make a manufacturing process as robust as possible. You want to make it as easy to create a feature as possible because that will create a better quality component more affordably and at larger scales. Now we get to text on the bottom of the part. The bottom of the part is whatever surface is pressed against the build plate of a production machine. This you also want to avoid because that first layer can have some amount of variance where side extrusions can end up smearing the text or squashing the text or blending it together in a way that doesn't create a consistent aesthetic. That first layer has a little bit more tolerance variation than other areas of the part, definitely from the sides. So you want to avoid text on the bottom of a part as much as possible. The other issue is, as the machine is laying out the outline of that text, it has to adhere just perfectly, but if the text is really fine, it will end up pulling and again smearing and deforming itself slightly on that first layer if it's not just perfect. So again, in order to create a really robust process, you want to make sure that you don't put text on the bottom. But we have a solution to this. If you really want to have text on the bottom, or really need to have text someplace where it doesn't really belong, but you want it there for maybe identification within your production line, you can do what we call a hidden text. And this is text that is actually inside of the part. This is impossible to manufacture with any other process, and it's a unique advantage of 3D printing. So now, instead of having your patent number stapled across the side of your part and maybe ruining the aesthetic of it, you can bury it inside of the part. Just beneath the surface, anywhere on the part, you can put text. Again, you have to make sure that it's thick text, somewhere between 0.5 and 1 millimeter thick, to make sure that it's legible and that the nozzle and the tool can actually produce it. But you put it just below the layer, and then you're able to print that text, cover it over, and then if you just shine a light through that part, now you see your text. Which means that your assembly technicians can verify what the part number is, identify the parts very easily in a well-lit environment just by holding it up to the lights inside the shop. But again, you do not have that surface defect of exterior prints or engravings or anything else that are not necessary. You can even do this with barcodes in some cases, or a QR code, or maybe just a secret message to your customer that is special to you, because now you can create some really interesting branding. So hopefully that explains all the ways to create really interesting text everywhere from how to do it on the side, how to do it on the top, how to do it on the bottom, and how to do it a way that only 3D printing actually can. If you use these tips in your design, you will make a part that is much more manufacturable and much more capable of getting to hundreds of thousands of units while still being very affordable and creating a nice quality part that you cannot get any other way, all without ever having to buy any sort of tooling or have all that risk of creating a new product that might need to be changed at some point, but you've already set it into stone. Flexible components. Flexible components are generally not something that people really lean into in 3D printing because there can be some challenges with it. But they really shouldn't be challenges. Really, all it is kind of a design tweak. So today we're going to walk you through some very basic kind of clasps, which you might find in any sort of piece of hardware that might need to connect with some other piece by sliding together and then snapping into place so that it can be removed, or just creating a little bit of resistance for a lid. A lot of people end up going down the wrong road on this, so we're going to give you some examples of how to do it well and how to design it so that it can actually be mass produced with 3D printing. So traditionally, when people make simple clasps, they end up making a small tab with a bump on it. And this little tab bends backwards in order to then pop into some little hole on some mating feature of some other piece. It's a very simple mechanism that has been used forever. But what folks always end up doing, and which always kind of stymies mass production with 3D printing, is they end up designing these tabs vertically, which means that the layer lines are going across them when they're printing. And that means that when that tab attempts to flex, then it breaks along those layer lines, which isn't really necessarily ideal. But there is no reason for this to occur. It's mating at a circular component. The flexure of the part really doesn't matter what axis that is occurring within. So why don't we just go ahead and take that and turn it sideways? If you turn it sideways, now that tab is operating within the layer line. So each layer line acts as an individual part of that spring. So there's no possibility that it will ever fatigue or break the way it would if the layer lines were going perpendicular across the part. This way you have the same amount of flexure as you would with any sort of typical isotropic part, and you make it actually easier to 3D print, because all you have to do is insert a small amount of support underneath that tab, which can either go through a vibratory cleaner or just have manual removal of it, which is not that big of a deal. Now here's the thing, almost always whenever you're designing some part for mass production, you never want to leave the slicer to make the decision about how that part is to be printed. So you generally want to go with actual designed supports. So since we have this overhang that is sticking out sideways, rather than having it supported by general slicer generated supports and leaving that up to chance, let's tighten it up a little bit and put in a design support, which is just a small little sprue. This small sprue needs to be about 1 millimeter in diameter in order to make sure that there's enough meat on it to actually be printed with a standard FDM nozzle. It goes up to right where the curve of that tab goes up into the air. And there's actually more tweaks we could do here, but this is more than enough for this video. That sprue then connects with the bottom. Now, once that part prints, all you have to do to remove that support is flick it. In fact, you might not even need to flick it. If you're designing it very well, that sprue could actually just be there permanently in the final part, and when it flexes and breaks out, it flexes and breaks out, which is not that big of a deal. If it's a part that is assembled only once, there's no reason to ever have that support removed, because it'll break across and that finding feature will mate with its partner and you'll be fine. But if it does need to be removed, it's a very trivial operation to snip that out of there, and is about equivalent to traditional injection molding, where tons of sprues connect different kinds of parts. So if you're ever looking at making a flexible part, something that needs to bend or give just a little bit, just to make sure to design in line with the layer lines. That way you get all of the strength of the material that you're printing with, whether it's nylon, a bioplastic, PET-G, or even ABS and those kind of things. You can design for that and you don't have to worry about the layer lines. They don't matter. Just figure out how to tweak the design just a little bit so that you can still get exactly what you want. But now you no longer have to deal with all the upfront cost and risk of traditional manufacturing. This way, you can just buy the part, try it out, use it, start selling it, and then scale up from there to hundreds of thousands without ever having to set your design in stone.
Today we're going to talk about the primary principles around the design for mass production 3D printing by showing you how to actually design a cube. So traditionally, if you were manufacturing a cube, what you would do is you would model up a cube and then you would cut a big old cavity out the side of it. But this is an injection molding, so let's go ahead and just make that a fully solid cube. If you have a fully solid cube, you do not want all the sharp edges. The very first thing you want to do is round any vertical edges that you might have. This creates a cleaner tool path for the machine, but then in addition to that, any part of the first layer you want to make sure to chamfer at least 1 millimeter so that you do not have any sort of elephant footing and you have a really reliable first layer going down. So there, you have a cube, you're all done. You have a solid cube that you'll never need to change at all ever, except for the fact that now it has kind of a little bit of an issue. So if we want to take this a little bit further, let's go ahead and add a cavity to the bottom. In mass production 3D printing, we use auto ejection, and that allows you to produce tens of thousands of parts as affordably as traditional methods. But in order to do that, you have to be able to reliably remove them from the bed. So you cannot have too much adhesion. So in order to reduce adhesion with the bed, we reduce the surface area in contact with it. This is why we have this bowl at the bottom of the part. This allows us to change how much adhesion we have with the bed in order to make sure that the part is still reliable, but easily removable. This radically reduces the cost because you no longer have manual removal of thousands of parts. But that's not always necessary, it's just a way to optimize. It's something that you can do in order to improve your part, but it's not necessary. You can make a fully solid cube if you want to, but now you're having to deal with the bed's surface finish on that one wall, which might be fine. But now, if we really want to improve this, you might not want the layer lines on this particular 3D printed cube. So how would we go about eliminating those? Well, one of the most reliable ways is to design in a texture yourself. Go into CAD and put in a cross-hatching or some type of random pattern and pattern it across all of the faces of the part. There's also a number of different solutions that we can use to add noise, add a height map to your part so that you can get a texture that you wouldn't otherwise be able to achieve. This is completely free to do with 3D printing, even though this would radically increase the cost of a mold. It allows you to create a new artistic style, it allows you to hide the layer lines, and allows you to create a product that was never really possible before. But all of this presumes that the print is actually put up on its flat surface. That's not actually necessary. You can put it up on a corner, and by putting it up on a corner, you both minimize the surface contact area and create more uniform surfaces because all of the sides are in the plane of the print lines. So now you have a uniform outer surface texture and allows you to make an absolutely beautiful and homogeneous looking perfect cube. So hopefully that covers most of the main design tricks with mass production 3D printing. Round the edges, minimize the surface contact area, and do what you can to control the surface rather than defaulting just to the normal 3D printing surface. This will reduce your costs, it will improve your quality, and it'll let you make parts that are way more reliable and way more differentiable when you're trying to produce tens to hundreds of thousands of them in a large print farm like here at Slant 3D.
Hello everyone and welcome to Design for 3D Printing. Today we're going to talk about how to eliminate supports in basically any design that you have by designing the part so that it just doesn't need them. So with this generic piece here, you can see we actually have a 90-degree overhang on it. And this is very common. Sometimes in boxes or any other type of part, you might have some sort of feature that needs to stick out this side. Now, normally, when you create a part like this and have it 3D printed, you have to have a whole bunch of support underneath it in order to keep it up in the air as those first layers of the overhang are printed. And this can add a ton of material to the cost of the part, as well as a ton of additional processing. So it'd be great if this support material just wasn't present. So what can you actually do in order to hit that? Well, the first option that most people go to is to add a fillet. And a fillet is fine, except for the fact that it doesn't actually eliminate support completely, because a fillet still goes to perfectly horizontal once it's created, which will still create some amount of material. It's less support material, but that very tip of the fillet will need supported because it is a perfectly horizontal surface, which is not ideal for FDM production. So if you're going to use fillets, make sure that you actually take them all the way and do the first initial large fillet that fills in the corner, but then also round out the tip. That way you have no support whatsoever. And you have a nice, clean, continuous part that looks really nice, looks really clean, and has no support at all. However, fillets are still less than ideal because you either have to have this very large outer fillet in order to blend this curve, or you make this too small and then this curve comes out and it slowly becomes so steep that it is more difficult to manufacture than other options. So if you're really going for maximum manufacturability, you should actually use a chamfer. A chamfer is quick, clean, and you have a consistent angle all the way up interfacing between the two edges. And again, has no support whatsoever. And if you want to, if you don't like the sharp edges of the chamfer, you can of course fillet it. But the question here now is, okay, what if the design does not allow a standard chamfer, a standard 45-degree chamfer that this one is? Well, you can go other directions. You can make it shallow or deeper if you have to. Now, a chamfer as high as 60 degrees is generally fine with FDM, but it does introduce the possibility of failure because if the flow is not quite right and the cooling is not quite right, you can get warping on these really steep surfaces. So if you want to take it to the extreme of manufacturability, you would have this really, really steep chamfer where there's basically as small of an incline as possible, and that makes the part very robust in mass production if you're producing hundreds of thousands of these. However, if the design necessitates it, you can get away with just a small chamfer, and this is still better than a very large fillet that would still need supported. So hopefully that covers it. Ultimately, this is what you want to get to, this highly steep chamfer, but if you have to, you can get away with a more shallow one, and it's better than a fillet always, but ultimately, all of them get rid of most of the support in almost every single situation.
So this is a very simple part. It's just a triangular prism. But when you try to 3D print it, or more importantly, print it at scale, there's a number of challenges around these three corners that we're going to show you a solution for today. So this type of part is a very simple part. This is a very simple example that we're going to use. But we're looking at these sharp corners. Sharp corners, when put down on the very first layer, are not something that's desirable. They cause dragging, where the nozzle will reach out to a point and then drag the corner back with it, which will cause a little bit of a warp. Or if you're creating a very dense part, if you were to print this totally solid, with the certain high warp materials, then these corners break up from the bed and you start to have a little bit of curling, which is also not desirable. And it's an error that can come up a lot, especially in mass production of a part like this, so we want to address it. Also, there's a lot of more complicated types of designs out there than this simple triangle. There's things like the shark, where there's a lot of sharp pointed edges, or something maybe like a tree design, or even something as simple as a gear, where warping at corners can be an issue. Now, the traditional type of solution to help with warping is to put a brim on this, where you have a single strip all the way around the outer side of the part. And that's fine, but it doesn't always work, and it adds a lot of post-processing because that brim has to be removed from the entire exterior of the part, when really the only thing we care about are these corners. So the other problem is also that the brim is a print setting, and you want the design to not be dependent upon the printer settings or the printer tuning itself. A good design can be manufactured basically with any printer at any time and at any scale. So how can we change the CAD of this so that it doesn't need a software generated brim? Well, the most common solution is actually called mouse ears. And mouse ears are these very simple circles that you place at very jagged corners, which round out the outline of the part so that it doesn't have the drag feature, and create a very high surface area for adhesion right here so that that corner is held against the bed very well.
The way you design them is you can place them on the corner and then you make them as thick as whatever the first layer would be. Generally 0.2 is a very good thickness for these types of features so that the software can catch them. And most softwares will catch them very reliably. This way, instead of having a brim all the way around that needs to be cleaned off, you have just a small area that can be trimmed off very quickly. But this can be optimized even more. This still has quite a bit of touch and can leave residue on that tip. So there's an evolution to this that can be utilized, which is to actually put kind of a sprue off the end of the corner. This way, instead of having to trim that edge and trim that edge, you instead just literally snip off the tip of this mouse here and it holds it to the corner. However, this one has been exaggerated in order to show that sprue. This is a little bit far spaced and a little bit long because what would happen is if this part was very dense and had a lot of warping or a lot of internal stresses, it would start to pull up on this little sprue and it would kind of stretch it and it would still potentially warp. So you want to make sure that this surface area of the disc is as close to the corner as possible. So what we'll do is we'll go in here and we'll edit this sketch and you'll basically move it in right to the edge. And that is a very good sprue where you have a very tight control of the part, but again, it snips off in a half a second so you can produce thousands of these inside of large print farms and not have to worry about a bunch of post-processing, labor cost, or additional cost. So that helps a huge amount with the part because 3D printed parts are really just the cost of the machine time and the material, but then a lot more cost comes in with post-processing. So rather than using software-generated brims or these kind of basic designs of the mouse ears, you can create these sprue-designed mouse ears which will hold together jagged corners that have a high potential to warp or to fail in the first layer, and they add very minimal extra post-processing to the part.
So how do you make sure something like this fits perfectly into something like this every single time without having to worry about print settings? So this is a super common problem inside of 3D printing, and it is dealing with tolerances, the fit of things going together. This exact same file printed on the exact same machine with a different color no longer fits the same, because a different color can change how the material shrinks and behaves. A different material obviously changes how everything shrinks and behaves. A different resolution changes it, a different infill changes it, a different machine changes it, a different nozzle size changes it. And it is almost impossible to rely on printer settings to make sure that the same files printed on different machines in different situations all behave exactly the same, unless you very, very intentionally design the parts appropriately so that they do. So let's go ahead and run through all the variations of how to design both the base and the lid so that you get them to fit exactly how you intended every single time, regardless of what material, color, or machine anyone is using. Let's go ahead and start with the baseline, very simple kind of CAD model where you just have a square base and a square lid and they fit together here. This is really poor design. This is kind of entry-level design. What you want to do is you want to actually optimize for the process that you're working with. The very first thing you want to do is go ahead and round all the edges. This ensures that you're able to get rid of any potential warp around these individual corners, and you also eliminate kind of contact stress areas at these sharp corners, because as the nozzle is going around, it can bounce or there can be flow delay, those kind of things that will cause these corners to suddenly become dimensionally inaccurate. If you round it off, you no longer have that bang bang location, which is what it's called, where you have a sharp corner and you have to change direction. You have this rounded out direction to where it can fit very snugly inside of there, and it's just these side faces that are far truer than individual sharp corners can be. In addition to that, on the bottom, you always add a chamfer to the bottom of any given part, and that ensures that you don't have to worry about elephant footing or anything on top, but that's more cosmetic than anything else. Right here, you can see the other little trick that we did on this one, which is one of the easiest and simplest to implement, which is this small chamfer over on this side. You can see that this edge is slightly angled as compared to this one, which is perfectly vertical. The reason you want to do this is because now, instead of having one single dimension that everything has to fit to, you can actually have multiple dimensions so that you know that will at least start and then it can be pressed in the rest of the way. And then you can adjust this and play around with it different ways in order to get more tightness. Since I just basically applied this chamfer right here, it fits a little bit loosely on there. But if I was to expand these dimensions just a hair, you would start to have this slide to where it comes in on the top and then it can slide in and interlock. And this is a really good way for making kind of one directional lids that just press together and then never come apart. But you know that it will always fit, and you know you will get that wonderful press fit without having to worry about it not being able to go together, like in this case, to where they can't even get started. You will allow this wedge to wedge into the cavity. Now there are ways of evolving this. Obviously you have the top right here with the chamfer on the side, so this acts a little bit like a wedge. But you can also just evolve it a bit to where you're using a fillet on the top so that you have this starter edge, and then you can still have this large horizontal surface so that you get better interface with the outer edges like that. This creates a tighter kind of a fit, but still allows you to start on it, but also creates that robust dimensioning while maintaining all the rounding out the edges that you need. But the problem with this one is that when you have the solid inner base, you have a potential shrinkage in there. Depending on how the infill direction is going or what type of infill is being used, the shrink on this can be different so that these side walls are a little bit different. In order to adjust for that, you can basically go to a thin wall. Just cut out the inner cavity, and now you not only get a little bit more flexibility on these if you make them really thin, but you also reduce the opportunity for infill to affect the dimensionality of your part, because this is basically just the walls, so you know they will always be solid. And in this case, you have a much more reliable set of dimensionality, because instead of having shrink pull this in to where it enters more easily, this part is much truer to true dimension and is therefore a little bit harder to get in there, because these two have the exact same dimensions, but for some reason this one goes in a little bit easier because it has a little bit more shrink than this one, which has a little bit less shrink. But you can take this idea of the thin walls a little bit further in order to get more flexibility in how you design this stuff. You can take those walls, make them very thin, and start to change their pattern. Right here, this is designed to literally just have contact with the outer corners. So with this, these four corners are now the only contact areas. It can slide in a little bit more easily, and since it's thinner walled than the original, these can actually flex a little bit. So if for some reason the dimensions are a little bit off, you know somebody can press it in and probably still pry it out, and know that they're not just grinding on the part and forcing it in there, because this is effectively a compliant mechanism. And you can lead into that even further. This is a truly compliant mechanism. What is the difference here? The difference is this one has the star fully embedded into that base plate to where it is a solid wall, whereas this one has had cuts taken out underneath the bottom here to where these individual walls are able to flex themselves, which again gives it more compliance so that it's able to insert in there even more easily than the original was able to, because it just has a little bit more space. But the danger with those kind of compliant features is that you want to give a gap underneath here of about 0.3. This ensures that at any resolution, the part can still be printed and that gap will still be present. But 0.3 is so small that sometimes slicers and 3D model systems will attempt to adjust it or consider it a defect. So right here, you can kind of see how there's this cross patterning right here. This is because there was that cut into the part in order to create the slot underneath here, but it's so subtle that the STL itself was kind of modified in order to create these artifacts that kind of close up those holes. So you can make it a hair bigger, you can go as large as 0.5, but at that point you can start to get deformation in your features. So you want to keep it as close as you can, minimum of 0.3, and then you can go bigger based on what you need to do. But now you're starting to get into the weirdness of slicer settings. 0.3 is generally the best. Make sure your STL is clean and good. One way of taking this compliance feature even further is with these types of shapes. Right here you can see a split version of this U shape that allows it to bend a lot because it's just two thumbs pressing up against the wall. And right here is a solid version that also has just a little bit less compliance because it's fully solid. But this allows you to have lots of flexibility. So if you want a part that's a little bit sloppy or just a really loose pull so that you know people can always get it out, but still have good contact, you can create these types of spring features in here. Again, gap between the layer, 0.3 high, and then you can just press it in there and it pops in there really well. And you can adjust the tightness of that by flattening out this U and that kind of stuff. And of course you can soften it up by splitting it so that it has less compression on the outer wall. And you can mess with these kind of compliant features in all kinds of different ways. I like this one because you have the square down at the bottom in order to position the lid appropriately in the base, but you still have plenty of room to mess around with the spring up here. And you can make it softer and harder by making these thicker, pushing it out a little bit so that it squashes more, all kinds of things you can do about that on the baseline of springs. But these are really good ways of designing the lid to fit into whatever base you have.
But the lid is not the only component in this part. Sometimes you cannot redesign the lid. Sometimes you only get to work with this. And this original design right here is also terrible because, again, sharp corners and bad design throughout. So first of all, let's go ahead and run through that design and make sure bottom is chamfered, make sure the inner corners are all rounded. Now you have a part that is well designed for 3D printing, at least as a baseline. But the corners create a lot of contact area to where if you have a standard type of lid, there's just so much surface area for it to interface with, maintaining a consistent fit and feel can be difficult. So what you can do is just reduce the amount of contact area. And a simple solution to that is doing things like this, where you basically cut out the corners so that they're no longer interfacing with the lid. And now you just have these nice flat outer sides that are very precise, very reliable, and very consistent. So you don't have the corners contacting anymore, you just have the outer walls. So now those two parts can press together really well, whereas the black and the purple do not fit together very reliably at all. And if they do, they're not coming apart. But with this design, it is still a solid part. It is going to hold its dimensions and it's not going to stretch or move at all. And having some level of compliance inside of your part can be a lot of help. So that's when these types of features can be handy. These little splits in the corners can allow the part to spread and bend so that when you have something big and rigid like that, the outer part can adjust and move so that it goes in really easily. Again, as compared to something like that. Now, these splits can be really dangerous because they are in the plane of the layer lines. So if you put a ton of these in there, they can help the parts split off. In this case, it's okay because they're 90 degrees from each other. So even if this one starts to split, it is still supported over here by the other side, but you can make them more and less subtle just to give you the little bit of an edge that you need. And just be aware of that potentiality. Don't try to make this an uber press-in part to where you're wanting these to splay out a 0.5 millimeter or something, because that will cause splitting in the layer lines. But if you just want, if you've tuned up all the tolerances for the most part as well as you can, and you just want a little bit of a safety factor there, that is where these can be really, really useful. But now let's go ahead and move into some really advanced stuff. And this is only for the pro modelers out there. These are great. These allow your part to bend and move a little bit in order to get it out. But you will still have variability in how the lid interfaces with it. Based on different lids and different colors and so on and so forth, all the things will fit just a little bit differently between these based on the pressing of it all. But if you want the exact same fit, the exact same force to press in and the exact same force to pull out, every single time, independent of anything about print settings, you need to really mechanize this thing, and you need to use something like grip fins. These are a large series of flexible fingers that not only decrease the contact with the part, but hold it at the exact same pressure all the time. These are an advanced engineering one, and the way of modeling these is that you literally just extrude them into the wall and then cut out underneath them so that they are free to flex. Now, plastics tend to creep, which means that over time they can kind of adjust their position and they just move to a new place if you keep on pushing on them. This is what grip fins can get to, but it depends on the plastic that you're using and how long you want them to be used for. This is a perfectly reasonable application because the pressures are distributed against a lot of grip fins, and in this case, they're deflecting so little that over time you're gonna lose almost none of the pressure that this lid is put under to hold it onto there. But this is stupidly reliable because each one of those is compliant, they look really cool, and they allow you to create a fit with the lid that will always work. This is easily the most reliable way of doing it. Compliant features within your systems are very easy to design. They do not have to be complex. But if you want them to be really good, you can go as complex as you want. And this allows you to make stuff that is really, really reliable, really, really robust, and can be made at any time, anywhere, all the time. And this is the reason we care about it, because inside of our print service teleport, we have people uploading whatever sort of part, and our machines aren't necessarily the same as your machines. So it's really important to design your parts to be reliable so that you can have them produced. And it's important to understand the engineering and the design to get that done. So how do you make sure something like this fits into something like this perfectly
every single time without having to worry about any of the slicer settings. In this video, we're going to talk about how to do that in a couple of different ways, but then finish off with designing some compliant mechanisms. So it's really important to make sure that your tolerances and clearances are all right when designing parts that fit together. And this can be really challenging because changing the color of a material will actually change how much it shrinks and how it fits together. It will also vary based on what your machine is, what your settings are, what your infill is, what your nozzle size is, what your resolution is. All of that will make things fit together differently. So the best way to get around this is to just design the parts to be really robust so that it does not matter what slicer, what printer, what material you're using, everything will just always fit together perfectly. Now, there's of course good design practices to follow. If you're designing a standard lid that's just going to be pressed into another thing, make sure you're rounding all the edges and of course chamfer the very first layer so that you don't have any elephant footing. And then everything will generally fit fairly true to what you have. But there are other things that you can do. This is a very simple kind of basic way of getting a design done, and it's not necessarily the right way of getting the design done. This has the problem of having a lot of touch on the outer walls. So if there's any deviation or anything else, you just have a lot of surface area to work against when trying to insert something together. One way of getting around this is to just remove the amount of surface contact on the outer edge of the part. This can be done simply by going around the outer side and just cutting out some holes, and then it can go together much more easily because you don't have as much interference and you don't have the layer lines interlocking either. So you can make a tighter fit, but still have it kind of loose. You can take this all the way down to like a single nubbin too, so that it just shoves right in there and there's only a couple of points where it's making contact with the walls, so it's easy to open back up. But if you want it to be permanent, go ahead and go with a solid version. But those are all solid versions, and solid versions aren't very useful because they don't change dimensions. They don't have a lot of flexibility or a lot of extra tolerance when pushing two things together. So let's go ahead and look at one of the most basic ways of having a universal lid. These are simple compliant mechanisms. They are side springs. Now, many people confuse 3D printing because they try to build these kind of springs vertical across the layer lines. But that's the wrong way to do it, because if they're perpendicular to the layer lines, they can push out and snap along the layer lines right there. These are right in plane of the part. And this allows you to have as much flexibility as you could possibly want there while still having good rigidity. If you want them to be a tighter fit inside of the box, all you can do is just thicken up these outer sprues so you can have a really tight fit or a really loose, nice fit. And of course, you can put small nubs on them so that they can really interface with either a dot inside of the box or just press into the wall. And this way you get a really nice action, very easy fit, and you can have a really, really low tolerance part and not have to worry about it. So these compliant springs can be a really good way of having a part fit universally. But you can take it even further. Maybe you want a tighter fit, and the problem with these is that one of them could break off or you want some redundancy. A thing you can do there is grip fins. This means you just take that little flange and you take it all the way around, and then you make the entire outer walls of this thing larger than this actual hole itself. These can be a great way to get a really nice tight fit, but still have enough compliance to where it's removable, as opposed to this thing to where you're just gonna pry it back out of there. This has just enough give to allow you to do something. And you can make these fins longer in order to make them a softer touch, or you can make them thicker and thinner. You can do all the things that you would do with springs in order to make these fit better. Now, of course, the trick to these is making sure that you actually do a cutout down along the bottom to make sure that they can actually flex freely. Generally, we recommend putting a 0.3 space between the bottom of the fin and the bottom of the part so that they can break loose and act just the way you want them to there. But 3D printing really has a superpower in that you can actually make true mechanisms inside of it. And this is something people don't really talk about and don't really very often understand. But while the grip fins are a really good, really universal, and really robust way of doing it, sometimes you want even more action and more play and more flexibility. And the only way that comes is from the part being able to move a great distance. But you need a spring that can move a great distance, and a fin going like this just isn't enough. Sometimes you want to go from here all the way up to there. This is where these types of parts come in. So these parts are literally internal springs, internal latches that have been designed into this lid. Since 3D printing can make really thick parts without causing shrinkage the way light molding does, you can do all sorts of interesting things. These small latches are just the front end of it all, and then inside you have a spring that pushes the latch in and out. The trick to this
is kind of tougher because you have to really mess with the design of it to make sure that it's robust. Otherwise, you can have hang on the bridging above the latch that will cause it to jam inside of there. But when you have it, these latches are able to move much further than a grip fin ever can. They have almost 2 millimeters of distance that they can travel in order to create a latch. And if you tune them in, you can get a really nice fit all the way around. But you can also have detents inside of the box so that there's actually some place for those to go. You can give them little channels. These are a really good mechanism of making sure that the lid fits the bottom box every single time. And this is the kind of universal theme here, is that many people design parts in order to have the clearances and tolerances just so that they always fit together. But it breaks so easily as you move from PETG to PLA, or from white to black, or from this machine to that machine. So it's much better if you can use all the powers of 3D printing to create latches and mechanisms and grip fins and all these other types of features. You can have parts fit together perfectly and always behave exactly the way you intend, regardless of where or how they're made. And this is really useful if you're designing files for other people to print, or if you're wanting to scale up production of your parts.
You could not have mass-produced something like this even just 5 years ago, but now you can. And in this video, we're going to go through the actual design of this part and what it would be competing against. So first of all, let's go ahead and look at what it's competing up against. Normally, this kind of part would be manufactured with injection molding. And the problem with injection molding is that you have the molds. And even more so with this part, since it's a mechanism where you have an interior slider and then a spring and all this other stuff, you have to make it in multiple parts. Very often it's 2 clamshell pieces that sandwich together, and then you have the latch in between. So you have to have 3 molds or a 3 cavity mold to at least hold those 3 pieces. But overall, it's just a complex system where you'll be spending somewhere between $2,000 and $15,000 to make a simple little plastic part. But then you have to realize that there's also all the downstream costs. You have the assembly of those pieces, the error rate within those pieces, transportation of those pieces, because in order to amortize the cost of the mold, you have to produce hundreds of thousands of them, because again, you have that big old upfront cost. Not to mention the fact that once you commit to the mold, that design is literally set in stone. So producing this with molding creates a lot of complexity if you're in a company or a startup where you want a lot of design flexibility, or you're in a company that's evolving quickly and trying to meet the new needs of customers. All of those issues are solved with mass production 3D printing, which is what we do here at Slant 3D. But if you're making something like this for 3D printing, the rules have entirely changed. You no longer want to use your injection molding designs to make them with 3D printing. You would have a lower quality product if you attempted to print injection molded designs. So let's go ahead and actually break down how to do this so that we can make a part that is actually better. Well, first of all, since 3D printing is additive, you're able to create really complex geometries that are enclosed so that you have multiple parts inside of one single print. And that's basically what we did here. We designed the outer box of this latch, and then we designed the small latch inside of it. This way, you basically have a ship inside of a bottle that you could never manufacture before. Now we're able to have the handle sticking out the side and integrate a spring. And now the spring is a really interesting deal, because normally that spring would come in from the side and would actually wobble in this direction. That is the way you would shoot it inside of a mold. Since we're using 3D printing, we're going to be printing it up on its long edge. The reason for this is so that it is easily knocked off of the machine so that you can produce hundreds of thousands of them affordably. If you lay it down flat, then you end up with an issue where it potentially doesn't auto-eject very well, and you also have issues with the smoothness of the latch. So you want to print on that small side. This creates a much more reliable print, a much more manufacturable print, and ensures that all of the interior mechanisms align right. But the spring now has to be designed in the opposite direction so that it is a vertical spring rather than horizontal. So the wobble is going along the vertical there, so you still have the compression. And you can readjust how hard or soft this spring is by either changing the thickness of it or changing the number of coils it has. All of that is adjustable. Now the latch itself, since we have the tongue of the latch sticking out the edge, we go ahead and chamfer that, which is great because it's necessary anyway so that this can work as a door latch closing in on something there. And then the tongue of this latch is actually inside of the box, and you have the roof of the box.
If you're doing large spread spots, then you can end up with sag, and sag could create an interference within the parts inside themselves as they're moving over each other. So in order to prevent that type of a sag, don't have horizontal surfaces. If you can, have them come to a point or to a ceiling of some sort. And that's what we did here. We basically created a chamfer on the roof of the outer box and the roof of the tongue itself. And this ensures that there is no overhang that can cause any sort of interference issues. And that way, again, you have a very robust part that can be mass produced. And then we have the handle coming out the side, and the handle is a very simple little deal there. But then the other thing that has to be done is you have the mounting holes. The mounting holes are pretty easy, but if you wanted to reinforce those so that screws going in don't end up splitting apart, you can go ahead and add a collar around each one of those holes. This reinforces the part, and you just make sure that everything moves around it. It's not that hard. One other thing about this that is also fairly challenging is the spot where the handle is sliding through. That is an overhang that would end up causing sag and interference. So how do you deal with that? Well, normally people would say, go ahead and generate support inside of there. That's the wrong solution. You never want to have auto-generated supports when optimizing for manufacturing. Everything should be in the CAD file. That way you know it's universal. That way you can print it through our API or just send it to us and know you're going to get back what you need. It eliminates any sort of interpretation issues. So the way to design those supports is you basically just design a block straight into it. You have a 0.3 spacing on top and a 0.3 spacing on the bottom, and then you just have it be the thickness of the part that it's supporting. And what's great about this is that you can actually put instructions on that block, like remove, and then those instructions indicate to the technician, we need to pluck that out. That way you don't have to worry about is it going to be supported or not, because you don't have to design the whole part and then design the slicing parameters for the part. You just design the part, and then the thing plucks right out with generic settings. It's much more reliable and much more robust because you also have support exactly where you want it as opposed to where we think it's supposed to go. And with complex pieces like this, support can become very tricky because there's areas that you might consider need to have support that actually don't, and you know that better because it's your design. So when using support, make sure you use design support, and there's ways to do it intelligently so that it's very efficient and quick. And then last of all, we went around, we chamfered and filleted everything to make sure that you don't have elephant foot or any sort of extrusion issues and that kind of thing. And then we just did a final touch up, and now you go ahead and print it. And once you print it, you have this really awesome mechanism that can be produced for the same or less cost than the mold. You don't have the upfront cost, you have design flexibility, and you have all of this stuff already assembled and ready to go so that a full latch does not have to go through a secondary processes. It can come off a machine, go right into a box, go right to a customer, and you know it's more reliable because you don't have human error in all those other steps that other manufacturing processes would have. You're actually able to create a product that was never possible before, and now you can create all kinds of new features that your competitors don't have. If we were to go through and refine this a little bit more, we could change how much the return of it is. We can mess around with the dimensions of it all and reinforce some other features. We could also apply an outer texture in order to eliminate layer lines.
We weren't able to ever really find this, so we just went ahead and did it, and did a direct comparison of the exact same part from conception to pricing. So in order to do this, there is way too much inside of manufacturing in order to take something like a generic toy, because there's way too many factors within that. So we started with something very simple, a cube. A theoretical client wants to come to us and they want to make a brick, a 50 millimeter brick. And they want to know what it would cost to do with injection molding or with 3D printing. Well, first of all, we tell them you have to design for the end process, because putting a square peg into a round hole will not work. If you have an injection molded design, it should not be 3D printed. If you have a 3D printed design, it should not be injection molded. And whatever process you decide to use in mass production, you should design towards. But since it's a cube, it's a fairly simple matter to show the two different options. If you were making an injection molded cube, the first thing you have to do is apply a draft angle. So you have to apply at least a 1.5 degree angle to the side of the cubes. It's no longer a cube now, but at least it can be removed from the mold. After that, you cannot have a solid brick or a large mass of plastic anywhere within inside an injection mold. Otherwise, it'll shrink and cause all sorts of problems with the final part. So you actually have to remove the entire center of the cube, removing an entire face so that a cavity can be made. We made the thin walls 2 millimeters thick in order to have it be a nice rigid functional part, because this cube is going to be used as an end cap for a fence post or something like that. So we removed that. And now the cube is is no longer a cube, it's more of like a dish with one wall missing and thin walls throughout, but it is injection moldable now. And then of course you want to go around and you want to fillet every single sharp edge because sharp edges do not exist in the real world. For the 3D printed version of this cube, all you have to do is take the design of the cube and fillet all the edges. There are a few other tricks that can be applied too, but they are tricks in small optimizations and are not necessary to print it. This is a fully solid cube that is now ready to 3D print. So much less design consideration for this particular part. Doesn't apply always, but in this case it does. All right, so we have two designs fully optimized for the process that they are intended for. So what we did is we went ahead and we took the injection molded cube and we had it quoted by an injection molder. We are not going to mention the name of this injection molder, but it is a name that you would recognize, and it is not the cheapest option, nor is it the most expensive option. We selected draft quality, the material was PLA, and we requested a 30-day lead time for this project. And then we sent it off to be quoted. It took about 2 days to come back. We did the exact same thing on the Slant 3D website, the way any client would who's coming to us. We had it requested for 10,000 units, a 30-day lead time out of PLA, and mentioned that it is a draft quality part which is meant to be on top of a fence post somewhere. It needs to be functional, but it does not need to be super pretty and does not have a glass smooth finish. The quotes come back in about 1 to 2 days. That is the same for Slant 3D, and it was the same for the injection molder that we worked with. And here is the total cost of the parts. For the injection molded version of the part, the cost per piece was $1.42. That is with the injection mold cost itself included in the cost per part, and it was going to continue to decrease as it went up, but it was flatlining around about $1 per part as you got into towards about 100,000. The 3D printed version of the part, quoted by Slant 3D, cost $1.55 per part. So you know we didn't cheat because we were more expensive than injection molding. But that is a pure per part cost for 10,000 units. Again, a bit more expensive than injection molding, but not extravagant. And you have to consider the whole rest of the supply chain whenever making the consideration. The part cost alone is not the only thing to look at. For fun, we also looked at 500 units just to show how 3D printing helps at lower volumes. At 500 units, the cost per part was $13, again because you still have the cost of the mold right off the bat. And the cost of the mold in this case for the simple cube was $5,700. Which is not a small amount, especially since that's what you have to pay in order to get your first part. Whereas the cost per part for 500 units with 3D printing was $5.12 a piece, which obviously is much less than the molding cost because you do not have the mold. And this is not something we generally want to highlight because we don't believe that 3D printing is a small scale production method. It is most certainly better than molding at small scales, but it is very clearly as good as injection molding up to production scales. Toyota considers 25,000 units to be mass production. So if we hit that, we are at the same manufacturing level as one of the best manufacturers on the planet. Very, very few products ever make more than 100,000 units in their entire lifetime, let alone between iterations. And this is something that has to be considered with molds too. What if the product comes out of the mold is not what you expect or not what you wanted? The cost to change the design is $5,700 every time, if not more, depending on how complex your design is. Whereas the cost for 3D printing is $150. That is the setup cost to start up production of a production run of parts. Lead time between the two was identical, but one of the bigger differences between these two also was the location the parts were made. The parts in this case would have been produced within Boise, Idaho in our main mega farm facility. The parts from the molder would have been produced in China, which means that after they are produced, they then have to cross an ocean, go through customs, be delivered at a warehouse, and then distributed to wherever the final product is going. Whereas with the 3D printed parts, they can be produced here and shipped to your main warehouse within the continental US, or they could be fulfilled one at a time from our warehouses. So you have much fewer steps in the supply chain with much lower cost. And while these two projects were quoted side by side, 30 days and 30 days, that is the wrong way to use 3D printing. If you were making 10,000 parts and these were to be used for the entire year, there is no reason to order 10,000 parts. You would go into a contract with us for 10,000 parts, but we would produce 1,000 parts per month and deliver them to you. This would reduce the amount of warehousing that you need to hold those pieces, and if you need to make changes based on customer feedback, you can do it in between batches rather than having to buy a $6,000 mold every time you make a modification to the parts. So ultimately, this is what we wanted to do. The 2 quotes are linked down below for folks to reference if you want to look at them. But what we wanted to do was just show a very simple part side by side with injection molding and 3D printing with very hard numbers from both organizations to make sure they can be compared side by side. Now, this is just an example. Whatever your part is can radically change how these dynamics work out. But this is simply a way of showing that you should be considering multiple processes whenever you manufacture your product. So this sample brick shows many of the pitfalls and many of the superpowers that 3D printing has that many people don't realize. So in this video, we're gonna go through it from bottom to top and talk about each one of them in detail. So the Slant 3D sample brick was actually designed several years ago, and we use it to communicate to clients core features around 3D printing, both to avoid and to go after. Starting at the very bottom, the first item that you see is actually this small hemisphere sticking out the side. You have a large one and a small one. This is to detail the fact that overhangs can be a problem. When you have a hemisphere, the first thing that can happen if you make it too large is that the very bottom can have just a little bit of sag and drip to it, because as the layers build up, initially a hemisphere starts coming out of the wall perfectly horizontal. Now when it's really small like this one, it's not really a big issue because it's able to build up gradually compared to the layer heights. But if it gets larger in proportion to the layer heights, then you can start to have more sag down here on the bottom. The way of fixing that is to apply a fillet to the bottom of it, as we did here with this cylinder sticking out the side. This allows you to then create something that has a nice smooth transition. But again, here in this case, if you keep it as a cylinder rather than a hemisphere, then you can have overhang again on the outer edge. So there you might actually want to use a chamfer. Turning around to the other side, you have a demonstration of all the various types of holes. Now you have, of course, circular holes, both small and large, and you can see that with small holes, generally the dimensional tolerances are maintained a little bit better, whereas with the large holes, again, the top of the hole can have sag compared to the layer lines, so you end up having what looks like a little bit of squashing of the hole. The way of fixing this is to use a teardrop shape. And then, of course, you have square holes where there's really no problem at all because you have straight, easy bridging. Until bridging gets so long that you can potentially have sag in the upper level of it, as demonstrated in this hole. That is something to be avoided. You want to avoid very long overhangs whenever you can, because they can lead to dimensional instability of that slot if you're making something large like that. Then over here on this side, we talk about overhangs even more. We have a standard unsupported overhang to demonstrate what can happen if you don't have supports designed in or activated, or if you're just designing a feature that is horizontal, because it's not always intuitive, the fact that 3D printing just shoots out into thin air and then comes back, and you end up with a sag right there. There is, first of all, the correct solution, which is to use a chamfer of about 45 to 35 degrees, so that you have a nice clean buildup in order to support that overhang. And then a less good solution, which is the fillet underneath, because again, it looks fine because you start out like that, but by the time you get to the top of it, it turns into a horizontal feature again. So you end up having just a little bit of sag out there on the edge. So that is to illustrate all of those. Then on this other side, we want to just show that you can do these really complex and kind of deep geometries. So if you want a grip or other sort of contact surface, you can make these really thick, deep surface textures that aren't really common with other types of manufacturing because they can be so expensive. Now moving up to the next layer where we actually highlight textures and also highlight some of the problems with textures. The very first and simplest texture is literally just a circle that has been embossed into the side of the part and just repeated over and over again. This is a really good texture for hiding layer lines because it can be really subtle, but it still looks pretty darn good. And then here on the side, you have a diamond pattern, just kind of a knurling, so people can get a feel of what that looks like when it's embedded just a 0.5 millimeter into the surface of the thing. Again, these textures are used to hide the surface finish, so you don't have to have the 3D printed look. You can make the layer lines disappear by applying these types of textures. But the thing to be afraid of is what happens over here on this other side. Right here, this surface, if you get in real close to it, you'll see that it's actually not a good surface. It looks kind of like leftover wispiness. This is because the surface edges were too thin to where the nozzle and the slicer doesn't really identify them cleanly, so that you end up with this just kind of partial extrusion out there onto the surface. So you want to make sure that you're making surfaces that have features that are at least the width of the nozzle. So in this case, 0.4 millimeters. These were a little bit thinner than that, so they end up just kind of being kind of there, but not really. So this is really important to detail, that you want to make sure features are thick enough to actually be printed. And then the last texture that we talk about over here is kind of inspired by the leaves on a forest floor. The leaves are all the same basic shape, but as they rotate and move around, you end up getting something that looks complex and completely random. This is what you can do with textures if you don't want the repeated like knurling pattern or the circles just repeated over. You can create a small section of patterning and then repeat that over and over again and potentially rotate and move it around depending on how good you are at CAD. And then you can create something that looks a lot more random and can help to disperse and move the texture around more and more so it's not as patterned looking. Coming around on these edges, we have an example of a filleted outer edge and then sharp main corners around here. This is to detail how you can have issues come up with this. You want to make sure you're rounding all of your vertical edges as much as you possibly can, because it creates a cleaner looking part and also helps to reduce print time. Whereas these sharp edges can lead to print failures because seams can all align there and you end up with retraction problems. But they also just are not always as crisp. So people have a tough time contextualizing how tight and sharp 3D printed parts can be, and these corners help to illustrate that. Moving up to section 3, the first thing that we have is text. We have both embossed and embedded so that you can see what the contrast is right there. When the text goes into the part, that's generally what you prefer because you don't have to worry about the overhangs of it as much, but you only want to go in about 0.5 millimeter, maybe 1 millimeter tops. Embossed, you have a much bigger problem with sag because the lettering is coming out, it's a horizontal overhang. If it's more than 0.5 millimeter, you see sag and drag at the bottom of these letters. But you can also see how the different fonts can vary, how stark and how crisp and clear they are. You never really want to do a font smaller than 1/8 of an inch on any part of a 3D printed part. And that's to detail this. So the slant up here is about 1/8 of an inch large, and then the 3D is 1/4 inch large, just so that you have good differentiation. But whenever you want to embed the text inside of there. Then on the other side, we have 2 holes. So these holes are actually connected. They're a curved hole through the top, which is generally fairly difficult to machine because you have to connect the holes and maintain a really smooth filleted inner corner, which can take a long time in machining because you have to slowly create that smooth curve in there many steps at a time. Whereas it's very easy to do with 3D printing. But then in addition to those 2 holes, we have a filleted hole and a chamfered hole so that you can see the full 360 behavior of those types of features into the side, both the fillet and the chamfer. The fillet you can kind of see again helps to keep the hole crisp and round, and you have less of the sagging that you see down in the holes down here. But the chamfer is even better because it's the perfect way of maintaining constant layer deposition as they're building up. Whereas again, the fillets start from infinity and then go up to level. A chamfer is a consistent stair step all the way up. And then on the very top, the thing we look at here is actually 2 types of holes. You have a hole without a filleted top edge, so that you have just a straight 90 degrees to the hole. And then you have a slight fillet on the other one, about a 1 millimeter fillet. You always want to fillet all of the vertical edges on your part whenever possible. And this is to really detail that. The one that is perfectly vertical and has a 90-degree interface with the top surface can potentially have problems of hole pull out and that kind of thing. If you fillet it just a little bit, it lets more layers kind of build up around the outer edge of the hole, so it remains clean, and doing things like heat inserts and that kind of stuff come along much better. It also serves as a funneling and finding feature, so if you put a screw in there, the hole just goes in. It's a countersink that you just want to do. And then lastly, we have a small dome sitting on top so that you can see how the layers build over and start to become more and more stark as the curve gets steeper. And that is how you top off the final Slant 3D sample brick. This sample brick, again, as we said, is meant to show all the ways 3D printing can be used well and usefully by like using textures which come free or detailed complex internal geometries that are actually fairly difficult to machine, like internal S-curves and that kind of thing. But then also the things to avoid, like bad sorts of inserts and overhangs, and also how to do text in a way that looks good for your particular application.
What's going on, guys? So today we're going to be designing some 3D printed wheels using Shaper 3D's new parametric modeling beta. This beta is currently free to download and is available on Windows, Mac, and iPad, so use the link down in our description if you'd like to try it out. And if you end up liking it, use code SLANT3D for 10% off your pro subscription. Now let's head over to Shaper and get started. All right, so we got Shaper open up here. And we're just going to go down here and tap Create New Project. And now we can explore around a little bit. So we are going to be doing this project in millimeters. But if you tap this middle button up here in the top right, you can go ahead and change to whatever unit of measurement you're comfortable with using. Like I said, we're going to be doing this in millimeters, so we're just going to go ahead and keep that there. And then we're going to make sure that this lock grid size is toggled on. And what this is going to do is just make sure that these squares on our grid don't change up on us or anything, because that can get kind of annoying. So now over here on this left-hand side, we have this items menu. And if we open that up, there's nothing in there right now, but this is basically going to be where anything that we create inside of this project is contained. So any sketches, bodies, planes, all of that will be held inside of the items menu. And then over here on the right-hand side, we have the history tab. And this is going to be where all of the parametric magic takes place. And it will contain basically a running timeline of each step we take throughout the design process. And that's going to allow us to do some pretty cool things in terms of the way we constrain our sketches and our models. So let's go ahead and create a new sketch. And we're going to grab this circle here. And we're going to draw outwards from this origin point. And we're going to set that to 70 millimeters. Cool. And now we're going to draw another circle within that circle. And we're going to set that to 20 millimeters. All right. Now let's go ahead and move these out of the way. Let's see a little bit better. So now we're going to rotate out of this view. And let's grab both of these circles. And we're just going to extrude those to, let's do 30 millimeters. Yeah, that'll be good. Now let's, oh, we lost our sketch. Let's open this items menu back up and turn that sketch back on so that we can grab this center circle. And then we are going to extrude that back by 5 millimeters. Okay, so now I want to open up this history sidebar so we can take a look at some of the features that parametric modeling enables. As you can see here, now we actually have some stuff going on in this menu. So we have the initial sketch that we made, and then we have the 2 extrusions as well. So let's open up this most recent extrusion that we made. Now, the main thing we're going to be looking at here is the extent feature. And this is basically going to control how we define our extrusions. So as you can see, it is currently set to distance. And a little bit above that, our distance is set to 5 millimeters. So basically what that's going to do is that's going to lock in that extrusion to that specific distance. So if we open up this first extrusion and we change this to 50 millimeters, and that second extrusion is going to stay locked in at 5 millimeters. So no matter how much we push and pull on this first extrusion, whatever we change that distance to, it's not going to affect that second extrusion because it is defined by that 5 millimeter distance. And this is kind of the general idea of parametric modeling. We create relationships between parts, and that allows us to go back and make changes, and everything else will update according to those constraints. So one of the really useful ways that we can take advantage of this is if we open up this extent menu here, you'll see we get this drop down with 3 options. We have distance, which is what we just talked about, and then we also have to object and to point. So if we select to object, that is going to allow us to now select an object that extrusion is defined by. So if we spin around here and select this back face, now that extrusion is going to extend all the way to that back face. And this is super useful because now if we select that first extrusion, we can change the width of this as much as we want, but that center hole is always going to extend all the way through to that back face because it is constrained to that object. All right, so let's get everything back to our original dimensions here. Cool. So now, before I forget, let's select this front face, or this front edge, and also this back edge. And we're gonna go ahead and just fillet this real quick to 10 millimeters. Okay, so now we need to create some screw holes so that this thing can actually attach to a vehicle. So we're gonna start a new sketch here by tapping on this front face. And we're gonna draw another circle from this center point here. And we are going to set that to 5 millimeters. And then we're gonna draw another circle above that, and we're gonna set that to 3 millimeters. So now what we wanna do is select the center points of both these circles, and that's gonna allow us to define the distance between those 2 points. So we're gonna lock those in at 6 millimeters. And this is just gonna give us the flexibility to be able to change the diameter of our wheel without affecting the mounting holes in the center there. So this is super useful if you want to create various sizes of a wheel, but you need that hardware to go in the same spot. So now we are gonna spin out of that, and we want to select those 2 circles that we just drew, and we're gonna extrude them back into our wheel. And it doesn't really matter how far we go here, because we are now gonna open up the history tab, and we're going to use that extend feature again. So we're gonna tap on that, select to object, tap on object, and then we're going to select the back face here. Perfect. So now our mounting holes are extending all the way through our wheel to that back face. So if we select this first extrusion and we extend that, our mounting holes are still going all the way through the part. So let's spin back around, and we're gonna zoom in here. And real quick here, I'm gonna open up this items menu. I'm gonna turn off that sketch real quick, just make things a little bit easier for us. And then we're gonna select the outer edge of this top hole, and we're gonna fillet that. And then we're going to select our center hole, and we are going to do the same thing. So the reason I'm doing this is because what we're gonna do now is we're going to pattern that top hole around our center hole. And I wanted to make sure that we had that fillet already done so that we don't have to go back and do it 3 more times after we make the pattern. So we're gonna choose the pattern tool over here. We're gonna make sure that's set to circular. And then we want to select this top hole, and we're gonna grab the pivot point and make sure that that is set to the center of our wheel. And then if we tap on quantity here, we're gonna set that to 4 because that's how many holes we wanna end up with. And then we're just gonna revolve 360 degrees all the way around. So now we've got all 4 of our mounting holes, and they are all already filleted. And if we spin around here, they are all extending all the way through to that back face. So let's do a quick check-in and grab this first extrusion and extend this out. And we are good. All 4 of our holes are extending all the way to this back face. And this is why it's super important when using parametric modeling to be thinking about your order of operations, because each step that we take can impact things later on down the line. And an example of this is I am just now noticing that I forgot to fillet these back holes. But that is okay, because now I can show you a pretty cool thing that Shaper did with this history panel. So I'm going to fillet this top circle, and I want to make sure I'm doing this to the top circle because that's the one that we eventually ended up patterning. And now you can see over in our history timeline, that fillet step shows up right below our pattern. So there's our fillet, and there's our pattern. But because we created that fillet after we made the pattern, it's not reflected on those patterned holes. But if we just drag that fillet up above our pattern, now it's going to treat this as if we had done it in that order. And this is just super nice for those instances when we don't really plan accordingly. Just being able to have that freedom to make those mistakes, but still be able to go back and do them in the correct order. So let's go ahead and reset everything. And then we're gonna fillet that center hole. Now we're gonna spin back around, and we're looking good. So let's go ahead and create some treads on this wheel. So we're going to want to create a new sketch, and we're going to go up to the top here, and now we're going to select the rectangle tool, and we want to make sure that that is set to center. So let's draw that. Set that to 3 millimeters by, let's do 6 millimeters. That'll be fine. Now we're going to rotate our view again, and we're going to zoom in and grab that rectangle that we just drew, and we're going to extrude that all the way through our wheel. And then we're going to open up this history tab again, and we're going to do the same thing. To object, select object, back face, and now that tread is defined by the width of our wheel. So let's spin back around, and we're going to want to pattern this as well. So let's select that sketch, grab the pivot point, drag it to the center of our circle, and then we're going to set this total angle to 360 degrees. And let's set the quantity to 40. That might be a little too much. Let's go 30. Yeah, that should do. Cool. So the reason we didn't just pattern that extrusion is because I want to show you guys another cool thing you can do in this history tab. So if we open up that extrusion 4 there, and then we tap on profile, this is going to allow us to add faces to that extrusion. So if we just go around here and select all of these and then press done, now all of those patterned sketches are going to be defined by that same extrusion that we made with our top tread there. So again, just another nice feature that they have for those times when you maybe overlook something and want to go back and make some changes. All right, I think things are looking pretty good here, but I do want to kind of round out this center part of our wheel here. So first thing I'm going to want to do is open up this history tab, and we're going to go to that second extrusion that we made, and we're going to extend that a little bit more. So let's set that to 20 millimeters. And now we can tap on that outer edge, and we're going to fillet that, and we'll put that to 20 millimeters as well. And now that fillet's going to extend all the way back to those mounting holes, which just makes things look a little bit nicer and also prevents us from needing screws that will extend all the way through our wheel. Just kind of shortens up that distance there. So now I want to go in and turn off the sketch real quick so we can see things a little bit better. And then we're going to go back into our history tab. And I know we've been doing this a lot, but it's good to just kind of get into this habit of checking in on things and making sure that everything is constrained properly. Because the last thing that we want is to get too far into this design and realize that things aren't behaving the way we want them to be. So this just kind of gives you a little bit of peace of mind going forward. All right, I think that looks like a wheel. So this last thing that I want to show you guys is something that both 3D printing and Shaper can make really easy, and that is creating product variations. So what we are going to do is we're going to open up this history tab again. And what you can do is long hold on any of these steps here and then tap insert breakpoint. And that's going to revert your model back to how it was up until that point. And now we're going to select the entire body and then duplicate it so that we can change up the features on the outside of this wheel. So now we're going to hit add and select construction plane. And then we're going to make sure that the type is set to mid plane. And then we're going to select this front face and this back face. And that's going to create a sketch plane for us down the center of our wheel here. Now we're going to tap on that, and that's going to start a new sketch on that plane. And we're going to make sure we've got our line selected here. And then we're just going to draw a line straight up the center of our wheel. And this will come in handy later. Now we're going to hit circle, and we're going to draw that. We want to make sure it's at that intersecting point between the line we just drew and the top of our wheel. So let's set that to 6 millimeters. And now we can select the right half of that circle. And then we're going to hit more, and we're going to choose this revolve tool right here. And this is why we drew that line earlier, because now we're going to use that as our center point to revolve this shape around. And that's going to create this sphere right here. So now we can select that sphere, make sure that we hit copy right here. And then we're just going to slide that over. Let's do 6 millimeters. And then we're going to do the same thing on this left side. And oh, forgot to hit copy. That's okay, because we can just do it now. Cool. And now we just want to pattern these 3 spheres around the exterior of our wheel. So let's do that. Set the angle to 360 and the quantity to 30. Nope, that's too many. Quantity to 20. And that looks good. Sweet. Now that I'm looking at it though, I don't really like how close those spheres are. So let's go up to those top spheres that we patterned. We're going to select that movement / rotation. That's where we copied the spheres. And we're just going to move those out 1 more millimeter. And you can see those patterned spheres are also going to move as well. And then let's just go ahead and do the same thing to the left side. And that's looking much better. So now if we go down to that breakpoint that we created and get rid of it, all of those features on our original design come right back. And so this is just a really easy way to create multiple product variations without having to spend a lot of time or effort. But the nice thing is that both of these wheels are still defined by the same constraints. So if we needed to, let's say, update the dimensions of our mounting holes, we can go into our first wheel that we made and make those adjustments, and all of our variations will update as well. So this is just one example of the many things that you can do by taking advantage of the benefits of mass production 3D printing, as well as Shaper 3D's new parametric based modeling.
So when both these blocks are printed horizontally, how do we make it so that the pin and the hole fit perfectly every single time? In this video, we're going to go through 9 different designs that you have not seen before about how to have a horizontal pin and hole fit just right. So what is the reason for wanting to print holes horizontally along with their pins? Well, the pins themselves, if you're printing them horizontally, they're in the plane of the layer lines. So this pin is much stronger than if you were printing vertically. And that's a fine and dandy deal. The same thing goes with the holes. You sometimes just have to put holes into the side of the part. Now, the issue with these types of pins is that you can end up with these types of problems where you have to have support underneath them in order to have them be crisp. And one of the worst things that you can ever do is just design a cylindrical pin straight out the side with a standard circular hole right there. None of these actually work. If you've ever printed them, you will find out that the holes end up kind of sagging or being oblong because the vertical edges sag just a little bit, creating a bad hole. So let's just start with very basic good design practices. Number 1, you don't want a simple cube with a simple cylinder standing out the side. You want to go through and optimize it a little bit. You want to chamfer the bottom, round the corners, but now you want to go and focus on the pin and the hole themselves. The pin itself, go ahead and give a chamfer to the tip of. The reason you want to use a chamfer rather than a fillet is that a chamfer is a consistent overhang of 45 degrees as opposed to a fillet, which goes from infinite overhang to nothing. And then you equally want to fillet the inserts to the holes so that they can slide together reliably and have a really nice fit right there. But you still have the tolerance problem of the holes, which will be always a little bit out of shape. So the very first thing that you want to do in order to get rid of that sag at the top of the holes, which is sometimes done by the slicer, sometimes done by the material, sometimes done by the print resolution that you're using. In order to have a good precision of the holes, one of the simplest things that you can do is just give the holes a small corner up on top. And you can make this fairly shallow, but this allows the hole to hold its shape without causing a tolerance issue. This way the hole doesn't compress as it's printed. And of course you want to make sure that you have support underneath the pin itself in order to keep it crisp and not have some nasty little sagging issue. So there we go, we're done. Pins and holes. You just round out all the edges and they slide together just really easily. But not really, you're still dealing with a tolerance problem. Different materials, different print settings, different infill types, different shrinkage, different slicer, different machine will all cause these holes and pins to fit together differently. So how do you create a design that works on any material, any machine, any slicer at any time without having to worry about the clearances and tolerances varying too much so that your design breaks? So let's go ahead and go into some more advanced techniques other than just a pin and hole. Remember how I showed you this design before, which has to have the support underneath? This support ended up just being wasted material that is flicked away. Why don't you use that as actually part of the design? This way you improve the rigidity of the part and are able to use it more. This is what you end up with. You take the pin and you apply a chamfer to the bottom and top of it so that it can be printed in any orientation and you don't have to worry about support generation holding the pin in the correct shape. And of course you have to mirror it over here on the other side so it's a nice keyhole. This allows you also to use those flanges as effectively tension areas, where you have the sidewalls, which are much higher tolerance, sliding together to hold it together without having to worry about the tops and bottoms of this pin interfacing with the hole itself. It's much more reliable, you get to use material rather than throwing it away as support, and you have a much stronger side feature. But this is also sort of a waste. Why do you need a circular pin there at all if you have already chamfered it? Just go ahead and lean into it and turn it into an actual slot. With basically the slotted design, you're able to have the side compression of the hole be the only thing that is interfacing with the actual tab here. And this is better than holes because you can really tune in the fit and get along with it really well. But this is still just a standard rectangular extrusion, which is then chamfered so that you don't have overhang and a rectangular hole. This doesn't really necessarily fit always because if we change to a different material, the fit would be different. So how can you create something robust? Well, the easiest way to do that is to make something thicker. If you make that slot and make them all thicker, then what you're able to do is take this tab right here and chamfer it just slightly so that the top is narrower than the entryway to the hole and the bottom is wider than the entryway of the hole, so that as you insert, it gets tighter and tighter so that you get a really good fit that comes together really well. And then if you have a couple of them slightly offset, you can make sure that you don't have this sort of offsetting issue to where it actually self-centers. So there's plenty of ways of dealing with that. But this allows you to get a really good fit rather than a potentially loose or potentially too tight type of a fit if you're relying purely on the precision of the material that you're using, which will always vary based on print settings, materials, machines, all of that stuff. So you want to make your design as robust as possible so that it produces the part that you're looking for every time. But this is still inconsistent. You're still reliant on the tolerances of the machines and materials that you're dealing with. How do you make sure that this works all the time? Rather than simply having a solid slot right here, which has set dimensions, you can instead have two tabs which allow you to always fit into the slot exactly as intended with a little bit of pressure on the outer walls. And since they can flex quite a great deal, regardless of what machine you make it on, they will always work. But now the issue with this is that these are flat, smooth tabs, so it can slide out really easily. You don't get a really tight pressure fit or something that can mechanically hold on really tightly. This is fine for like a finding feature, but if you want to hold it together, it doesn't hold it together very tight. But that can be fixed with just the addition of a couple of small bumps and a couple of small holes inside of the slot itself. This way, when you press them together, they can actually interlock, and now you get a nice little popping in order to hold them together. Now, this is a basic demonstration of how it works, but using these grip fins with little locking features at the end and mating features on the inside allows you to get a nice, perfect, tight fit every time that holds together really, really well, and you do not have to worry about the tolerances of the material or how much shrink there is or what print settings are being used, so you can make sure that your pins always fit right into the holes perfectly every single time. Hopefully these designs were useful to you. This is the type of thing that we go through in order to educate people how to design parts that are really manufacturable. And you want this when using external services or wanting to mass produce a 3D printed part. You want it to be as robust as possible so that you don't have to tune the design to a particular machine or process. This is especially true in places like our Teleport Print on Demand app, where you can plug the Slant 3D print farm that has hundreds of machines directly into your Etsy store or your eBay store or your Amazon store, and you want your product to be made the same way. The easiest way to do that is to design the product to be manufacturable in multiple different processes at multiple different times. Many people get caught in the trap of designing specifically for their one machine, maybe it's their brand, their material, whatever it happens to be, and having their own particular bespoke settings. But that gets you stuck in an artisan kind of a layout, whereas if you do very simple design tweaks, you can have your part be made by anyone. This is also particularly useful if you are selling the files to other people who want to 3D print them as well, because as soon as you sell the file and somebody prints it on a machine that isn't good, it can also create issues with the perception of your file.
Hey everybody, so today what we wanted to do is design actually a new spool holder, because quite frankly, spool holders suck right now. So I'm going to see if I can help with that a little bit. So we're going to start with a triangle, because triangles be good. Let's go ahead. Actually, I'm going to delete that line because I don't like it. I'm going to go ahead and start right here. That is actually a bit too big. I'm going to take that down to 30. And I need the dimensions from there to there to be, I think it's about 1/7. There we go. Cool. Now we'll put that right there. That'll be good. And then we'll do a line like this and like this. There we are. There we go. So, what we're trying to go for is a spool holder that can both be mounted to a wall and stand. So, for that to be fairly reliable, it's got to have a wide base on both sides, but preferably not using too much material throughout this whole thing. This core size is chosen because that is the core size of a 3.5 kg spool. So we're going to try and get that all there. There we go. Cool. That'll be the baseline for this whole thing. I don't want it to be super thick, but I'm going to go for 15 because it's going to need some sideways rigidity. Actually, no, I was wrong about that. We can get to that from a different direction. So I'm just going to go for 10 so that we minimize it. And I'll show you a nifty trick here. So I'm going to go ahead and make our spool core real kind of spoke here. Get that center line right there, and we'll go 27. I think I'm going to have to go back into the other design too and expand that out because there's some things I want to do. And that needs to be 100 for the spool size. Okay, so that's good. Now I'm going to go back into that other design and widen this out so that there's a lip for it to catch against. There we go. Now I'm happier. That looks much better. Problem with this though, we want this to be along the base, otherwise we're going to have problems. So I'm going to actually change this up just a bit. I also, circular designs are not very desirable because they create a weird situation where you have the sagging on the bottom that you either have to support or you have a skewed up piece. So I'm going to try to do a polygon here, right there, right there. There we go. And I want that to be an 8-sided. Because an 8-sided is one set up from a cube, and you can see right here, those are 45-degree angles, which are exactly what we want. Now I'm actually going to go back into the previous design because I completely forgot about this. Let's get that out the way we want it. There we go. I'm going to have to come back to that. But an octagon is very nearly a circle. And I want polygon. There we go. There we go. Now I'm going to delete that. I'm going to go from there to there. I might come back and readjust that again. Because why not? This is actually, there was a textured aesthetic that I wanted to do on this, and that gives me the excuse to do that. I don't like that. I want that to be about 25, nope, 30. There we go. Oh, they did that to me. Okay, never mind. Let's dimension that. That'll be fine, and then we'll dimension that, which will be fine. Let's make sure those are parallel. Actually, no, they're coincident. Oh, right. My bad. There we go. I'm happy with that. I'm going to take that down to... Actually, I'm going to delete that because I want these to be dimensionally basically identical. 10's a lot. I'm going to go for 8. And if I'm being real clever, I'll scale that outer one down so that this is at the same distance. In fact, I'll do that. No, I'm not going to do that yet. There we go. Alright, now we're moving in the right direction. Cool. Now we got the thing. Alright, so when you have this printing, what I'm going to do is actually print it just like this. This way you have all the layers in line with the spool itself. And I'm going to extend that more because I'm sure that's wrong. There we go. In line with the spool itself. That makes it a lot easier, a lot more reliable, and you don't have to deal with any sort of silliness. Now, okay. We're probably going to have to make that smaller and create a wider lip on the other side. That way the spool can go on. But we'll come back to that in a moment here. The first thing I want to do is build the backboard for this sucker. The back right here, wall mounted, just like so. I'm just sort of scoping this out for now, and we'll see where we end up with it all. I want it to be symmetrical, so I'm going to go ahead and take this 150. Oops. 150, and we're going to go to distance. Can I go up to object? Yes, I can. Nice. Done. Cool. Covered for forever. All right. Now, here's the interesting thing. We don't want this to hang upside down, because if it was hanging in this orientation, you'd have screws up here, which means that this has a lot of leverage on those screws. So we actually want it to be pushing into the wall, and we want the most structural part down here to be the top. So in order to make sure everybody mounts it like this, and we don't have any problems, I'm gonna just go ahead and kind of create some visual language to try to induce that idea. And I think I'm going to start... I don't want to put a top and bottom on here because labels be dumb, but we'll probably have to. Right here, this is the minimum distance between the edge of the spool and knot. So up here, I'm able to put in a rib that will give us the rigidity that we want. So I'm going to start with that first, actually. Yeah. Actually, if I was doing this rib correctly, I need to do this as like a 3-point construction. Playing through 2 edges, playing through 3 points. There we go. Now I'm happy. So let's go ahead and project up a couple of those details so I have something to trace against. And I don't really care about the side direction, but I do care about the total depth, because that has to be less than the radius. And actually, not measured from there, measured from... I'm going to eyeball it. There we go. Measure from there up to this. And, yeah, 140 will be fine, I think, on that. There we go. Again, just kind of laying it out here, so it's not the end of the world if it's not all perfectly symmetrical yet. Join those. Okay, cool. Now we have sideways rigidity on this thing. And the bottom, as viewed here, is actually going to be the top, so no one will ever really notice. And if I'm being real clever, I might turn that into like a shelf or something underneath there, so that you have like nippers that can be hung behind the spool. We'll mess with that a little bit later on, but before that, there's an error in this that will need to be addressed, because this mounts to the wall fine, but it doesn't actually stand fine. It's actually going to fall forward. It doesn't have a good center of gravity, and I don't want that. So we're going to have to take this whole triangle and move it down to one side there. Hopefully that's not a giant... Oh, it's going to be kind of a giant problem. I'm going to lock in that one. I'm going to delete this dimension. I'm going to delete that line, apparently. There we are, that's more better. I'm going to take this line, go here. There we are. And make those two coincident. Sweet. Now I'm going to recreate that dimension again. I'm sure that's too much, but we're going to live with it for a moment here. Then we move this around. There we are. How far is this? It should be a driven constraint, but I want to... Well, so... in order to fix my baseline thing, I need this to be 46. Oops, wrong one. There we go. There we are. Now that's all symmetric the way I like it. That looks pretty darn nifty. Except now, my rib is on the wrong side. Because I want that rib down at the bottom so that everything is as structurally sound as it can be. So I'm going to go ahead and kill the rib. And that axis, delete. And we're actually going to put this back on the other side where it belongs. Okay, so now let's go ahead and sketch on that. And we're going to take, darn it. Project that, project that, project that, project everything. Just need everything all the time. Everything, everywhere, all at once. There we are. Okay. Now that is right there. And right there. Then we're going to take that, make sure it's 140 away at least. Project the edge of this to make sure we've got good distancing. And then we're going to go ahead and take this and take that and go 140. Well, that's not what I want to do. Actually, that is what I'm going to do. I'm going to go back to the core because this means I've messed something else up. 200, there we go. There we are. Now my rib's a little bit more better. I'm going to make it fairly beefy because this is the only thing that is holding this reliably. Make sure that we're joining there, and there we are. We have a nice little rib. So now this will print on this edge. The rib will be fine. This edge will be fine. I need to clean that up a little bit more so that it's laying flat against the bed. But we have a good spoke here. The edge goes all the way out to there. Okay, good stuff. You only need 2 holes in this type of a mount because it's supported both directions by the wall itself. So you only need enough screws to provide really good strength in a single area. And quite frankly, if you have connection to a stud, you should just use like 1 screw, just enough to mount it to the wall because all the lateral support is already there. So there's not a lot to be gained with putting a ton of screw holes in here except to create more holes in your wall. I'm going to go ahead and dimension those independently from there. They're going to be biased slightly inward so that we have support over by the arm where it actually matters and closer to that rib. Because again, yeah, the outer edge just doesn't do anything, so what do we care? Come on, give me some dimensions. Okay. Then, on top of that, I want to countersink these holes just a tad, so that if you're using wood screws or something that doesn't look nice, they'll disappear. And they will end up looking nice. Plus, countersinking allows the walls to be further in on the screw, so there's not as much of an opportunity for something to break through, because the walls are supporting it better. Whereas if the walls are backed by infill, cracks are able to get started more readily. So if we just print this thing with really thick walls, we can basically have no infill, which will improve the manufacturability of this a bit. Actually, I'm going to take that in 3. Actually, I'm going to take that in 5. And then, again, to reduce cracks and make everything look better, we're going to fillet all of this just as much as we possibly can around these holes. Otherwise, you'll end up with all kinds of problems. There we go. And then we'll fillet the holes themselves, but I'm going to save that till the end. Okay. I'm going to change this backstop because it doesn't need to be that thick, and there's no reason to waste that material on it. There we go. 140. Actually, I'm going to go 130. This is going to create some weirdness, but I'm okay with that. There we are. Now, I want to kind of maintain our design language here. So, I'm going to do this and this. Make those 10. 20, I mean. Oops. 20. There we go. There we are. Now we're kind of following constructive paths with all this. Actually, I need to undo that because I need to mess with this sidewall some more. The thing I forgot to do is add this line out here, right there. Make sure it is coincident with this. And now we need to extrude that. There we are. Now we don't have a little weird spot in the back. But again, now I can come back and do my chamfers. I'm going to give that 5. Again, just trying to clean it up a bit. And then modify my chamfer. There we are. And right there. And actually right here as well. See how far we can go with that. How far will it allow us to go with that? Let's go 15. I'm going to try to make it a little bit smaller so that it doesn't jack up all this. I'm actually going to remove that one. We'll come back to that. There we go. Now we have a spool holder that can be mounted to your wall, and it prints on its edge right here. We'll have to settle that inside of the slicer, but that's okay. Now, here's the thing. I don't want a solid piece right here because that doesn't look very interesting. Oh, the other thing we got to do. I want this to be a polygon and inscribed just like that. Then we'll do dimension here. This only needs, oops, not what I want. Let's go parallel. There we are. And then this needs to be coincident right there. And actually, I can do something really interesting here because I can have that align with that, and that align with that, and it's not exactly what I was going for. Can I? I don't like that very much. So the issue is that it doesn't create symmetry and the function that I want. So I want the best of both worlds all the way through, all the time. There we are. So we're going to do that. And we're going to make that 5 because it doesn't need to be much. Although I kind of like it to be symmetrical. There we go. There. Now that should prevent the spool from falling off the edge. It does kind of mess with some things that I was trying to do, but I think we'll be okay. We also need to dimension this smaller, like I stated before, just because this is not going to let the spool onto it. But now you have a spool holder that can stand horizontally or hang to a wall. And while this is, the base is narrower than that, I do want the base to continue to be narrower for, again, saving material and looking better, but it's not necessary. But the center of gravity when the spool is mounted on here will be over the base still, so you shouldn't have a tipping problem, but that is an issue. We gotta kind of address that, so, but I'm gonna circle back. Well, nuts, darn. If I do that, darn, that doesn't look good at all. I don't like it at all. Oh, also that screw hole is right behind the pin, which means it's going to be stupid hard to put in. So let me spread those out some more so that it's actually easy to access and mount this thing. There we are. That's much better. Now you can actually get in there with a drill to put this together. All right. So that's the way I want that. That's the basic shape and form. Let's see. What else is going to bite us on this? I want to fill this in completely. So I'm actually going to add some more chamfers to this. Because this rib, as a rib, I don't like. There we go. That looks better. I like a block back there more than the alternatives. And again, leaves the spool lots of space, looks better. Regular ribs are just ugly. And plus, it creates more structure, and yeah, it looks better. But since I can do that, let's see here. The rib. There we are. Let me rename this. I want to make that smaller, shallower, -1. That way, you don't have a block and then the rib. It's just a nice, solid piece back in there. Much better. And it's right next to the screw, so the screw would have to go through all that to tear out, which is all better. Okay, that's good. And yes, we've got a nice, decently wide base on this. I might adjust it and move this up a little bit, actually. Let's take that direction a bit. There we go. We'll put it dead center. Dead center-ish. Now, the other benefit of this is that the fact that this is laying flat, this is going to be angled forward, which means that the walls are actually stronger because you have a greater thickness inside of there. And it's not running straight along the layer lines. Like if it was printing just like this and the layer lines were going straight perpendicularly across that, they would split across there. But this way, the layer lines are going to be coming across at an angle, so they won't actually tear through as easily because it's got to tear through so much more and across layers. So that radically improves the structural integrity of the part. I still hate this. So we're gonna, while maintaining our design language here, I'm gonna create a triangular slot in this that will remove material, which is not really what you want, but it'll break up that giant mass of stuff. And in fact, if I was being smarter about this, I'd turn this into like an up arrow, which I like even more, because it doesn't create a stress concentration there. Let's go back into that sketch. I'm going to go ahead and create some slot designs here. Create slot right there, slot right there. Now remember, here as I'm working on this, down is up. So we gotta work around that. I'm gonna make this actually 5. And let's dimension this as 5. Let's do a radius 2.5. Let's get those all concentric with each other. Actually, not what I wanted. Nuts. Waive the concentricity constraints. Darn. Okay, let's just go full clean sheet here. Create slot. There we go. I'm going to make that 8. And then I'm going to create another new slot. And the challenge that I'm having here with this is that I gotta put it... Oh no, this is going to be okay. We're going to survive here. There we go. Let's get this dimensioned. There we go. There we go. Yes, I should make this symmetric, but I don't care right now. That tip of that arrow is right in line with that hole, so I'm going to pull that back some. Right here, right here. Okay, fine. I'm paying for my laziness already. Let's go right here and right here. Oops. There we are. That's better. And this is now in line with the other hole, so we'll adjust that too, so that it doesn't ruin our part. There we are. And now this breaks up that big old open space that's so ugly. And puts a really nice -5. Actually, I'm going to take this all the way back to -8. That way the back wall is 2 millimeters thick, which is perfect to have basically solid wall. There we go. And now people know how to update this, and also probably how to kind of feed it. We may end up making this base wider. I want to print and test it to see how easily it pulls over, but really we're kind of thinking of this as being also like mounted to the desk, so I'm not too concerned about it. And again, I really want to kill these two holes too, because they're just not necessary. I think if we went to one hole and changed slicer settings so that it's solid through that hole, that'd be fine, and there's nothing else weird that has to be done. And then it's perfectly structural all the way through. Because 2 screws, you don't need 2 screws. There's no structural reason to need 2 screws here. Except to hold the part, to distribute the load across the screws. But even when like this is hanging on the wall, the top screw is having full pull out. So you still we only need 1 hole here. I was an idiot. We don't need 2 screws. It's just a need for symmetry, and that's dumb. Screw holes are not necessary at all. We don't need that one. Done. Okay, now, again, I have this weird sort of big empty space, but I'm actually going to fix that because triangles be awesome. Now, let's go ahead and delete this chamfer, and I can go ahead and create a chamfer right here. It's about 50 big, or 100 actually. There we go. Actually, I should only do that like 50. Now I'm going to do it at 80. There we go. And now you can see that this design kind of leans everything towards the hole, which is very useful. And because of that, I can now suppress this arrow. I'm not going to delete it because who knows what mistake I made. But see how it's minimalizing towards triangles? That's kind of what we want. And again, since we're taking off this chunk over here, I can probably lengthen it out some more again, or take this and actually make that 170, like so, and that way this can go closer to center, and then this could be defined by this. Oh no, let's go, I want the coincidence. There we go, That will fix that. And now I can make that chamfer bigger. And now we still only have one hole because this is the top. This is the spot that's where it's mounted from. And again, since we're increasing this angle, this whole strength of it gets better. So when you optimize, everything can get better all at once. And quite frankly, if it doesn't, you're doing something wrong. Oh, that's starting to look really good now. I'm quite pleased with that. And this is supported by thicker material right there, but since we make it thinner, the walls themselves are the main structure, but it's diagonal, so it prints better. All of this is coming together pretty darn well. That pretty much structurally is fine for now, I think. For the outside, I want to change the structure of it a little bit. So you don't want to do through holes. You never want to do through holes on 3D printed parts. They're a terrible idea because they're a waste of print time and material and effort, and they create an aesthetic problem, all the problems with that. But a texture would be really cool on this, and I think what I'll do, I'm okay with the hexagonal shape, but I don't want to emulate other designs. So I think actually I might lean on a triangle. I kind of like to do something with scales. Let's create a poly. Actually, that's how to get it done. I'm going to go ahead and create a polygon, an inscribed polygon here. I want it to be 10, and I want it to be 3-sided. Oh, I want it to be 5. There we go. Okay, now this thing, I'm gonna dimension from here to there. Yeah, that'll work. Create driven. Oops. There we go. Yeah, 10. I want a good solid border around the outer edge of all this stuff. Okay, and then 10. And now I'm going to rotate this around because I want this triangle to be the opposite from the main. Because number one, that's just more interesting. Okay. Now I'm going to extrude that just a hair into it. -2. Actually, -1. -1, yeah. Textures you don't want to make super deep. Alright, so I'm happy with that. Now I'm going to pattern that. And I'm going to use features. Take this, and then I'm going to go from here and there. I'm going to go 10 at 20 spacing. That was not enough. Oh, it's an extent. I don't want an extent. I want spacing. There we go. 20. Okay. Oh, darn. I made a mistake. Although I kind of like that. I'm going to run with it. Let's go 20. Oops, too many. Now the great thing about these triangles is that they're kind of low effort computationally, so I don't have to worry about a bunch of slicing on this. And there is our pattern on that, which looks kind of nice, but now we don't want to clean it up a little bit. I don't want it to be that ugly. So I'm going to go around and create this nifty little border all the way around to there, and from there to there. And now I'm going to go from here to there, to there, to there, to there, to there. And now, through the magic of constraints, and then dimensioning, I want this to be 10, because 10 is kind of the magic number. That's too much. Down at the end it's going to look weird, so I'm going to make that 7. There we go. That's much better. The proportions are much better in that regard. It might actually win out, though, now that I say that out loud. Now that I'm seeing it here, all mounted up. We got to close this off. I don't really care too much about it. This might bite me later on. Don't care. Can I select that sketch? No. Okay, fine. Get all these chunks and pieces here. You know what's really going to hit me on this is when I decide I want full triangles rather than that little cropped triangle. I kind of like the cropped shape right now, so I'm kind of going to keep it. One. Actually, one. There we go. Okay. There we go. There we are. That looks pretty good. That's a kind of a nifty diamond pattern. And yeah, we'll imprint the logo on it at some point there, and I will clean up those. I'll get to it, don't worry. By golly, that's a new spool holder.
Almost everyone is designing cavities in parts completely wrong. In this video, we're going to talk about why that is and the solutions to actually design them correctly in order to take full advantage of mass production 3D printing and get out of the old school way of cutting out these cavities and wasting a lot of time, effort, and material. So if you were producing a traditional part, generally what you have to do is you would get it molded, which means that you have to conform to the design parameters of that process, which generally requires that you cannot have thick features inside of the part. This ends up creating a situation where you want to remove material from the part. You would generally have like ribs or something inside of the piece, but you would cut out large sections of it because any thick monolithic part can't be molded because shrinkage would cause it to deform, or it just can't flow right and you create all kinds of weird surface deviations in how the part is actually made. So very often people end up going through and cutting out pieces like this, cutting out these large cavities. And while that's okay, it's not really an optimum way to make a part because it's an attempt to try to remove material, but in the context of mass production 3D printing, it can actually do the opposite and actually hurt the cost of the part. One of the first reasons is the fact that these additional cavities increase tool motion. So very often print times can increase if you are putting cavities into it, since most printed parts are kind of like this, where the interior is a solid infill, kind of a composite part, and then the outer walls are where most of the material is. If you cut cavities into the part, then you're basically increasing the amount of material because you have these extra tool paths out here, whereas if you eliminated them, you would just have the simple infill, which can be varied up and down to different levels of density so that you can actually have less material while still having an exceptional amount of structure on there, because you can almost have a person stand on this and you can't break it. And if we did a correct type of infill, like a triangle or something along those lines, then it would be as strong as a standard truss. So this old style of designing cavities is something that's left over that many 3D printing designers actually do because it seems like the process to do is to remove volume to remove material. But actually it's the opposite. What you want to do is you want to decrease surface area in order to minimize print time, cost, and volume. The other thing with this is that this actually increases complexity of the part and therefore increases failure rate. Because with these circles, you could potentially have stringing, you could have a deviation, you have the surface area where the outer nozzle is fully exposed, so if it has a slight misflow of some type, it's viewable inside of there. Whereas if anything goes wrong inside of this piece, since that part is solid from the outside and you can't see any sort of deviation inside of there, a cosmetic error does not cause the part to be a failure. So again, you want to minimize that surface finish in order to minimize rejection rate, minimize print time and material, and just make the part look a little bit better. Because ultimately, the right way to design this part would be like this. Because now you have a solid part that is arguably much more attractive than this, where you have a bunch of cutouts that look like they were added there to keep it alive. But again, you have all of that structure. And like in this case, since this piece has that internal structure inside of there, it's almost like a composite honeycomb, like a carbon fiber honeycomb, to where it has these outer wall flats that add a shear plate to the whole thing, and then the interior structure there, which gives all of the strength to it. So it's almost like an I-beam rather than just an engineered part there. That all being said, optimally, a 3D printed part would be fully solid. But there are times when you want to break that rule. There are situations where cavities can actually provide an advantage. If you have normal infill, then you have a consistent and isotropic kind of strength profile across here. Whatever the infill happens to be, it's going to be the same strength throughout. But what if you want to reinforce this, or you want to thicken up that infill and make it even stronger? Well, this is a situation when you can use cavities. By using cavities inside of this half arch here, we're actually able to increase the wall thicknesses of that lattice and make it very dense, because now it's fully solid as opposed to a solid outer wall and then the infill lines themselves.
putting in these cavities creates basically thick walls throughout, which means that we have an even stronger part than just standard infill, even though it's a lot heavier. But what you can also do with this is you can actually take these cavities and apply them to certain areas of a part. So now you can increase the strength of a very specific area. So like going back to the wing, you can put cavities across the leading edge of the wing so that it's exceptionally rigid right through there and much stronger without really adding that much more material. But ultimately, with these cavities, you still want to end up with a solid part because it looks better. So rather than cutting them out and leaving them viewable or cutting them all the way through, please don't cut them all the way through ever. Make sure there's always a shear plate on the back of it because it makes all of printing easier. Having through holes actually increases all kinds of problems with the first layer and so on and so forth. Please don't do it. But if you need to have cavities inside of the part where you're trying to change the strength of the piece, go ahead and still cover them over so that you can have these circles or whatever kind of leading edge issue is inside of there, but it's still inside the part and it still looks exactly the same from the outside. That way the cavities don't collect dust and dirt and bugs, and they don't create, again, manufacturing defects that could be visible because, again, they're increasing surface area, but allow them to be stringy. So like with this part, you can see right here we have all this fuzz because this is an interior feature and we wanted to induce this in order to make this point. But if this was fully enclosed and this was a cavity inside of there, like one of these circles, well, if we close off these circles, you'll never see that fuzz. You still have the same structural benefit, but it decreases post-processing and cleanup to get rid of those sorts of issues that could potentially arise. So cavities do have their place, but they're mainly for a structural component. Do not use them to remove material from a part. If you are trying to remove material from a part, just bias towards filling it in solid. Because again, you have the part basically filled with air, but you can also have the structure along with that air. So hopefully that covers where cavities are really useful. They are something that can be used, but most people really misuse them because there's an old ancient technology that is informing how people design for 3D printing, and it's really not helpful. Cavities are a bygone era when you can create a fully enclosed part, which has never really been possible before. You can put in internal cavities, you can place them where you want, you can modify how the part behaves in different areas so that you have this micro engineering capability to really control how the part behaves throughout the part without having to change materials or have complex assemblies or anything else. It's really a superpower of 3D printing because you can create these really complex geometries that were never possible before. So rafts are a very common and very useful feature inside of 3D printing slicers. They can protect the base layer of your 3D print. They can compensate for any sort of variation in leveling on the bed. They can make sure you maintain high tolerances on the parts, and they can help to keep the part stuck down to the bed without having significant post-processing like brims and that kind of thing. But the issue is that slicers are freaking terrible at making rafts. Here's the issue. So most rafts are designed with a rastering pattern on the base layer so that it can be removed from the bed easily, and then multiple layers on top. Many slicers are really bad at defining how these features work. And since they are dependent upon the slicer that is made on, it's very difficult to prototype a part and then send it into mass production at a giant print farm like ours. Our slicer might be a little bit different from yours. The spacing might be a little bit different on your raft. The cooling might be a little bit different. All of these factors really affect how the raft performs, and they are really ambiguous about what they are. How thick is your top layer? How thick is your first layer? So on and so forth. All of this is just kind of silly. And if you're running through like an automated system, if you like submitted something through our API or our Etsy plugin where it's blind and the part is just sliced and then printed, you don't really want to have to rely on print settings. You want to make sure that you control how that part is going to come out so that it's really, really reliable. And the only way to do this is inside of CAD. But let's talk about regular rafts just a little bit. Not only are they not user-friendly and not consistent or reliable across platforms, but the way they're designed is incorrect. Many of them have the rastering pattern. That rastering pattern is generally one large bead of plastic. When dealing with high warp plastics, such as ABS, that large bead creates a really thick concentration of material that then shrinks. So the raft itself peels up from the bed and creates stress concentrations and stress forces, internal forces inside of the raft that make it want to peel. It's a really bad way of designing that first layer. They should be thin and small, but you can't do that because the raft has to stick down to the bed. The subsequent layers also on many slicers are spaced out too much, and you can tune these, but it's very difficult to get them to where they need to be. A lot of them are kind of stringy because they're like, oh, the raft needs to peel off easily, but you end up peeling off and leaving material on the core part. And inside of slicers, when you're spacing the raft, the part can often become disconnected from the raft itself so that you can remove the raft, but then the part isn't actually cinched down to the bed, and you create all of these issues. So, The best way of fixing all of this is to design a raft into the part itself. It's not difficult. At the most basic level, you can just create a plane, a sheet that is then printed underneath the part. This gives you the reliability of the part, the strength of the part, make sure that the part is cinched down well, make sure the spacing is all there, and you don't have to deal with fiddling the settings inside of a slicer that might be ambiguous. Now, that doesn't fix any of the other issues with the raft, but let's start with a cube. First of all, make sure you fillet the vertical edges of the cube. That improves print quality and print speed, and you do not need sharp corners anywhere inside of a part. So you put the plane underneath it. That plane generally can be spaced out by the distance of the layer height that you're using, maybe a little bit less if you want to increase adhesion. So if we're printing at 0.2 layer height, go ahead and space out the designed raft 0.2 from that part. That's the baseline, easiest thing to do, super simple. Make sure the outer edges of the raft are rounded, again, as much as possible. If you could put a circle underneath the part, that's ideal, because then you don't have potential areas where they can warp. Sharp corners warp on a first layer if you're dealing with those types of materials. Now that's the very basic and most simple type of raft you can possibly get. Now let's get a little bit more interesting. This raft is not holding down the part. You have to tune spacing. That's a little bit too much effort. The corners of the cube could warp and peel up from the raft, so let's go ahead and just tie those down. What you can do is you put some small 1mm struts underneath the edges of the part so that they are physically connected to the raft, and now the raft can hold down the part and serve as increased adhesion holding down the piece. But when you remove the part, they're 1mm struts, so they're very easy to either snip off or just manually break off. You essentially create a very simple zipper that's able to break away, and then you can still have good strength adhering to the raft, but a part that's easy to remove and process. But now let's go ahead and go to the raft itself. The part is stuck to the raft well enough now, but the raft itself now has to stick to the bed and be reliable. Like we said, round the outer edges, that's great. A lot of problems though with rafts is that the rastering is very often linear on any of these parts, and when it's linear, you have that shrinking problem again, where there's a big old long streak of material that then shrinks and causes the raft to warp. In order to fix that, break up that big old long streak of material. You can do it by just removing a very small section of the base layer of the raft. You can do this by just putting a big old circle underneath and pulling that up like 0.2mm again, so that you just lose a single layer, so the raft is still sound and the raft can still potentially kind of stick to the bed. But you don't have these continuous layers, and you just have the outer edges sticking down to the bed, so that the places where the force is most necessary are there, but the interior peels off easily. This also improves mass production because auto ejection is more reliable and all that kind of thing. You can take this a step further because, again, that rastering, if you're working in these corners, you can have some corners with longer streaks of materials than ones on the other side where they're turned 90 degrees. You can also cut like an X through the raft, which will break up those continuous lines so that, again, you just have material sticking to the bed, but you don't have these long shrink regions that can cause issues on the raft and other pieces of material. And you can play around with these patterns. We could probably do another video where these patterns can be very explicitly designed, because there's a lot of really cool stuff you can do with zigzags and that kind of thing that can really improve this. But that improves the raft first layer so that it's reliable, sticks down to the bed, but it's still easily removable, but still also holds down as well. All of these factors that you're playing with. Now, very lastly though, there is one more thing that we can do with the print itself to make sure it's stuck to the raft. And this is an advanced feature that requires a lot of teamwork between supplier and designer. And what you can do is now thicken the raft so that it's very thick and rigid, which can be useful because, again, if a raft is thick, it's more difficult for it to warp if you're using the correct type of materials. You can effectively have infill, and now you have a strut underneath the part. But if you are trying to stick the part really reliably to the raft with a really high warp material that, like, the little struts don't work, you can't just space it just right, all the rest of this, a thing you can do is effectively create long lines of connection so that you have this kind of Velcro disconnect feature. The way of doing this is with just hemispheres, and then make sure that each one of the interface locations is one layer thick. That simple one layer lets us break it away really easily, because one layer of printed parts will break away really easily. So you can do a hemisphere, make sure that the tips of the spaces in between the hemispheres are 1 layer thick, which means 0.4 millimeters, or maybe 0.5 if you want to stretch it up to, again, make sure it auto slices well and it's not like a thin wall that's ignored. But then you can have that whole row along the bottom, and then the part will break away from that whole row, but still have really, really good adhesion because it's effectively the same part. That lets you connect the piece more tightly to the raft, but still be able to break it away.
Almost everyone uses auto-generated supports from their default slicer in order to support parts that require it, which are a whole bunch of different types of parts. But this is kind of the worst way of doing it. So in this video, we're going to talk about why auto-generated supports are just horrible, and also go through the multiple different solutions to either prepare for those supports or design entirely clean alternatives. Okay, so why do auto-generated supports suck? Well, at a very generic level, it's because they are the default. They are a generic solution. They are a catch-all solution. And a generic solution is fine, it works, but it always gives you kind of a generic result. This is especially true for designers who are creating parts that many different people will print on many different types of machines. If you are a designer, you don't want people to perceive your product as bad because the individual settings that they're using are not correct for that thing. You want that part to be printable just as is, so that somebody can just upload the model and print it regardless of what their device is. This also holds true for services. If you are wanting to mass produce a product or put it into a service like our print-on-demand teleport service, in that case, you want the part to be really reliable so that you're not worried across thousands of pieces of certain defects coming in. You can engineer to avoid certain common issues that auto-default, auto-generated stuff can create. So that's the reason to kind of avoid just the default support settings. It's fine if you're an individual and just doing a one-off, but for all professional use cases, you really want to tune supports in. And in order to do that, you want to be totally isolated from the slicer itself. So there's two ways to actually do this. The very first one is to prep the part to be supported. This is going through a couple of different tricks to where supports end up where you want them to be or not at all. And then the other one is to actually design the supports from scratch yourself inside of CAD or through a couple of different solutions. So let's go ahead and look at that first category. If you're prepping a part for support, obviously the very best solution is to design the part to need no supports at all. This could be something as simple as just rotating it 45 degrees. If you have a cube, chamfer the outer edge, turn it sideways 45 degrees, and now it needs no support at all. It just prints up on a corner and it's stronger, looks better, and you have no supports anywhere that need to be removed. That's an optimal solution. You can also chamfer edges so there are no direct 90-degree overhangs, all kinds of things. And we go through all of this in a separate video where we talk about how to design parts so you don't really need supports. But if you do need supported areas, there's a couple of things you can do. Say you have something like a tooth and a dragon. We have this default model here that is just to demonstrate that. With this sort of a situation, what you want to do is actually create a support thumbtack. And you can either move this in there in a program like 3D Builder where you just position an STL and then merge them, or you can design it in CAD yourself. And basically that is to take a single little spike out of the bottom of that spike and then give it a broad lower surface. This catches all the support and gives it a nice firm foundation, and then that cone of the tooth can grow out of that. These types of pins are really, really useful because the failure of auto-generated support is that it doesn't actually touch the part. So these type of overhang pieces, when they're first growing, the tooth is just coming up like this and has nothing around it holding it vertical. It can start to rotate and fall into the support, into the nest around it, so that you end up with weird aberrations on the side of the part. But if you use this thumbtack method, you know it's held all the time, always, so you don't have to worry about it suddenly kind of settling into the support and causing features on the outside of the surface that would be undesirable. But let's get into the real meat. You don't want to use auto-generated supports at all. Get rid of them, they just leave hangy-draggy messes all over the place. You want to actually design supports into your part so that you can upload it and know that it comes out exactly as you intended. In this case, what you can do is you can just design a piece of support that is offset from the part. You can use the offset tool inside of your CAD program, or you can model it, or you can use a negative inside of something like 3D Builder to kind of create it and then scale it down. There's a lot of ways of getting the modeling done,
But this is basically, you just design a piece underneath it that contours to the shape of the part so that it supports the part as it's being made. And that way you know that the overhang is supported exactly as you intended, you can verify it, and that's fine. The problem with this is that you are restricted to very certain types of materials and parts. It's not always universal, because if you set the settings just a little bit off, then material expansion might be an issue, the machine might still be an issue. The best solution is to give spacing of about 0.2 to 0.3 millimeters, and then test a couple of times to verify. And of course, if you were designing exclusively for a particular machine or a particular service or method, then once you know kind of the feel for it, you know the rules of it all, then you can design everything that way and you can throw up whatever you want and you know it will work. But if you're on your first try, you want to verify it after a couple of tries. Quick side bubble on the design support and the thumbtack. If you're using the thumbtack as we had in this case, you actually have to have support generated up underneath it. And while it's great for defining that support, it's still a really tall, thin piece of support, which can fall over and create a failure, which we actually ran into during this video. But if you use design support, you can actually use the support comb methodology to where you have these small sprues reaching out of the main part, holding up that support so that you know the support is really reliable and really fixed in the position where it needs to be, and you don't have to worry about the printer knocking it over and losing that support, which would cause a print failure. So again, being able to design makes you ensure that the part will print successfully. That's kind of the obvious version of design support, which is to just replace generic support with the designed support. And that's fine, and it works fine, but it is kind of a lot of work. But with design support, you're actually able to get some benefits that you otherwise wouldn't have from standard support. You can have minimized material, and you can support areas that you just need to support. Again, auto-generated will put it wherever the auto-generation decides it should go. With design support, you get to place it explicitly where it's necessary so that you get something really good. The other way to kind of prep a part to not really need support or to reduce it is to actually use a support fin. A support fin basically is just meant to increase the base contact area of the part. So with that cube, if you rotate it 45 degrees, it's fine, it's symmetrical. But what if you have something long and skinny? If we go back to our demo part, if we just rotated it around a little bit weirdly, now you don't have support on that tooth there anymore. But now if you try to print it just like that, it's gonna fall over because its center of gravity is too far to the left. There's a bunch of mass sitting out to the side that wants to fall over as it's being printed. So you want to design a support fin underneath there. And a support fin, you can design it to where it's basically just a triangular prism underneath there that is spaced off from the part. But again, you're dealing with that settling problem to where the part could fall over into the support in just that point little two space between the support and the piece itself, so it's still removable, that you don't want to actually do that. Instead, add just a few little prongs through there that are about 0.5 millimeter thick and 0.5 to 1 millimeter wide, that are perfectly horizontal so that they are a single layer into the side of the part. These hold the part stable and make sure that it doesn't fall or settle into the support, which means that you again have a really reliable piece. But here's the trick with this. You want to make sure that this support fin is also removable. In order to do that, it needs to be able to bend and flex. You can make it really thin, but if you do that, you need to give it a wide base so that it doesn't unpeel from the bed. You can make it fat. In that case, just make sure to chamfer or fillet the front of it so that when somebody is removing it, they can bend and twist and break off all of those little tines that are holding the part stable, or snip it off and get access to it. You don't want to bury them in the middle of a really thick support fin. But that's the design of a support fin, and now you're able to print the part at a diagonal angle and you don't have to worry about it potentially falling over or anything like that. You can also use these type of support fins to just give more rigidity to like really tall, thin pieces. And again, we go through this in a whole separate video. Okay, that's the overhang for the tooth. It's the one that could kind of need like a really optimized type of design. But what if you're just trying to support like a bridged area, something like a tunnel through a cube? We'll do this really simple example here. With this one, literally, since most machines can bridge 1 to 2 inches pretty readily, you don't need a ton of support in here. You can just insert a little cube. Now, many people would model just a solid cube. That's not really very desirable because it can be tough to remove depending on how big it is. You want to make sure that this part can be removed. Make sure that the top has like a 0.2 clearance and the bottom has a 0.2 to 0.3 clearance as well. This is kind of the generic sort of dimensions, but again, test based on the material and systems that you're using. But if you have a solid cube in there, do put some text on the side that says support so that post-processors know how to remove it. This is one of the cool advantages of designing support. You get to put instructions there that your customers can use. Kind of like removing shipping screws or tape and that kind of stuff inside of a machine when you receive it. Things that hold it stable in shipping, you might want that support to arrive at your customer and then they pluck it out. In that case, you want to define it as support so they can't mess it up. But if you want it to be more easily removable than a solid brick, which can be quite difficult, instead, you can actually just cut a hole through it. Now it's crushable. If somebody crushes that with some pliers, the two sides will collapse in and then it plucks straight out. That's very, very easy. Now, if for some reason you have a part that is too large to do that kind of just cut through design, because it is bridging itself, of course, then you want a solid support inside of there, that's fine. Just make sure that that support is removable, which means that you probably need the ability to twist it. So again, in this case, don't make it a solid rectangle, make sure to chamfer the edges of it, and now you still get to have your text telling people that it's support, it's more easy to remove, all of the optimizations are there. So there's a number of different directions to go with this, depending on what your actual use case is. But again, engineer it how you feel is best to accommodate the instructions, the crushability and the removability, and whatever sort of intention you want with that. You're designing support, so design it. Okay, if you're not really that good at CAD, but you just want to like use a service like Teleport, but you don't like the auto-generated results, then you can design the supports yourself without having to design them. The way this works is we're going to use the default example of Prusa. Prusa Slicer allows you to export tree supports as a solid 3D model. And this is an interesting thing that most people are not aware of. If you go into the standard FDM settings of Prusa Slicer and then change the system over to an SLA printer, and then you can turn on tree supports and define them to be fat and thick because we're dealing with FDM parts. And with those fat and thick supports, you can generate them automatically, and now you have a really clean and pure model that can now be exported as an STL so that all your geometry is in place. It's not a tool path or exporting the G code. You're actually exporting the tree supports. They're a little bit weird because they're not always quite dense enough, but this is a really good way of auto-generating supports, making sure they're placed where you as the designer intend them to be, and then you can upload them to a service or share them with your community so that they can print them, and you know that they don't need to generate supports themselves. So, if you don't want to go through all the CAD, then you can actually auto-generate supports, control where those land because you're familiar with the slicer, and export those designed supports to be used by someone else.
Sometimes you've designed a 3D printed part and you want to give it off to somebody else to make it, but when the sample comes back or the first batch of parts comes back, they're different from what you had expected. Why is that, and how can you avoid it? In this video, we're going to talk about how to design parts so that they can be made on any machine with any slicer settings at any time with any material without having to worry about the translation in between, so that anyone at any time with any machine in any material and any slicer settings can produce that part reliably. Now, why does this actually matter? Well, it matters for wanting to manufacture the part. If you are just making it yourself on your own machine, you are an artisan. That's like saying, I have this tool that I like and I sharpened it just so, and I use it with so much strength and I have this much skill. It's very specific to you. But if you want somebody else to make your parts for you, you need to be able to design a part that can be made and manufactured. This is true of every type of process: CNC machining, injection molding, 3D printing. You have to design for that process so that the part is robust, so that it can be made reliably by other people without special tricks or special expertise or special little recipes. If you have secret sauce in how your product is made that someone has to know in order to make it, then your product is not manufacturable and you'll never be able to get past just the artisan hobby sort of stage. So you want to make sure that you're designing parts to be robust so that they can be made at any time in any way. So there are about 6 primary features of this that you want to be aware of that we're going to go through in depth all the way through here. Number 1, designing so that your part either has reliable supports or it does not need supports. Designing so that it is strong without needing to have variations in infill or special wall thickness settings. Making sure all the edges are tight and crisp and pretty and there's no wobble or weird artifacts in the surface of your part. Making sure that the part cannot warp or does not have deformation on the first layer that can cause defects that make the part look less quality. Surface finish, again, ensuring there's no aberrations, and if they come up, they don't jack up the cost of your parts in production, and you are actually able to produce thousands of them without having problems cause a bunch of them to be defects. And lastly, tolerances. How do you make sure that all of your parts always fit together regardless of the material or the machine that they're being made with? So let's go ahead and dive right in, starting off with supports. So if you are outsourcing your part to be designed, you generally do not want to use auto-generated supports. They're very difficult to remove. They increase the cost of your part. They can cause damage to your part and cause it to look bad. And sometimes you just don't need them all. Sometimes you just need a couple of small pillars. So the best option, if you have to have support, is to design the support yourself inside of CAD. We have an entire video talking about how to design support into a piece, and you can go ahead and check that out here. But of course, really the best option for support is no support at all. There's very simple design rules that you can follow in order to eliminate support. Make sure there's no vertical overhangs. Chamfer them, smooth them out so that something is built up to them. Make sure the part is oriented so that supports are minimized. And make sure you design certain areas of the part so they don't need support. Again, you can throw in little support bridges and pillars inside of places. So like if you have a hole in the side of a part, you can just put a small little vertical bar inside of there so that that hole doesn't have a big old long bridge. And lastly, if you have an area that is supported, maybe just fill it in. 3D printed parts are able to have a lot of volume. You can make something chunky and big. So if you feel like you have this vertical overhang because you needed to cut out all the material underneath it, don't do that. Just leave that material there and have it be a part of the part. It can improve the aesthetics of it all. It definitely improves the support situation, and it can improve the strength of it all. So lean into the chunkiness of the part. And if you do that, you eliminate a lot of the needs for support. Next, strength. Strength is a really big one. 3D printed parts are a little bit weird. This part is weaker in this direction than it is side to side. So you want to make sure that you have the density or the wall thickness that you want. Now, normally this is done inside of slicers. You will make the wall thicker in order to make it stronger on the outside, kind of like an I-beam. And then you might increase the density of the infill so that the part is stronger in that direction. But neither of those are particularly very good. A better way of getting strength in the walls is to actually put in what we call micro features on the outside. Again, something you can do inside of CAD so that regardless of slicer settings, it will always have the strength that you want it for. A simple way of doing this is basically running really small tubes up along the inner side of the wall. So it's a really reliable way to get that thick wall feature so that you have a strong outer wall that can be really stiff. You can also use the same sort of technique to sprinkle in strength. If you have a corner or a gap that needs to be stronger, so you need more material down there, you can put in those micro features which will induce more walls inside of that area so that it's stronger at the core, but then the rest of it can be really lightweight and easy. And lastly, again, just make it fatter. Don't design an I-beam, design a brick, but allow the brick to be filled in with infill. And that allows you to get a lot of strength without a lot of material. This is what a lot of people misunderstand if they come from previous ways of designing stuff. Most other processes are all about removing volume. If you're molding something, you need to cut as much out as you can. That is not true for 3D printing because we fill it in with infill. So if you need a part to be stronger, make it fatter. You're allowed. It's okay. Don't try to slim it down and then try to make it strong by throwing in a bunch of infill because that's just nothing. Just imagine the same amount of infill and then you spread it out and make it less dense over a wider area. You end up with a stronger part without having to deal with slicer settings. So just modify the geometry of the piece so that it is stronger. You can also do simple things like chamfering corners and that kind of stuff, which is a great way to lead into this next feature. Chamfering corners not only has a strength benefit, because if you go from a really sharp corner to something kind of rounded, the rounded shape is able to distribute force over it a lot more so it can be stronger. But rounding corners is actually valuable in another way. If you are printing a part vertically like this, again, coming up this direction, you want all of the outer corners to be a little bit filleted, because what that allows the machine to do is to move around that corner easily rather than taking a 90-degree turn. Imagine you were in a car and you don't change your speed and you just turn 90 degrees versus going around a smooth roundabout. There's a big difference in how that behaves. The car forces you to the outside. Well, when a nozzle does that, it does the same thing and it shows up as vibration along the outside of the part, or maybe that corner will just be a little bit out of whack. So just make sure that you round out those corners in the vertical edges, and that will improve that a lot. But then you also want to do one thing other for the lower edges, which is chamfering the first layer edge. So this part that's sitting on the bed right here, has a very small chamfer along the outer side. We generally recommend about 1 millimeter. That chamfer makes sure that you don't have to worry about side extrusion or different flow rates. It all disappears with a simple chamfer along the bottom. So that's the way to clean up all of your edges so that you get a part that looks really crisp and really nice and really beautiful. And then if you have a chamfer on the bottom, you can apply one to the top in order to create symmetry throughout. And again, this part right here can be printed with any resolution, any material, on any machine, and it will still function just fine as intended. It's actually a print in place. So we're gonna use this for a couple more examples. So warp. Warp can be a huge issue, even with simple materials like PLA. If you have a big, long, square part with sharp edges on it all, those edges can pull and shrink and warp up on the edges. So how do you eliminate that warp or make sure it's not an issue? Well, again, you don't want to turn on a brim or turn on a raft or turn on some special setting or have the temperatures just set just right for your material so that it doesn't warp for your part. You want it to be reliable. The easiest way to design this into CAD so that it'll work everywhere is to use mouse ears. If you have a sharp corner, put just a small circle over there on that corner, and then it is held down. It has more surface area to adhere to the bed. And then those brims can be easily removed. They don't leave a large defect or mar on the part in any sort of way. And if you're being really clever with it, you can design the mouse ears so they just barely touch the corners so that they can be snipped off clean, and you just have the smallest little pot mark there rather than some big old grind in a razor blade removal that can be indeterminate. If you really have a complex part, then you can design in a brim, and a way of doing this is to literally just design a 0.3 millimeter plane, insert it into your model, and then merge your model with that plane. But then you basically have this big round sheet. You do want it to be round, you don't want it to be square, again warping, but with that round plane, that gives you a sheet to work from. You can also design in a raft by making a thicker, like 1 millimeter plane, and then spacing it out about 0.1 to 0.2 millimeters from the actual part that you want to be printed. That way the first layer of the part is clean and can come off of that designed raft, which can be really, really useful. Especially if your part has a really complex first layer, like if you're trying to stack up 100 tiny little parts on one single build plate, you should design a raft for that so that they all come off on that raft and then you just twist it and they all fly off. That is the most reliable way of designing a part like that so that you can knock off 100 tiny little pieces without having to worry about one failing while a first layer is going down. So designing that first layer and using a raft, a brim, or mouse ears in order to hold it down reliably is really important and can also improve the quality of your parts. Surface finish. A lot of people don't like the way 3D printed parts look or think they're worried about it. Generally, consumers really don't care if a part is 3D printed. Like this looks perfectly all right and perfectly reasonable in the context of consumer products. But sometimes you don't want the layer lines or you want to print it really fast with draft angles. The easiest way of getting around this to make sure that, again, one printer doesn't have a different surface finish from another printer if you're uploading it to a surface like Teleport, the way to do it is to just apply a texture. There are tools like Formlabs Texture Engine where you can basically just create a black and white image of the texture that you want on this part, upload the STL, and then it will apply the texture across the entire outer surface of the part. This is really useful if you want to brand it because you can basically take a logo and have it spattered across the outside of your part, which can be really, really nifty. The other thing you can do is just apply a little bit of noise to the outside to where it's roughened up. You can do this actually by doing this type of knurling. If you take these knurling patterns, make them a 0.5 millimeter wide and 0.5 millimeter spaced, they will show up as fuzzy texturing at the top and they won't look like knurling, like these lines right there. It'll just look like fuzz. So that's an easy way to create that sort of texture on a part, which is just to create a spiral around the outside that's really small and really tight. And unlike every other manufacturing process in existence, texturing is free for 3D printing because it adds some print time to it, but it doesn't really add any material. So it's a really efficient way to get a different surface finish. When with other processes, you would have to do all these other sorts of features in order to get to what you wanted. Last, and probably one of the hardest, is tolerances. If you want this part to twist and work the way you want it to everywhere, how do you design it so that the tolerances are universal? Well, number one, you want to design it so that you have as much room as possible. So if you're asking what should be the space between the cylinder and the outer rim of this part that twists like this, well, the answer to that is just as much space as you can possibly give it. That's an easy one. If you can go for a low tolerance, that's really safe and you don't have to worry about textures or anything else getting in the way. Make the gaps and the holes as big as possible. Now you're still dealing with quality, and you can hear that while we have a rattle in there, it's mainly from the pills, it's not really from the parts. So you can see the tolerance on this, that lid is not really moving. It is in there tight. How do you make something appear tight and premium? Well, number one, you want to design it so that you have what are called compliant features. And compliant features are basically a spring. So a little spring to sit along here. So if my hands were both springs, they can sit here and press it right there, and it looks like that is sitting in there tightly, even though it's just being pressed by springs. Don't design a hole and another part the same size as that hole. Make the hole have some little springs and leaflets around the outside. We call them grip fins, so that when you insert something into it, those fins hold it stable and tight. We have a little bit of a feature like this. This is a spring down on the bottom to where those bumps move from one bump to the next, which holds this really stable and looks nice and also helps to create that clicking feature that we wanted with this part. So using compliant features like that to where a part is pressed into position can help a lot. If you want a lid, don't have it just drop into there. You might add threads, that way it can tighten down onto it, and threads can be really sloppy so that it goes on loose and easy, but then it tightens down firmly. Another thing you can do is to make sure, again, to design chamfered edges on all your parts so that it starts out inserting really easily, and then it gets tighter the further you press it in. That is really great for like square lids to where you want to insert a top plate that locks in. You're going to insert the top plate, tamp it down, and then it locks in and the layer lines interact with each other. This is a really good way of doing lids. So just go really low tolerance right from the start and then use mechanisms to make it more valuable there. Because like this sort of thing was not possible to manufacture just a few years ago, but now you can manufacture it in anything that you want. So this wasn't even an option to where high tolerance was required, but now high tolerance is not required because you can create these really complex mechanisms inside of a part for free. But again, the basic principles of using wedges, allowing your parts to be a little bit compliant and to give a little bit or to press in on stuff, that will all help a bunch.
How do you make something like this fit into something like this every single time without having to worry about print settings and make sure that that thing doesn't snap off every time you try to force them together? So vertical pins are something that comes up a lot. People like to make these types of pins in order to act as finding features with something that will be pressing down on top of it. But vertical pins and vertical holes can have a few tricks to them. The biggest one is just the fact that that wants to snap off every single time it gets tweaked a little bit, and the two of them don't always want to fit together. So let's start off with very basics right here. This part is very poorly designed. The reason is because that top cylinder is just a cylinder, there is no filleting anywhere, and that hole is the exact same size as the bottom. So let's go ahead and get past this basic kind of noob mistake and move on to a correct one. First of all, the bottom hole has a fillet in the top so that it's possible for something to be pressed into it, to be funneled into it. That's the very simple one right there. This hole is also made just a hair larger than the actual pin that is meant to go into it, so that there's margin there around the shrinkage of it all. This is about 1/4 of a millimeter. You can sometimes go up to 1/2 millimeter depending on the shrink of your materials, but 1/4 is generally fine. The pin itself is where we're gonna focus. Now, with that original red one, it was just a cylinder straight up in the air, but it's small and thin. The very first thing to make a 3D printed part stronger is to make it fatter. You increase the diameter of that pin and now it won't break off quite as easily. But then, where is it going to break off? Well, it's going to break off down at the base of the pin. So fillet that just a little bit, and it will match perfectly with the fillet on your hole. And then, in order to make sure that it can actually enter into the hole reliably, we're going to round off the top of it so that, again, the two want to join together, as opposed to just a sharp hole and just a sharp pin trying to find each other and press together. You don't want to do that. So this is basic good design. You add in a little bit of clearance in there for the actual parts to fit together, you round off all the edges, and you allow them to actually insert correctly by deburring and getting rid of sharp corners and that kind of thing. These are all good general rules. And of course we follow all those rules with all the rest of the cube as well, putting a chamfer on the bottom, rounding the outer corners, all the things you're supposed to do. But that's the basic stuff. We want to make this even stronger yet. So maybe this is under a lot of torque or it's sliding or something like that, and you want to make sure that there's no way that can snap off. Well, the other really basic sort of solution is to just make it shorter. These are generally better for like sliding features and that kind of thing, but they can still be useful. There is no reason to make it any longer than it has to be. If you can make it shorter, and that decreases the amount of torsion that it can occur on the base of it all. Okay, that's it for all the easy things to do. But why does this want to snap off? Well, if a force is applied to the top right here, this is effectively a lever arm, and it's going to try to bend across this lower corner down here. And then it's going to split along the layer lines. So you engineer around that.
Since the layers need to have a large amount of contact between themselves in order to not split very readily, what you can do is rather than simply just having the outer skin of a circular cross section, you can actually increase the amount of area that the layers are touching. And the very simplest version of that is doing this. Use a cross pattern. It still has the same function. It presses right into it just like that, but you have more strength because these individual sections are able to give you more strength in the direction that the push is happening. As opposed to this that just has that outer skin, and then as soon as a crack forms, it breaks on through. This has a lot more direct structural stuff in that axis to hold it together. Now we're gonna get into some subtle design tricks on this, because while this fits into this, you're gonna have to tune your clearance and your tolerances in order for those to fit every time. And if you ever move to a different machine or a different material or a different printer settings or a different resolution, it's all gonna break down. So how do you make sure that this actually fits into there every single time? The very first solution is a very simple little chamfer here. You can see just a slight draft angle. So you can make the base slightly wider than the hole, and you can make the top narrower than the hole, so that as you're pressing in, the top definitely goes in, and then you can force it in the rest of the way. So that chamfer allows you to get it worked in there, and then this cross-section design allows it to kind of wear in. So if you're gonna repeatedly do this, you can actually make sure that it starts to fit the other hole well, rather than simply going in and getting locked. This is a really good benefit of this, is that there's not direct binding of the outer walls together, and you don't have to worry about that clearance. This is a much more universal way of getting it done. But you can evolve this even more. Again, you want to sharpen off the tip of it all so that it's able to insert into the hole reliably and make sure that the base is filleted out. Or you can apply the chamfer to have it just fit in there just right and move from there. Both of them have the main cross section so that you have the maximum amount of strength that you can have, because there's the most interlayer adhesion, most surface area of each layer that you can get a hold of, which is so much better than just a simple round pin. But if surface area and outer surface contact is the goal, why not just maximize it? Why not just go the whole way? These still can have infill and are still wasting surface that could be used. Those inner corners right there could be filled up with material if you had the circle. But the problem with the circle is that it can be filled up with infill. So with our final design here, what we have done is we have wrinkled the outer edge of the circle so that you have the maximum amount of material on the outer edge where the crack would want to form, so that there's as much resistance to that as possible. But in addition to that, I put a cross on the inside of there so that this upper pin is effectively fully solid. This is something called micro features. And with micro features, what you do is you basically put a 0.2 millimeter slot into your model. And what will happen is that that effectively turns into walls inside of your model. So you're able to apply solid areas to particular areas of the model. And with those slots, I can actually drive them down, not just to the surface, but deep into this part a little ways, so that you get the maximum amount of strength that you can possibly get from a 3D printed part here. Because while all the rest of it is printed with regular infill, the pin is effectively solid, and it has enough outer surface area that cracks cannot form on those outer edges. And with a little bit of chamfering and rounding the top and all the other basic design rules, it will press together and fit perfectly every single time, regardless of what color, what material, or anything else you want to use. Now, why is it so important to make sure that you design CAD like this so that it's reliable, independent of your print settings? Well, if you ever wanted to mass produce this or have it produced on demand as a product through a print farm, like in our teleport service, where you can just upload a file and send it off to somebody, you want to make sure that it can be printed right off of any type of machine at any given time, without needing tuned or tweaked. If you're tweaking slicer settings, you are not designing a product. You are being an artisan. It's like carving wood. But if you actually design it well, then it's something that can go into a factory and be produced reliably every single time. Will create a really good quality product for your customers and be more reliable than anything else you could ever possibly do.
This part is really, really challenging to make. The reason being is because it's so tall and thin. Now this one actually has a little bit of forgiveness in it, because if we look at the layers, we could actually support it from the bottom, but you have to have some sort of support spacing here in order for the support to be removable. You can't have the support embedded in the part. And this also doesn't work for very tall, thin plates that might be perfectly vertical to where support can't possibly generate. So how can you possibly produce this part without having a ton of Z-banding and wobbling near the top, especially on something like a bedslinger printer where this thing is zooming back and forth? Ideally, you have a better printer than that, but if you don't, The other option to address this is with what is called support combs. Now, a support comb is something that we'll create inside a 3D builder here. It is an external STL that we're gonna bring in. And actually, here it is right here. This is a basic support comb, and we'll actually share this file over on our Patreon. But you can see it is a vertical post with a wide base with several small sprues coming out the side. These are 1 millimeter in diameter because that's the smallest reasonable size for most 3D printers, and they are perfectly horizontal, which means that as the nozzle comes around, it will travel out to the end of this and then come back, and you'll have a small kind of thread or finger sticking into the part. So in order for these to work, we first pull the part into 3D Builder, and then position this where we want it to be. You want it to be as close as possible because obviously you don't want flex anywhere in here. And these fingers are made to be extra long so that they can reach out into these weird curved parts like this. But the issue is that now you have these fingers sticking out the other side, and we don't want that. We want this to be perfectly contoured with the part. But first thing we're gonna do is we're gonna get this comb shoved in as close as we can. We do not want it all the way up to the top of the cones. You wanna have a little bit of just finger there, and that will do us quite well. All right, so I'm gonna copy that plate, and it's gonna move exactly a single axis over. And then we're gonna go up here to edit, and we're gonna subtract that plate from this part. And now you can see the fingers have been split based along the profile of this part, and we're gonna get rid of the opposite side. And then we're gonna take this and move it back into position. Take the duplicate and move it into position. Just like so. And then we can take this and shift it in just a little bit to make sure that those fingers are sinking in because it was cut along the profile. So you want to go a little bit further. And now we can go ahead and merge these two parts. And now you have a part that has support all along the side. It has this single pillar, which is a piece of structure, and then these really small sprues going into the piece that can then be snipped off with flesh cutters from the outside. And we use this for a number of different kind of tall, thin parts in order to allow them to be printed reliably and quickly and in the same plane as the layers themselves without having to be laying flat. It improves the surface finish of the part because doesn't have to be some large flat side on this fin. It can print up from the small area, and then you just have a few small pock marks, very similar to like resin prints that appear on the outer surface. And if you're using PLA, you can hit those with a heat gun and they will basically disappear. So hopefully this helped you. And this is a solution for supporting very tall, thin parts without actually having to have support or having to re-engineer the part in some way. It's a very quick type of disposable support that can be engineered to the part itself.
So you're looking to have a part mass produced with 3D printing, but you're wondering what that part is going to look like. So in this video, we're going to go through what many of the standard types of surfaces are for FDM type of 3D printing, so that you have an idea what you might expect and what can be adjusted and changed in order to get just the look that you want for the part that you're making. So within surfaces, the surfaces of most 3D printed parts are defined by the thickness of the layers. When you're 3D printing a part, you're putting one layer on top of another and building them up over time. And since each one of those layers have thickness, you end up with a linear type of surface finish, oddly enough. Now, these layers can be varying amounts of thicknesses. They generally vary between somewhere in 0.1 and 0.3, but they can go larger and they can go a bit smaller. There are layer lines as small as 50 microns, which are the thickness of a human hair. 0.1 millimeters is 100 microns, so 2 human hairs, and then so on from there. Very often it's slant 3D. The most common surface finish that we recommend is actually 0.2 millimeter resolution, because to the human eye, this looks almost the same as a 0.1, which is twice as long to print and therefore more expensive, but still higher quality than a 0.3 layer resolution, which is generally used for draft parts, industrial hardware, things where surface finish or appearance really is not that important. So if you're trying to optimize cost and print time, 0.2 layer height is generally the best way to go. Now, sometimes you don't want the linear surface finish. You want a 3D print to look like not a 3D print. So how do you get around this? Well, there are smoothing options out there, but generally we do not recommend post-processing processes because they add to the cost of the part and they limit the amount of scale. Smoothing processes, painting, that kind of thing can all change the surface finish of a part, but they're not ideal because they just cause more problems and more cost. If you design for the process, you can actually get around it. One of the huge advantages of 3D printing is the fact that it's able to apply textures to a part for basically zero cost. With any other type of manufacturing process, adding a subtle texture to the piece can radically change the cost to produce that part. But with 3D printing, it's free, so we might as well use that. So one of the most simple textures that you can apply is actually what's called a fuzzy feature, which is basically where we introduce a little bit of noise to the outer surface of the part. And this creates kind of wrinkling and vibration throughout it, so that each one of the individual layers is actually a different kind of a texture and a little bit more noise. So you sort of rough up and apply a small texture to the print. Now this can be really subtle to where it just kind of makes the layer lines sort of meld into sort of a matte finish, or you can make them really distinct to where the part almost becomes hairy. And there aren't a lot of applications where that's terribly useful outside of areas like toys and some sort of consumer devices, but it can be useful for like filtration if you explicitly want the part to collect particulates and that kind of a thing. So that kind of rough surface texture can be useful. And it's also useful in industrial hardware if you're trying to create a high friction surface. So if you're using like a TPU or some type of rubber, you can have the friction of normal rubber, but then you can add that texture and get even more power into it. Those are basic surface textures, but if you want something more complex and more distinct, like a diamond or knurling or any other sort of pattern, orange peel that you might want, all of those can be created within CAD and within slicers on our side. So there's a number of different methodologies of getting this achieved, and it can create a huge amount of value for your part because, again, adding these textures are free. But that's a general summary of what the 3D printing textures are that are out there. You can start with just the virgin layered look, which can be very useful and has a very distinct aesthetic, very much like the grain inside of wood. So you can design around it and control it in certain ways, or you can attempt to hide it by applying a different texture over the top of that part so that you hide the native layer lines and create something completely original that cannot be manufactured easily with any other sort of method. So textures are something that 3D printing can actually lean into and create in ways that were never possible before and allow you to create products that could never be created affordably before.
Fillets are a fantastic feature that should be used everywhere inside of a 3D printed part, except on the first layer. You should not have fillets on the bottom of your part. The reason is this: if you fillet the bottom of a part, you end up with effectively a near horizontal first couple of layers, where you have an overhang that either has to be supported or is just going to get deformed and nasty down there on the first part, because you have the first layer go down and then the next layer goes way far out into space, and then the next layer builds on that and then it slowly recovers. That's not a very good way of doing it. If you do have to have the fillets on the bottom of a feature, don't use standard perfectly circular fillets where each edge is tangent to the edge that it's interfacing with. Instead, design kind of a custom fillet where it comes down and just kind of curves in a little bit. This creates the same aesthetic, but then you don't have that overhang issue where the layers can build on top of each other very easily. And you end up with a part that comes off a lot cleaner. Now you end up with a larger contact area down here, which kind of changes your geometry. You also end up with a slightly sharper edge than you would otherwise have. But again, no messed up bottom that looks all rough and nasty. Now, technically, the maximum that an overhang should ever be inside of a 3D printed part is 30 degrees. And you can actually create this when designing your custom fillet for some type of rotational item or when cropping it off. But even with 30 degrees, you still run the risk of having a certain amount of deformation or kind of a ring wobble on the bottom of your part as those first layers go down. Because again, you have the first layer and then the next layer on top of it ends up way out here. So the shallower you can make this angle, the better. But again, you don't want the angle. In a perfect world, you just use a chamfer. That way, every layer is exactly one stair-step ratio up from the next, and again, make that whole thing a minimum of 30 degrees, and you create something that's really viable. Now, when is this actually relevant? Well, it often comes up with pieces like this. This would be something that's like a switch cover or something, where you have a switch come through there, and people can flick it and move it around. But this cover would generally be beveled, and the bevels themselves, folks often go kind of the lazy route of creating a perfectly circular fillet. But again, you end up with that saginess right here on this lower corner, which is not ideal and makes it look bad. But if you create that slightly decreased bevel, then you get the same general aesthetic that's not too darn different from the standard fillet. So it looks curved and smooth, and you have the aesthetic that you're going for, but you don't end up with the wonkiness on the bottom of the part. So hopefully now you know better how to design fillets on the bottom of your piece so that you get a part that looks really good, is mass producible,
and doesn't create any sort of wonkiness or bad print artifacts.
Kids' building blocks are pretty much done, right? You cut a piece of wood into a square and that's it. There's not much more that you can add to that. But, you know, as technologies evolve and we move past cavemen beating rocks together, maybe it is time to revisit the kids' building block. So let's talk about how you design a kids' building block with 3D printing. So this is not the first time this kind of stuff has been possible. Lego has utilized new technologies to make blocks that never existed before. I mean, before they came along, there were just wooden blocks, and you might have had, I don't know, a Tinker Toy or something like that. But with injection molding and high precision injection molding, Lego was able to create a building kit that never existed before and functioned in a way that nobody else ever had before. They used a new technology in order to create a new type of block. Well, the challenge with blocks and with 3D printing is the fact that blocks take up a lot of space. They're heavy, they're dense. 3D printing a solid brick of something is not really very efficient because there are better ways of doing it. You can use molding, you can use wood, you can use all kinds of things to make a block that just stands up and piles on top of each other. There are cheaper ways of knocking out a bunch of that kind of stuff. Heck, you can just knock off a branch and give a kid a bunch of round cylinders and let them start stacking them up. They don't know the difference, they're 3. What do they care? But if you want to build something unique and original, the new Tinker Toy, the new Lego, 3D printing gives you a competitive advantage and a new way of going about it. So when we looked at this project, we thought, how about we use Vase mode? Now, Vase mode is a challenging way of producing parts because it requires a design expertise in and of itself. We've talked about the Be Friends line that was created by Benet in order to show how Vase mode products could be premium and really unique but still structural. So how do you apply a lot of that to these? Vase mode takes the outer contours of whatever the 3D model is and just does a single outline there. This is very material efficient, very lightweight, and very fast to produce something. Most Vase mode things are vases. They're kind of squishy and flat, and they're like a sheet of paper that's been wrapped around into a cylinder. But the issue is that it doesn't generally have much structure. So how do you make it structural? Well, you start giving it depth. You give it wobbles and angles and creases. What we've done is we've gone ahead and designed a brick. But instead of doing a simple square, where if we printed it in Vase mode, we just have a square with a hole in the top that would be basically a little square cup, which is not very interesting and kids don't really enjoy that. We wanted to invent something new. We wanted a geometry where these blocks can start to lock together and intermingle and stack in different ways. But in order to do this, you need structure. We can't just crush these with our hands. They need to have some strength. So in order to do that, we designed this kind of prismatic shape so that it folds in on itself and you gain thickness. As it goes around the outer edge, it builds up more and more and more and creates something really interesting. Now it's printed on its side like this, so that if you're looking top down, you can see all the way through, and you have these two outer edges. Now, each of these sides print out and that's all fine and you have a continuous loop up there. But then you get to the top and you have a situation where you can't actually do Vase mode up here because you would have a single thin wall, which is now fragile. So in order to do that, you have to start doing subtle things. You actually start cutting through the wall. So we have a small slot up here so that this entire edge of this block is still one continuous outline. And that allows us to create the structure, the thickness, allows it to fold in on itself to where you create this kind of composite part where multiple planes are interacting with each other so that it doesn't just twist and it's not just a film that's been folded together or a sheet of paper. It actually has structure that can hold up for a minute. And since we're using 3D printing, we're able to create this shape. This trapezoidal prismatic type of a shape is very difficult to manufacture normally because you need a mold coming in from multiple different directions, shoving it all together, a lot of releases. It's just complicated, and in order to keep it perfectly square, you are not actually able to do that with molding because you have to have draft angles. There's ways around that, but it's really challenging. 3D printing gives you so much more freedom, and since these are produced in Vase mode, they use very little material, are produced very quickly, so these can be produced for pennies and dimes and nickels rather than dollars. So they are cost effective compared to other ways of making a kid's block. Now, there's a lot more that you would have to do with this in order to make it consumer ready. Now, one of the first steps of bringing a product to market is setting up a company, setting up an LLC. This might sound complicated, but the sponsor of today's video makes it very easy. Zen Business. Zen Business is an all-in-one solution to help you start and grow your business. So if you're looking to take your 3D printing passion to the next level by creating something like these building blocks, Zen Business can help you get a company set up. Whether that be forming an LLC or doing state paperwork, they can help with all of that. So now you don't have to worry about that paperwork or the legal jargon or compliance requirements. Zen Business has the resources available to take care of all of that for you. This includes things like registered agent services, expense tracking, and even creating a business bank account. It's like you've got a business partner who takes care of all the boring paperwork for you while you focus on making awesome new products and making customers happier. And the best part is that it's straightforward and affordable. Zen Business has plans starting at $0 plus just state fees. So if you're ready to take your passion for 3D printing to the next level, go ahead and check out www.zblinks.com/slant-3D and let them handle all the boring stuff so that you can focus on the actual fun parts of designing awesome new parts and pieces and figuring out how to sell them to customers who really love them. Now, if this was for kids, and particularly for kids under 3, you have to start dealing with the issues of like child safety and that kind of stuff, which means that you need to be selecting materials and continuing to improve the design even more. Right now, we printed these demonstrations in PLA, which is both very eco-friendly and a quick, easy way to get stuff knocked out if it's for kids 10 plus, but those kids aren't generally working with blocks. If you're wanting to work with kids who are younger, you need this to be very durable to where somebody can bite on it and not swallow any chunks or pieces. The 3D printing process can create a part that is that reliable, but you have to use a material that holds up that well and doesn't delaminate or crush if we start cracking it and having pieces peel off like we did with this demonstrator right here. In order to get that, you might want to look at a material like TPU to where you could tear and twist and pull and no part would ever come off, so it can actually meet child safety testing standards. So there are ways to make a final product with 3D printing that will get there, and this demonstration is just meant to show you the potential of the design methodology to create something more unique. Because again, this is very lightweight. Now you are able to create a kid's toy and set of blocks that are able to be shipped through fulfillment services like Amazon or through our print-on-demand service and are still very cost-effective. Normally, kids' building blocks are just really expensive to move around because a box full of wood blocks weighs a ton, even though the blocks have to be affordable, but you have to spend $50 shipping the box around. This lets you create an equivalent type of experience, but it's much lighter weight because you're able to create these geometries that just weren't possible before.
So how strong can a 3D printed hammer actually be? In this video, we go through a number of different design iterations and we end up testing these all the way to the end in order to see how much abuse they can actually take as compared to a regular hammer. So very often when designing a product for 3D printing, people have fears about the overall structural integrity of the part because of the layer lines within it. And while this is a common concern, it's really not terribly relevant because very often if you just design for the material that you're actually using, i.e. a 3D printed insert thermoplastic, you can design around the constraints of that material within its native strength zones and create something that is actually very viable. So in this video, we actually created a number of hammers. And when we started with the hammer project, the first thing we started with were basic mallets, because mallets are something that you can place a lot of material into. So we thought, okay, we want to make sure that this hammer is fully reliable and comparable to a regular hammer. In order to do that, we're going to need to shove a lot of material into it. So initially we started with a mallet. We made sure that the outer walls were quite thick, and we started with a standard handle. And that mallet actually ended up performing quite well. We ended up starting off with soda cans that were to be crushed because we thought, these will be easy. And it turned out that actually they're kind of tough to crush, a soda can. And it ended up being more an experiment of how those work than anything else. Because we used the 3D printed mallet and we thought, it's too light or it's not strong enough to really crush this can, because since these mallets were fully plastic, they were much lighter than a typical type of hammer, almost like a rubber mallet. But then we went and got a dead blow hammer, which is full of lead shot, and it also kind of had trouble crushing the soda can. So these things were just way stronger than we had expected. So what we ended up doing was taking that test and basically making it a tie, because both hammers performed about the same. The lighter mallet that was 3D printed did not have any damage to the handle, did not have any real damage to the head of it at all. And the dead blow hammer, which had lead shot, was also pretty much performing the same. But since it had more effort to get going, it had about as much force as the lighter hammer, which had less effort to get it going. So it was more of an ergonomic issue than it was really a material restriction. So we went on to the next biggest thing that we could whack, which was a cinder block. And while the plastic hammer did take abuse from whacking the cinder block, it was able to ultimately crush the cinder block. And many of the areas that people would generally attribute to the failure point, which would be like the handle itself,
were fine. The overall structural integrity of the part was fine, but since it was plastic, it takes a lot of abuse, and it was not the type of plastic that was intended to take a large amounts of impact at its point of impact. It was PLA, which has a very high rigidity, but is also quite brittle. So a hammerhead is really not the best option for it. If we ever wanted to reprint this hammer, we might use something like ABS or nylon, and it would hold up about as well as a dead blow hammer. And you also have to remember that while we were using a solid plastic mallet for the 3D printed version, it would be very easy to design in a hollowed cavity and insert some kind of weight into these parts as well. 3D printing allows you to pause a print, insert material, and then continue on with the print so that you can create the same kind of overmolded situation as the dead blow hammer that has a bunch of lead shot inside of it. So it's very easy to insert extra materials into a 3D printed part in order to improve its properties and its performance as a finished product. But then we went on and did many other tests. Throughout the process of this video, we actually iterated on the design of the mallet a couple of times. We wanted to make the handle, so we added an extension to the handle, which ended up creating a leverage point to where the hammer would perform fine, but the handle extension itself would break off. So if we were to do that again, we would probably change the material being used and figure out some way of reinforcing it by like wrapping it in some kind of fabric so that it cannot shatter. We also hadn't glued it together, so that extra level of adhesion would have helped with that issue. The other issue was that with that hammer, we had actually added on flanges because we thought that the handle might actually be the place to where it would break. And since it's a 3D printed part, we don't really have any geometry constraints of like other typical processes. So adding on flanges, but having a lower material density, as in like an infill of like 25%, has the same strength at the neck of the hammer, but allows us to still have a lightweight system if we want a lightweight system. But ultimately the flange just wasn't necessary because it offered no benefits over what the typical hammer did when we fully printed it. We never had failures of the handles itself at the head of the hammer, which is something that we kind of anticipated. But that's because we rounded out the stress concentration so there was no single sharp corner there. Just a large fillet or a chamfer itself could be something to create an extra piece of structure at those type of bending points if you were creating something other than a hammer. Now, we did take that mallet and we were like, okay, well, it's a hammer, it should be able to put in nails. And the mallet itself actually was able to put in nails. But because it's solid plastic, it's not something that you want to put in nails with because the nails create this very concentrated point of force to where you will degrade the head of the hammer over time. Though again, the mallet held up really well for a PLA part. We expected it to have a nail go shoving right through it. But since PLA is such a hard plastic, it actually holds up quite well than softer plastics like an ABS or something would. Because since it's so hard, it's actually able to resist the nail quite well. But we wanted to make a hammer that was actually for hammering, a very real hammer. These were all fine demos, but a mallet is not very common, not very practical, and is not really viable for like mass production with printing. So if you were to make a hammer that was to be mass produced, how would you actually do it? Well, we want to make sure that it doesn't really mess with people at all. So we want it to be a good size and good proportions. So we went with a standard kind of hammer shape, standard hammer proportions. And then we went ahead and made the handle just slightly oval. That oval shape makes the handle a lot more reliable and durable over time. It also helps it to fit into your hand just a little bit better than a fully circular handle does. But the other thing we wanted to do is make sure that the hammer wouldn't really necessarily wear out. And in order to do that, you actually have to use metal, because that is why hammers are made from metal, is because it's very durable and will last forever. So if we wanted this hammer to have a good long lifespan, we had to have a metal component in it because plastic will never be able to hold up to that. But if you're designing for a hybrid system, what you can do is design a 3D printed part to accept a metal insert. In this case, we used some bolts that were lying around, which ended up giving us a smaller tip than we actually wanted, but that's okay for this demo. We could always make the bolts bigger if we wanted to make a very rod head hammer. This ended up kind of being more of a finishing type of hammer. So we have that bolt embedded into the tip of the hammer. Now you have something that is durable enough through the hammer and the head and everything else to last for quite a while. But then we took this hammer and we put some nails in. We started with a very basic finishing nail and it went in just fine. Again, the hammer is a little bit light, so we might add a little bit more heft to it if we were redoing it, but it wasn't that big of a deal. But if you were a carpenter, it'd certainly be irritating if you were putting in nails all day long. But as like a hobby hammer, it's fine, but long term, it would need to have a lot more heft in it. And then we went in and put in a standard penny nail that you would find around. And it was able to put that nail in as well. Compared to the regular hammer, it performed fine. And again, it was a little bit lighter, but not that big of a deal. There was no structural damage to it at all, and we ended up putting in several more nails all day long. This hammer would not break down. There was degradation around the tip because, again, we had created the tip to encase that bolt. If we were to redo it, we would have the bolt be a little bit longer and have it be the full front head of the hammer, so it's not an issue. But again, this was just a demo to show how could you design a part that could be produced. This hammer right here could be a finished product right here. This could be a finishing hobby hammer or a little sand hammer or a little rock hammer or something else. There are ways to turn this into a real product, and the fundamental principles of how to print it in this orientation so that the handle is strong, giving it an oval handle and giving it a tip that is reinforced with some other material because it's very easy to add inserts to something like this. All of those can be applied to all types of different parts and pieces out there. So hopefully this video was a little bit useful to you and showing you how 3D printed parts can actually be engineered to do pretty much whatever you want. You just have to be aware of what you're working with so that you can design for it, but then still be able to create an equivalent product so long as you know how you're using your process and how you're using your materials. This way, you get all the advantages that 3D printing can offer as far as like no molding cost and lower minimum volumes so that the business model can be a little bit better, but you have to make sure that the engineering follows along and is able to create a commensurate and comparable product that doesn't disappoint a customer in any sort of way.
So actually, how strong is a 3D printed part? Today we've lined up 5 items to be tested on. We've got a Deadpool head, a normal can of soda, a piece of wood to be cut into kindling, a cinder block, and an actual piece of wood that we will cut into the side of as if we're chopping down a tree. And this is going to show us how strong our 3D printed parts actually are. But these parts are going to be a little bit different. We are actually going to test actual real 3D printed axe heads to see how far these can actually go and if they can actually replace their metal counterparts even though they happen to be 3D printed. Now, there is something special about these. We not only have one, we actually have 2. And what we're going to be trying is not just the material, which in this case is PLA, we will actually be trying the orientation. This one has been printed flat, just like this, so that the layer lines all move along the blade and give it as much strength in that direction as it possibly can. This one has been printed vertically, which is just a slight 90-degree rotation to where the layer lines are now going this direction. So will this make the front of this one split open while this one still is able to stay strong and cut all the way to the end, or will they all just go out here when trying to chop kindling? That's what we're going to find out today. So the very first test we're going to try is the standard blue axe head with the layer lines going this direction. And it's going to go up against a 3D printed Deadpool head. This has normal standard infill on the inside and it's also made out of PLA. So let's just see what this can actually do to it. Ooh. So we've got some real nice splitting there. That axe head is really in there. So you can see how a normal 3D printed part is really kind of just hairy once it's split apart, and it tends to shatter to where you get all this splintering. The axe head itself has basically nothing wrong with it. It was not really affected at all in any sort of way. It's very clean, still very sharp. I think we knocked off like a brim down there a little bit, but I'm gonna go at this a little bit more. I'm gonna see if I can just take his nose off. There we are. Yeah. Oh yeah, that's nothing. All right, well, a 3D printed part will stand up against a 3D printed part. On to the next one. So our next little experiment is just a can of soda. Not a real big challenge generally, but you never know. And it can be useful. If this thing isn't actually able to do something useful for you, like opening a can of soda, what good is it? Oh, frick. I didn't expect that. We actually broke it on the first one. I don't think that was a fair test. I think I hit it weird and wackadoo. I think what happened is I hit this corner just a little bit so that it did cause it to split lengthwise. I thought we were gonna get way further than that. Oh no, we're still going on. We're still going on though with this one. I'm gonna take this all the way. Where'd the can go? I'll be totally honest with you guys, we printed off a couple of these beforehand and have run through some of these tests, so we sort of knew what was gonna happen, but I didn't think it was gonna break that early on. You can actually see that we have these really thick outer layer walls to give it a lot of strength and basically solid infill. But I think we can keep on going with this. I don't think it's gonna break away right away. So we're gonna move on to the kindling test here. And what we have is just a 4x6 piece of wood, and we're gonna try to chop this just as you would normal fire kindling, because I think this can keep on going a little bit further. So we're just gonna start right here and just give it a couple whacks. There we go. So the thing I'm noticing with these mainly is the fact that since it doesn't have any weight, it's really tough to do it normally. I gotta get a big old go at it, which I don't really like with my fingers down there. Whereas with a normal axe, you can kind of get a little bit more protection because you don't have to move so quick. Oh, I got that big old knot in the bottom of that wood. Hang on. Ah, we lost another chunk of our blade. That's okay. We don't need it. Because I'm so strong. Here we go. You know, this is holding up way better than I thought. And you can see like the end of the blades are starting to get some notching out of it, but even though we have half a blade, you know, it's usable. I would imagine that we could keep on using this for quite a while. So that's all the way through kindling. I'm gonna carry this on and use this edge of this hammer until it's gone and falls off the handle. So we're gonna move on to the cinder block now. Okay. So this is a test. If you guys haven't already commented about whether you think this is gonna break with what's left of my little blue handle, please comment down below what you think is gonna happen, because I actually don't know how this is gonna go. We're gonna go ahead and use the blunt end of the axe here and kind of use it as a hammer. I'm not gonna hit it right with the tip. We might get to that, but I don't want to quite yet because I think the blunt end will be tougher for doing this. So we're just gonna get lined up right here and see what we can do. There we go. Again, it doesn't have a lot of weight because it's a light PLA plastic part, but we'll see how much of a heave I can get at it. Ooh. Nothing. Wait, I still got axe though. Okay, now it's broken. So that was the axe head printed horizontally like this. And basically what we've gotten is all the delamination of the layers there. I would argue that if we hadn't used this blue, which has kind of more chalkiness from it, from the color, we might have gotten better layer adhesion, but that is what it is. We're not able to get up to the cinder block. Man, I kind of thought it was gonna break through there, but I guess we'll have to swap this out and we're gonna move on to the horizontal test where it was printed on its side. So with this yellow axe head, it was printed on the printer just like this. So all the layers should theoretically be a little bit stronger because they have kind of multi-dimensional strength in there. And the way we put this on is just like a typical axe head. You're gonna start it like that, give it a couple taps down here, and now we got the axe head. I do see something interesting. Since it is printed vertically like this, the back of it has very thin layers through there which can delaminate, and we can see right here, we've already got a crack in the back. I don't think it's gonna ruin us, but we're gonna give it a shot anyway. So let's start up the test, and we're gonna start off with our Deadpool head. So right here, we got our Deadpool head. This guy, we're just gonna go ahead and start with the axe just the way we normally do, and just see what we can do. I started with taking off the nose last time. I'm gonna go ahead and do that again. Very nicely. Yeah, tough enough, it can do it. We actually got some more chipping out of the top of this than I was sort of expecting from that. Again, since it's only a single layer going out there to the tip without the support of if it was printed like this, instead of having basically two beads of plastic supporting the tip of the axe, we only have one single layer going all the way out there to the tip, which then breaks away until it gets to other layers. So you kind of have a weaker sort of situation where it stair steps up to more and more support. So I do kind of expect the tip of this to sort of break down. But theoretically, I think we're gonna get all the way to the cinder block on this one. Alrighty, we got the soda can again. I wanna see if I can just cap this one off because I think this axe is a little bit sharper than the last one, so I want to know if I can cleanly just take off the top. The one thing I'm kind of, and I also want to avoid running into the pallet and the table underneath here while I'm working on this one, because I think last time I kind of jerry-rigged this a little bit. All right, take it up right here, and it worked. Perfect. shearing right off the top, just like that. Oh man, I've never seen the inside of a can before. Cool and refreshing. All right, next one, chopping the kindling. All right, so now we're gonna go ahead and cut chip kindling again. Right now, we're just gonna go right along the grain here until we can get this all knocked down. I'm a little bit worried about the tip of this breaking off from this, but we'll see. Here we go. Yeah, it's all there. Yeah, big old chunk right out of the tip. Basically bit it off. I'll bet if I look at the tip here, yeah, you can see the edge of our axe right inside of there. All right, I'm gonna go from a distance here and not try to do that one-handed niceness thing. There we go. My hand is a little bit loose. That'll happen. One more whack, one more whack. There we go. Yeah, we can cut kindling with this. You can see that the axe blade is basically starting to level off because, like I said, it's breaking off until it gets to a layer thickness that actually is strong enough to not snap off. So except for that big old bite where I twisted it off inside of that little kindling piece, it's starting to level out straight. All right, the cinder block. I'm hopeful and not hopeful about this. I'm hopeful because number one, we have a lot more meat in the back of this head than in the other one, or at least a little bit more. And I think that the layer alignment in this direction will give it a little bit more reinforcement so that we can actually bust through this sucker. But at the same time, this is already compromised. We've got a crack back here just from putting the axe head on there because the layer lines were not aligned for that at all. So I'm still kind of a fan of the old blue one, even though it gave out real early on. But we're gonna see how far we can get here. All right. Well, that's that. Nothing. Nothing at all. Where's our blade? So, yeah, we split right out the back of it. And basically, the two sides of the axe head came apart just like this. Where it had already been compromised back there, we busted through into the infill where it gave and collapsed on itself and then just carried that crack all the way through and into the front. So that alignment, even though it technically makes the front blade a little bit sharper, and you would sometimes almost kind of consider it to be stronger because you have planes of material out that direction, kind of like a laminate, it's not as strong as the blue one, because with the blue one, when the blue one broke, it would break along the layer lines again, but it would break in such a way to where you would still have axe around and there's still the full length of the blade is fully supported around the entire perimeter of the profile of the blade. So I would still lean into this. We have one more test though, and we're gonna show you guys this. When we were experimenting with this the other day, we had printed out this axe head, which actually used a different slicer from these. This axe head, we actually had gotten all the way up to the standard a block of wood where we were chopping it down like a tree, coming in from the side like this, and we beat on it, and that's all the damage of the axe head that we got. This one is printed vertically like this. Since it is printed like that, it's a lot tougher than obviously the other yellow one, which was printed horizontally. And I'm gonna bet that the yellow, because of the colorant difference, is a little bit stronger than the blue, because blue tends to have more white inside of it. But first of all, I'm gonna take it up, use this one, what's left of it, to chop at this just a little bit so people have some context about it. You can see that even though this is a 3D printed plastic part that is made with a really low grade material, and even though it's blunt and beat up, it's still holding up quite well. And if I had the whole blade still, that wasn't all rounded off at this point, because now I basically just have a small pick at the bottom. It holds up pretty darn decently, because even right now the tip of it is basically just wearing down, but I don't have any more fatigue. This is not splitting along there, which I would kind of have to expect. but it can hold up to that. But now I'm gonna take this one and I wanna see if we can actually get through the cinder block, because I think it's possible. So I'm just gonna take this one and slowly kind of lean up to it a bit. Let's see if we can get this done. Dang. We're getting chunks, but since I'm not putting on the axe handle correctly, you know, actually, by the way, this is a really good demo. See that? Not breaking. That could be dangerous. I think we're through the outer layer, so it may just start collapsing, but we're actually making dents in it. I'm gonna switch to the other side here. 3D printed axe head, made out of PLA, broke the cinder block. This one, I don't know what the difference is. The difference in this is somehow within the slicing, because it's the same material as both the yellow and the blue. Obviously, orientation makes a difference. But this was an experimental, very quick print. So basically our draft print settings are better than our optimized ones. But that part is actually tough enough to break a cinder block and keep on breaking it. Oh man, we didn't really expect that. We were planning on our new fancy schmancy demo ones to be the ones that held up, but it was the one that was just Old Faithful, the little prototype guy who held it out all the way to the end. That's that, guys. We basically just wanted to show you how tough 3D printed parts could be. Totally unscientific test, but hopefully it was a little bit fun to watch. If you design a part well, it can do almost anything. Now, obviously you don't want to 3D print an axe head. Metal axe heads are fine. But in any other application that you might actually be going after, you want to consider what the process is that you're using to make your product. Because it can be really tough if you actually respect it and use it the way it should be and understand all of the factors that can make a difference in it. And hopefully this gives you just a little bit of an intuitive example of how tough a 3D printed part can be if for some reason you thought they were just going to break like glass.
Dyson fans are really quite interesting devices. They don't have blades, and yet they're able to move quite large amounts of air. And the reason they're able to do this is from a number of really interesting engineering solutions that they've created. The first of which that they use is that the Dyson bladeless fans aren't really bladeless. There is a motor down in the base of these fans that is a centrifugal motor. It spins very quickly and forces air up through it. That air is then passed through a series of tubes up into the vanes of the fan. And when you look at one of those oval shapes, you'll see it actually has a small slit in the back of it. The way the slit works is that air is forced out through this small slit over basically an airfoil. And using aerodynamics, you're able to have that air follow that airfoil. It basically kind of sticks to it. And that is fine, but it doesn't really increase airflow. The reason Dyson fans are able to blow more air than what their fan might actually be able to produce by itself is that as that air is moving over that airfoil, it interacts with the air inside of the circle, inside of that oval. This is called entrainment, where basically air drags other air along with it. Since the Dyson fan is designed so well so that the airflow sticks to the airfoil inside of that ring and then also brings other air with it, it's able to force air through the ring that is pushed along with the air that is actually pushed by the motor. And this is actually a really good system because number one, it looks amazing, and number two, it actually does create a more efficient system. Whereas traditional rotary fans have only the action of the rotor itself, the propeller inside of there, which is less safe because a kid could put their fingers into the fan if you have an open fan that's spinning super fast and has old metal vanes from 1950, but it also just looks really good. And this is a very Dyson-esque solution because it's elegant, it works better than what is currently out there, and it's a nifty engineering solution. But this system has some trade-offs. It is much more expensive to manufacture than just a standard propeller. With a standard propeller, you have a mold for the propeller and then you shove it on the front of a motor and then you're done. With the Dyson fan, what they actually have to do is stamp an inner ring that is the airfoil and then stamp or mold the outer ring that contains it all and lets the air flow through it. And then they have all these other components inside that are controlling airflow and that kind of thing. So it's a very complex mechanism. But this is also why a Dyson fan would be ideally produced with 3D printing.
3D printing has a number of key advantages. First of all, if you have multiple components, you're able to design them so that they're able to be printed all at once. Rather than having an inner ring that is cast or stamped and then an outer ring that is molded, you can instead just have the single vein with holes and internal channels printed, which is great because you've just eliminated all that assembly, all that extra processing, and all that extra design to design for each one of those individual processes. Now, here's the other thing that's interesting. When we designed our Dyson fan, we made it a little bit simpler. We're not going for a $500 or $700 fan. We needed something that we could make in a day to prove out the concept. So what we did is we got a basic centrifugal motor that is actually used for inflating an airbed, and we designed an internal cavity around that so that it can be shoved up into the bottom of this. The outer side is a basic cylinder so that it looks nice, and we proportioned it with respect to the vanes so it looks decent. This is a decent enough fan to where you could have it inside the house, and it looks interesting. It doesn't look like a fan. The vanes themselves, we have some channeling inside of here that splits the air from that motor into these two vanes. It then comes up into two slots inside of here to where it can blow out. And then on top, we designed airfoils that allow the air to follow along that and ideally in train drag along air through here so that as the air is flying quickly over this airfoil right here, it's able to drag more along with it. And you know, for a first shot that was built in 24 hours, it works pretty darn well. And it demonstrates all kinds of nifty capabilities with 3D printing. Not only were we able to kind of start reproducing a system that Dyson has to put probably several hundred pieces into and get it down to one piece plus a motor module, we were able to get some interesting capabilities out of it. So like this bottom texture right here, you will notice that the top are smooth, but the bottom here is textured, even though it's the same part. This is possible because we were able to digitally apply a texture down here that almost looks like pinning, as if we had sandblasted it, which creates a really nice surface finish that doesn't look like it was 3D printed and is really robust in mass production. If we wanted to make 1,000 or 1,000,000 of these, we totally could because it's simple enough to be designed. There's no weird overhangs. And then the upper vanes, again, have all that complex internal channeling, which would generally need to be created from a really complex putting pipes and tubes together, whereas right now we just have it embedded in a monolithic block. So this is a great demonstration of all the advantages of 3D printing. The other thing that we're able to do is actually vary density of this part. If we were printing this in real life, we would probably make it denser down here so that the bottom of it is weighted down in addition to just what the motor module is, so that this thing always balances and these can be much lighter. Also, if we were going through and doing an industrial design pass of this thing, we would probably embellish and bevel and change this upper surface a little bit. We would actually probably also add a dome over the top, an arch right here, because it wouldn't really be functionally useful for anything because we don't want to control the air that direction, but it would modify the design and make it look nicer and make it look more like the Dyson fans. The other thing that we would do is when we were designing the interior channels, we did not compensate for the airflow changes over time, so the airflow distribution along this line is really uneven. It really shoots up towards the end and then is forced out right there. We should have rocket nozzled it a little bit more so that it compresses so that there's constant pressure all the way up so that air is going out through the whole thing. But again, this is a part that was designed in 24 hours in order to demonstrate how you can combine really complex mechanisms to create really complex products that had never really been possible before. Dyson is able to manufacture their fans, but they're not really able to do it super affordably, which is fine for their brand because they're a premium brand. But they aren't able to really create something that's really mass market. This fan could be modified and have the extra bit of engineering done to it to make it really effective and useful. And this would be a really cool piece that could be mass produced. You could plug into a print farm like ours here at Slant 3D to produce thousands and even up to tens of thousands or hundreds of thousands of these without having the upfront cost of molds or all the tooling or having to do all the engineering of 100 different parts that Dyson had to spend millions of dollars to do to get their bladeless fan. But it's also just a really cool concept because the airflow dynamics of bladeless fans is just interesting in general, even if you're not interested in manufacturing itself. The way these things work is great, and they create all kinds of new advantages because there is no danger of somebody's fingers getting whacked. There is no spinning fan blade that looks kind of gross. It does not take up much room because you're able to use a very condensed motor package, and you're able to create really unique aesthetics and geometries that are really complex but very easy to manufacture because you can use mass production 3D printing. So at Slant 3D, every day we give a lot of advice to people about how to design for mass production 3D printing, both through this channel and through our normal day-to-day business where people submit parts to us. But we don't really think it's fair for us to give that type of advice if we don't actually eat our own cooking. So we went ahead and made a Kickstarter for a set of massage rollers, and we're going to tell you why we did it, how we did it, and what you can learn about how to design your own products from it. So Kickstarter is an excellent platform for testing new products. In the old days, people used to try to fund actual products with it, but that turned out to not be a very good option. But today it is a very good way to find out if people care about your product. So if you are going to run a Kickstarter, have that as the expectation. Don't expect to be profitable with it. Don't expect to launch something with it and pay for the manufacturing. Have that lined up and use Kickstarter as a jumping off point and a customer feedback location. That is what we're doing with these. These are a whole batch of new massage rollers that we designed and are putting out on Kickstarter as of the publishing of this video. If you want to go over there, you can actually purchase the parts themselves, or if you are a DIYer, you can actually purchase the designs to 3D print yourselves. So with this campaign, what we did is we started with a very simple premise. How can we make a very nice set of massage rollers that can meet the needs of what people want? And people need different things. Right now, massage rollers as they're made are very limited. Most people just have a very basic pattern that rolls around and you can move it around your legs and that kind of thing, but you're not able to get a very specific type of feel. For example, you might want something that grinds and does really deep tissue kind of stuff, or you might want something more subtle. So we're able to take advantage of 3D printing to create many different variations and actually find out what people want. On the Kickstarter, people are able to order a roller, and then when they make their purchase, they will be able to select from the designs that we have available. From that, we will be able to use the Kickstarter to find out what designs are actually popular and which ones should never see the light of day anymore. That allows us to really focus on the products that people want rather than the products that we think that people want. And from a business standpoint, these different designs allow you to target different SEO, different core demographics, and different things that people are wanting. Maybe you could call this like the gentle massage roller, and this is as an aggressive deep tissue massage roller. And you can go through all of these different options. This is very much like software, and that's not surprising since 3D printing enables digital control of a product the same way you could edit a website to get a different color to make people click more readily. You can now actually edit physical stuff so that you can create what people are actually looking for. So what we did is we started with the basic core cylinder, and then we just started making variations that give different types of feels. You can have different levels of randomness and different levels of patterning and sharpness and that kind of thing. But we also wanted it to look good, and very often people don't really prefer 3D printed parts. Well, this was pretty easy to adjust for because number one, the overall design is very amenable to 3D printing. It is a thick, simple cylinder where all the layer lines are in the plane of rotation, so you don't have to really worry about it too much. So you're able to, number one, create something that is very durable, can be used for long periods of time, and actually looks very good. In addition to just the general designs and the main patterns that you can see, we have a texture that we apply to the whole piece that makes it look matted and very naturalistic, almost like tree bark. Because when we were going for this green and tan look, we wanted something that would fit inside of a yoga studio or on a desktop without being glaring or ostentatious or weird looking. One of these parts just sitting there doesn't necessarily say workout gear. It can be something more in the environment without having to really stick out. It doesn't need to be purple. It can just be there. And then in order to stay on with that naturalistic tone, we just used a wooden dowel made of poplar so that you have a baseline shape that again is very adjustable, gives a lot, and allows you to get whatever grip you want on it, whether you want to double fist it like this or just go along on your arm or your back or whatever it may be. So there's a number of ways of doing this, and again, it maintains the entire aesthetic. So even though it's 3D printed, it doesn't really matter. That's just the manufacturing process. It is irrelevant to the quality of the product. The fact that we actually use the dowel also simplifies it so that when people want to order batches of these, they're able to actually swap them out and they don't have to have multiple dowels, and you don't have to worry about really complex assembly, which is not really the case with other types of tools where you have to make sure everything's all put together. These are very simple, they're very basic. The other benefit is also that each one of these rollers can actually stand by itself, and even if you don't have the dowel, you can still use it. or use it for like massaging your foot. You can put it down and massage the arches of your feet and that kind of thing. So there's a lot of flexibility in a very simple shape. Now, the other thing that we did on this is that if we wanted to produce tens of thousands of these, we want to make sure that they can be produced automatically. You don't want people collecting parts from 3D printers. So when we designed them, we actually designed them to very explicitly have a very small contact area with the bed of the printer. This way you don't have to worry about staining or any sort of first layer problems. So what we also did is we chamfered that first layer so that it has a minimum amount of contact area. We also chamfered the interior of the holes so that the dowel will always feed in and there's never a tolerance concern with assembly when people are using these. A lot of people would design that hole as just flush, but it does not look very good and is not that great. So ultimately, we end up with a lot of different massage rollers. Now, again, we put these up on Kickstarter. Now, why would we not just put them up on our website right away? Well, we don't know what are going to be popular and what are not. Kickstarter will be able to give us the feedback about, do people like a real deep tissue kind of pine cone style shape, or do they prefer something softer? Once we know what style customers are interested in, then we're able to focus on the style and now create many more variations of this while ignoring variations of this. This allows you to focus in on what your customers actually want and create more styles like that. And then you can move on from there. Because again, since we don't have fixed tooling, you're able to create more variations basically on the fly to get whatever people are asking for. And as the Kickstarter goes on and we get feedback, we very likely may create new variations during the campaign that will help people be convinced to transfer over and purchase these. But ultimately, this is a very simple design study and product example of what 3D printing enables. You can create a very high quality, very good looking product that people can enjoy and have in their life that does not look cheap, does not function cheaply, but also has all kinds of benefits from the process itself. Because you can create high numbers of variations, you can create really original textures and aesthetics that were never possible before, because many of these just could not be manufactured affordably before without some type of complex yoga in order to make the manufacturing process work, whereas it's very simple for 3D printing to make these types of objects so that you can try whatever might actually work. So you are a toy company. You have a lot of products. A lot of those products are toy trucks, RC cars, something to wheel around. All of these things have tires. So you go ahead and you design a standard tire. It's a wheel. It's got a hub and an outer side that needs to be a little bit rubbery. That's not a big deal. Mold it, machine it, make it with 3D printing. But here's the thing. If you made it with 3D printing, you have the tire, you're producing hundreds of thousands of them. But now you want to expand. A new movie has come out and you want to be on brand. You want to address something on social media. So you go ahead and modify that tire. You maybe change the treads or you change the overall shape of it. That's easy. Now you just send a file over and every tire going forward is updated. And you can continue producing the old design until people don't want it anymore, but you can move into the new design, all with no capital expenditure because there's no upfront tooling cost. So now you've addressed the trends of the day, but you keep on listening to your customers and they're like, well, the tires are a little bit stiff. It would be great if they had more flexibility. So now you go ahead and say, well, we want these to be airless tires. Let's go ahead and make some cutouts on the side. That's totally fine, but then you get some more feedback from your customers and they're like, those cutouts are great. The tire's a lot softer, a lot more flexible, has a lot more give and more traction, but now it's collecting all kinds of dirt and debris inside of those grooves on the side. Surely you can't change those, can you? Well, now you're making it with 3D printing, so you can make any geometry you want. So instead of having those cutouts on the side, you simply make some interior pockets. So now you still have the springiness and you're able to create this impossible geometry of this enclosed bubble that is impossible to make any other way. But now you have the same feature as the tire, but it looks just like your old one, but now it's better and it doesn't collect all the dust and dirt. That's great. Now you're addressing what your customers want even more. But then your customers come back again and they say, that's all fantastic, but we'd really buy a whole lot more over in this part of the country if you could change this tire so it could work on sand or have even more traction. Those old treads just don't grip enough. So you say, okay, fine, let's update the file again. And you end up adding some nice deep tread onto the side of the tire. It's really easy. You email over the file and now every tire going forward has that updated tread. And it costs nothing more to make than the tire before because all you did was change the file. And since it's still the same baseline, you don't have to change settings, you don't have to change setup, you don't have to change material. All you had to do was change a digital design, and now your product, your physical product, has been updated. And that's fantastic. Your customers are ecstatic. They're as happy as they can be. You're addressing everything that they want when they want it. You're riding social media trends. You're addressing the new generations of customers who try your product and the new ideas that people want to pursue, the new hobbies that expand. Maybe it's RC cars, maybe it's toy trucks, maybe it's something for a Lego kit. But you're able to address it every time because all you have to do is update a digital file. And now you're making hundreds of thousands of a new product with no upfront cost. But now, something happens. A pandemic comes along. The supplier of your hubs has gone out of business. The thing that mounts to your tires, that sets those 4 holes that need 4 screws. You found a new supplier, but they only manufacture that aluminum hub with 6 holes. So what do? Well, you're going to go into that model and you're going to update that hub to have 6 holes. But you're not going to lose any of your production because you can modify your design a little bit and every tire going forward is now updated to work with that new supplier. No muss, no fuss. And if you were really being smart about this, since you were using 3D printing, you were able to make those tires exactly at the rate that customers were asking for them. So you don't have huge warehouses full of inventory that are now out of date. Oh no, you just updated the file and whatever's left of this month's batch might have to be thrown away, but it could probably be recycled or maybe sold to old customers as spare parts. But next month, every tire will be updated and your inventory will be fully updated.
So today we're going to talk about how to design a part like this that can actually be strong and robust with 3D printing. These types of parts are often used for mounting something to a wall. It might be like conduit or wire or whatever it happens to be. You have some kind of mounting bracket and then a 90-degree rotated flat plate coming out from the side. And the issue with this is that it's very often, if printed, very brittle like that. Now they're designed like this in order to minimize material. Processes like molding are not able to have thick, chunky parts because you have shrinkage and all kinds of other issues that come up. So you end up creating these really thin sort of pieces, which even when molded are very susceptible to fatigue and all sorts of other issues, isotropic or not. But then once you then combine that with the non-isotropic nature of 3D printing, then you can get something that can be very brittle. Now you can get around it a little bit by picking good materials and of course using better print settings than we used on this stuff, but it's best if you actually design the part for the process. So if you're starting out with a simple part like this that is molded and you are trying to get it mass production 3D printed at a large print farm like ours, then the first thing you should do is try to take the injection molded design and just optimize it for printing a little bit. The very first and the biggest solution is to just put a big old fat chamfer there. Try to blend those pieces as much as possible. Have as much of the surface area of the vertical component merge with the surface area of the bottom component. Now a chamfer is a simple solution, but you can also do lofts and blends and all kinds of other things like that, so that now this becomes really robust because you have this really thick area that kind of serves as an I-beam against the breaking force of the layer lines. And of course, the thing to do also is make sure that all the vertical edges are rounded because this improves reliability, print time, and everything else. And make sure that you blend any other corners throughout the place. That way you don't have any stress concentrations on those layer lines. These are all very simple things that can take something that will fail in the field and turn it into a reliable part. And again, since printing doesn't have a problem with thick areas, this does not increase the cost of the part because that's effectively hollow. But those thick areas serve as high beams because the outer skin serves as the point of strength and the inner part just moves the moment of inertia out away from the rest of it. But this is not ideal. This is forcing injection molding to work inside of 3D printing. If you actually want to make a 3D printing optimized part, you start with a brick and then you go backwards from there. Molding is very much about adding small, thin features together, but printing is about removing the features that you want and cutting them out of a block. That's the best way to think about it. In this case, you go ahead and you start with the part that you have and the constraints that you have to work within. Then you start to create the features inside of it. You remove the conduit support, and then you cut out the holes where you want them, and you use countersinks in order to make them reliable. If you wanted to, you can maybe shave off a little bit of that, but this overall block
is indestructible. No matter how much I whack it, it's not gonna break apart because it has so much of that internal strength from the outer skin. So whenever you're designing 3D printed parts, you wanna make them blocky, you wanna make them chunky, you wanna make them fat and lugubrious. These are the way to design these type of parts. This way, when you mount this inside of a car or inside of a machine that will be under vibration for forever, maybe a little bit of load from the conduit wearing back and forth, you have something that will be reliable, probably longer than a molded part ever would be, because you don't have these small, fragile pieces that can have crack propagation over time. You have ones with basically so much engineering margin just implicit to the process that you are able to have it be really reliable while still maintaining a very highly affordable part. Because again, this is not a solid brick. This is hollow, which means that it uses minimally more material than if it was refined down to thin walls. All the surface area of this is now just in the outer surface area of this, and it's placed where it's more functional, more reliable, and more useful. So this is how you would design a 90-degree part to actually be mass producible with 3D printing and to hit all the engineering specs that you might have for that project. If you have a need for mass production, go ahead and reach out to us and we can get you a quote, or just subscribe to this channel for more content about how to design for mass production 3D printing. Have a great day, everybody.